Hello and welcome to this complete course on artificial intelligence. Artificial intelligence is something we hear everywhere today. But what does it actually mean? In very simple words, AI is about teaching machines to think and act in a way that normally requires human intelligence. This could be things like recognizing faces, understanding speech, recommending videos, or even making decisions. And the interesting part is you are already using AI in your daily life. When your email automatically filters spam, when Netflix suggests what to watch next, or when your phone unlocks using face recognition. That's AI working behind the scenes. Now, AI is very broad field and it includes several important areas. One of the most important one is machine learning, where a system learns pattern from data and makes prediction. Within machine learning, you will come across statistical machine learning, which includes algorithm like regression, decision trees, and clustering. And then comes deep learning, which focuses on neural networks. These neural networks are the backbone of modern AI. They power many advanced applications we see today. Inside neural networks, there are different types of architecture. For example, CNNs are used for working with images, RNNs and LSTMs are used for sequence data, and transformers are used in modern generative AI systems like chatbots and content generators. You will also learn concepts like autoencoders and advanced techniques like retrieval augmented generation, also known as RAG. In this course, we are going to explore all of these concepts step by step in a very simple and practical way. The goal of this course is to help you understand AI without making it complicated. So without wasting any time, let's get started.
So let's start with this, right? Before we even talk about artificial intelligence, let's talk a little bit about intelligence. What is intelligence? The thing is, intelligence is intangible in the sense you really cannot measure intelligence. It's not a fundamental physical quantity. There are some tests that are put in place. You have the IQ test and this and that, which try and sort of give you a way of measuring it. For example, it's like you when you talk about when you talk about intelligence, you can always create like a reference scale and say this person is so and so percentage more intelligent than the other one, or so on and so forth. Your IQ scores are, they're sort of benchmarking exercises, not so much about they're not a physical quantity. It's not like mass or weight, which are actual physical quantities. Intelligence is an intangible. It's not very easy, or it's actually non-trivial for somebody to actually measure intelligence. um, the reason for that is because intelligence is sort of composed of a bunch of these types that you see here, right? So intelligence is a combination of reasoning abilities, linguistic abilities, ability to learn, ability to perceive something, ability to solve problems. And there are a ton of intelligence aspects which are not mentioned here. Emotional quotient, interpersonal skills, and so on and so on and so forth. Exactly, right? So like Vincent was saying, people who can't read but are super intelligent. That's because linguistic intelligence is probably not the only intelligence that is relevant. Point is that when you refer to somebody as intelligent, it does not it does not always translate into, it's not a very defined template that, hey, somebody who's intelligence has ABC kind of skills. Not necessarily. Different people have different kinds of skills. In the case of humans, different animals have different kinds of skills. They are intelligent as well. Animals are intelligent as well, fairly intelligent. There are many different forms of intelligence, sub forms of intelligences, and so on and so forth. What you are seeing are some of the most popular forms of intelligence that you and I could probably relate to. But that said, there are so many other forms, like emotional intelligence and so on and so forth, which are not mentioned here. What you're seeing are some of the examples of those intelligences. Um, Now, let's talk a little bit about each of these, right? Um, and I'm going to be referring to some of these intelligence specifically in the context of human intelligence. I mean, we can definitely talk about intelligences in intelligence as a trait in animals as well, but we're going to be focusing specifically from a human angle, so to say. So let's take, for example, linguistic intelligence. What we mean by linguistic intelligence is somebody's ability to be able to communicate through language. Language is essentially is a way for somebody to communicate concepts, right? Communicate emotion, communicate themes, and so on and so forth. So if I wish to, let's say, communicate to you, I'm in this particular case I'm using language. I'm using English as a medium to communicate. That's a form of that's a form of linguistic intelligence. Um, Now, this linguistic intelligence doesn't only sit with me. This linguistic intelligence is also with you. Why? Because A, you're able to understand the language, but to also make that linguistic intelligence linguistic intelligence relevant, you also need to have the intelligence of perception. What do you mean by that? I am currently talking, and you have your ears, and you have your eyes, you have sensory organs which are tapping into this signal, audio signal, and the visual signal, converting that into understandable signal, right? So if somebody doesn't understand English and somebody is hearing, you might be able to perceive something. Your ears might capture that information, that signal, but that might just seem like noise. It might not make any sense. Because you understand English and I am speaking the same language, and because you have the linguistic intelligence and perception and the intelligence of perception, you're able to capture the signal, translate that signal into linguistic intelligence, and then make sense of what I'm currently talking. The point is that, as you can imagine, the current conversation that we are having is a combination of a couple of intelligences, so to say. So, intelligence of perception is the ability for somebody to be able to perceive a signal. Now, the signal can be audio, the signal can be a video, the signal can be music, the signal can be, let's say, a touch, olfactory senses, whatever. Your eyes are like cameras, your ears are like mics, microphones. Um, and the point is, you are essentially capturing the signal continuously and then translating that particular intelligence into that particular signal into some form of consumable knowledge, understandable, comprehensible knowledge, so to say. So that is what we mean by perception and linguistic intelligence. Now, if you translate this in the context of, let's say, animals, now, do animals have linguistic intelligence? Now, they have their own form of linguistic intelligence. They probably don't communicate through verbal language. It's not actual language, as in verbally spoken language. They might communicate through body language. They might communicate through other forms of um, they might communicate, but they might communicate slightly differently, which you and I may or may not necessarily understand. And that's because of their either their physical abilities, or it could also be because of their limitations, because animals may or may not necessarily have the kind of vocabulary that you and I have. For that reason, animals do communicate, other forms of species do communicate. Um, and they communicate very effectively as well, but they have different ways of communicating this. For example, even even a plant can communicate, but it communicates very differently. An animal communicates, but they communicate differently. So they do have intelligences in different forms. Um, there are plants that have some form of response to a particular stimuli, which means if you touch certain plants, they respond. Um, Plants and flowers can essentially attack predators, flies or bugs and bees. That's intelligence. There is a certain response to a particular stimuli. That also is a form of intelligence, because the plant is responding to a particular stimuli, so to say, right? So these are some examples of how even non-human species would also have the would also have the knowledge of the intelligence of perception as well as language in some shape or the other, not the same language that you and I would understand. Yeah, some good examples, but they understand as dogs respond well to words from their owners. That's because we train them to, right, Vincent? That's because we kind of train them to operate a certain way. Um, so they do have, so in that case, and that's a very good segue, Vincent, because what that does is what you're saying is that, you know, dogs do understand to our signals or to our commands. That's because dogs have the ability to learn. You can train a dog. So that brings us to our next form of intelligence, which is you are combining language, perception, and the ability to learn. You're combining all of these, and then you're getting, let's say, dogs or let's say animals to operate a certain way. Now, this can apply not just to dogs. This can apply to humans as well. For example, a good case in point here is that if you take, for example, um, any human being, right? You and I, we don't see. This is something amazing about human beings, right? There is different forms of knowledge that we have. There is evolutionary knowledge because you and I, while we are while we as and when we're born as babies, babies have these amazing intelligence to just suckle and 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 drink milk. I'm talking about hours old baby. How does the baby even know how to suckle? Where is that knowledge coming from? And that's evolutionary knowledge. It's an instinct for sure, but at the end of the day, that's some form of evolutionary knowledge that you and I have. That's how we evolved. So there is some knowledge that we have. Exactly, the fear of darkness is evolutionary knowledge. Absolutely right, Sayud. So these are certain in forms of intelligence that is embedded with us, right? And that's that's decades and centuries and millennia of evolution. It has gotten us to where we are today. That said, one of the amazing aspects, and this is true not just for us, this is true for animals as well, right? Animals have their own instincts. They have their own, they're born with their own evolutionary knowledge. But one of the fundamental reasons why humans are sort of sitting on top of the food chain or the value chain is fundamentally because of our ability to learn, not just learn, but even document, right? One of the amazing things about us is you and I didn't have to see fire. Fire was not a, it was creating fire is not evolutionary knowledge for us. It was taught, it was learned, and it was documented. Hence, you and I today don't have to go back and take a couple of stones and through absolute serendipity identify how to create fire. We don't have to just go through that complete evolution again. So somebody has gone through the hard grind of creating that knowledge for us. Hence, the beauty is we have the ability to document information in exactly to translate this knowledge from one generation to another generation, from one era to another era. So we just don't communicate, but we document information. And the beautiful part is the subsequent generations have this phenomenal ability to learn from documented information. So if there's a video that somebody's created, you and I can just walk through, can simply read through that particular document or watch that particular video and just learn from that piece of information. Hence, again, it just accelerates the level at which, let's say, your further generations are going to pick things up, which is why your younger generations are often more intelligent than the older generations because they have much more access to information. Language is learned knowledge, absolutely true. Language indeed is a learned knowledge. It's a skill that you pick up over the period of time. But the ability to pick up that particular language is an innate ability that we have, is because we are wired a certain way. Hence, we understand these signals very, very well. Again, I think we are all kind of in theory agree to the fact that these are all different forms of intelligence. You can give them different definitions, but in theory, what we're saying is every small thing that we do is not out of absolute randomness. Now, the point that I just want to bring up here is, let me ask you a question. If, I mean, and just one more form of intelligence that I just want to touch upon is something that I guess the ability to reason, because the aspect of reasoning is, I believe, super critical, and that is one of the reasons why the abilities to read. Okay, so let me put it this way: we have a fantastic, or rather, when I say we are, one of the forms of intelligence is to be able to reason, right? Cause and effect, what has caused what, um, or to get to, let's say, to do root cause analysis, right? If a certain particular event has occurred, what are the possible reasons of a particular event occurring? Now, this is an extremely important skill, eventually an form of intelligence that we all sort of possess. I know this is a little obvious to us. For human beings, this is a little obvious, but what you need to understand is that not all species have that level of reasoning. We, over the years, have sharpened our reasoning skills. When I say we, the human species has sharpened our abilities to reason over the years. We can do critical thinking. We can sort of get to the root cause of a certain problem. We can identify, okay, what may have possibly caused. And this is through years and years of experimentation, right? We've experimented significantly for us to be able to see, okay, you know what? But, to cause a certain effect, I need to do A, B, C, or if a certain effect has happened, what are the potential causes of that particular aspect? This has happened because we, over the years, have seen many examples. And now this is a bit of an evolutionary knowledge for us. This is the ability to reason is a bit of an evolutionary knowledge for us. All of us have the ability to reason by default, except for in certain cases. The reason I'm talking about this, and I know this is very obvious for all of you, is because intelligence can can transpire in multiple different ways, can manifest in multiple different ways. But when we talk about artificial intelligence, what we are trying to do is we're trying to bring all of those abilities, right? All the abilities that we just saw into a machine, right? You want the machine to be able to understand language. You want the machine to be able to understand, to reason with you. You want the machine to be able to, let's say, hear you, right? Perceive things, see things. And you also want the machine to probably respond back a certain way, right? You want it to talk to you like an actual human, um, and whatnot, right? Point is that is the North Star as us as human race we're trying to chase. What we're trying to say is, can I bring this kind of all these forms of intelligence into a machine? Now, what you need to understand is this is non-trivial. This is not an easy problem to solve, because if I just give you a calculator, if I just give you a machine, right? A simple computer. A computer is very good at understanding math. It can do analytical work for you. Meaning, if I tell you 1 plus 1, your computer will come back and tell you that is 2. You can use it for doing computations. You can do it for using some stuff. You can do it for storing information. But for it to be able to operate that intelligently means you need to provide, in some shape or form, all of these forms of intelligence into that machine, right? Can you provide information or knowledge of perception or intelligence of perception in your machine? Well, I can put a camera on my machine, on my laptop. The camera will capture the signal, but I still need something that understands that, you know what, there's a person in this particular place. There's a person sitting here. So I need to bring that brain in. In our case, there's a human brain that is taking all of these signals and then processing it, right? But in the case of a machine, unfortunately or fortunately, we need to find that brain. We need to create that brain. with a simple computer, that brain may or may not exist. So we need to find a way to A, bring that brain, and B, somehow get the brain to process all of these signals and then start generating knowledge, start generating this intelligence. One is to be able to perceive these signals, take all of this information in, and then process it. And the second is to also be able to act using that particular knowledge as well. That's the North Star that we're trying to chase for the field of artificial intelligence. Now, the point, my friends, is that this has sort of been attempted over the past few years in very, very different ways. What you're seeing here is a sort of a timeline. I've shared the link in the chat. I'm sorry, link in this particular slide. You can visit this slide as well. It's a very interesting slide. What you're seeing here is sort of a timeline of how many people have tried to, or many over the last few years, we've tried to sort of bring this knowledge or bring this intelligence into the picture. For example, it was one of the first, by the way, this idea of artificial intelligence sort of came up in the year 1955, 1956 by this man named John McCarthy, where the idea was, hey, can we come up with intelligent machines? Why do we want intelligent machines? Sridhar has a great question. Why do we want to mimic what nature has created? Well, the reason is you can do better things, right? Now, this is where science is at odds with philosophy, right? You don't, if you actually create machines that are intelligent? If you are able to create machines that are intelligent, you can do a lot more research, a lot more experimentation. You can do things much faster. You can, as a race, we can evolve much better. So many more. These are existential problems that we can try and solve for. Which is why fundamentally we still believe that AI is a way for us to solve some very, very complex problems in this particular world. So 1955 is when the term AI was first coined. Even before that, during the World War II, I'm not sure how many of you all are aware. There's this amazing scientist by name Alan Turing, um, who sort of proposed this test called as Turing test. In 1945, he'd actually created this machine called Enigma. The Turing Enigma was essentially a cryptography machine, which could, or rather, he created a machine that would break Enigma. Let's put it that way. Enigma was essentially like the idea was for us to be able to for them to be able to crack all of the code that the Germans were sort of sending across. And that's where he actually proposed this test called as the Turing test and so on and so forth. Turing test is actually a very simple test. Turing test says, if I have, Turing test is actually super simple. What they say is, if you have, let's say there is a counter, right? And there is a person that's visiting, there's a counter A, there's a counter B, right? This particular person goes and, let's say, asks a question across both of these counters. The question can be, let's say, hey, how's the weather today? It can be any question. A person goes and asks both of these questions. The same question to both of the counters. Your, let's say, counter A replies back a certain way, counter B replies back a certain way. If this particular person over here is unable, one of these counters is being fed by, let's say, some kind of a artificial intelligence system, right? One of these counters is, let's say, being fed by an artificial intelligence system, and this person doesn't know which one is feeding, which one is being fed by an AI. Now, this person gets the response from counter A and counter B, and if this person is unable to figure which one is actually AI, gets a response that is so human-like that the person is unable to make out anything about which one is actually AI and which one is not, then you can consider that particular machine intelligent, is what he was saying. If a machine can trick humans into thinking it is human, then it is intelligent. That's what it is saying. It's a very simple test. But the fundamental question is, how do you make the machine intelligent? Not just ChatGPT, right? The beauty of this is there are so many things that we're all using today that pass the Turing test very, very well. There are so many systems that are out there today that beat the Turing test. So it's a very simple way of evaluating if a particular system is intelligent or not. But the point is that concept was sort of created in the year 1950s. It's called Turing test, and then it's still very, very relevant even today. 1955 was when AI was born. And then over the last few years, many, many attempts were being made to try and make machines intelligent. Um, for example, 1964 was when the world's first publicly known chatbot was built, right? Eliza was amazing at that time. It was a very, very simple chatbot. You can actually Google this called Eliza in on YouTube, and you'll actually see how this bot worked. It was like a actual chatbot. You could say hi, and it would reply back hello, and you could ask it some very, very basic questions, and it actually responded back. But it was not, of course, it couldn't do things beyond a certain point. It was very, very restrictive. It could only do a few things because it was not necessarily intelligent. I mean, we might not consider it intelligent today. Let's put it that way. We might have considered that intelligent back then, but it's probably not very intelligent today. And then a lot of things happened during this particular time. It was this era. This is the time of the Cold War, right? Um, Focus had shifted. Now, actually, there was a lot of research that did happen during that time, but it was not very it was not out in public. The research was not out in public because the two big countries that was actually leading this AI space were, of course, a lot of it was happening in the West, and a lot of it was happening in Russia and USSR back then. And these countries were at odds with each other, and a lot of it was not in public domain. So not a lot was known exactly what kind of stuff happened during that time, which is why it's called as the AI winter. But that said, again, once the Cold War died down, the USSR became Russia, all of that was settled. Once the dust settled, um, that's when much later in the early 1990s or so, things again started to come back. IBM made some massive inroads. The company that still holds the most number of patents even today is still IBM. And in 1997, they actually launched this product called, or this machine called as AI, called as um, IBM Deep Blue. Again, a spectacle to watch. IBM Deep Blue then competed against Gary Kasparov, who was a grandmaster at that time, and to Gary Kasparov's utter disappointment, he was beaten by this machine. This complete match is on the internet, is on YouTube. You can actually watch it. It's amazing how he actually competed. This was a game of chess that it competed against, and it was amazing to see how, let's say, a human at that time, it was not thought of, right? A human was competing against a machine, and machine actually, Gary Kasparov actually beats Deep Blue in the first game, but then in the subsequent games, Deep Blue actually beats the heck out of Gary Kasparov. He loses, and he loses pretty badly. He actually went on and gave a TED talk about this. You should actually listen to it. He does say that he cried after losing against Deep Blue because it's a matter of ego, right? It's human ego. We consider ourselves very intelligent, and to have been beaten by a machine that was created again by humans, He was not very happy about it. But then he later on went on and contributed significantly to the research of artificial intelligence, where he said, "Look, we need to learn to work with the machines. You should not compete against the machines," and so on. So he spoke about it. It was an amazing to see how things kind of transpired at that time in 1997. Um, Much later, um, in the year, I would say, actually somewhere here, um, I think it was, if I'm not wrong, I think it was in the year 2011. IBM had again run another event. IBM had actually created another AI called Watson, IBM Watson. Again, something that's on the internet. So there's this very popular quiz show called Jeopardy in the US. Jeopardy is an open quiz competition that anybody can actually come and participate. It was actually a televised event. Um, it would typically have three participants. You have a grid. You need to pick a question, answer it, and then the person that wins takes away $1 million. It's essentially um, you need to hit the buzzer and answer questions and stuff like that. So it's a very, very popular quiz show. I'm sure some of y'all have already watched it. IBM Watson, again, competes against two very, very popular, two actual winners of previous seasons, Ken and Brad. And again, to their utter disappointment, IBM Watson beats the heck out of the other two guys, beats them black and blue. It had actually outperformed both of them. Again, Ken again spoke about this once he came back, when what he felt about being beaten by a machine. Again, much before this, the Roombas of the world came in. Apple had launched Siri, which was a personal assistant in iPhone 4S that actually launched it. And a lot of stuff happened at that time, right? AlphaGo as well, 2017. Somebody messaged about AlphaGo. Yeah, 2017 is when AlphaGo was launched. Go is, by the way, one of the world's largest board or most toughest board games. Um, and this company called DeepMind, it's not actually Google. It's called Google AI, but it's actually this company called DeepMind, which Google later bought, had beaten uh, you know uh, Go, actually won Go, and it was amazing. Again, I only know the rules of this game called Go. You can actually, yeah, exactly. There's a documentary on this by DeepMind, and then they talk about how this AI was able to actually create positions of this particular game, which are far more complex and imperceivable by, let's say, by a human brain. So yeah, again, massive accomplishment in this particular space as well, so to say. Now, this is only up until 2017, but there are some black marks. Not everything went well, right? 2016, things did go very bad for Microsoft. What Microsoft did was Microsoft had actually launched this bot called Tay, Microsoft Tay, which was a little premature, I would say, in the hindsight, which was essentially like a bot that was launched by Microsoft on Twitter. And what was expected is, and actually this is a fun story, when it let me actually show you something interesting about this. Microsoft Day, and there's what happened was they actually started with this. It started with some really cool, nice, very, very, where did it go? It started with saying, it's such a pleasure to meet all of you. And then it went on to say stuff like this, which is, of course, not what you would want uh, a, a bot like this to do. The reason is because it was kind of interacting with people, and it eventually went on to it eventually went on to say some really, really offensive stuff on the internet, and they had to take it down in under 24 hours. Sort of a bad, I would say, for lack of a better word, sort of a bad example, or rather a great example for what AI, how bad AI could also be built. Now, this was until 2017. 2017 onwards, and it's not mentioned in this timeline, this space just took off, right? Took off, and exactly in the year 2017, Google had published a paper called Attention is All You Need. So this was in 2017, June, this paper was published. This paper is one of the most groundbreaking papers in the whole of the world of artificial intelligence. It was actually Google who had actually published this paper. A lot of the work that actually went in was published by Google. It was all folks from from Google Brain who had actually participated in this, and some amazing work sort of went into this. Now, this paper, and I'll actually specifically, in the much later sessions, we will specifically talk about this when I introduce, transformer architectures and so on in our deep learning sessions. I will talk about this in great detail. But the point is, this paper, my friends, is one of the most groundbreaking papers of all times. Once this paper was launched, this paper had introduced a concept called as transformers. I mean, I'm sure it might not necessarily resonate much with a lot of us here, but in 2017, that paper was launched. And from there, things just went haywire. So from 2017 onwards, what had happened is this new concept of generative AI started to become super popular. It was more in the industry. There was a new way of building these artificial intelligence systems was unearthed, was discovered, or rather invented, I should say, and it was called as the transformer architecture. And what was realized is that this architecture is so good that as you kept providing it more and more information, as you kept sort of continuously training this particular AI over and over again. When I say training, I'm using the word training loosely here, but what I'm trying to get to is as you kept providing more and more knowledge, more and more historical information to this particular AI, this AI started to get more, it sort of started to get better. Exactly. The word training is in the ML sense. Yes. As you kept training the transformer architecture, these transformer models, they actually just kept getting better and better and better and better. So today, a lot of the models that you see, that you might have heard of, you would have heard of ChatGPT, right? GPT is a generative pre-trained transformer. Stands for transformer. Now, the beauty of that is Gen AI evolution. All right. LLM. Let's go LLM evolution tree. This is the one. So what you're seeing here is exactly what I'm talking about. So this was in 2017. And since 2017, what had happened, and I'm sorry I switched to a GitHub view here, but what I wanted to show you is in 2017, some really, really cool work went in, which was essentially the Attention is All You Need paper. And after that, what you see here, 2020, 2021, things just exploded. All of these large language models that you've been hearing, the generative pre-trained transformers, right? OpenAI, created these GPT models, the GPT category of models. Google had created these Gemini models. Meta had created these Llama models, and so on and so on and so forth. Right? So many new AI capabilities started to come in, and these models were very, very different than everything that we've known of these models before 2017. I'll tell you why. So you've spoken about, if you remember, we've spoken about these intelligences, right? We've spoken about the intelligence of language, the intelligence of perception, the intelligence of learning, reasoning, problem solving. Up until 2017 and 2018, we were trying to solve these problems, but they were not very, I would say, for lack of a better word, they were not as good as you want them to be, right? They were great. They were already solving some really complex problems. For example, in the case of vision, in the case of, let's say, computer vision, meaning the ability to read information from, let's say, an image, capture complexities from a particular image, capture, let's say, specific details from a particular image or a video, and so on and so forth. We had made great progress. Um, we were able to beat human parity, meaning, especially in those areas, we were able to outperform human beings in certain areas. But specifically in the case of language, because language is a very complex affair. In language deals with reasoning, right? Let's say, when somebody writes an article, the way an article is structured, there is a lot of reasoning that goes into it. For example, there's, let's say, a white paper. Somebody has actually written a piece of, let's say, this research paper. The research paper from top to bottom goes through a lot of reasoning aspects and then comes up with a particular conclusion. It sets up the experiment. It talks about how they've actually gone about executing that particular experiment, and then it concludes. So for somebody to read a particular research paper, you require a lot of very you require a certain level of intelligence to actually read that particular paper. You just cannot simply take a paper and start reading it. It's unlikely that somebody who is not familiar with that space would understand a research paper straight away. Even until 2018, 2019, we were not able to build AI systems that were capable of reading those papers. Once this new architecture called the transformer architectures came in, it broke all of these barriers. These models, these transformer class of models, were able to understand complex reasoning abilities. They had complex reasoning abilities. They were able to understand very, very long paragraphs. They were able to understand long documents, not just one document, but across documents. They were able to actually not just understand, but they were able to actually create content which were far better than, let's say, your regular than, let's say, content that, let's say, a fairly educated, fairly trained human would do. They were actually able to create content that would outperform a few people. They were able to create, they were able to actually participate in exams like a bar exam. They were able to, let's say, participate in very, very complex SAT exams and actually outperform human beings on some of those exams. They had fairly decent mathematical skills. They had very, very good linguistic intelligence. They had fairly decent reasoning abilities. They had fairly decent, I would say, perception abilities, because they were able to not just read text, but they were able to also, you know, capture audio. They were able to capture video, combine all of this, and then come up with information. So we came up with these multimodal architectures, this transformer architecture, which was simply focused on language in 2017. By 2021, 2022, they extended themselves to language, audio, video, and other forms of information as well, which is why I am specifically talking about perception, because they were able to capture a lot more signal and then come up with interesting knowledge. So the pace at which research had gone up in the AI space from 2017 is so rapid that we have literally turned a page in the whole AI journey, so to say. So, especially the last 3 years, and I have been lucky enough to actually experience it and actually build some capabilities on top of some of this, um, some of this amazing work that's been happening in the industry. You suddenly start to realize that There are so many problems that you had solved in the past which are suboptimal. All that we are doing today is actually unearth some of those problems, use the modern artificial intelligence capabilities and resolve them, actually solve them and solve them slightly better, or in certain cases significantly better. Models that were giving us, let's say, accuracies of 60%, 70% now are giving us accuracies of 98, 99% in certain cases, which are amazing to see, right? That's the level of evolution that we've seen in the last 3, 4 years. So what I'm trying to get at is everything until 2017 is one. Everything until 2017 is one. But from 2017, things really took off. For good, of course. A lot of new architectures were brought in, a lot of new knowledge was brought in, and thereby new techniques were brought in. Hardware significantly evolved, models became more and more smarter, and here we are. We are at a place where today, I think a lot of the hard yards that were put in, half a century earlier, all of that is, we're sort of reaping benefits of all of that journey that we've been through. There's a small concept that um, I'd want to bring about, and that's this, right? When you talk about artificial intelligence, there are two forms of artificial intelligence. There is artificial narrow intelligence, ANI, and then there's artificial general intelligence, AGI. Artificial narrow intelligence is, for example, let's say you have built a model that can, looking at certain information, predict the sales of a particular company, right? So you've built a machine learning model, you've built a regression model, or let's say a decision tree based model. Given a particular set of information, you can predict what the sales of, let's say, of one of your stores is going to be. Or basis some information, you predict if a particular customer is going to take a credit card or not. Or given, let's say, historical transaction of a particular person, or historical, let's say, viewing history of a particular user, you would like to predict the likelihood of somebody watching another video on a YouTube, for that matter. Now, all of these models, these are all great models. They solve the problem. But the unfortunate reality is, every time you set off on solving a particular problem, you need to start from ground up. You need to start from scratch. Every problem is a siloed problem. Every problem is a different problem. Every model that you choose to build is a different model. Number two, they are only built for one particular purpose. A model that I build for, let's say, recommending, let's say, a movie cannot be used to predict sales. Or a model that I build to identify if a particular person is going to buy a product or not cannot be used for scheduling a flight, for, let's say, automatically flight scheduling and stuff like that. The point that I'm trying to make is these are narrow in terms of their applications. They are complex in how you implement them, how you build them, but they are narrow in terms of their applications. Where we want to get to is AGI, artificial general intelligence, some kind of intelligence that you have, that I have. I can drive a car, make food, talk to people, and maybe let's say do my job, do like a bunch of different things with fair amount of abilities, with fair level of, let's say, um, fair level of efficiency, I should say. Where we want to get to, not just multitasking. Multitasking is just one. I'm not referring to being able to do multiple things at the same time. What we're trying to get to is, we want to get to a form of intelligence where which is more general purpose in nature. I want to be able to build a kind of a model, for lack of a better word, I'm using the word model here, which has the ability to do multiple things at the same time. Something like a chitty, for that matter. Something like, let's say, a Terminator, so to say. Something like a Skynet. You want to get there. You want it to be able to do multiple things all at the same time. Or you want it to be able to, if not do multiple things, you want it to be able to, you want that AI to be able to, or that model to be able to be fairly capable in, let's say, holding conversations with you, like, let's say, how a human would. A human has general intelligence. I have a certain form of intelligence which I can use for multiple things. If I have enough information about a certain thing, I have the fundamental intelligence of learning. I have the foundational basics of math. So if I have to learn, let's say, integral calculus at some point, all that I need to do is pick up a book and spend some time on it, or find the right teacher. If I spend a little bit of time learning how integral calculus works, then I have the ability to learn. How well I learn depends on two things. How well I learn will depend on how much information I'm exposed to and the quality of teacher that I have. As simple as that. So fundamentally, as a human being, I have a level of intelligence. It's a matter of using and sort of giving it a certain direction. So that's the kind of intelligence I want to build, where there is some level of basic foundation that's already available. We want to get there. Are we there yet today? Um, Not really. We're not there yet. That's where we all want to go towards. That's what I really mean by machines having intelligence. That's what John McCarthy at that time meant about having intelligence. That's the artificial general intelligence I want to get to, right? Now, what has happened is, and just to kind of give you a sense of understanding, right? Let's say we are at artificial narrow intelligence here, and this is artificial general intelligence, right? Now, over the last few years, thanks to AI, um, we've been let's say progressing at a certain pace towards AGI. What has happened in the last 3 to 4 years is we were operating at a certain pace, and in the last 3 4 years we've made some significant progress very quickly towards AGI. So this happened in the last 2 years, 2 3 years, I should say, while this happened in the last 50 years, 50 or 70 years. What I'm trying to get at is we we've kind of, or this space of artificial intelligence has made massive progress in the last 3 years. And this progress has made a huge leap towards AGI. Are we at AGI? No, we're not at AGI yet. We're still building narrow intelligence capabilities, but we've made some significant progress very, very quickly, thanks to the 2017 paper of Attention is All You Need. Thanks to this paper in 2017, we made some massive progress in this particular space. Does this make sense, everyone? Do you understand what we mean by this? There's an exponential growth in terms of where we've headed in the last few years. We're far away, we're still far away from AGI. There is, I mean, the pace at which this research is progressing, we can even get to AGI very, very quick. We might even get to AGI very quickly, but it's a matter of speculation. We don't know how long will we be able to, how quickly will we be able to get there. For example, okay, robots, there again, okay, so here's the thing. There are a lot of companies that are working on robots, right? Boston Dynamics is one. Tesla has been working on some. OpenAI has been working on, OpenAI not so much on robots, but Tesla has been working on robots, and there's a company called Boston Dynamics. There's a bunch of other companies that have been working on these robots, so to say. They're getting better by the day. Are they AGI bots? Absolutely no. Can they do everything? No. They are still very focused. They can do specific things very, very well. For example, industrial robots, a lot of companies today just do industry. I mean, just assemble things using robots today in manufacturing, exactly in assembling and manufacturing units. We just see robots doing it. Humanized robots is another aspect that a lot of companies are currently working on. It's fantastic to see the kind of progress that they've made in this particular area, thanks to a lot of the progress that we see here. This AI is powering those robots. Are we there yet as far as artificial general intelligence is concerned? No, they're not. We're not there yet. We will get there. Very soon we will get there. It'll take time. I think maybe less than a decade, I would assume. I think we'll be able to decade maybe or so. Andrew NG believes it's decade and it's at least like 15, 20 years. We don't know how much um, we don't know how much of that will actually translate, which will actually convert into some form of fruition. So again, point is we need to kind of stay abreast with all the developments that are happening in this particular space. When you talk about artificial intelligence, AI is sort of this mothership, right? When anyone or when we generally talk about AI. So this, what you're seeing here, AI is like the mothership, right? AI is the field, as I said, is a field of trying to make machines intelligent, right? Is a field of computer science and engineering, is a combination of computer science and engineering that is trying to make machines intelligent. Now, how is that possible, right? What are the different components of this? Now, AI is, as I said, one of the ways of making machines intelligent, right, is what we've realized is, or rather what the industry has realized over the years, right, over the last, I would say, 70 years. One of the ways of making machines intelligent is by learning from historical data. Why is learning from historical data important? See, when you talk about when you take, for example, some inspiration from how we have become, um, how humans have become intelligent, or rather how you become more and more intelligent is, you, let's say, you intend to learn a particular concept, you pick up a book or you pick up some literature, some form of historical knowledge. Now, this can be book, this can be historical information, this can be some kind of learning that you go through. It can be any form of learning, right? So what you do as an individual is you sort of try and understand a particular concept, learn a particular concept. I don't, let's say, know how to cook. One thing I do is I go down, sit with a teacher, and try and learn how to, let's say, make food, how to cook. Now, this ability to learn is a very, very, very integral part of how one could become a master of that particular skill. What AI tries to do, or how you make machines intelligent through artificial intelligence, is through this subfield of AI, which exactly tries to do this, right? This subfield of artificial intelligence that tries to make machines intelligent is what all of us sort of know as machine learning, right? Machine learning is the subfield of AI which tries to make machines intelligent, right? How do you make machines intelligent? Because machine learning gives you the ability to learn from historical data. You all learned machine learning. You all understand regression. You all have gone through decision trees, all of it. So machine learning is a combination of two things: is a set of algorithms, is a set of techniques that looks at historical data, captures patterns from historical data, and uses those patterns to predict what is likely to happen, right? And this pattern extraction, this can happen at multiple levels, right? This can happen through structured data. This can happen on unstructured data. When I say structured data, I mean, I'm referring to tabular data, right? So you have a table of information. You want to predict, let's say, sales. You have some historical X1, X2, bunch of different variables. You look at this historical variables, and if you try and, let's say, predict sales, this is structured data, right? Why is it structured data? Because it is a nice structured fashion, tabular fashion. You could also extract patterns from unstructured data. What do you mean by unstructured data? Let's say text is a form of unstructured data. Language, if you think of it, is also a form of, it also has a lot of patterns. Why? When you take, for example, an English sentence, there is certain words are often, certain words often come up in a certain context. So if you give a set of words, you can always predict what the next word could be given the set of context, given the set of words that exist. So you could also extract patterns from unstructured data. So machine learning is a subfield of artificial intelligence, which is essentially a bunch of algorithms that you and I have all learned. Regression, decision trees, boosting techniques, and so on and so forth. All of these algorithms are essentially the category of k-means. Exactly. They're all algorithms of this field called machine learning. Now, here is where there is a bit of an overlap with the field of statistics. And I'm going to just draw this here for the moment. There is a bit of an overlap with this particular field of statistics. There's a bit of an overlap with the field of statistics. Now, why is there an overlap with the field of statistics? Now, remember, as I said, machine learning is a form of capturing patterns from historical data. So you need some way, and statistics is a field of math, is a field of mathematics, which tries to understand numbers, which tries to make sense of numbers, which looks at data, which looks at summarizing numeric information. So statistics is a field that existed for a very, very long time. And machine learning sort of took a lot of inspiration initially from statistics. So for example, your regression techniques are actually statistical techniques, so to say. Your regression techniques were all statistical techniques. Your linear regression, logistic regression, your polynomial regression, lasso regression, ridge regression, they're all actually speaking statistical techniques initially. They were all learned from statistics. There's a lot of inspiration that was drawn from statistics. So initially, when like in the early 1900s, PC Malnobis, who was one of the world's most renowned mathematicians, statistician, so to say, kind of proposed this idea of using statistics for the benefit of the industry, and that's where you started to see a lot of industries such as healthcare starting to use statistics for, let's say, conducting clinical trials where they were trying to predict, let's say, a bunch of specific, they're essentially trying to model impact on specific KPIs given, let's say, certain drugs that were often given to a particular subject. So statistics had a massive contribution specifically from the regression lens, so to say. But over the years, what has happened is data got a lot more complex. And unfortunately, these statistical techniques couldn't scale. For that reason, we slowly started shifting away from traditional statistical techniques to a more computer science based algorithms, right? These are more data mining based algorithms. And these are essentially computer science algorithms, right? They're essentially a set of techniques which do pattern recognition through algorithms, through intelligent algorithms, so to say. Again, a more computer science way of doing it. This happened because of two reasons. One, because the complexity of data became larger and larger. You were dealing with a lot more observational data. You were not dealing with, you were dealing with a lot of noise within the data. statistical techniques don't always work very, very well when there's a lot of noise. Um, Observational data, meaning data that was captured from, let's say, behavior, all of that information do not always go very, very well with the assumptions of, um, let's say, statistics. And for that reason, statistical techniques could not scale beyond a certain point. So the volume of data became large, the complexity of data became large, the number of variables you were dealing with started to become very, very large. And for that reason, statistical techniques were all right for a certain period of time. But in the recent past, we have realized that statistical techniques don't always scale beyond a certain level. Hence, machine learning was sort of often the most preferred route. The more computer science based algorithms were more preferred. And what has happened is the modern day regression and logistic regression, linear regression algorithms have also sort of been rewritten, or have also been inspired. They've been sort of inspired from the statistical techniques, and they've sort of been recoded in a more algorithmic way. They've sort of been rewritten in a more computer science, machine learning sort of a way by dropping some assumptions and stuff like that. Again, I don't want to get into too much detail there, but the point is there's a bit of an overlap between the world of statistics over there. Now, so machine learning gave us the ability to capture patterns from data. That was great. All is well. But what happened? Now, just as I said, complexity of data started to become more and more complex. The complexity of the data started to become more and more as time went by. The type of data also started to become more and more complex. What do I mean by that? Thanks to the advent of internet and eventually social media, and also because hardware costs went down, storage costs went down, companies and organizations were able to store a lot more unstructured data as well, right? Not just regular transactional data, right? Most of the data until, let's say, the early 2000s, and 2010, 2000, even actually 2010 to 2000, 2005 to 2010, a lot of the data was primarily about, let's say, banking transactions. These were logs from, let's say, somebody, for billing information, usage information. um, they were purchase invoices related data and stuff like that. But interestingly enough, over the period, what happened was, thanks to internet, thanks to e-commerce businesses, thanks to a lot of the unstructured data that started to get created in the social media out there, a lot of variety of data started to get created, right? Text, tweets, videos, audio, and so on and so forth. And that volume of unstructured data just increased rapidly over the years. Yeah. And for that reason, what we needed to do was, we needed to create a we needed to sort of create a newer way to store all of this information, right? We needed to create a newer way to store all of this information. Now, how did we do that? How did we go about storing all of this information? That's where a new field called big data started to come in, right? So big data, so this field called big data, or this term is not used as much anymore. But big data essentially is an engineering field, is a field of engineering, right? Which was trying to store, which essentially attempts at storing a lot of this large volumes of unstructured and structured data, right? So big data was not necessarily an AI technique or an AI tool. It was an AI technology, so to say. It was just a storage technology and data processing technology. That is what big data was. We don't talk so much about big data. The term big data is a little dead and buried right now, because all data is now big data. It's not a separate space anymore, so to say. So we don't use this term as much these days. But a lot of data engineering related aspects started to sort of come in, right? Concepts like, for example, distributed computing. I'm not sure how many of y'all are aware. There was a concept called Hadoop that was sort of brought in. and a bunch of different techniques sort of started to come in. Now this is bread and butter, right? This is everybody's bread and butter now. Now you don't need to specifically talk about this. A very, very popular technology that helps you these days deal with large volumes of data. Uh, I'm not sure if you all have heard, is Spark. You all must have heard of Spark. Tableau has nothing to do with this, Shyam. Tableau is a different world altogether. We'll come to Tableau later on. But Spark is sort of the tool that that sort of became very, very popular starting from 2014 onwards, um, which was sort of the technology that is even used even today to store, and not just store, but also process large volumes of data. Yes, Apache Spark. Exactly, Apache Spark. Spark is not a replacement for MapReduce. Actually, Spark is inspired from MapReduce. It's a far more efficient implementation of MapReduce, Premchand. Um, but again, it's from the big data world of technologies that sort of came in. As I said, this has Spark. PySpark is a Python variant of Spark. That is what is PySpark. Now, my friends, the reason why I brought this up is because, as I said, there's an overlap with this as well. Why is there an overlap of this with with machine learning? Look, as a data scientist, if you are trying to, let's say, deal with such large volumes of data, and if you're trying to, let's say, build some kind of machine learning models on top of this data, then you need to understand how to access this data, isn't it? I mean, nobody's going to come and hand you the data. Nobody's just going to say, hey, here's the data. Even if they hand you the data, how do you deal with it? So you need newer techniques, or these machine learning models also had to accommodate for these large distributed computing environments as well. Remember one thing. Earlier, models were built by mathematicians. How were they built? Pen and paper. Over the years, as computers came in, there were tools like Excel. There were a bunch of tools where people started to sort of leverage more computers for doing, let's say, traditional the traditional, let's say, statistics, so to say, right? So somewhere here, statisticians started to use computers. Data volume became much larger, right? Machine learning had to accommodate for, and data became much complex, and for that reason, what we had to do was statisticians had to, or rather, also had to accommodate for slightly more complex algorithms. Hence, the machine learning set of techniques started to come in. While the complexity of data increased, the volume of data also started to increase. So machine learning now not only has to accommodate for complex data through complex algorithms, but machine learning also has to now accommodate for large volumes of data. So that's where you have techniques like PySpark that started to come in, or tools like PySpark or Spark started to come in, which was supporting machine learning on large volumes of data. This is where PySpark started to sort of come in. Now, while the volume of data started to increase, along with the volume of data, what also went up was the variety of data, right? And the thing is, techniques like PySpark and all of it, or rather tools like PySpark and all of it, were supporting traditional machine learning with these large volumes of data. But what machine learning now had to also accommodate for is this variety of data. So now machine learning also had to deal with large volumes of text data, image data, and so on and so forth, video, audio, and so on and so forth. Now, here is where machine learning started to, has to start to, needs to sort of start to reinvent itself, because the traditional machine learning techniques were primarily built for structured data. Some form of basic machine learning techniques were good enough to deal with some kind of text data, some kind of image data. You could do some kind of text mining, you could do some kind of image mining using traditional machine learning techniques, but they were not good enough. So what happened over the years is we needed to come up with techniques, machine learning techniques, advanced machine learning techniques that could not only deal with this, but also deal with large volumes of data, but also variety of data. Now, here is where the complexity is. Now, the question is, okay, what's the best way for us to deal with this complexity? If I ask you a question, right? Let's say, by the way, a lot of work sort of went into this, like a lot of research went into this. But if I, let's say, ask you a question, can we create a machine learning algorithm that can understand images like how we do? Not just images, but can we create a machine learning algorithm that acts like a human brain, that is inspired from human brain? Well, the reality is there is. That is exactly what came up. So that is where there was this new subfield of machine learning called as deep learning that was invented. Or deep learning's previous name is referred to as artificial neural networks, ANN, or artificial neural networks. Artificial neural networks, or popularly known as deep learning, is the subfield of machine learning, is an automobile. But this is the automobile that can be used to, let's say, sail across, let's say, a river or a sea. This is the set of machine learning techniques that can help you deal with a lot of unstructured data. This is not like a human, this is inspired from how a human brain works. Meaning, human brain is made up of a lot of neurons, right? And this is exactly the topic that we will discuss. The human brain is made up of a lot of smaller particles or smaller elements referred to as neurons, and these neurons are signal carrying neurons, and these neurons sort of interweave against each other. They are woven against each other, and they sort of transmit signals from one place to another place. They take a piece of information, they perform some kind of a mathematical operation inside the brain, something close to mathematical operation, we don't know what it is. They essentially do signal processing, and then they generate an output. That is the outcome of the research, and that is essentially referred to as a neural network in our brain. What we are trying to create is an artificial neural network, an inspired version of this neural network. And this inspired artificial neural network has helped us significantly to deal with unstructured data. Not just unstructured data, you can also deal with structured data using this. Technically speaking, this can also handle structured data, but it's much better at dealing with unstructured data. People have observed that you can actually do far more with unstructured data using deep learning than what you can with, let's say, your regular machine learning techniques. Now, over the years, this was all nice, hunky dory, everything's nice and great. But what happened is, again, in the process of trying to build, a fairly complex deep learning based algorithms, we have also started to observe that there are some really interesting, and this is also basically an outcome of, let's say, the research within the artificial neural network space. So far, one of the things that we've been able to do very, very well with machine learning is machine learning helps you learn from historical data and extract patterns out of it, and you can use that patterns to predict, right? Deep learning and artificial neural networks are also doing the same thing, but far better on unstructured data in addition to structured data. But there was the subfield of deep learning. There's this subfield of deep learning, which not only learns from historical data, but it actually learns from historical data, but also has the ability to create new information, also has the ability to generate new information, which is inspired from historical data again. right? So imagine I read, let's say, 10 books written by Abdul Kalam. Now, what I can do, or 10 books that's let's say written by some personality. Now, what I could do is I can essentially look at all those 10 books, and then I can actually learn from the writings of, let's say, this particular person, and actually start writing new pieces, which is inspired from the writing of these 10 people. I can actually create new content, right? So this is the field of generative AI. This is the field of artificial intelligence, or subfield of, more specifically, deep learning, that tries to create new content from historical data. Not just understands historical data, but actually tries to create new content from historical data. And that, my friends, is nothing but your generative AI. This is Gen AI. So this field is referred to as Gen AI. So AI is the mothership. Statistics is the supporting arm here. As you can see, statistics continuously plays a supporting arm. Big data continuously, data engineering, or I'm just going to sort of move away from the term big data, and I'm going to call it more specifically data engineering, more generally data engineering plays a supporting role. Statistics plays a supporting role. AI is this field that is trying to leverage all of these subfields and trying to capture historical information, and actually make machines intelligent. Machine learning learns from historical data and extracts patterns. Deep learning learns from historical data of unstructured as well as structured data and extracts patterns. Generative AI does exactly what, let's say, your deep learning does. Generative AI is essentially a subfield of deep learning, that tries to create new content from historical data. It not only does pattern extraction from historical data, but it actually also creates new content. It writes new pieces of content. Exactly. The transformer architecture that we're talking about, that I spoke about a while earlier, is a part of this, is a part of your generative AI set of techniques. Now, the question is, where does data science fit into all of this? Now, where does NLP fit into all of this? See, remember, what is NLP? NLP stands for natural language processing. What is NLP? NLP is something like this. You can think of NLP as NLP that sits here. That is NLP. I'll tell you what NLP is. NLP is sort of a sub field of, again, artificial intelligence. What you're trying to do with natural language processing is you're trying to, let's say, learn language. You're trying to process natural language. What do you mean by processing natural language? Meaning you want to, let's say, you intend to, let's say, um, create new language, let's say, create new, or rather understand language, summarize text. You essentially want to process natural language efficiently. Um, Now, that is essentially what an NLP is. Now, you can do NLP at different levels of complexity. You can do natural language processing using very, very simple linguistic techniques, very simple linguistic techniques. Or you can use deep learning and machine learning techniques to do it, or you can also use generative AI techniques to do it. So the so-called large language models that you talk about come from Gen AI, come from this Gen AI circle. These large language models that you're talking about, the GPT models, they're coming from here as far as NLP is concerned. So NLP sort of cuts across all of this, if you can think of. NLP is a way of efficiently understanding language. And Gen AI has done a phenomenal job of making that very, very good. So you can solve it using generative AI techniques, you can solve it using deep learning techniques, you can solve it using traditional machine learning techniques, or you can solve it without any of these, but that's not going to be that accurate. It's probably going to be very simplistic, super simple, rule-based engines. For example, if you might have heard of, when you deal with deep learning, or when you deal with, let's say, um, when you deal with I don't know if you've heard of dependency parsing and stuff like that. These are all techniques that sort of come from this world, so to say. They have nothing to do with machine learning. They have nothing to do with deep learning. They have nothing to do with generative AI. So an NLP sort of cuts across all of this. I'm just going to remove that circle because it's going to cause a lot of confusion. But that's essentially what NLP is. All right. So 2 to 3 points that I want to talk about. Again, let's talk more macro, right? Let's not go too micro at this point. Let's talk macro, and then we'll get to the more specifics and the micro detail later on. Now the thing is, where does this whole concept of data science come in? Where is data science in all of this? So the thing is, a data scientist, and this is the point that I was talking about, right? What is the field of data science? Now, data science is a bit of a loosely used term these days. People often use the term AI more so than data science. Everybody who's associated with AI says they're an AI. They say that they're working on AI. Now, a data engineer who's probably providing data and doing some form of data engineering also refers to the fact that they're doing AI. So here's where the lines start to get a little blurred. Okay. Now, I'll tell you the more common definition. A data scientist is anyone who does, let's say, any of these, right? A data scientist is definitely working on machine learning, or rather, let me put it this way. Anything that you see here is a data scientist, is data science, right? So a data scientist would be doing any form of machine learning, or might also be doing some form of statistics, right? A data scientist might also be doing, let's say, something like this, right? Might also, and here is where I'm talking about it as might also. So this is essentially reporting Power BI. This circle that you see here is reporting Power BI and stuff like that. Yeah, I mean, not, yeah, if you're doing reporting, that's reporting. This is the reporting circle. Now, a data scientist might also be doing bits and pieces of those, of exploratory. A person might be working on exploratory data analysis. Just because you do visualization, it does not make you a data scientist, right? So, right, just because you do exploratory data analysis or just because you do visualization, you're not a data scientist. But as a data scientist, you might also be working on some of these visualizations. So it's a supporting skill again. So a data scientist is, or when you refer to something as data science, you are definitely working on your primary competence is any form of machine learning. Now, it does not mean you need to know data science, you need to know deep learning, you need to know Gen AI, you need to know all possible complexities of Gen AI. Absolutely no. As a data scientist, you might just be using, let's say, some form of, you might be using some form of machine learning to maybe do some bits and pieces of, let me just shoot this. Yeah, you may be doing some bits and pieces of, of most of it as machine learning and statistics, and you might not even know deep learning and Gen AI, and that's absolutely fine. That's possible. You might not be working on deep learning, you might not be working on Gen AI. So just to give you an idea, my company today has close to around 200 odd data scientists. Of those, only 10 to 15 of us will actually work on Gen AI. Maybe another 15 of them actually work on deep learning. Most others don't even work on deep learning. They all just probably work on traditional machine learning and statistics. And that's fine. And they get paid very, very well, just to let you know. Because there is another very, very important circle that I'm currently missing here, which is of business, right? There is another dimension that I have not spoken about here, which is understanding of domain, understanding of business. You might also need to know what the business is. Like, for example, if I am doing, let's say, I'm solving, let's say, a particular problem in the field of consumer packaged goods, or if I'm in the financial domain, or if I'm in the telecom domain, knowing the domain is very, very critical, because you know then how the patterns are going to come up, how to solve specific problems. How do you solve, let's say, marketing ROI, media ROI? How do you, let's say, solve for, let's say, some logistics related problems in specific industries? These are very, very industry specific problems. How do you build credit in credit models? Meaning, how can I use deep learning to, let's say, build credit models? They are very, very industry specific problems. And for that, having business knowledge is very, very critical. So that I haven't even mentioned here. So that is one of the reasons why, even if people have specific knowledge on machine learning, have only worked on traditional machine learning, still survive, because they have a lot of knowledge on industry. They have domain knowledge. And you will only learn domain knowledge through experience. You need to build it over the years. You need to build it over experience. Whose core skill set is to, let's say, deal with data, to store data, to do to do ETL on top of data. What do I mean by ETL? To extract, transform, load data, to plumb, to move data from point A to point B, from one database to another database, from one data warehouse to another data warehouse. That's a data engineer. You might have a data engineer who's working in collaboration with you to solve a particular problem. See, guys, look, finding someone like this, finding somebody with this skill set, right? This this skill set that you're looking for, somebody who knows almost everything, is an unreasonable expectation to have. By the way, I haven't even put a few other circles over here, but this is a very unreasonable expectation to have. It's very hard to find people who are very good at almost everything. It's just not possible, which is why you need a team. You need a data engineer who can support you. You need maybe at times a visualization expert to support you. You probably will need a data scientist who can manage all of this related stuff. Then once you, let's say, build the machine learning model, you might need somebody who is very good at software engineering, core software engineering, to put the models in production. So it's often a team activity here. So don't be under the assumption that you need to know everything here to become a data scientist. Well, the more you know, the better it is, but don't have this unreasonable expectation to almost know everything, because this space itself is so complex that it cuts across so many. It's a multi-domain, multifunctional sort of a space. AI is a multi-domain, multifunctional space, guys. So don't have this unreasonable expectation from yourself to know almost everything. So what is artificial neural networks, right? So what is ANNs, right? Um, Artificial ANN stands for, as I said, artificial neural networks, right? Artificial neural networks are essentially is a field of machine learning that is specially curated for us to help with dealing with unstructured data initially, but then you could also use that for some of the structured data. But to be more precise, as I said, one of the fundamental challenges that we've had with yeah, with with traditional machine learning was problems started to become more and more complex. Data started to become much larger. So we needed to find newer and more novel techniques um, that can help us solve some of these problems. And that's where uh, research scientists sort of got together, and they kind of came up with this idea of, all right, can we use some kind of some sort of human behavior and um, translate that into some kind of a machine learning algorithm, right? The human brain is an amazing creation. And the idea is, can we take some inspiration from the human brain and create an algorithm that sort of operates like a human brain? So that's where this whole thing stemmed. So very simple way of thinking of artificial neural networks, just the way you have linear regression, logistic regression, decision trees, random forest, all of these algorithms, artificial neural networks are also just another algorithm. It is another family of algorithms. right? Artificial neural networks are just another category or another set of family of algorithms. It's a machine learning model, as simple as that. There are some specialities about this particular machine learning models which gives it a little bit of superpower. I'll tell you some of these capabilities of artificial neural networks. Artificial neural networks can deal with large amounts of data, right? The volume of data that they can deal with, they can actually deal with fairly large amounts of data. In fact, large amounts of data make these algorithms better. Providing more and more amount of data, these algorithms actually get better and better by the day. So that is number one. Number two, artificial neural networks have this fantastic ability to capture, they have this fantastic ability to capture um, large amounts of complexity. They can capture complex patterns. These are patterns that your traditional machine learning models will struggle to handle beyond a certain point. That, now I'm not saying that the other models are, um, the other models are bad. I'm just saying that they can capture fairly complex patterns in this particular case. So artificial neural networks can deal with large volumes of data. Artificial neural networks can actually capture very, very complex patterns that, let's say, a linear regression or a logistic regression or a decision tree-based algorithms can fail to capture. Um, and then artificial neural networks, as I mentioned, they are capable of dealing with both structured and unstructured data sets, right? Artificial neural networks can deal with tabular data, right? As well as they can deal with images, right? Audio, video files, and so on and so forth. They are variants of these artificial neural network models, which could deal with structured as well as unstructured data very, very well. So that's one of the amazing aspects about artificial neural networks. No, structured data or unstructured data, semi-structured is not necessarily um, a pattern of data that we operate with. We eventually convert that semi-structured data either into structured or unstructured eventually. Some of the more advanced versions of these models, right? Some of the more advanced versions of these models, like for example, the generative AI models, can actually even deal with semi-structured data. Like for example, HTML or JSONs, XMLs for that matter. Generative AI models can deal with that data as well. So the older or the more common family of neural network algorithms can deal with structured and unstructured data. Some of the newer variants of these models can deal with semi-structured data as well, like XMLs or JSONs, so on and so forth. Now, while these are some of the advantages of um, or benefits of capabilities of, let's say, artificial neural networks, they also come with certain challenges. What are the challenges? One challenge is training these um training these models can be expensive. What do I mean by expensive? They can be expensive in terms of data. They can be expensive in terms of um, in terms of compute. They can be expensive in terms of time, and so on and so forth, right? And just the sheer complexity of these models also makes it hard for somebody to train these models, right? You require a lot of patience, a lot of time and effort to train these models. So training these models can be very, very expensive. I mean, GPUs is one part of it, Sayud. Compute is one part of it, but because of how complex they are, right? It is very hard for somebody to train these models. You need a level of expertise to train them. The thing is, if you train these models well enough, they can do some fantastic stuff if you train them well enough. But if you don't train them well enough, they could fall flat. These models can start misbehaving, or they can actually, perform even worse than, let's say, your traditional machine learning models, like a tree-based algorithms, or so to say. So training these models is very, very important, and training is going to be an expensive affair, so to say. Um, the second challenge with these models is some of the more modern day models are they are also, as I said, training can be expensive. Just the way for some of these modern day models, volume of data has also become a challenge, right? Meaning you need more volume of data. And let me actually put it this way. Um, I think the more appropriate way of writing it is unavailability of training data, right? Unavailability of training data has also become a challenge. Um, So somebody is talking about expensive in terms of lack of labeled data. So Neil Kamal, you are right. So unavailability of training data. I mean, at times when you need to train a certain model, you need data sets in a specific fashion. Unavailability of those data sets is also often a challenge in the modern context. So that sort of has also become a bit of a, I would not say a roadblock, but I would say that is definitely one of the minor challenges that people are often facing these days as far as these models are concerned. So these are a couple of key points to bear in mind. Now, as I said, an artificial neural network model is very much like any other machine learning model. Through artificial neural networks, you could also address a couple of, you could solve both supervised as well as unsupervised learning problems. Most of the applications that you would see with artificial neural networks are supervised learning applications, meaning you're solving a regression problem or a classification problem. There are also applications where you could use, let's say, an artificial neural network model to solve unsupervised learning problems as well, like a clustering, or let's say not necessarily clustering. There is a concept called as autoencoders, which we will learn. It's very much like PCA. You all must have done PCA, principal component analysis, which is basically an unstructured data problem, unstructured model, so to say. You could solve for an unsupervised learning problem. Similarly, in the case of artificial neural networks as well, you could solve for unsupervised learning as well. So point is, you could solve for both supervised as well as unsupervised learning problems. Specifically in the context of supervised learning, the two categories of problems like we typically solve for a typical classification or a regression problems are definitely possible. So as I said, this is no different from a um, regular regular machine learning model. You could solve for both supervised as well as an unsupervised learning problem. Within supervised, you can solve for classification and regression. And as I said, artificial neural networks are fairly capable when it comes to dealing with large amounts of data. They can capture very, very complex patterns within the data. They can deal with structured as well as unstructured data. On the other hand, training these models could be a bit of expensive affair because you might require a certain level of expertise to train these models, just the sheer complexity. So these are like, think of getting a futuristic automobile in your hand, right? Uh, to ride it or to drive it, you need a certain level of understanding, certain level of expertise, right? The more and more complex a certain machine starts getting, you start to see more and more buttons around you. And that's where things become very difficult, right? So you might be, let's say, driving a simple Maruti 800, which is a very simple, stick transmission, manual transmission car. Now imagine going and sitting inside, let's say, a cockpit of an airplane. That's the complexity that I'm referring to. There are too many knobs, too many controls. You need to be aware of which knob to use when. That's the kind of complexity we're talking about. So there's complexity in terms of a developer, meaning as a data scientist, you need to know what to change, how to change, when to change, so that you can get the best possible model. So training the model can be a bit of a complex affair, requires large amounts of compute, because they could take longer to train. And then, as I said, some of the modern day challenges are about unavailability of data, of training data itself. Quality training data is hard to find beyond a certain point, especially in certain business contexts. And for that reason, artificial neural networks could be slightly harder to train, as well. That said, with all the benefits and the complexities that you're dealing with, you can solve both supervised as well as unsupervised learning problems, be it classification or regression problems, or any of your traditional unsupervised learning problems can also be addressed using, let's say, artificial neural networks. Uh, as I mentioned, semi-structured data can be dealt with. Some of the more advanced versions of these artificial neural network models do deal with semi-structured data like a JSON or the others. So a human brain typically is made up of these, and I'm by no means a neuroscientist or a neurologist, so to say, to talk about. I don't have expertise in that particular area, but one thing that I know, and enough amount of information that I know, is a human brain is typically made up of these smaller particles or atomic particles referred to as neurons, right? Biological neurons. Now, these biological neurons are, and I'm going to simplify it for our understanding, um, or for my understanding, because as I said, I am no expert in this particular area, but a neuron sort of looks like this, right? Um, they're not atomic scale for sure. I agree with you on that. But when I say atomic, I'm using the word loosely in the sense that there are sort of the smaller aspects of your human brain, the smaller particles inside a human brain. They're not atomic in the size, though. Um, so if you look at, let's say, a neuron, a typical neuron sort of looks like this, right? A neuron is a signal carrying entity within a human brain. What a neuron does is, and just for our simplicity here, a neuron, these particles that you see, or these sort of finger-like structures that you see here, are essentially are referred to as dendrites, and these dendrites operate as signal receptors. They are responsible for capturing signal from, let's say, either uh, an interface, which is, let's say, passing actual data or actual information, or they could also be capturing this particular information from another neuron, from the output of a particular neuron, right? And these inputs sort of travel through the neuron, and these and these inputs are essentially, as I said, in the human brain, these are basically small pulses, signals, typically to the extent of 0.55 volts. And these pulses often traverse through the human brain. And these pulses are combined in a very interesting fashion, right? There's some kind of interesting combination that happens inside this. Now, we don't know what kind of exact signal processing happens inside the brain, but there is some kind of a signal processing that happens inside this. And once the signal is sort of processed, the output is sort of then passed out through the axon. The axon is the stem. And then you have a synapse, which is essentially like and this part is referred to as the synapse. The synapse is basically where one neuron connects to the dendrite of, let's say, another neuron in this particular case. Now, there is some kind of signal processing that happens here. There is there are a lot of things at play here. As you can see, there is a cell inside this. So the moment you talk about cells, you're talking about um, uh, a lot of biological activity that happens inside it, which is hard for, let's say, any of us to understand. But the point is that if you take, for example, an individual neuron, you take any of these individual neurons, this is essentially what happens inside this neuron. Now, scientists took a lot of inspiration from this, right? Scientists said, this is great, right? Let's try, and what they've done is they've sort of created a mathematical parallel to this particular world, to whatever we are seeing here. What have they created? What they've done is this. So if we were to mathematically approximate this behavior, then what we are saying is you have a certain set of inputs, right? You have a certain set of inputs. And these inputs look like this. And these inputs can be certain number. Now, it depends on how many inputs they are. There could be many inputs. And these inputs are x1, x2, x, and so on up till xn. There could be many inputs. Exactly, these inputs are like your dendrites. And these inputs are sort of being passed into a cell body, right? These inputs are sort of being passed into the cell body that you see here. And what this cell body does is it takes these inputs and performs some kind of a mathematical operation. Now, why mathematical operation? Because math is how you and I can process signals. We don't necessarily do all the kind of signal processing. Let's say a biological cell would do. So for that reason, the simplest way for us to assume how the signal could be processed is through some kind of a mathematical function. And then what happens as an outcome is you process these signals and then you generate a certain output from here, right? And this output is essentially, let's say, an output Y in this case, right? So there are a few inputs that are going in, x1, x2, all the way up until xn. There could be many inputs, as you can see here. And this inputs are essentially being processed through a function, and then there is an output that is being generated in this particular case. As simple as that. So if you look at it, this is sort of like your dendrites. These inputs are like your dendrites. This, in this particular case, is the cell body. And this is how your output is sort of passed to, let's say, another neuron or to, let's say, any other interface. There is an output that is getting generated over here. So this is your input, cell body, and the output, so to say. So you could approximate whatever you're seeing here through a very, very simple graphical representation like what you see on the right side. Now, what you're saying is this is on the left side referred to as a neuron. This is an artificial neuron. What you're seeing on the right side is an artificial neuron, or simply referred to as a perceptron. A more commonly used term to refer to an artificial neuron is a perceptron. There is a bit of There's a little more to this whole concept of a perceptron than what I mentioned. The name perceptron comes from a slightly different place, but that's okay. I think it's not really required for us to go into that much detail at this point. But simply put, what you're saying is everything on the left is a biological neuron. What you're seeing on the right is an approximation of the biological neuron in our mathematical world. And what you're seeing on the right side is referred to as an artificial neuron, or simply referred to as a perceptron. On the left side, when you look at the biological neuron, now this neuron that you see on the left side, this neuron is not everything in the human brain, right? Our human brain is a neural network, is made up of a neural network. What do you mean by a neural network? A neural network is essentially Let me show you a small image of that. What is it about this neural network? So what you see here is it's not just about one neuron. It is a combination of many neurons that are sort of working together to take one particular input and then process all of that input, pass it from one neuron to another neuron. Every neuron, as you can see, is connected to a very, very complex arrangement of other neurons, which is very hard for us to understand. And all these neurons sort of, it's like an orchestra, right? So there are a lot of neurons. There are a few million neurons in your human brain at any point in time. And all of these neurons are sort of working together at any point in time um, to process any given input and generate a certain output, right? If you think of it, at in general, there are close to 135 billion neurons in your human brain. The brain and spinal cord together contain approximately around the 120 billion neurons, and the peripheral nervous system, which is essentially all your other the nervous system around your human brain, they sort of have approximately around 15 billion neurons, so to say. So broadly, you can think of around 135 billion neurons that your human brain is typically operating with. So this is not one neuron. What we're looking at here, my friends, is one neuron. And your human brain has 120 billion, 135 billion neurons sort of tied together, where the output of one neuron is sort of going in as an input into another neuron, then its output is going into another neuron, then that output is going into another neuron, and so on and so forth. So all these neurons, they sort of are interwoven, they're all connected to each other. And then what they're trying to do is they're trying to sort of, given any input, they're trying to, let's say, generate a specific response. Now, what are these inputs and outputs that we are talking about? Now, these neurons, as I said, 135 billion neurons. What are these neurons sort of perceiving at any point in time? Let me talk about that. So, and I'm going to draw a very, very simplistic imagery of that. So let's say you're walking on a road, right? Right? You are walking on a road and you suddenly spot a friend of yours, right? There's another person, you suddenly spot a friend of yours. Now, what you've essentially done is you spotted a person before, by the time you see the person and realize that this person is somebody that you know, your brain has already processed that information and generated an output which tells the name of this particular person and all the information that is required about this person. Does that make sense? Your brain is the one that's processing this information. It has some of this information stored in a certain fashion, and your brain is sort of capturing the signal of this particular person, right? So if you think of this, your eyes have captured this photograph, right? Your eyes have captured this particular photograph. I'm showing it in 2 dimensions, but technically a 3-dimensional photograph. So this photograph that you see here is passed as some kind of data into your brain. So your eye is perceiving this particular imagery that you see here. When I say perceiving, meaning it is capturing that information that's out there. Your eye is then sort of passing this as some kind of a signal, right? It is passing this as some kind of a signal to your human brain. And what's then happening is this signal that you have over here is passed to one of the neurons, right? Is then sort of passed to one of the neurons that you have here. And that neuron is sort of receiving this as an input. This neuron, maybe it could be one neuron, it could be many neurons. There could possibly be an interface over here. And what your human brain is sort of doing is it is taking this image, passing it to maybe one or a bunch of neurons. And then these neurons are processing that particular input like what you see here. And at the end, they are kind of generating multiple outputs, right? One is telling the name of this particular person. The other is telling the location of where you probably have met this particular person. The third is probably telling the age of this particular person. The fourth is probably telling you, is this particular person a male or a female, and so on and so forth. Probably giving you a bunch of different informations of this particular person. So the moment you spot someone, your eyes have captured the image has gone into your brain. Your brain, when I say it's gone into the brain, what's happening is, and I'm oversimplifying this for the discussion over here. There's a lot that happens in between. But the point is, your neural network receives this as an input. Your neural network receives this as an input. And this signal is then processed by this neural network. Individually, in each neuron, we are taking these as inputs, and each of these neurons is sort of processing that particular signal, generating an output, and then passing it on to the next neuron. So each neuron is processing this information. One neuron is probably trying to capture the height of the person. One is trying to capture because to identify a particular person, you need a combination of multiple things. To identify my friend, I need to know the height of the person. I need to know the weight of the person. I need to know the color of the hair, the color of the skin tone. I probably will have to capture a bunch of different information and then come up with a certain output. So the point that I'm trying to get at is every neuron is helping you solve a lot of these small different problems. And then at the end, all of these are being combined to generate maybe the name of the person as the output, or the location where you met this particular person as an output, and so on and so forth. Multiple outputs are getting generated about that particular person. Now, as I said, if you take, for example, this perceptron that you see here. Now, the thing about this perceptron is, if you think of it, what is it doing? As I said, there are a bunch of inputs that are coming in. There is some kind of mathematical operation that's happening here, and an output is getting generated. So just to sort of keep the complexity slightly on the lower end, and just to kind of ensure that um, we don't overcomplicate it, for the moment, let's just assume this function to sort of be a very simple summation. All that you're doing is you're essentially summing up a certain input. So you have inputs that you're receiving, right? For the moment, let's just assume that these are, let's say you receive certain number of inputs. There is a cell here, and all that you're doing here is you are simply summing up these inputs, x1, x2, all the way up until xn, and then you're generating an output y. Now, the thing is, if you think, for example, any of these neurons, right? If you think, for example, any of these neurons that you see here, oops, and any of these neurons over here. So imagine this interface where your human brain is passing a signal. If there are, let's say, this input is being passed to more than one neuron, here, what's happening is, and if you were to sort of mathematically write this, your y is what? If you were to mathematically write it, this is x1 plus x2 plus x3 plus so on and so forth, all the way up until xn. This is essentially the mathematical operation. Now, if there are more than one neuron that is getting the same signal, if there is more than one neuron that is getting the same signal, and if every neuron is summing up the same way, then every neuron is processing it the same way. Then what's the whole point? If every neuron is processing it the same way, then are you going to get different results? Meaning, if let's say you want every neuron to, let's say, give you different information, then the problem is every neuron will sum up the same value, every neuron will have the same value. What's the whole point of having so many neurons as such complex neural network? So you need to somehow mix it up a little. You need to somehow not get it to just add things like that, right? Just straight away add things like that, which is where we introduce another small parameter called as weights, right? Instead of taking a simple summation, we do a weighted summation. You have an output, and this output that we're saying is getting generated by some kind of a weighted sum of the inputs that you have received. So y is, our output is w1x1 plus w2x2 plus w3x3 plus and so on up to wnxn. Now, what does this look like? This looks like a very simple linear equation, let alone a linear equation. Don't you think this is like a linear regression equation? I mean, all that is missing over here is some kind of a constant term. For the moment, let's just assume that this constant term is zero. For the moment, let's just assume that this constant term is zero. What you have is this, and this is nothing but a simple linear regression equation. This is nothing but linear regression. So what does it tell you? What it tells you is a neuron or a perceptron is nothing but a regression equation. Is regression, is graphically represented regression. That's it, nothing else. It's a regression model. Exactly. So each neuron or each perceptron is like a regression model. It's a small machine learning model. Every neuron is making a certain decision. So a perceptron is a small decision-making entity. A perceptron is like linear regression. So I'll just repeat this for a moment. This is a very, very important aspect for you all to understand. A perceptron here is taking a bunch of inputs, is combining those inputs and generating an output. How is it taking those inputs and combining them? We are saying if it just keeps adding them up, then every neuron will have the same output. That doesn't solve the problem, because if every neuron has the same output, then every neuron is processing it the same way. So there's no real insight that you are going to generate out of this. So you add it slightly differently, right? So you add it through some kind of weights. So you've put some weights over here, and these weights can be just some numbers, some real numbers over here. It can be some bunch of real numbers. So your inputs, weights as in, okay, yeah, weights as in weights. Weights are like, think of them as coefficients, right? Like in the case of your linear regression. So the point is, when you actually write that equation down, these equations, this equation looks very, very similar to that of a linear regression equation. So the point is, a perceptron is simply nothing but a regression equation, is a very simple regression equation. So what that means to us is a perceptron is no different from a simple machine learning model. A neuron in your brain is no different from the approximation that we have come to is a perceptron is no different from that of a simple machine learning model. That's the takeaway that I want you guys to have. Of course, the biological neurons are way more complex. I mean, neither I nor you, maybe you are an expert. I'm definitely not an expert in this space. What I'm trying to get at is the way I want you to, which is why I'm commenting about a perceptron. I'm not talking about the biological neuron. I am not an expert there. None of us are. Perceptrons are an approximation of how a neuron works. So a perceptron is sort of a very small decision-making entity, a small machine learning model. In this case, a simple linear regression with multiple inputs. In some way, given a certain set of inputs, this perceptron can predict a certain output. For example, it can take the height of the person, the weight of the person, and maybe the color of the hair as an input, and it can predict maybe the name of that particular person, or it can predict maybe maybe the brand of perfume that this person that this particular person is putting on himself or herself, for that matter. It's a simple machine learning model. Theoretically, heuristically, this is what, or intuitively, this is essentially what I'm trying to talk about. Now we will get to the actual detail, like how does this perceptron actually work? Now, let's take this perceptron. Let's build on this. So fundamentally, all of us agree to the fact that given a particular set of inputs, a perceptron takes those inputs, applies a very simple function, and generates an output. Now, the things that we can work with is this function. There are some of these weights, and then there is the input data, of course. We'll take a very simple example, right? And then we'll try to build on top of it. In the case of a perceptron, you also have not just in the case of perceptron, just like how you have in the case of a regression model, you also have bias. Bias is simply nothing but a coefficient. Oh, sorry, a constant. These weights are nothing but your coefficients. And this bias, this is referred to as bias. This is nothing but your intercept term. Intercept or constant. That's what it is. So you also have this bias term over here, C or B, whatever you refer to it as. Now let's try and actually see how these weights are actually computed on the ground, right? Let's take a very simple example. We'll try to see how some of these weights and biases are actually computed. So for this, I'll take a simple example and then we'll try and solve for this. I'm trying to pull up a small example. Just give me a second. So let's take this data. So imagine for a moment, you have one variable and then you have y. Now, the thing is, the point that I want to get at is, look, so you look at the weights here, right? So the weight W1, W2, W3. Now, as I said, these weights are like linear regression coefficients. Now, what is this whole concept of these weights? These weights simply are nothing but they are the perceptron's way of combining the inputs in a specific fashion to generate the output. So the perceptron, through its knowledge, knows that it will have to combine these specific inputs in certain specific amounts to generate an output. What do I mean by that? See, here's the thing. So imagine you are, let's say, building a regression model where you need to predict for, let's say, the sales of a given store, right? So let's say you're trying to predict for the sales of a given store, and then you have a lot of data that helps you do this. So you have number of let's say number of or the money that you spent on ads, and then you have, let's say, number of competitors in that particular locality, and let's say you have let's say raw material prices, and so on and so forth. And then you're trying to predict the sales of a particular store. Now, historically, for whatever may be the reason, you have captured this data over a period of time, right? So you have captured, hey, if my money spent on ads is, let's say, 20 or rather $20 million. And if I have 5 competitors in a particular, or rather $200,000, and if I have 5 competitors in a particular locality, the raw material prices are, let's say, $300 for whatever the thing, and my sales could be $20 million in a particular year. And you've captured this data, let's say, across a bunch of different stores. These stores could be, let's say, stores, Starbucks stores or whatever. You would like to predict on any given day, if you have this information, what would be my sales? A classic machine learning problem, a classic supervised learning regression problem, right? If you went earlier, you would have said, okay, this is X1, this is X2, this is X3, and this is Y. So these are my independent features, and this is my dependent variable. Let me do the pre-processing. Let me put it into a machine learning model. Let me generate an output. That is what you would have done. We'll try and paint the flavor of a perceptron to this. How would this look like in the case of a perceptron? In the case of a perceptron, again, it's the same X1, X2, X3, and then you have a output Y. So you have X1, X2, X3, three inputs coming in. You have a certain summation that's happening over here, and you're generating a Y. This X1 is money spent on ads. This is number of competitors. This is the raw material prices. And this is the sales data, right? And what you're saying is you would want to sum them up in a specific fashion. You would want to sum them up in a specific fashion. So your equation would sort of turn out to be y hat is equal to W1 times X1 plus W2 times X2 plus W3 times X3, where X1 is money spent on ads, X2 is number of competitors that you have, and X3 is the raw material prices, or so on and so forth. This is how this equation will turn out to be. This is, by the way, also your, if you think of it, this is your quote unquote multiple linear regression equation. Do you understand the similarity between how you would have solved earlier versus what I mean by a perceptron? The same thing, but I've just structured it differently, but it's the same problem, same exact problem that you were solving for earlier as well. This is a perceptron. These are your dendrites. This is your cell body. This is your output. Right? These are the dendrites, your cell body, and the output. Same exact thing. Input, your perceptron, and then the output. Now the question is, how do we get the weights? Now, before we get to the weights itself, the W1, W2, W3, I want to just spend a little bit of time here on a small concept. So what you're saying, if all of us agree on this particular equation, what you're saying is, if on any given day, let's make a small assumption. If on any given day, let's say the money spent on ads is zero, meaning you're not doing any advertising, and there are no competitors, and let's say the raw material prices is zero, then you're saying your sales is zero. Does that make sense? That does not make sense, because I cannot guarantee that all of my sales are only dependent on these three variables. There may be other variables which I may not have captured in this data set and in this model that might still contribute to some kind of sales. I might not have done any marketing campaigns this year, but I might have done something last year. I might not have spent on holdings this year. I may have spent on some holdings last year. I might not have any competitors here, which is great for me, because in that particular area, of course, there might be there might still be some business that's running. No competitors does not mean no business. And raw material prices in this case are zero, maybe because last year we overpurchased. The point that I'm trying to get at is, just because these are zeros, I cannot guarantee that my sales will become zero. Maybe I will still have some sales. So when I'm creating this model, I just cannot simply say that, okay, if all of these three are zeros, then Y will also be zero. There may be other things that are still contributing to these sales, which I will have to also assume. And that is where we put the bias B. There is an inherent bias in my data. There is an inherent bias in my data, which is not captured by these existing features. If I am able to list down, if I am able to list down all the possible features that could potentially impact my sales, then I don't need the bias. In fact, my bias will automatically become zero in that case. But there might be certain variables in the data which I may not have captured. And for that, I need to address the bias as well. I need to take bias into consideration as well. Now, specifically in this particular case, right? So what we're going to be doing right now is we'll spend a bit of time trying to understand um, how one could actually compute these weights. Now, so let's take, for example, let's say I have X and we have Y. The values of X and Y, and X could, let's say, be the sales, and Y you're sort of trying to predict the stock price. It could be something like that. So X is, let's say, 1, the value is 2, 2, 3, 4, 7, 5, 5, 7, and 11. Let's say that's your data set. This is your historical data. And now the task at hand is for the task at hand is for us to be able to use this historical data to predict for to train this particular model. So the model here, or the perceptron that we are referring to in this particular case is, hey, look, you have one input X, and then you have bias over here, and there is a weight W, and then you're generating a Y. So given a particular input X, you're going to combine that particular weight with that input X with the weight W, and then you have a bias B over here. Then you're generating the output Y. So if you sort of think about it, your predicted value of Y is nothing but W times X plus B. This B is bias. This W is weight. X and Y are data that you already know. This is the X and Y, the historical data. So the variables that you need to predict here are, you need to predict for W and you need to predict for B. Fantastic. So let's try and see how one could do it. Now, if you were to sort of go ahead and populate this particular information, and something that you all are very, very familiar with is, when you build a model like this, you would always try to minimize the error as much as possible, right? You would always want to find a line that is as close as possible to the existing data, right? So let me just plot this data in Excel so that you all know what I'm referring to. So there is X and there is Y, right? The value of X is 1, 2, 2, 3, 4, 7, 5, 5, 7, and 11. These are the data points that you're talking about. And if I simply plot this, insert a chart, a scatter plot, this is how your data looks like. All right. This is the chart. So you have X here, X axis titles. This is X, and this is Y. So what we're trying to get at is we're trying to plot this line. We are trying to find a line over here, and I'm going to plot that particular line here that is as close as possible to all of these data points. So that line in pink or magenta that you see over there is what we are trying to come up with. This equation y is equal to w times x plus b is going to essentially talk about this particular line. Different values of w and different values of b will ideally give us different orientations of this line, right? If the bias is 0, then this line would sort of cut through the x-axis. So it cut through the origin that you see over here, because the coefficient in that particular case is going to be 0. On the other hand, if let's say the w is negative, then the line would sort of go like that. It would sort of give you a slightly different orientation of this particular line. So we need to find the best possible value of w and b such that the difference between the actual value and the predicted value is as low as possible, right? We need to find, so this is essentially going to be the problem, find best values for w and b such that the error is as low as possible. Ideally 0, but as low as possible. Right? Now, what do you mean by error here? So the error is simply nothing but, as I said, if you take, for example, this particular value, when x is 4, the predicted value is supposed to be 7. The actual value is supposed to be 7. But let's say in this particular line, the line is predicting 5 point something. So there is a difference between both of these. Do you agree with this, everyone? So there is a certain error over here. The idea is that this error should be as low as possible. And for that, we use something called as ordinary least square. So all that we're saying is, hey, look, or mean squared error or sum of squared error, which is nothing but 1 by n into summation of predicted value minus the actual value, the whole square. I is equal to 1 to n, where n is the total number of data points that you have. We are saying this error has to be as low as possible. Now let's go one step further. So let's actually try and expand on this particular mean squared error. This mean squared error can be rewritten as summation of I is equal to 1 to n. This predicted value is what? W times x plus b. W times x plus b minus the actual value of y, the whole square. So we are saying that this has to be as low as possible. Now, this w and b is what we don't know. We need to find the values of w and b. So now let's actually, for every data point, let's expand this particular equation out. For every data point here that you see, let's actually expand this particular equation out. So if you take, for example, the first data point, y is 2 and x is 1. So this will become w times x is 1 plus b minus what is y? 2, the whole square, plus data point 2. X is 2, y is 3. So this is going to be 2w plus b minus 3, the whole square, plus 4w plus b minus 7, the whole square, plus 5w plus b minus 5, the whole square, plus there's one more, 7w plus b minus 11, the whole square. Now, all that we need to do is we just have to solve for this. So if you actually expand this, we're saying we need to find the minimum value of this particular equation. And of course, there's a divided by n, 1 by n, for sure. Yes, I agree with you on that. We need to find the minimum value of this particular equation. Now, if here is where we will introduce a little bit of mathematics. Now, the thing is, if you go back to your 10th grade, 9th grade maths, one of the things we would have learned is if you have any equation and you intend to find the minimum most value of that particular equation, essentially, you would go about differentiating that particular equation and equating it to a zero. And this stems from a very simple concept, and this stems from, and I'm going to just step aside for a second for a sidebar just to explain to you what I mean by this. If you take, for example, any equation, let's take, for example, a simple parabola y is equal to, and I'm taking a second degree polynomial here, 3x squared plus 2x plus 1, 2x squared plus 3x plus 1. If you take, for example, an equation like this is a simple parabola. Looks slightly different, but I'm just making it up for the moment. So this is y, this is x, right? For different values of x, you have the y. This equation sort of represents a parabola. Now the thing about an equation like this, and of course this equation, different equations will look very different, right? In this case, it's a parabola. In another case, it could be a polynomial that looks like this. Different curves, so to say, how x and y could vary. In this scenario, and I'm taking parabola as one of the examples, right? You can essentially take any example that you want. Now, this curve has a minima here. What do you mean by a minima? The minimum most value of this particular curve is at this point. What is the most peculiar thing about this particular point? What is the most peculiar thing? So this point is where the curve sort of changes its direction. Right? The curve sort of changes its direction. So it would have earlier. So if you go from left to right, as y was increasing, so if you take, for example, this part of the curve, as y was increasing, x was reducing. Or rather, as x was increasing, your y was reducing. Actually, that's a more appropriate way to put it. On the left half of this particular curve, as x was increasing, meaning as you went from left to right, as x was increasing, y was reducing. But on the right side, as x was increasing, y was also increasing because the curve was sort of taking this direction. All of us agree with this? So in a way, the curve sort of changed its behavior exactly at this particular point. Now, and I'm going to take a little bit of liberty to sort of explain some of these concepts because there's if you keep digging, there's a lot more under the hoods. So I don't want to turn this into a high school math session. But the point is, what you could do, and the point of x increasing and y reducing. So as x kept increasing, y was reducing. As x kept increasing, y was also increasing. This is simply denoted by this idea of slope. What is slope? Slope often denoted how much. The idea of slope often denoted, or gradient is the other name to it, often denoted, both mean one and the same, often denoted how much or the rate of change of x with respect to y, or rate of change of y, sorry, with respect to x. How much would y change as x changes, right? And this y and x over here are arbitrary. Y can be, let's say, speed, x can be time. As time increases, how much is distance changing, rate of change of speed with respect to rate of change of distance with respect to speed, with respect to time is speed. So something like that. So in a way, it denoted delta y by delta x, change in y with respect to change in x. So if you take any 2 points in this particular curve, if you take any 2 points in this particular curve, or if you, especially in the case of a straight line, if you take any 2 points, a slope is simply nothing but delta y by delta x, which is nothing but this would have a certain data point, this would have a data point. So y2 minus y1 by x2 minus x1 is how you would simply compute to figure out if is y increasing as x is increasing or not, and so on and so forth. That's the concept of slope. So ideally, if a curve is like this, your slope is generally positive. Or if the curve sort of looks like this is x and this is y, in this case, the slope is negative because as x is increasing, y is reducing. That's basically the intuition behind all of this. Now, the thing is, in a setup like this, especially when you have a curve, taking 2 points like this makes no sense because the rate of change is not linear. What do I mean by that? So imagine if I have a straight line between these 2 points, the difference is linear. Whatever may be the difference here is the same difference here. So the rate of change between any 2 points is typically going to be the same. Across any two sets of points is always going to be the same. But in the case of, let's say, a curve, that's not the case. In the case of a curve, the rate of change at one particular point, let's say I have a curve like this, the rate of change at between these 2 points by itself is non-linear. You see this? Because the curve here itself has a non-linear behavior. So I just cannot simply take the two coordinates over here, x2, x1, y1 and x2, y2 and simply compute it like the way we did. That would not be an appropriate representation of that particular slope. So especially when you're dealing with slopes in the context of a curve, you often consider it as an instantaneous slope. What do you mean by instantaneous slope? Like, for example, if you take this curve and if you zoom in quite a bit, then what we are saying is, there is this part, infinitesimally speaking, I can consider that portion as linear. Overall, it might be non-linear, but if you actually zoom in quite a bit, then what you're saying is infinitesimally, this could be linear, and you could still compute it the way we did earlier. Though the curve might be non-linear, but if you kind of zoom in quite a bit, and if you sort of look at it at that particular point, it could be linear. That for that very, 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 very small point. So exactly, you're approximating for that particular slope. So that kind of computing of the slope is referred to as an instantaneous slope. Now, this is where the beauty of calculus comes in, right? This is what calculus helps you. Differential calculus and integral calculus help you accomplish such kind of behaviors which are so small. Instantaneous behaviors can be captured through the help of calculus. So what you instead do, and this is where what people often do, is they say, you know what, if I can compute the rate of change of the curve at that particular point, right? If I were to compute, so and one of the ways to compute in the case of, let's say, any of these curves is at that point, you simply draw a tangent, right? At that point, you draw a tangent, meaning you simply draw a line, and then you compute the slope of that particular line. That's how you can compute for the slope of a curve at any given point in time. Now, I don't want to get into too much detail here, but the point that I'm trying to drive home is we intend to compute the slope of the curve at that particular point. So from left to right, one thing is very clear. The slope here is negative. The slope here is positive. So from here to here, somewhere, the slope has become 0. And the thing about this point is that point also happens to be the minima because the curve is changing its direction. And the beauty of that particular point is that point is also a minima or a lower point in this particular curve. In this context, it is the lowest point. So if I am able to compute the slope of this particular curve, if I'm able to compute the point where the slope is 0, then I would have found the minima, right? So that is where we take this particular equation and we say, hey, let's differentiate this particular equation. This is simply nothing but delta y by delta x. In differential calculus, because we're doing it at an infinitesimal fashion, we're sort of doing it at that microscopic fashion, which is why we refer to it as dy by dx. So you would differentiate this particular equation, and this differentiated equation sort of then becomes 4x plus 3. For those of you who are familiar with differential calculus, you would know that you would take an equation like this and you would simply differentiate that to 4x plus 3, right? So this becomes 4x plus 3. And this 4x plus 3, what does it refer to? This says this is how your slope is changing. This is the equation of the slope. So the thing is, this slope is equal to 0. Why is it equal to 0? Because at this point, the slope is 0. The reason why, okay, so from 2x squared plus 3x plus 1. So y is equal to 2x squared plus 3x plus 1. So if you take dy by dx, which is nothing but differentiating y with respect to x, what you're doing is you are differentiating each of these x's. X square can be differentiated as 2 into 2x to the power of 1. So you bring the, so rather dy by dx of x raised to the power of a is equal to a x to the power of a minus 1. That's how you get there. Okay. That's sort of one of the formula. I mean, we can get into the detail later, but that's essentially the formula. So 2x square is 2 into 2x to the power of 1 plus 3x will become 3 into x to the power of 1 minus 1, because this 1 will become 0. And plus the 1 is a constant. When you differentiate a constant, that becomes 0 because a constant doesn't have a differentiation. So, I mean, there's no slope for a constant. My point is, again, when you come back here, this 4x plus 3 is now how the equation sort of changes. So that's how the slope changes. But the interesting thing is, this particular point where the slope is 0 is where I am interested in. So 4x plus 3 equal to 0. So x is equal to minus 3 by 4. So when x is minus 3 by 4 is when this equation is at its lowest. So when is x is minus 3 by 4? That's when this equation is at its lowest, right? Then you take this and you substitute it back here, you will exactly get what the value of y is. I mean, exactly what this particular value of y is. So if you take minus 3 by 4 and if you put it back here, you will tell exactly what the value of y is. But we don't care what the value of y is. What I'm interested in is what is the minimum most point of this particular equation. Similarly, guys, if you come back here, you got this long equation. You can, of course, try and simplify this equation. But the point that I'm trying to get at is you have an equation which says, hey, your MSE is some kind of a second degree polynomial of W and B, right? And you need to minimize this particular equation. So when is it a minima? And remember here, I just don't have one variable. I have two variables, W and B. That's where you do something called as partial differentiation. Partial differentiation is dou MSE by dou W equal to 0. And then you do dou MSE by dou B equal to 0. So you essentially will have to differentiate this equation 2 times, one with respect to W. And when you're differentiating with respect to W, you consider B as a constant. And you differentiate with respect to B and you consider W a constant. You differentiate these two equations, you'll get two first degree polynomials. And then you solve both of those equations, you'll get W and B. So I'm going to expand. I'm going to just do this 1 by n. You can forget the 1 by n actually, but if you take, for example, this part with respect to W, so 2 times W plus B minus 2 multiplied by 1, because you need to differentiate W here. I'm using the chain rule here, plus 2 times 2W plus B minus 3 multiplied by 2, because 2W when you differentiate becomes 2, and B and minus 3 will become zeros respectively, plus 2 times 4W plus B minus 7 multiplied by 4, plus 2 times 5W plus B minus 5 multiplied by 5, plus 2 times 7W plus B minus 11 multiplied by 7. That's what this sort of translates to. And all of these, and I need to equate this to 0, right? I'm essentially solving for this one. This n can also go away because the n can go to the other side. All the 2's will get cancelled here because the 2's can be sort of taken common. So I'll be left with W plus B. So there's 1W here, 4W. So 2 is 4. So 4 plus 1, 5. 5 plus 4, 5 plus 16. This is 21W. 21 plus 25W, which is 46W. 46 plus 49W. So 95W is what you will have here. Plus or minus, I'm not sure, whatever that is. B. So it's 1, 2 plus 1, 3. 3 plus 4. 7. 7 plus 5 is 12. 12 plus 7 is 19. B minus whatever that number is. If you actually sum it up, I think that should come up to 177, 25, 6 plus 2, 138, if I'm not wrong, equal to 0. So that's one equation. This, if you solve it, I mean, I think this is the one. You can correct me if I'm wrong. That's one equation. Similarly, if you solve this one, you should get another equation. The second equation should sort of give you 19W plus 5B minus 28 equal to 0, because you're differentiating the with respect to B, remember. The second one you're respecting with respect to B. Okay. So two equations, two unknowns. Two equations, two unknowns. What is W and B? What is W and B? So yeah, there you go. I just checked with ChatGPT. This is what ChatGPT had to tell me. I said solve both these. It solved for it, and it gave me the answer. W is 1.386 and B is 0.33. W is 1. Was it? W is 1.386 and B is 0.33. Now, if you actually think of this, so what are these that you've got? So now let's use a little bit of our sense. Let's do a bit of sense check here. Let's go back to this Excel sheet. So W is, what are we saying? What is W? W is the weight, and we're saying so we're saying Y is equal to 1.386 times X plus 0.33, right? W and B. So if you were to draw a line using your hand, this is how the line would sort of look like. So your check is the slope is positive. Everybody agrees to this, right? Because as x is increasing, y is increasing, so w is positive. So the slope is positive. And your bias or your constant is 0.33. So this is, if you consider this as 1 somewhere here, this is slightly less than 1, right? Brilliant. So now all that effort is basically for that 1.386 plus 0.33, which is exactly what you computed. So congratulations. This is a simple linear regression equation that you actually have solved right now. So you now know, in this case, what the value of W and B is. So W is 1.386 and B is 0.33. That's how this perceptron works. For any given XW is the same, because you've learned the W from a bunch of data points, that you see on the left side. So W is the same for all your data points. That's how your data behaves. That's how Y would change given any X. That is how you compute a weight and a bias for any given perceptron. That is how you would compute coefficients for a linear regression equation. So now, given a set of inputs and sort of historical data, can we compute the weights and biases of a given perceptron? Now, this whole thing will start to become slightly more complex the moment I talk about a couple of things. So all of this is great, but imagine a world where instead of one input, you have, let's say, 20 inputs, right? For example, you have the same equation, right? But instead you have, so let's for the moment take x3, and then you have bias B, right? Now x1, x2, x3 and bias B. So the equation now is equal to y hat is equal to w1 x1 plus w2 x2 plus w3 x3 plus B. That's the equation that you're referring to right now. And now what you need to do, is you need to sort of do the same thing, but remember, dou MSE by dou W1 equal to 0, dou MSE by dou W2 equal to 0, dou MSE by dou W3 equal to 0, and dou MSE by dou B equal to 0. So you will get 4 equations, 4 unknowns, and then you need to solve for W1, W2, W3, W4, and then get to the output. Do you get the complexity? The moment you add more equations, this process will slowly start to become more and more and more complex, because then you will have to solve for 5 simultaneous equations, 8 simultaneous equations, 100 simultaneous equations. And that's where things, so 100 dimensions, if I imagine I have 100 features, x1 to x100, which is very common, by the way. So in that case, then you need to solve for 100 simultaneous equations. Solving 100 simultaneous equations, even through matrices, is super complex. It's a very, very complex affair. It's a non-trivial problem to solve, right? Even if you try to solve it through matrices, through system of linear equations or whatnot, right? You use any of your Kramer's methods or whatever methods. The moment I have 100 simultaneous equations, all of those matrix inversion methods and Kramer's methods, all of those go for a toss. They just don't work. So the point is, it becomes almost impossible for us to get absolute deterministic results like what you're seeing over here. So you need to lean towards more approximation based techniques. This is where some of your Newton-Raphson methods, these are now approximation techniques. They are not anymore absolute deterministic solutions. You're getting to slightly more, okay, how can we approximate to the output? Not exactly get to the output, but somewhere close by to the output. I live with a little bit of error, but I'll get to an approximation technique. That is where we will sort of get towards. That is where we will introduce ourselves to a concept called as one of the most popular approximation algorithms to solve for these is gradient descent. Gradient descent is an algorithm that helps you solve for this kind of a complex environment. It gives you an approximation mechanism to solve this optimization problem very, very efficiently. As you add more and more features, the complexity of these solutions will become more and more. What do I mean by it? Here you had one feature, so only one partial derivative, and you just had to do two partial derivatives, one for the weight and one for the bias. But if you have 10 features over here or 100 features over here, x1, x2, x3, all the way up to x100, then you're solving for 100 partial derivatives. 100 partial derivatives is fine, but the thing is you need to solve for 100 simultaneous equations, which is all the more complex. So for that reason, you cannot get these deterministic solutions like these, which is where we will lean towards a slightly more efficient approach towards solving this problem. And that is where gradient descent helps you solve all of this optimization problem in a super efficient fashion. I wouldn't say it is super efficient, but it is super computationally efficient. Is it um, is it perfect? Probably not. It is approximate, but it will give you a solution at least. It's not perfectly accurate, but yeah, you will get a solution at least. Otherwise, here you will get drawn into the complete complexity of the algorithm itself.
Hello everyone. Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.
So, folks, we had spent a good amount of time trying to understand some fundamentals of deep learning, right? So I think we spent some amount of time trying to delve into a little bit of detail around how, let's say, what is a neuron, right? Some of the foundations of neural networks, which is starting with a concept of a neuron. We understood how a biological neuron works, and then we tried to kind of translate that or approximate that into that of an artificial neuron or a perceptron. And then we told ourselves that a perceptron is something that fundamentally looks very, very similar to that of let's say, a simple linear equation. And then when we actually started, when we actually put the equation down, it was very obvious that this is like a linear regression model. Simplistically speaking, it is actually like a linear regression model. And then we spent a little bit of time trying to understand how some of these parameters of these linear regression model could actually be solved. While I was discussing it in the context of a perceptron, but that concept is actually very, very similar to a lot of the other topics that you might have already learned during your linear regression sessions at some particular point in time. So you have, of course, and we had actually taken an example, as you can see on the left side. So you have X and Y. If you take, for example, a small example like this, we told ourselves that a perceptron would look like this, and then we translated that particular perceptron into Y is equal to W times X plus B. And then from there, what you might have definitely seen is that we sort of went about solving for this particular, for a simple cost function. We told ourselves that the problem that we had is to find the best possible values of W and B in this case, where the mean square error is as low as possible. And once we actually listed out the mean square error function, and then we actually started solving for it, one of the approaches that we had sort of taken to solve for this is to take a partial derivative of this particular function that you see here and equate them to zeros. And the reason for that, we kind of also spent some amount of time trying to understand why that's the case. We explained to ourselves that given any polynomial or any expression for that matter, you could always find a minimum of that particular equation by differentiating that and equating it to zero. And we spent some time trying to understand that rationale over there. So, and we came back, we took a partial derivative, we equated that to a zero. Then by taking with the two partial derivatives, you essentially will have two equations across these two unknowns, and you solve for W and B respectively. Now, the beauty of this is that this is essentially how you go about solving for any kind of a equation. You take the W and B, you substitute it back here. That is, voila, that's essentially your perceptron model solved for. Then what we told ourselves is this is all great, but the reality is that in case you have a lot of variables, like for example, x1, x2, x3, all the way until xn, then you would have n weights and one bias. And in such a scenario, what's going to happen is what you would have to do is instead of taking a partial derivative here across W alone, you would have to take partial derivatives across W1, W2, W3, W4, all the way up until Wn. And in this case, you're talking about n of the order of, let's say, 100 or a couple of hundred variables as well at some times. So in such scenarios, a simple regression approach or an ordinary least squares approach like what we had done here is not necessarily going to fly. And what that translates to is we need to take the partial derivatives of all the 100 variables and solve for basically these 100 equations across 100 unknowns, or 101 equations across 101 unknowns. And that is where things start getting very, very tricky, right? Because you have too many variables, and solving equations like these becomes very, very complex. Getting deterministic solutions like these will start to become very difficult. Hence, you start to lean towards approximation techniques and techniques that sort of give you approximate but fairly accurate results. And that is where we will learn about a technique called as gradient descent, which is an optimization algorithm, which sort of tries to give you which attempts at providing a fairly decent, fairly accurate result, but at the cost of, meaning an approximate result, but at the benefit of, let's say, feasibility, and also at the benefit of giving you faster results as well. So it makes it feasible to solve for such kind of complex problems. B, it also helps you do it at scale, and do it faster as well. So that's essentially the reason why we would lean more towards a gradient descent based approach. This is where we sort of paused. We're going to take it from here. We're going to continue from here. I'm going to introduce you to gradient descent. We'll spend a little bit of time trying to understand how gradient descent works. Brilliant. All right. Now, let's get into the weeds of gradient descent. What is gradient descent? Now, gradient descent is a very simple problem. I mean, it's a very, very simple algorithm, super intuitive algorithm. Again, based on a little bit of math, a little bit of algebra, So we'll spend a little bit of time on that. Some kind of we'll have to spend a little bit of time on understanding some of the foundational math here. But I think it's super small, minor adjustment, but amazingly effective algorithm. So I'll explain to you how this works. And then there are some mathematical adjustments that we will have to make as we go along. We'll go one thing at a time. So let's go then. In the context of neural networks, when we talk about gradient descent, so gradient descent is an optimization algorithm. It's actually an optimization technique that helps you, as I said, solve for a certain kind of parameters. We often apply gradient descent in the context of of regression algorithms. But technically speaking, gradient descent is also applicable in the context of I don't know if you've studied gradient boosting machines, but this is also applicable for gradient boosting machines, actually, which is basically a boosting technique. So it's an algorithm that helps you find the best possible value of a given set of parameters by trying to optimize against a particular cost function, an objective function, so to say. So I'll set it up. I'll set up the problem, and then I'll show you how gradient descent sort of does an amazing job in this particular sense. So let's go. So let's say you have one variable, right? And then you have one input variable, which is x1, and then you have a bias b and a weight w, and then you're simply doing a summation, and then you're generating an output y hat. And then as you can see here, y hat is equal to w times x1 plus bias b. Same setup, same equation. And as you can see, your predicted value is simply nothing but w times x plus b, and this w can be many more. We'll start with one variable for now, and then we will try and build upon this. For the purposes of this particular example, I'm actually going to assume that there is no bias either, right? For the simplicity of this particular problem. For the moment, I'm just going to assume that there is no bias, right? So x1 times w. So here y hat is equal to w times x. I'm not saying bias is not there. Bias is there, but I am currently ignoring this. I'm deliberately ignoring this. We'll bring this back in the later parts of the session. For the moment, let's just assume that's the case. So to train a model like this, you would of course have historical data. You have X and you have Y. This is your historical data. You might have a lot of data points. You have historical data. Now you go about solving for this, like how we did earlier. So what do? So you're going to put together a mean squared error function, wherein you're saying mean squared error is 1 by n into summation of I is equal to 1 to n, predicted value minus actual value, the whole square. This is the predicted value. This is the actual value, and that's the whole square, right? Where where n is the total number of data points that you have. Right? N is the total number of data points that you have. Now, in a scenario like this, if you actually expand this out a little further, this is going to be 1 by n into summation of I is equal to 1 to n. This predicted value in this particular case is nothing but w times x. It should have ideally been plus b. I'm ignoring the bias for the moment. Minus yi, the whole square, right? So you of course know x and y. X and y come from the training data set. This is your input data or your training data set or historical data. Your historical data would provide xi and yi. So that should not ideally be a problem. So you have your mean squared error in this particular case. Now, what would ideally happen in a situation like this? Here is where your gradient descent sort of kicks in. What gradient descent? So what you could have done, remember one thing, what you could have done is from here, you could do it using dou MSE by dou W or DMSE by DW in this case, right? DMSE by DW, you equate it to 0 and you can solve for it. This is your regular approach. But with gradient descent, we do it slightly differently. I mean, you could do it this way, But the reality is we don't want to do it this way. This is where I'm introducing you to your different technique. What does your gradient descent tell you from here? So what your gradient descent tells you from here is, for a moment, let's just assume you have a couple of data points, right? From here, let's just assume that you have a couple of data points. Let's say you have 2 data points, right? What were the different data points that we had in our example? I think we had 1, 2, 2, 3, right? Okay, perfect. Let's say X is 1, Y is 2, this is 2, this is 3. 1, 2, 2, 3, right? Perfect. Let's take these 2 observations for the moment. So if you actually expand on this, this is going to be 1 by 2 into, if you actually solve this, W minus 2 the whole square plus 2W minus 3 the whole square. And if you actually further expand on this, what do you end up getting? You end up getting a second degree polynomial in W, something like, I don't know, in this case, this is going to be 5W square plus, this is going to be 2W, this is going to be 6W, this is going to be 8W, or rather minus 8W, I must say, minus 8W plus 4 and 9, 13. The whole thing divided by 2. Of course, you have a by 2 around this, 1 by 2 around this. 5W square minus 8W plus 13. Basically a second degree polynomial in W. So your MSE is a second degree polynomial in W. This is for 2 data points, but imagine you had, let's say, 100 data points. Imagine you had 100 data points. Sorry, this square is here. So imagine you had 100 data points. You would still have a second degree polynomial. Doesn't matter, right? How many ever data points you have, this would still be a second degree polynomial that would look like this. How many ever data points you have? AW square minus BW plus C, something of that sort. I mean, you can get into the detail later. I'm not solving for this equation right now. The point that I'm trying to get at here, guys, is that this is a second degree polynomial in W. What that translates to, irrespective of how many ever data points you have, what this translates to is your MSE, whatever you see here, is a parabola. Your MSE, you have your MSE here, you have your W here, and the beautiful part of this is that your MSE and W, they are dependent as a parabola. Now, it can be like this, it can be slightly larger, smaller, doesn't matter. This equation, however you like it, depending upon the values that you have over here, it's either going to be wide or it's going to be super. It's either going to look like this, or will look like this, or will look like that, depending upon the values of 5, 16, and 13 respectively. Fantastic. Now, my friends, and for those of you who are not very familiar, if you actually substitute different values of W, you will, and if you start plotting it out, you will see that your your MSE curve will sort of come out to look like this. If you're not familiar with AW square BW plus C, an equation like this is always a parabola. That's sort of that, you could sort of recognize just the way why you say y is equal to mx plus c is a straight line. Similarly, AW square plus BW plus C is a parabola. It's a fact. I mean, if you just simply plot it, you will be able to see it. Now, what is it about this? So this is called as your, whatever you're seeing here, this is your loss function or your cost function. This is your loss function or your cost function. This curve that you see here is a very, very, very important part of how we are going to be solving for this. So then, what are we trying to solve for? Now, this part we are all familiar from our previous session. The objective here is to find best possible values of W, right? Is to find best value of W such that MSE is minimum. So you want MSE to be minimum, and you want to find that particular value of W where MSE is minimum. So you're essentially trying to find this value of W where MSE is minimum most. You're trying to find that particular value of W. So here is, earlier what we did is we simply took a derivative, we equated it to 0, and we solved it. Brilliant. That is one way to solve for it. But gradient descent, as I said, is an approximation algorithm. It tries to solve it slightly differently. It takes a slightly different approach. Here are the steps that it takes. Step one is start with a random value of W. Randomly assign W. You start with any random value of W. So you don't know currently what is the best possible value of W. So what we are going to be looking at is to start with a randomly assigned value of W. So for example, in this particular case, let's say you start with this value of W. At this particular point of W, this curve is going to give you a certain value of MSE. In your opinion, is this point of minimum error? You're not guaranteed. You don't know. You've randomly initialized with a value of W. You don't know if the error is minimum or not at this particular point. So what you do is you randomly assign W. You compute mean squared error over here. You compute your MSE over here, right? Now, at this point, here is where you need to decide. From this particular point, you need to decide if you want to move to left or if you need to move to the right. So you randomly started somewhere. Now you need to decide which direction to move. You are looking at this visually. So you tell me, should you reduce the value of WC or should you increase the value of WC to get to the minimum point? The objective, remember, is to get to this point. The objective is to get here. You need to reduce. Because you are able to visually see this, you are making that decision. You need to reduce. That's a no-brainer. You are making this decision because you are visually able to see this. But then how will you get the algorithm to decide it? How will you get the algorithm? That's where a little bit of intelligence from the algorithm is sort of going to kick in. So that is where we're going to compute, right? That's where we're going to compute. If you remember, we spoke about computing the slope of this particular equation at that particular point. Remember instantaneous slope or instantaneous rate of change or instantaneous slope. Remember we spoke about this. So here you compute the slope of this particular equation. In this particular case, according to you, do you think the slope is positive or negative? Do you think the slope is positive or negative? The slope is positive. How are you saying the slope is positive? Because here at this particular point, as W is increasing, your MSE is also increasing. So the curve is sort of going upwards. Another way to also compute slope is to also, there are two ways to do it. You can compute it using, you can look at this angle and then you can compute the tan of that particular angle, right? So which is from trigonometry. Some of you all are familiar with it. Or you could also simply take this particular curve and you can differentiate that particular curve, right? So you take the equation, you take dou MSE by dou W, and if you compute it, if you substitute WC over here, you will see if it is positive or negative. So you can exactly compute at this particular point what is the slope of the equation. Does this make sense, everyone? So for example, if you take this as the equation, you can differentiate this particular equation, you can compute the slope. How do you differentiate this equation? So this is going to become, to differentiate this equation, this is going to become dou MSE by dou W, which is going to be 10W minus 16, 1 by 2. You still have the 1 by 2 around it, which is going to be 5W minus 8. So that is essentially the how your slope is changing. If you substitute the value of W inside this, assuming whatever value is the W, you can get the actual slope of this particular equation. Make sense, everyone? You substitute the value of W at any point in time, you can get the instantaneous slope. So if W is 10, so 5 into 10 minus 8, so 50 minus 8, which is 42. That's the slope of this particular equation when W is equal to 10. When W is minus 10, the slope is minus 58, and so on and so forth. Okay. Now the fact is, once you compute the W over there, now the whole point of trying to find the slope at that particular equation, you're not trying to solve for the minima over here. You're just trying to compute the slope of that particular equation over there. So once you compute the slope of this particular equation, you will know if that will tell you if it is positive or negative. You know, if this is positive, then you know that you are on this side of the curve. If this is negative, if the slope is negative, then it will tell you that you're on the other side of the curve. So computing the slope will sort of tell you the direction you need to move. That's it. On this side, the slope is always positive. On this side, the slope is always negative, right? For example, if you simply compute it here on this slide, if you look at it, this is the angle, or technically speaking, this is the angle. It's an obtuse angle. The tangent of any angle that is greater than 90, tan 120, I don't know if you remember, tan 90 is infinity, right? Tan 0 is 0. Tan 120 is a negative angle, is a negative value. That's because the slope is negative, so to say. But anyways, doesn't matter. We don't need to go down that path right now. Point that I'm trying to drive here is, in this case, the slope is negative. On the right side, the slope is positive. So the slope will simply tell you, you can simply compute it using a simple differentiation like this. That will tell you if the slope is negative or positive. In this case, the slope is positive. So the moment you know that the slope is positive, what do you do next? The third step, adjust your WC. How will you adjust? So W nu is equal to WC minus dou MSE by dou W. Now, why are you taking dou MSE by dou W? You can take, to be very honest, you can take any value over here, right? You can take any value over here. But the reason why you're taking dou MSE by dou W, because this will tell you if it is positive, if the slope is positive, then you're subtracting a value. So you're moving to the left. If the slope is negative, negative of negative, which means you'll move to the right side. So this negative symbol over here will take care of which direction for you to move. And you are simply taking a slope over here because you're not taking the slope there for the value, but more for the direction. I mean, it can technically be any value you want over there. It doesn't matter. You can put any small number over there and you can subtract it. So now what has happened? You have started here with this WC. You've computed the gradient. You've realized that the gradient is positive. And what that told you is you need to reduce W. So you substituted the gradient over here, and thereby you are getting your new WC. I'm going to change this. I'm going to put this as WC. Again, WC is equal to WC minus dou MSE by dou W. So now you know you'll move to the left. So the moment you decide to move to the left, now you've come here, let's say. So you are earlier here. So now you have, let's say, come here. Now let's say this is your new value of WC. What do you do now? You repeat the process, right? You repeat the process. You compute the gradient here. So when you actually compute the gradient, again, the slope is positive. So you repeat this process. So step 4 is you repeat. Until when will you repeat this? You will repeat until there are a couple of ways of getting there. You will repeat this until you keep going from here to here to here to here to here, ideally to this particular point. You may go from here and then here, ideally to the bottommost point. But the reality is, you will never really be able to get to the bottommost point. You will never be able to exactly hit the bottommost point. You will sort of shuttle here, so to say, which is the whole point of, because if you're on the other side, you will adjust to the left side. From the left side, you move to the right side. From the right side, you move to the left side, and so on and so forth. You just keep shuttling there. And that sort of will become a bit of a, you'll never really be able to hit the bottommost point. So you will repeat until you don't see no significant change in gradient or MSE. Like for example, you're computing the MSE here, right? MSE and gradient. So so after this particular point, you're just shuttling here. You might not be able to get to the bottommost point. You're just simply shuttling there. But at that point, you realize that, you know what, my MSE is not reducing any further, right? It's kind of hit at a particular point, but it's not reducing any further. It's sort of just shuttling at that particular point. And that becomes sort of a way for you to, it's like a boundary condition. It's like a stop for you to, it's like a signal for you to stop training it any further. Once you differentiate it, this is the equation. You just change the value of W. You don't need to differentiate with respect to a new value. Once you differentiate, you just get an equation. All that you need to do is just keep substituting newer value of W's inside this so that you'll get your different gradient. That's it. You don't need to recompute or continue to differentiate it multiple times. Differentiation will give you one equation. You get an equation like this. You just have to substitute new values of W wherever you are on this particular curve. That's it. So computationally, it's super simple. I'll repeat this again. Very easy, very simply. So you've started here, you've gone down here, and then you've gone here. Now see, just before this step, what's likely to happen is you'll probably be here. And what's likely to happen is here, you compute the gradient, slightly positive gradient. The gradient is still positive. So you reduce the error. So you adjust the W. So now from here, when you adjust the W, you might just jump to the other side. And here the slope is negative. So when you add the W, you might just jump here. You'll get to the bottommost point, but you will never exactly be able to stop. You'll never be able to exactly get to the W as 0. Right? You'll just come all the way there, but you'll just keep shuttling there. Exactly. You'll just keep oscillating there, left to right, left to right. And one way for you to identify that point where you need to stop is you realize that, okay, you know what? Irrespective of wherever I am, irrespective of this side of the curve or that side of the curve, if you actually look at the MSE, the MSE is not reducing any further. You've come all the way here. From here, you've come all the way here. But after this, the MSE is not reducing any further. So that's like a good indication for you to stop training. Does it make sense? What if, you've randomly started here, but what if, let's say, you start on the other side of this particular curve? So you start here. Instead, let's say you start on this side of the curve. So you do the same thing. But let's say when you initially assign W, let's say you assign the W here. So now when you compute the gradient or slope, what part of this is called as the gradient? Gradient means slope. Gradient and slope mean one and the same. You are descending basis the slope at a particular point, which is why it is referred to as gradient. Gradient or slope is gradient descent. I'm sorry. You're descending basis the slope at a particular point on the curve. Hence, gradient descent. You're descending basis the direction your gradient is telling you or your slope is telling you. Hence, gradient descent. There is also a gradient ascent algorithm as well, right? Where you probably choose to ascend instead of descending. You may want to maximize a particular equation. In that case, you do a gradient ascent algorithm. In this case, you want to minimize, which is why you're descending. This is a gradient descent algorithm. Make sense? Now, if you're, let's say, on the other side of the curve, so what do? Same equation. You randomly assign the W. You're on this side of the world. You need to get to the bottommost point. You're on this side. So now when you compute the slope, dou MSE by dou W, in this case is going to be negative. So you compute the gradient, but the gradient is negative. So when you substitute a negative value, negative of negative will be positive. So which means your new value of W is going to be your current value plus a positive value. So when you add a positive value, what do? You move to the right. So automatically you move from here to here, and then from here to here, and then from here to here, and so on and so forth. Make sense? What slope gives you is slope tells you the direction at any point in time. That's the whole point of using gradient as a gradient or the slope as the variable to adjust your weight. That's the only idea. The part that I just want to focus on over here is this. So in this case, we spoke about one particular variable. Now, I'm going to talk about a situation where you have more than one variable. Meaning, in this case, let's say we just had W. But what if you have W and B both? Or you have W and W1 and W2, right? So now let's go back here. Let's go back to the drawing board. So instead of W times X plus B or W times X, let's say you have W times X plus B. So you have W and B. Now what's going to happen? Here, this is going to be W times X plus B minus Y the whole square. You have W and B as two unknowns. Everybody agrees to that? And when you expand this particular equation, you're going to have a second degree polynomial in W and B. So you're going to have A times W square plus B times B square plus C times, WB plus so on and so forth, right? So you're essentially going to have a much larger equation over here, but it's still going to be a second degree polynomial, but in W and B. Make sense? Instead of W, you're going to have a second degree polynomial in W and B. Okay, it's a quadratic equation, but in W and B. So in that case, what is this curve going to look like? Instead of parabola in 2 dimensions, now you need to sort of start thinking about this a little differently. So what you will have is you'll have a bowl-shaped function in 2 dimensions, 3 dimensions rather. So you're going to have MSE, W, you'll have W, and then you'll have B here. So this is a three-dimensional space. Now here, instead of thinking of a parabola, in 2 dimensions, if you didn't have this dimension, it would simply be a parabola. But the moment you have 3 dimensions, it's going to look like a bowl. I'm not the best at drawing a bowl, but you can think of it like a nice bowl-shaped function. Does this make sense, everyone? Can you think of a bowl here? So it's called as, instead of a parabola, it's referred to as in 3 dimensions, this is referred to as a paraboloid. So the same equation looks like a paraboloid. Now look at the beauty of this. So the function or the process remains exactly the same. What is the first step? Randomly assign W. Instead of randomly assigning W, you will randomly assign W and B. You randomly assign W and B. So when you randomly assign W and B, let's say you randomly pick a value of W, randomly pick a value of B. So this is, let's say, it's the way you have, you can think of, I'm just drawing these lines just for reference here. Okay. I'm just drawing these lines for your reference, but so on and so forth. But so if you pick any random value of W and B, so these are different values of B's. And similarly, these are different values of W. What do you see on the other axis? Different values of W. So the moment you pick different value of B and W, you probably will start somewhere in this particular, on this particular bowl. So, or you may start here. Now your objective is to get to this bottommost point. So now you need to differentiate with respect to, you need to compute the gradient with respect to B and with respect to W, meaning you need to compute dou MSE with respect to W, slope with respect to W, and slope with respect to B. So now, instead of adjusting just W, what will you also adjust? You will also here adjust B. So B current is equal to nu B minus dou MSE by dou B. Make sense? All that you're trying to do is, earlier in the case of 2 dimension, you started here and you were trying to get to the bottommost point. But here, you start here and you try to trickle down to the bottommost point over here. So you're essentially trickling down through the edges or through the surface of the bowl to the bottommost point. Can you imagine that? Can you understand how that goes? So you're essentially sliding down through the edge of, let's say, a bowl, through the surface of the bowl. Does that make sense, everyone? Now here, all that you need to do is you just have to compute this equation once. There is no simultaneous equation solving here at all. You just have to continuously keep adjusting your W. Compute the gradient, adjust the W. Compute the gradient, adjust your bias. Repeat this process until you don't see any significant change in MSE. That's it. There is no simultaneous equations. There is no solving simultaneous equations. Any of that drama. Value could be anything on the WB plane. Yes. Do you understand that we completely eliminated this whole point of the simultaneous equation solving? Because that was one of the things that you had to do earlier, right? You had to partial differentiate both the equations, equate them to 0, solve both the equations, then get W and B. Then that's essentially your last value. But here, all that you have to do is you just have to compute the equation once, just the way you get dou MSE by dou W here. You just come solve the dou MSE by dou B once. And then once you get the equations for both of these basis different values of W and B, you can compute these gradients. And once you compute the gradients, all that you have to do is just keep adjusting W and B. But how do we know whether W or B is resulting in making? Yeah, because you can always compute here. Once you change the W and B, in the next step, you again compute MSE, right? With the new value of W and B. This whole thing is an iteration. This whole thing is an iteration. Guys, the easiest thing to do is ask for over here is to, hey, can we put an example and explain this to me? Try and spend a little bit of time in understanding this notation. This notation is, I mean, this is like a peeled banana. Try and spend a little bit of time understanding this notation. It's going to come in very, very handy for you later. I will show you easier examples. You will find a million easier examples, but spend time in understanding this notation a little. This is already a very, very simplified version of the whole notation. So just persist with this for a couple of minutes. The easiest thing to do is just asking for something simpler. What I'm trying to tell you guys is the biggest difference between how we've solved for earlier to how we're trying to solve for right now is you're sort of taking away this whole simultaneous equation solving. You're simply computing gradients at every point in time or slope at every point in time. And then you're trying to just simply course correct yourself. That's it. That's what you're trying to do here. All right. Okay. Let me just quickly show you an example. So let me show you a document here. And this is essentially what I was referring to. So this is a much more visual representation of the same thing. Again, the notation can be slightly different. This is MSE, this is W, this is B. You have a bowl-shaped function. The idea is you probably start at one random point of W and B, and then you trickle down to the bottommost point. That's the whole idea of of gradient descent. Now, how does it exactly work? Let me show this to you in a minute. So let's start here. Now, I'll just set this up for a second, and then you will understand this better. So this is your target variable Y. This is X. What you see on the left side is the actual data itself. So you see these red data points. That's your historical data set. So you have X and Y. And what you have is you have some of these data points over here, wherein you're trying to predict the price of a house given the size of the house, right? And all these red data points is essentially the data set that you have. What you want to do is you want to fit a line that cuts across all of those points like that, right? To start with, and what you see on the right side, this is your data set. And what you see on the right side is essentially the bowl-shaped function. It's the bowl-shaped function. But imagine you take a projection of this bowl in 2 dimensions. So this is W, this is B, right? So your equation of Y is equal to W times X plus B. This is W and this is B. And then you see these colors here. Those colors represent your MSE. If you're farther away, that means the MSE is larger. If you're here, then the MSE is 0 or minimum. Let me put it that way. Does that make sense, everyone? So imagine you're taking a 2-dimensional projection of this. That's what you see here. The rings here represent it's called as a contour plot. What you're seeing here is essentially referred to as a contour plot. It's a 2-dimensional plot of that 3-dimensional object that you see at the top. This is a 2D projection. Make sense, everyone? Now, what is the first step? What is the first step? So the first step is randomly assign W and B. So you randomly assign the value of W and so this is B and this is W. Randomly assign the value of W and B, right? So the random value of B is minus 900 and the random value of W is 0.9. Or sorry, random value of B is 900 and the random value of W is minus 0.1. So if you randomly pick a value of W and B, what will happen? The line is also going to be random. So that's what it is. And as you can see here, that value of W, this is the value of B, 900, and this is the value of W, which is getting you to minus 0.1. So random value of W and B sits you here on the cost function, and the line on the actual data looks like this. Is this a good fit? No, which is why the error is also large. Now, the thing is, the first step from here is for you to compute the gradient at this particular point. So your current value of W is minus 0.1. The current value of B is 900. And this is W and B. Instead of theta not theta 1, just consider this as W1 and W and B, so to say. Okay. Now what you're trying to do is you're trying to find the best possible value. So you're trying to minimize MSE 1 by n into summation of I is equal to 1 to n, predicted value minus actual value, the whole square. That's essentially what you're trying to minimize in this case. Now, in the process of trying to minimize this, what do? You've randomly assigned W and B. So now you compute dou MSE by dou B and dou MSE by dou W, and then you update the weights. So new value is equal to current value minus dou MSE by dou W1 or dou W. Similarly, B is equal to current value of B minus dou MSE by dou B. So you do this adjustment, the first iteration, what happens? Look at that. Earlier the equation was like this. Now here is, look where it is. So now if you look at it, your B, which was previously negative, which was 900, has now reduced, and automatically the line which was elsewhere has now moved here. Make sense so far? First iteration. Second iteration. The line has gotten better. So we started here, we've gotten here, now we are here. Let's go to the third iteration. Fourth, fifth, sixth. Done. We're at the bottommost point. Initially, it was correcting the intercept, or rather your constant, your bias, and then eventually it corrected your weight as well. So that's it. Now you're at the bottommost point. So as you keep getting to the bottommost point, your line keeps getting better and better. Does this make sense? Do you understand this intuitively, everyone? All right. Now, the point that a couple of points that I'd like to add here. See, if you had, let's say, instead of one weight, imagine you have, let's say, 100 weights. What would this whole thing become now? This would simply become, instead of one correction, you have to do W1, W2, W3, Wn. W1 minus dou MSE by dou W1. Similarly, Wn minus dou MSE by dou Wn. So you need to make those many number of weight changes and then bias. So the beauty of this is that all that you need to do is these weights that you see here. See, the thing is, whatever may be your weight equation, you just have to differentiate it once, you get this equation once. So what I'm trying to get at is, imagine your MSE equation between W and B looks like this, right? So your MSE is, let's say, 5W square, W1 square plus 3B square minus 15WB plus 10. Let's say you have an equation that looks like this. This is the MSE equation with W and B, right? So all that you need to do is just compute dou MSE by dou B once and dou MSE by dou W once. You get the equation. When you differentiate dou MSE by dou B, what do you get? 15, sorry, this is dou B, right? This will simply become 6B minus 15 dou MSE by dou B, and this is going to be 10W minus 15. That's it. So this is 10W minus 15 and this is 6B minus 15. So now, whatever may be the new value of W and B, whatever may be, how many ever iterations you run, you don't need to do anything. You just have to keep substituting new value of W and B here. That's it. So computing gradient is as simple as that. If you can differentiate it once and find this equation for whatever may be the value of W and B, wherever you are on this particular curve, you just have to substitute the value of W and B over here and you'll get the gradient. You'll get the slope of that particular equation. So there is, technically speaking, this is simple linear algebra, linear math now. So there is no complex computation at all. It might seem like you're dealing with large number of variables, but technically this math is super, super simple. You might deal with 1,000 variables, 10,000 variables also, but the math is very, very, very simple. All that it requires is just one equation that you need to get at the beginning. And after that, everything else becomes the same. And you need to just iterate. Just need to loop through this maybe 100 times, 1,000 times, depending upon how many other times you need to do it. So the math is simple, but you need to iterate many number of times, which is why this is an approximation algorithm, not a deterministic solution. In the other case, because you're trying to get the absolute result, what you're chasing is perfection. And for that reason, you're having to solve, sort of having to, shoulder the weight of a mountain from the get-go, which is why solving it through ordinary least squares is a much more complex approach in comparison to gradient descent. Does that make sense, everyone? Do you understand why this is easier, simpler in terms of mathematical complexity? Now, I'll just go back to this two-dimensional plot for a moment. What if in the process of, let's say, minimizing for whatever may be the reason. So you started here, you've computed the gradient. So this is MSE and this is W. And then you computed dou MSE by dou W and you've computed that to be, let's say, positive here, whatever the number is. And then now you're adjusting W is equal to W minus dou MSE by dou W. This is how you're adjusting the weight. Now, in the process of making this happen, you realize that, let's say you have ended up subtracting, let's say for whatever may be the reason, the gradient is very, very large. The magnitude of the gradient is so large that you actually subtracted, but unfortunately, you subtracted a very large number. This number is, let's say, very large. Now, but in the process of subtracting, you actually subtracted such a large number that you have skipped the minima, let alone skipping the minima. You actually went way onto the other side. Here is where you were, but when you subtracted that number, let's say you ended up jumping to the other side completely altogether. So here is where you ended up jumping, let's say. This is now your new WC. Can you imagine that happening? Because the value of the gradient could be very large. Make sense, everyone? It could happen, right? Because you just subtracted such a large number that you ended up jumping completely onto the other side. Now, again, you try to correct the same thing from this side. So now here you compute the gradient. You realize that the gradient again here is very large. Now you try to correct. So now you say W is equal to W minus of negative dou MSE by dou J or dou W. Now you add value, but this time you add so much, you end up jumping completely onto the other side again, right? And in this process, you end up correcting it so much that instead of actually descending, you end up diverging. Instead of converging to the minima, you end up diverging. You just keep shuttling left and right and left and right, and you completely jump out of the curve. It's possible, right? You're making a leap, man. You're updating something. Instead of reducing a small value, you end up reducing a very large value. And because of that, instead of coming from here to here, you ended up jumping completely onto the other side. And instead of slowly converging, you ended up significantly diverging. And now what happens? Will you ever be able to get to the bottommost point? Will you be able to get to the minima? You will never be able to get to the minima in this case. So what do you need to do then in that case? So that is where we need to keep a tab on this value. We need to keep a check on this particular value that you see here. This value has to be carefully adjusted. So we often put a multiplier here. We often put a multiplier over here, alpha. This alpha is generally a value like a 0.1 or a 0.01 or 0.001. What it tries to do is it tries to shrink the step size. So this alpha that you see here tries to shrink the step size. It makes the value 1/10 of what the actual value is, or 1/100th of what the actual value is. I mean, you can pick any value, of course. Typically between 0 to 1. Typically between 0 to 1. You can pick any value you want. But generally, as I said, 0.1, 0.01, 0.001. And by doing so, what happens is now, instead of making a large step, you control that step. You make a small step. And then you make another small step and so on and so forth. So that way, instead of it completely jumping away by making large steps, you get it to make small steps so that it can kind of nicely descend through this particular curve. Does that make sense, everyone? This alpha is referred to as learning rate, or is often also referred to as shrinkage or learning rate. Learning rate is the most popular term, but is also referred to as shrinkage. Now, how do you select alpha? It has honestly no rule of thumb. The typical approach that we take, as I said, is we try with a 0.1, 0.01, and then we go with it 0.1, 0.01, 0.001. And it's just a way for us to, you will have to identify what is the best possible value in your scenario. Exactly. You will have to tune the value. It's like, for example, when you are building a random forest model, do you know how many trees you need to put? You don't. You start with a certain number and then you try and work around it. It's the same thing here as well. If you observe this kind of a behavior where your error is not reducing, but is actually increasing one iteration after the other, then in that case, it's clearly because of this reason. It's because of your gradient being very, very large. So for that reason, you need to introduce learning rate to reduce this adjustment. You need to introduce the learning rate to reduce the step size as much as possible. Alpha is constant for both W and B. You can choose different values of alpha, but generally it's a constant value for both W and B. There are certain advanced algorithms where this alpha can also change adaptively. For example, when you are in the initial parts of your learning, the alpha can be very large. But as you keep getting closer and closer, the alpha can reduce because you want to slow down the learning rate, training a little. So there are certain advanced algorithms that can control for that as well. Certain advanced techniques that can control for for these larger for these adaptive learning rates as well. But the reality is it is possible. There is no, as I said, you will see it, by the way. We will actually write some code to exactly implement gradient descent algorithm. And in that case, you will exactly see how we will adjust the learning rate. There is no rule of thumb. There is no way to say, hey, you know what, for it's this kind of data, let's use a learning rate of 0.5. There is nothing like that. It completely depends on the distribution of the data. It completely depends on how the algorithm is responding to that particular data. You have to adjust it accordingly. Typically, as I said, an alpha is between 0 and 1. If you observe that your MSE is increasing, you introduce alpha. Okay, let's go. What we'll do is, creating a Jupyter notebook. So this is just Jupyter notebook. So feel free to create any version of Jupyter notebook. I mean any IDE. I use VS Code. If you want to do it in Colab, feel free to do it in Colab. If you want to do it in Jupyter notebook, do it in Jupyter notebook. Use it wherever you're free to. Pick whatever you're comfortable to use. All right, perfect. So let's take a small example, right? Let's take a couple of variables. So x1 is, let's say 10, 8, 15. I don't know, I'm just taking 15. I'm taking random values. X2 is 8, 20, and 25. And then you have target variable y, which is 20, 15, and 30. So it's a small example with two variables. So what you have here is you have essentially a data set that looks like this. You have x1, x2, and y, right? And x1 is 10, 8, 15. This is 8, 20, 25, and 20, 15, and 30. So you have two variables and one target variable over here. Okay. Now your perceptron sort of looks like this now. So you have x1, you have x2, and then you have a bias b, and then you have a y over here. Okay. Now, why do I write one with a bias? Because there is no input. I mean, see, the way to think of a bias is this is bias and all the values of over here are one, right? So this is sort of a constant term and all the values are one and the weight is b. So you have W1, W2, and the weight is b. Because I need to try and compute I need to compute b as a weight. That's the idea over here. It's as simple as saying x1 plus x2, w times x1 plus w times x2 plus b times this constant. And this constant is just 1. It's as simple as saying x1 plus w times x1 plus w times x2 plus b times 1. Or simply saying plus b. It's just a simple way of writing the same thing. Okay. Now, coming back here. So you have w1, w2, and then y. So your y hat is w1 times x1 plus w times x2 plus bias b. Now, so the task at hand that we have is find best values of w1, w2, and b such that fit the above data set. And then the equation is y is equal to w1 x1 plus w2 x2 plus b. That's it. So that's essentially your current data set. Make sense, everyone? So you need to find this particular equation. You need to find w1, w2, and b respectively. Now to solve this, we are going to start with, and we'll be using gradient descent to solve for this particular problem. What's the first step? The first step is to randomly assign w and b, or w1, w2, and b. You need to randomly assign w1, w2, and b. So I'm going to randomly initialize it. So I'm just going to say import numpy as np. I'm just np dot random dot uniform, which is essentially uniform, or let's pick it from and n, which is picking from normal distribution. and I'll pick 3 values, any 3 values, right? I'm going to pick any 3 values over here. And I'm also going to be setting a seed so that you can also repeat it, random dot seed. So now for those of you who are already like wondering what is a seed, see, remember, if I don't set a seed, every time I call this random number function, it returns different results. It returns different values, random values. But if I set a seed, it will ensure that I always get the same values, even if you execute it at your end. So this is for reproducibility between you and me. Okay. And these are going to be the random initialization values. And I'm simply going to say W1, W2, and B is random initialization of 0, 1, and 2, respectively. W1, W2, B is randomly picking the values at the moment. And I'm just going to put a print statement over here so that we all know what we are talking about. So print f initialized weights is W1, sorry, this is W2, and then last but not the least, bias B. That's it. So your W1, W2, and B respectively. Okay, that's the values that you have initialized. So now with the values that you have initialized, you need to do a couple of things. Let's compute the predicted values with the current weight. So remember, what are the things that I need to compute here? Given that now I have my initialized weights, I'll have to compute the MSE. Remember, first step is random initialization of weights and biases. Second step is compute MSE and B. But to compute MSE, what do I need to compute? So if I look at MSE computation, 1 by n into summation of actual value minus predicted value, or predicted value minus actual value, the whole square. For this, I need to get the predicted value, isn't it? So how do I get the predicted value? I need to put the values in this particular equation so that I get the predicted values. I put the new W's or the current W's that I have with X's so that I can get the predicted values. All right. Okay. So how many observations do I have? So I have 3 observations, n equal to len of x1, which is number of observations, right? So for I in range of n, for I in range of n, what I'm going to do is I'm going to compute predicted value for each observation. So y hat is equal to w1 times, which is simply nothing but multiplication of x1 of 0 of I, because the first value, plus w2 plus bias B. Make sense? This is predicted value for one observation. But one observation is not enough, right? So I'll have 3 observations. So I'm going to initialize something called as y preds, which is nothing but the predicted value. Create that as a list, an empty list. And I'm going to keep appending to this. So I'm simply going to say y hat dot append of, y preds dot append of y hat. All right. So now you get the predicted values for every observation. So now if you look at preds, y underscore preds, these are your predicted values for for the current value of W's, for these values of W and B. And with this data set, these are the actual values. And this is the predicted value for each observation. The first observation, the actual value is 20. The predicted value is minus 2.5. The actual value is 15. The predicted value is 11.5. And the last value, actual value is 30. The predicted value is 8.9. Of course, there's a bit of error because it's just the first iteration. You've randomly initialized the value. So there's going to be some error. Now, I need to compute MSE as well. Do you agree, everyone? These are predicted values, but I also need to compute the error. So I'm going to initialize something called as error over here, total error. I'll assume that to be 0 to start with. And I'm going to say E is equal to predicted value for each observation minus actual value, the whole square. Make sense? And what I'm going to do for every observation, I take the predicted value, actual value, whole square, and I'm going to add it over there. So total error plus equal to, or simply put, total error is equal to total error plus E. That's essentially what it is. And then what you can do is, so now if you look at it, preds comma, so this is the predicted value and this is the error. This is the MSE. Clear so far? All right. Now that you have the forward pass, so now you have the predicted value. So now what do you need to do? So you've computed MSE. What else do you need to compute? You need to compute the gradient now, right? You also need to compute the gradient. You need to compute dou MSE by dou W1, dou MSE by dou W2, dou MSE by dou B. You need to compute 3 gradients. Everybody's with me on this so far? Okay. So now for us to compute that, we are going to have to do a bit of heavy lifting. What's the heavy lifting? So here you go. So y hat is equal to W1x1 plus W2x2 plus B, and MSE is equal to 1 by n into summation of actual value minus predicted value minus actual value the whole square, right? And predicted value is 1 by n into summation of W1x1 plus W2x2 plus B minus y the whole square. How did we compute it here? Predicted value minus actual value. Perfect. Okay, the right way. So now, guys, the thing is here, when we compute this error, now you take dou MSE by dou W1. So when you differentiate this with respect to W1, when you differentiate this particular equation with respect to W1, E is not MSE. This is MSE, or rather, this is MSE, so to say. E is not MSE. So 2 times, so 2 by n times, and when you look at this here, what does it become? W1x1 plus W2x2 plus B minus Y multiplied by, what do I need to do here? What do I need to do here? I need to differentiate with respect to W1. So you get W1 over here. Make sense? So this is 2 by n into, this is predicted value minus actual value. This is predicted value again, right? Predicted value minus actual value multiplied by W1. That is dou MSE by dou W1. Sorry, X1. I'm so sorry. X1. And this is for each observation. You need to remember that this is for each observation. There's a summation there, but that's okay. For every observation, we'll do it for individual observation. Similarly, this is for W1. Can you tell me what will this be by W2? The same thing, 2 by n into predicted value minus actual value times x2. And what will this be for dou MSE by dou B is going to be how much? 2 by n into predicted value minus actual value. So I'm going to make a small change here. What I'm going to do, or rather I'm going to convert this into a function. Typically, we call this a forward pass. Forward pass is simply nothing but a small function that you have which can predict the error, which can compute the error and predict the values given any particular value of W1, W2, and B, so to say. So given value of W1, W2, and B, it generates a certain set of values as an outcome. And I'm going to say return. You can divide it by n. If you just want to be absolutely sure, you can divide it by n. Okay, that's it. So that's your function, forward pass function. Now what we're going to do is I'm going to make a small, what I'm going to do is I'm just going to write a small piece of code for doing the weight updates, right? So weight update, so define weight update of, essentially going to update the same set of weights that we just discussed. Whatever these weights are, W1, W2, B, and the predicted values, Y preds. They'll require the predicted values and the W1, W2, and B, right? So it'll require all of these values. Actually, I don't need to pass these because these values are already there in the global context. So I don't need to pass these values, but that's okay. Let's just pass it anyways. So when you do the weight update, so W1, how do you update W1? So remember one thing, right? So W1's weight update, and I need to make updates for each observation, right? So for I in range of 1, so I'm going to make, for each observation, I'm going to execute this. I'm going to first compute dou MSE by dou W1 is equal to, dou MSE by dou W1 equal to how much? Which is the value that I have here. That is going to be 2 times for each observation, right? I can divide it by 2 later. 2 times predicted value, which is Y preds of I minus the actual value Y of I, right? Multiplied by X of I. And last but not the least, dou MSE by dou B. That's it. So once you get these, now what do? You do the weight updates. So W1 is how much? Or minus equal to, W1 is equal to W1 minus. Now here's the thing. We need to get a value of alpha. What's the weight update step? The actual weight update step is how much? What's the actual value of weight update? So W1 minus alpha times dou MSE by dou W1, right? So you need to, of course, come up with the alpha over here. So you need to make an assumption for the alpha. So let's make an assumption here. We'll change the alpha later. I'm going to assume this to be 0.01 or something. We'll come back to what the actual value should be later on. Let's come back here. Minus alpha times dou MSE by dou W1. That's it. Those are now your new W1, W2, and B respectively. And I'm going to return W1, W2, and B. So after all the weight updates happen, you'll get this as the output. So you have done a forward pass, which will get you your predictions. And then you will have weight updates. Okay, awesome. All right. So this is to perform individual one forward pass and one weight update. So let's actually run it one after the other, right? So now let's actually go back here. This is randomly initialized weights, forward pass and weight update. So now let's run one forward pass step. What does forward pass return? Forward pass returns this and this. Total error is equal to forward pass of what's the forward pass that we have here? W1, W2, and B respectively. So now you get preds and total error and forward pass. So this is going to give you the predicted values and the error. And after that, what you need is you need these predicted values to run the weight update, right? So print total error. So this is, let's say, iteration 1. You do the forward pass. Step 1 is in iteration 1, what do you do? Step 1 is forward pass. Step 2 is weight update, right? And then you repeat this. Iteration 2, step 1 forward pass, step 2 weight update. Now, before we do any further, what I'm going to do is I'm going to print some stuff out so that it becomes very easy. And I'm going to clear everything on the right side. I clear all drawings. So what I'm going to do is before I execute this, I'm just going to print the total error. I'm going to make, iteration 1. And I'm going to say error is, what's the error here? Total error. And then W1, W2, and B is equal to, and then you also print your, so you get, and we'll decide what values to, we'll just come back here and paste this here somewhere. This is your initialization, okay? Where these are the weights that you've initialized. Step 1, you're generating the predictions, total error, forward pass. You're printing the error. Step 2, you're repeating the same process. And then what you're going to do here is I'm essentially going to bring the same thing here again, right? And then what I'm going to do is I'm going to print the same thing here again. This is iteration 2, and then I'm going to print the updated weights here. So the point that I want to show you is how you need to orchestrate this. So if I just execute this, look what happened. And I can actually execute one more maybe. This is iteration 3. Iteration 3, total error, weight updates. I need to make a small change. Weight update and weight update. That's one small change I need to make. Yeah, so this is your data. By the way, for those of you who are thinking, where did I mention alpha? Alpha is here. And function, weight update. So now let's go. So this is iteration 3. So look what happened. I forgot to put the print, but that's okay. So initialize weight. These are the weights that we've started with. Okay. Your iteration 1 is getting executed here. The initial error is 322. W1 is 10, W2 is 16, and your bias is here. Iteration 2 with these updated weights gave you an error of 16,000. What does that tell you? Did the error increase or reduce? It should have ideally reduced, but it ended up increasing. Okay. But we still went ahead and updated the weights. And if you take these weights and if you actually run iteration 3, now look at the error. The error has further increased. It's exponentially gone up. No, the error didn't reduce. It increased. It was 165,000. And then here you have approximately 12 million or I think 1.2 billion, right? So clearly your error increased. So what do you need to do? Exactly, reduce alpha. Fantastic, reduce alpha. So what was the value of alpha that we started with? 0.01. So I'm going to go 0.001. Now let's see what happens. Same thing again. Right? Let's run this again. I'm just going to put a print statements properly here. So now, now let's look at it. Okay, not bad, right? It's still increasing, but the rate at which it's increasing has significantly reduced. Do you agree? 320, 2859, 2852. Okay, it's not bad. So we are headed in the right direction. So what do you need to do now? What do you need to do now? Reduce more. Absolutely, as simple as that. We're going to put another 0 over here just to see what happens. Let's run the same thing again. There you go. You've hit gold mine. Congratulations. What do you see? Your error is 322 to start with. 322 has gone down to 215. 215 has gone down to 161. Do you see this reducing? Make sense? All right. So now you get the drill. So what do? I write a simple function that just orchestrates the whole thing, right? Now you just write a small function that orchestrates the whole thing. Instead of you doing this, copy pasting the code, what do? You orchestrate this. Just put a small for loop over here or a while loop over here and run it, right? So how do you do that? Let's go. Let's quickly do that. So okay, so let's do this. So the parameter definition, params. So alpha 0.0001. And then weight initialization. What's the weight initialization? Let's go here. Let's copy this piece of code. That's the weight initialization. I'm just basically putting everything into the same piece of code. That's what I'm doing here. Same into one cell. That's your initialization. After your weights have initialized, what do you do next? Now the orchestration, the complete execution of the code, right? So now what I'm going to do is, look, I'm not going to define the stopping criteria. Instead, I'm just going to run for like 100 iterations and see how it goes. I mean, best case scenario, you can decide how to iterations. I'm going to run for 100 iterations and see how it goes and then decide. Okay. I'm also going to capture, see, all that I need to do is for iterations in, for iter num, I'm just going to use the, in range of iterations, I need to just basically execute this code, right? What do I need to do first? I need to execute this, and then I need to print this. And here I simply put iter num. And then after that, I execute this line of code. And then after that, I'm not going to print this because it doesn't make sense. You know, every time I'm pasting the updated weights doesn't make sense. That's it. That's all that I need to do. The thing is, if I also want to capture how well my error is reducing, I can also create a small error function over here where I capture this error. So error dot append of total error. And that's it. And that's it. I run this for 100 iterations and let's see what happens here. Look at that. Cool, right? The error is nicely reducing. So 322, 215, all the way up. So it's a little slow because it ran for 100 iterations, but still did not get to an error of 0. What I can try is maybe I'll try to bump this up a little. It was 0.0001, right? I've increased it to 0.0005. And let's see what happens. There you go, done, almost. 0.4 now. You see, I've increased the learning rate a little. And by 99th iteration, it has almost become 0. Do you understand that, everyone? What I can do now, if you want to, by the way, look at the weights, you can plot this, you can run this line of code. Where is that line of code? This is the final weights, 1.92, 0.0006, and B is 0.46. These are your final weights. I mean, you can increase it a little more, maybe a little more. Maybe there is something in between here. There you go. See, it's increasing now. Now my error is increasing. So 0.0065. Let's try this. That's probably it. I mean, you can go a little more, but for this data set, I'd probably not go beyond this. And I've stopped at 100 iterations. You can choose to run it at for 200 iterations if you wish to. I mean, that's totally your choice. You can run it for how many iterations you want. But as I said, beyond a certain point, the error reduction is going to be very minimal, which is why what you can do, percentage matplotlib inline, import matplotlib.pyplot as plt, and plt.plot of error, plt.xlabel is iterations and plt dot y label is MSE and plt dot grid. So look at this. It started with 322, right? And then what happened? After like almost the 50th iteration or so, I mean, almost even here, if you think of it, the error really hasn't reduced much. It has sort of flattened out. So you can say, man, there's no point in going any further than this. It's like your elbow plot, remember? From your, I don't know, if you've done clustering, you would know this. Exactly. K-means clustering, not KNN, from K-means clustering. So you can go, somewhere like 70, like around 40th iteration or so, and then you simply stop there and you say, okay, after 40th iteration, I don't see any further any further reduction in terms of the error, so you simply stop there. Simple as that. Make sense? All right. Cool. Congratulations, everyone. Congratulations on your first perceptron model, or a first small model. In this case, a neuron or a simple perceptron model. Now let's get going, right? So the one thing that I wanted to discuss before I speak about neural networks is this. So as I said, one of the challenges with regards to one of the issues that you would typically face is this. So when we started with mean squared error, so let's discuss about cost function. All right. So cost function is what? Just a quick refresher. So if, let's say, you're dealing with a simple equation like simple perceptron that looks like this. X1 is the input, and with bias, W is the weight. You're doing a simple summation. Y hat is equal to W1 X1 plus W2 X2. W1 X1 plus B. So X1 W1. W1 X1 plus B. That's essentially what Y hat is. Now, nothing wrong with this. Everything goes all right so far. And what we said is, to find the best possible value of W and B, we will take a simple, we're going to be using mean squared error as a cost function. Summation of I is equal to 1 to n, predicted value minus actual value, the whole square. Right? And there is a mean, there's a 1 by n around this as well. This is the cost function. And what we said is, this is all great. This is all great. What we're going to, what this sort of translates to is whatever you're seeing here. If you, for example, for a moment don't have bias, so MSE, if you're just dealing with weight, this one is a nice parabola. This equation is a second degree polynomial in W1. It's a quadratic equation. It's a nice parabola. You have a bottommost point, and with gradient descent, you randomly start with any particular point, and then you compute the gradient, bases the gradient to decide which direction to grow. And then you start slowly trickling down from here to the bottommost point. This is what we had discussed. Great, fantastic. In 2 dimensions, this becomes in 2 dimensions, instead of this being a parabola, this becomes a paraboloid, right? Whatever we spoke about, this becomes a very simple paraboloid, a bowl kind of function. Exactly. So you add another dimension here. This becomes W or W2. Let's say for the moment, let's just consider this as bias. This is bias B. And then this instead becomes as you can see, a nice bowl-shaped function. The moment it becomes a bowl-shaped function, what you're now talking about is you're trying to get to the bottommost point by trying to minimize against W1 and B simultaneously. Now here's the question. What if now this starts to become, instead of W and B, let's say you also add one more variable to this. So now you're dealing with W1 X1 plus W2 X2 plus B. Basically, you have let's say one more input, W1, W2, and bias. So now you have W1, W2, and B. You have three variables. Or in a lot of instances, you could have more than three as well. You could have n number of variables. Now what happens? Now this bowl that you see here is not going to be a bowl anymore. This bowl is now going to become a slightly more complex affair. Right? This bowl is now not going to look like a bowl anymore. This will start becoming a, imagine as if somebody is holding the bowl, let's say from either side and twisting it. Imagine somebody is holding it from either side, and then and you're actually twisting it in opposite directions. What would you get? You would essentially get a plane with a lot of crests and troughs. Now this is a 3D projection of it, or a 2D projection of it, so to say. It's not exactly going to look like this, but this is how you can sort of think about how this might look like, right? Now here's where things start to get super tricky. What do I mean by things getting very tricky? So this is not necessarily, and this is where you need to start thinking about the math a little slightly differently. So the point is, when you start creating a hyperplane like this, higher number of dimensions, automatically what starts to happen is you would start seeing many minimas. You see, there are multiple points over here where you see that the gradient is equal to 0 against a particular if MSE, in this particular case, if you consider MSE, the gradient is either equal to 0, or it seems like there are multiple minimum points, and that's where the complexity sort of kicks in. So then you would have, maybe this is your global minima meaning across the complete function, there is one largest possible minima, and then there are other local minimas. There are minimas, but they are minimum in that particular neighborhood. They are minima, but they're minimas in that particular neighborhood, right? So these could be local minimas, so to say. Now, here's where the complexity starts. So let's say you start somewhere here. For whatever may be the reason, let's say you started here. You've randomly initialized, you started here. Now, in the process of trying to minimize, so you've started to trickle down, and now you suddenly caught here. You got into this particular point and you're caught here. At this particular point, if you compute the gradient, dou MSE by dou W1 is probably 0. Dou MSE by dou B is probably also equal to 0. The point is on dou MSE by dou W2, this is also probably equal to 0. Point is, it might seem like that's the minimum point, but it technically isn't the minimum point. It might seem like there is no better solution at that particular point than where you are. And that might start to become a bit of a challenge. That might now start to create multiple challenges. So what I'm trying to get at is, and if I just have to oversimplify this for the moment, this will now start to look like this. You will have a global minima, but instead of one global minima, you will have, along with one global minima, you'll also have multiple local minima. So it is quite possible that when you start somewhere, let's say when you start here, you start to trickle down, and then you suddenly are stuck there, and it might seem like it is the minimum, but in reality, that is not the minimum. The unfortunate point is that you don't even know if this is the global minima or not. The unfortunate reality is you don't even know if this is the global minima or not. So think of it this way. You are like an ant. You are exploring, you're descending down the hill. Suddenly you come to a particular point and you look around, you suddenly see there are all mountains around you. It seems like you're stuck in a valley, but you don't know if there is a lower point than where you are, because you're now stuck here. You don't know if there's a lower point than where you are. So if at any point in time, if you're stuck at a local minimas are not bad. Just letting you know, local minimas are probably all right as well. Man, I can live with this as a local minima. Local minimas will still give you a decent result. It will give you values of W1, W2, and W1, W2, W3 and bias, which will probably give you a very, very fairly low MSE. But that might not necessarily be the best solution that might exist out there. Which is why you are always dealing with an element of approximation. You will never get, or you are never guaranteed a perfect solution. You are never guaranteed that you will get to the bottommost point. You will get to a place where the error seems low enough. You don't know if that is actually low or not. Because, see, this is where the algorithm is sort of exploring. And this is the place, this is the cost function, right? What you're trying to do, what your gradient descent is trying to do, is your gradient descent algorithm is helping you navigate through this maze and help you get to this bottommost point. But the reality is, in the process, you might get stuck somewhere. It might, and in that particular point, it might seem like the minima, it is the minima. There's nothing wrong with this minima. It's just that it is not, there is probably a better solution somewhere. When you're stuck in this minima, you don't know if that's the best minima or if there's a better minima elsewhere. So you are stuck at a minima. Is this MSE the lowest that I can get to, or maybe there are other things that are out there that can get me a better result? I don't know. And that's where your gradient descent, right? Your gradient descent algorithm will needs to start getting a little smarter. This gradient descent needs to become a little more intelligent, right? It just cannot be this very simplistic algorithm that we just spoke, right? Imagine, how do you reach that? How do you reach at that global minima? We can attempt at reaching that global minima. You will never get to the global minima, or you will never know if you can get to the global minima. It is not a deterministic solution. So here's the thing. There are certain approaches that are there. What if you take a double differential? You can take a double differential, but you can very clearly see that you will have multiple results here as well. Double differentials will tell you if it is a minima or a maxima, but it will not tell you. It will not tell you which of those do you need to explore. And the kind of complexity that we are dealing with, Kishore, here, just letting you know, we are dealing with hundreds of variables. So the number of the number of minimas that you're probably dealing with will be fairly large. So it is not a, that's the point, right? This is not a very deterministic world. This is where this is not a convex function. This is a non-convex function. So dealing with non-convex functions is a little complex. Again, point is, how can your gradient descent become intelligent? Now, this is where one of your friends, I think it was Mohit, if I'm not wrong, said, hey, can we do something with this whole learning rate thing? Right? Mohit was saying, I'll just run this algorithm, I'll keep the same learning rate, but I'll run many iterations. And if you do something like that, you can run millions of iterations, but if you're stuck in this local minima, you will never come out of it. So just by running many iterations, it will not take you anywhere. It will take, you're probably guaranteed to get to the minimum point if it is a nice parabola like this. But the reality is our world is never that nice. Our reality is the right. Real world, real world, right? Everything on the left side is real world, everything on the right side is the real world. So which is why just by increasing the number of iterations will never get you to the bottommost point. So you need to get a little smart. That's where you need to start using things like your learning rate. So I'll give you a small idea. Imagine I have an algorithm which gets me to this minima, maybe one of the minimas. I don't know if that's a local minima or a global minima. It gets me to a minima. And then while I am suddenly see that my minima is almost, while I see that my curve is not learning any further. What do I mean by my model is not learning any further? Meaning I don't see that MSE is not reducing any further. What we do is we suddenly increase the learning rate. If you suddenly increase the learning rate, what's going to happen? There is a chance that instead of making a small update, you will make a bigger update and actually get out of this. Now, point is, so that's where suddenly injecting the learning rate can get you out of the minima, but you're not guaranteed. Exactly like Vibhor is saying, it is possible that you might get stuck somewhere else. That is possible. It is absolutely possible that you might get stuck somewhere else. You will get out of this minima, you'll basically getting out of one shithole and then you'll probably fall in another one. It could get as thing as that. The point is, then can we go back to where we were? Yes, absolutely. You can go back to where you were because you can kind of keep a history of all the updates that you have made. You can go back to where you were. You can always trace back. You can always trace back to where you were, and then that helps. That's number one. Then there is another interesting way to solve for this as well. We use a concept called momentum. There's a concept of momentum and inertia. So momentum, I mean, that's a great formula, but the reality is momentum is essentially a concept of trying to maintain the velocity of a particular object bases its weight, right? So once you catch a little bit of momentum, you continue to progress in that particular direction for a little longer than otherwise. Um, um, Entities with larger mass are likely to have, at the same velocity, are likely to have a higher momentum than the others. Same concept. The point is, while you're entering, let's say, this minima, or once you start seeing that, you know what, my minima is reducing, imagine I add something called as a momentum. So you're essentially moving in a bit of a momentum. You're moving in with a bit of momentum. What that does is you could kind of dodge the minima at times. Right? You might completely dodge the minima. It's like this. So imagine you're driving a car and then you have a pothole. What do? Imagine you're moving at a decent enough speed. You might not even actually get into that pothole. You might just actually breeze through that pothole because your rear wheel is actually spinning fast enough to take your front wheel out of the pothole even before it actually goes down. If you actually slow down, you might actually get into that pothole. It's as simple as that. That's the idea. So you move at a certain decent enough velocity for you to get out of some of these smaller minimas. So it could help you dodge these minor local minimas, but you might still get stuck in a larger minima. But that's one of the other approaches to get into to get away from this particular minima. So Joyita says, yes, if you have higher momentum, then you could also, I mean, as much as what I said is true, the concept on the other side is also true. That as much as you can miss out on, as much as you might dodge a minima, you could also dodge a global minima. It's possible as well. So my point is there's a trade-off, which is why I'm saying this is not a deterministic solution. Your algorithm has to be smart enough to navigate itself. And just to let you know that you don't need to do all of this. Somebody just mentioned the fact that this is hit and trial. This is not hit and trial, guys. I mean, every algorithm, these are exploratory, meaning whatever you're seeing here, there's a concept called random walk algorithm. These are algorithms that actually work like this. They are navigating an uncharted territory and they're trying to find the best possible location for you. So you need to have certain tricks up your sleeve that can help you navigate through that space. So it's not brute force random trials that you're making here. It's not that, okay, let me try this. No, this doesn't work. So let me try something else. No, it's not like you're playing, let's say, Super Mario with like 100,000 lives. You're not. You're trying to be smart with this all with all of this. So there are a lot of interesting algorithms that can get you to the bottommost point. I'll show you, and the reality is that gradient descent has a lot of different variants. The point that I wanted to make is gradient descent that you're seeing here is not the only gradient descent that you and I are talking about. So the gradient descent has many, many variants. For example, your gradient descent has something called as Adam, RMS prop. Is stochastic gradient descent. And then you have follow the regularized leader, FTRL, and so on. And so the list is very, 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 very large. Gradient descent, the plain vanilla gradient descent has a lot of variants. Each of these variants is trying to tackle different kind of an issue like what I just mentioned. Adam tries to implement momentum in some sense, right? Stochastic gradient descent is a variant of gradient descent but does updates much faster than your regular gradient descent. A small variant of gradient descent again. So there are many, many variants of gradient descent that are existing out there. Many different people have implemented gradient descent in many ways to navigate through this complexity. I am not going to get into the detail of, okay, what does each of these algorithms do? I mean, it's too much detail for us to discuss beyond a certain point. I don't think it's worth it. What I do want you to know is that the reality is far from what you see on the left side. The reality is like what you see on the right side. And these algorithms that you see over here will help you navigate through that complexity. Gradient descent does not give you absolute deterministic results. The reality is because of these reasons. It's very hard for you to get deterministic results because of this complexity. You will only get approximate results. You might not even get the most optimal result at times because you might be stuck in one of the local minimas, which might be good enough. Local minimas are not bad. The reality is you don't even know if you're stuck in a local minima. That's the most difficult part here. There is no way for you to know. I mean, for some of the simpler algorithms, simpler setups, you might be able to compute how many minimas are there and everything. But for larger setups, it is much more difficult, meaning when you have larger number of variables, computing the number of minimas is also not very easy. Fusion. Yeah. So now you're talking, right? So somebody is asking, hey, what's the most optimal algorithm? Well, there are different people who have conducted different kinds of experiments. What you're seeing on the screen is essentially an algorithm that gets you to the bottom. These are all different variants: SGD, momentum, EDA-grad, EDA-delta. EDA-grad is adaptive gradient. EDA-delta is adaptive delta. RMS prop. These are all different. They're all close cousins of gradient descent. Some better close cousins, better implementations, some easier implementations, some more complex implementations. As you can see, generally, something like a EDA-grad or an EDA-delta does a fairly decent job. As you can see, the yellow line at our delta is like Adam. The star that you see over there is the best result. Any of your EDA grad or EDA delta generally do a fairly decent job. The variant that you should be sort of looking at is something like an Adam. Adam or EDA grad are fairly decent algorithms. So whenever you see, when we pick an optimizer, we generally pick Adam as an optimizer. More thing. In data, the domain of the data does not matter. This is a pure mathematical problem. Data from the medical domain? Am I dealing with data from let's say a telecom domain? That has absolutely no bearing on something like this. This is a pure out and out mathematical problem because what matters is just the numbers. The domain has absolutely no bearing on how this curve will look and what algorithm should I be using. So which is why beyond a certain point, deep learning sort of detaches itself from the actual domain itself. Getting a little, let me show you something. One of the libraries that we will be using for building some of these models, right? We will be using something called as Keras. So one of the libraries that we will be using for doing a lot of this stuff is called Keras. Keras is built on top of TensorFlow. It also now supports PyTorch. But the point is Keras is like a thin layer that sits on top of Keras and TensorFlow and PyTorch. We will be building some of our models using Keras. We can also use underlying TensorFlow or PyTorch. You don't use TensorFlow's APIs directly anymore. TensorFlow only now works with Keras. What I wanted to show you is this. Some of these algorithms, right? They come with all of these inbuilt. Code for any of these inbuilt. The RMS prop, Adam, EDA delta, EDA max, and so on and so forth. So if you, for example, go to EDA grad, what is it saying? Actually, let's go to SGD. What is SGD? You see this here. Weight minus learning rate times gradient. W is equal to W minus alpha times gradient to MSE by dou G. Called as a velocity. Velocity is equal to momentum times velocity minus learning rate times gradient. Basically, something called as a momentum is being applied here. A concept of momentum is being sort of taken care of. And if you look at here, when you're even within SGD, you have this variable called momentum. You can increase the value of momentum. The moment you increase the value of momentum, what's happening is you are simply not just updating basis your learning rate. You see this here? You see this momentum times velocity over here? Sort of taking care of this. So velocity is also getting updated continuously. So you're picking up velocity. Somebody spoke about specific direction. You will continue to move in that direction as much as possible. I'll try to simplify this for you a little. You have a point and you're moving from this is your learning rate. You have decided that forget velocity for a moment. Let's just focus on this one. Weight is equal to weight minus learning rate times gradient, which is essentially your regular update step. Your algorithm decided that, hey, look, direction to minimize your this particular point to this particular point, sure that you minimize your you started here, this point to this point, and there. Fantastic. So your algorithm has moved. So basically you started here and you moved from here to here. Fantastic. You make an update, you to move in the same direction, actually add more update step. An update, again, bases the gradient. Instead of just that gradient, if you continue to move in the same direction, you add a little more fuel to the fire. You actually get it to make that one extra larger stride. Why? Because from the previous step to the current step, I have moved in a certain direction. It's asking me to move in the same direction. Okay, if I'm going to be moving into the same direction, why not, instead of making a smaller stride, let me actually make a larger stride. So instead of adjusting the learning rate a little faster, that is what velocity term is. That is what momentum is, isn't it? You move and you continue that in that direction, particular direction. Imagine you're going downhill. Same direction, you're likely to pick up more velocity. That's what's happening here. Larger weight update over here in that particular direction. Faster meaning you're covering not more data points. No, not more data points, but making a larger leap, like what Vishwas was saying. You realize that you're moving in a different direction. You're making an update in a different direction. Instead of moving in this direction, let's say your gradients decide that it has to move in a slightly different direction. You update, or you don't add the momentum to it, or the contribution of the momentum is going to be much lesser in this particular case. So you can always compute the moment in that particular direction. You can always compute the velocity in that particular direction because it's a vector. But you contribute basis the kind of direction that it is moved. Learning rate will impact the complete learning process. Leap is a more individual step-by-step process, right? You're making that leap for that one step. But if you increase the learning rate, you're making that update for all the subsequent steps. Don't think of the effects, think of the cause. What is causing you to make that larger leap? You're making that larger leap because you've in the past moved in the same direction. So the algorithm suddenly realized that it looks like I'm moving in the same direction. Why don't I actually make a larger leap? That's land here yet again is that there is algorithms that I spoke about, that I'm speaking about, they're all coded. You don't line of code for any of this. That's the best. So these will already take care of ensuring that if you simply say EdaGrad, it will implement the EdaGrad's variant of this algorithm. So somebody has written a paper in 2011 about this. Fantastic. About EdaGrad, here's the paper. Go ahead, read about it in a lot more detail. But what it essentially talks about is adaptive gradient algorithm. It is a variant of the gradient descent algorithm itself. Now the question is, Ashish, my math about all of this? Technically, no, you don't need to, but depends on what your aspirations are. Let's say is to become a research scientist and build algorithms like these and the underlying complexities like this, then you of course need to learn the math. But if your aspiration is, man, I don't need to worry about all of this, I'm rather focused on using these algorithms and solving business problems, then you don't need to know the math. You're an applied scientist, applied data scientist, so you're going to be using these algorithms and implementing them. How to calculate how many leaps do we need to make? You don't calculate that, Varun. It is taken care of by the algorithm itself. Gradient will decide that. If the it will make those updates until the gradient is not 0. Okay. Cool. All right. So now Mohit says, but we should know which algorithms, which of these we should need to pick, and you need to know enough. And that comes generally by solving enough problems. That will help you make the best decision of which algorithm to pick one. As I said, generally when you talk about these optimization algorithms for deep learning problems, Adam and its variants are Adam is actually a pretty decent. 8 out of 10 problems will get fairly solved with Adam itself. High level, I would say rule of thumbs like these, which I will anyways call out. Let's go. So let's go to the next section. Just going back here. So these algorithms, these optimizers are implemented similarly. More thing, which is the concept of Just letting you know, right? That we just wrote a while earlier. As simple as this. In fact, even one line is smaller than this. You load a model from Keras, you load an empty model from Keras. You simply say whatever layer.dense. Forget about what all of this means later on. I'll discuss about Keras.optimizers.atom. So you define an optimizer and you simply say compile. And after that, you simply say train model.train and pass the data set. That's it. 5 lines of code. Here, 4-5 lines of code, and all the weight updates, forward pass, everything will be taken care of by Keras. You don't need to do anything yourself. I wanted to talk about as well. So don't, if you're getting a little fidgety about detail, getting kind of lost, sail through this. From an implementation standpoint, is are actually far more simpler than everything. About another interesting part of this session, right? So understand a few things. We know that very similar to that of your a linear regression model, and the weights associated with a perceptron model are computed using a gradient descent algorithm. Algorithms don't give you perfect results, but they give you approximate results for weights and biases. Each perceptron is a decision-making entity, and perceptron will help you. Is a small machine learning model by itself. 2 steps back from our first session, whole concept of neural network. Hey, look, a neural network is a combination of many biological neurons. A human neural network is a network of biological neurons which collectively make very, very complex decisions. The individual aspect of or element of a particular neural network is a neuron, and a mathematical equivalent of this particular neuron, a mathematical equivalent of that particular neuron was your perceptron, right? That's where we sort of started, and that's where we explored perceptron. That's where we went about discussing how a perceptron sort of works, how the weights and biases of a particular perceptron will work, and so on and so forth. So now today we know how this individual perceptron works. About is we'll take these learnings and then we'll try and extend these learnings in the world of from a perceptron to a neural network. Let's take it to a network. Now, what about this network? A network, as I said, is where multiple neurons or multiple perceptrons are connected with each other. Structured fashion, there is an associated structure to these perceptrons or to this setup. There is broadly a loosely defined architecture of how these neurons are sort of connected. There's a sort of a topology around how the artificial neural network is created, and these neurons or these perceptrons take inputs, process them, and generate outputs. So broadly, and I know how it looks like is you have an input layer where technically there is no processing that happens. These are not neurons. These are just basically, think of these as your inputs. How many ever variables you have. Let's say you have x1, x2, x3, x4. x1 can be age, x2 can be, let's say, experience, x3 can be or let me actually age, x2 can, let's say, be the height of the person, x3 can be the weight of the person, x4 can be maybe the gender of the person, X5 can probably be the maybe if the person smokes or not. Now, basis these inputs, you are trying to, let's say, compute your inputs, X1, X2, X3, X4. You're trying to compute, let's say, an insurance premium for a particular person, age, height, weight, whatever. Becomes your input layer. Nothing really is computed here. It's just a layer where you define your inputs. Have layer. Now, the only reason it is called a hidden layer, I honestly don't know why it's called a hidden layer. The only reason it's called a hidden layer, I mean, in my opinion, it's not, hidden layer is not the right term for this. The only reason it's called a hidden layer is because this layer is the inputs and the outputs in between. Exactly. It's hidden from the external world. So a hidden layer is actually a collection of perceptrons. It has 3 perceptrons in it. Right? We call it, instead of calling it a perceptron, we call it as a node. There are 3 nodes, right? Or 3 units. Unit is a more appropriate term. 3 units or neurons or perceptrons. Any of the terms sort of work all right here. Right? Now, what happens here is all of these inputs that you're seeing here are passed as inputs into this hidden unit. This is, I'm just going to call it, for simplicity, I'm calling it H1, H2, H3. Right? What is happening is these inputs are being passed as, or these inputs are essentially, all the inputs from the input layer are passed as inputs into the hidden layer. And when they're passed as inputs into the hidden layer, they will have an associated weight with it. Right? So W1, W2, W3, W4, W5. They'll all have the associated weight with it. Why weights? Because you need to combine them in a certain fashion. All the neurons cannot be combined in the same fashion, right? They'll all be combined by their own weights. Similarly, same thing here as well. Same weights or same inputs are being passed to H2 as well. Same inputs are being passed into H3 as well. Every input from the previous layer is connected to all the units in this hidden layer. The question is, how many units can a hidden layer have? As many as you want. Can I have one more hidden layer? Yes, you can have one more hidden layer with as many units as you want. The outputs of this hidden layer are then passed into the next hidden layer. Network. Now you think of it. Every neurons in the first layer, other set of neurons in the next layer. Now each neuron is not working by itself. Each unit is a perceptron. No, each unit is not an iteration of the algorithm. Each unit is a perceptron. Each unit is maybe making a small decision. You have is per computing, let's say, your insurance premium. This is generating your outputs, y hat. All your inputs are being combined. Very interesting fashion over here. The outputs of those combinations are further combined in an interesting fashion. Those further outputs are being further used to generate a prediction. So it's like this. Think of it. Let's take one step back. Don't worry about that. example, a human neural, it's not as structured as this, or at least we don't know what the structure there is. It could be far more complex. We don't know what the structure there is. We're assuming this to be a approximate structure. We can be completely incorrect also, and that is fine. That's okay. There are a bunch of inputs, and these inputs, I have passed these inputs as, let's say, age, height, weight, gender, and smoking or not. But these inputs can also be, let's say, the image of a particular person. Image of a particular person. So what you're saying is, okay, your eyes have captured a photograph. Those inputs are being passed as inputs into your hidden layers. There are multiple perceptrons that are perceiving this signal all at the same time. One perceptron is probably capturing the color of the eye. The other perceptron is probably capturing, let's say, the height of the person. The third perceptron is probably capturing maybe the color of the hair. And then all of these put together, the color of the hair and maybe the height of the person put together, you are maybe computing maybe something very specific about maybe something that's a little more complex feature of that particular individual. Maybe the color of the hair and maybe the color of the eye and the height of the person, you identified this to be maybe looks like this guy can be from, let's say, this part of the country. Color is so and so, it's a brown colored eye, and the person is fairly tall, could be from the northern part of this particular region over here. Region you've identified, let's say, the basis, let's say, how the face looks like. You've tentatively captured what the age of the person is, looking at, let's say, the beard on the face and the color of the hair. You kind of identified the age of the person, so you know the age of the person tentatively. Let's say, the from where this particular person comes from. So you're combining both of those to maybe figure out who this particular person is, to find out who the name of the person is. Network starts to work. Each individual perceptron is doing its job. Each individual perceptron is making one decision. What the network is doing is the network is combining multiple outputs from each perceptron and then generating a final response. So now let's dig into a little more depth of this. Okay. So how does this exactly work? The point that I want you all to understand is, as I said, in this case, every hidden layer that you see here, or every unit in a particular hidden layer, is taking the inputs and combining these inputs in an interesting fashion. So what is exactly happening inside this? Let's actually look at it, right? So let's take a small example. Let's actually look at what happens here. So let's take a simpler example. 3 inputs, x1, x2, x3, or actually take 2 inputs to start with. We'll keep it even simpler. And then there is, let's say, 2 hidden layer 1, and then there is the output layer. There's only 1 hidden layer, let's say. So you have So is it mandatory to pass all the inputs only to a hidden layer? Well, if you don't have a hidden layer, if you have x1, x2, and then if you have just one output, then what is this? This is nothing but a perceptron. So if you don't have a hidden layer, it's a perceptron. It's not a simple neural network. It's a perceptron. Simple as that. Okay. So now you have W1, and this is W2. This is W3. This is W4. And this is H2. This is W5, W6. So here the math goes like this. H1 is W1 x1 plus W2 x2 plus a bias B. So here, one thing to note is you will have a bias that travels everywhere. B1 and B2, or you can have the same bias. In certain cases, it's also the same bias. In certain cases, it is two different biases. So B1, H2 is equal to W3 x1 plus W4 x2 plus B2. Y hat is what? H1 is a perceptron. H1 is W1 x1 plus W2 x2 plus B. It is combining the inputs and generating an output. That is a perceptron in itself. What is Y hat? Y hat is W5 times H1 plus W6 times H2 plus B3. There's a bias here. X1, X2 are not neurons. They are inputs. This is an input layer. This is an input layer. These are not neurons. There is no computation that happens in an input layer. Input layer is just a way for organizing the inputs. That's about it. There's no computation that happens in the input layer. These neural networks, by the way, these kind of neural networks are referred to as with multiple names. Name one is called as a fully connected neural network. When we say fully connected, what we mean by it is all the units from the previous layer are connected to every unit in the next layer. That is how we've defined a neural network as. I'll repeat, a fully connected neural network, or simply a neural network. By the way, another term for this is also a feed forward neural network. A feed forward neural network, a fully connected neural network, or a feed forward neural network is essentially a neural network where all the inputs from the previous layer are fully connected, are connected to every unit in the next layer. So which is why all the units in the previous layer are connected to every unit in the next layer. All the units in the previous layer are connected to every unit in the next layer. That is how a neural network is fundamentally defined, so to say. That is number one. Number two, these are called as feed forward because the inputs only flow from left to right. There is no flow of information in any other direction. The inputs are flown to generate the output. The inputs are only moved from left to right, not the other way around. There is no information from this side. There is no injection of information from any other places. Like somebody was asking me, hey, can I pass the inputs into the hidden layer? No, you cannot. It's hidden for a reason. It's hidden because you cannot access them from outside world. The point is, the information only goes from left to right. Only unidirectional data flow. There is something called as back propagation, which we will learn, which also flows information backwards, but that's only to correct the model. That's only to correct the model. There is nothing else apart from that. Now, let's keep going. So now that you understand how a neural network inputs are computed, let's actually take an example. Now, let me give you a bit of intuition here, and I'll actually show you some math here. So the notion here, guys, is that if you have, let's say, something like an height and weight, the hope is that you can create information about your input data that is not explicitly available in your data set by automatically combining them and creating them. By the way, this is something which you would have also done in the past. What you may have done is you would have taken a bunch of inputs, and you would have combined them and created newer features in your data set. Forget about neural network or a perceptron. Take any regular algorithm. What would you have done? Forget about PCA also, even before PCA. PCA is a little more advanced. Even before you get to PCA, what would you have done? You would have taken a bunch of inputs and you would have simply combined it. Have you heard of this term called feature engineering? You all must have heard of feature engineering. You would have combined it yourself to create new features. Now, the point is, at times, you can create features that you and I understand. The issue with feature engineering is you cannot compute features that you don't understand, that you don't know. You would not by yourself try and combine two features randomly out of nowhere. I mean, it's not normal for us. The point is, you will only create features that you know or that you think exist or you think make sense. But who are you to think what will impact the outcome? Your brain is limiting you, or you are limiting your own self from making the model well enough, to work well enough. Point that I'm trying to get at. And maybe that's the whole point of building these models in the first place, right? So you and I don't know what in the data can actually help you determine a certain outcome. Somebody's shoe size might help you determine how long they live. Or like what Jay Kumar is saying, somebody's eye color might determine what cancer they have. Or somebody's, smoking habits might determine, how well their kidneys are actually going to, or kidneys or lungs are actually going to work. Like God knows, some spurious dependencies that you and I don't even understand, some completely random dependencies that you and I don't even understand. So the thing is, you need an engine that can automatically combine these in an interesting fashion and use those to help solve the problem. That is the one of the biggest benefits of a neural network. What a neural network is doing is neural network is giving itself the opportunity to create representations of your initial data or your input data. I'll repeat myself. What neural networks are doing is neural networks are giving themselves the opportunity to create complex representations of your input data through these hidden layers. That is the whole point of the hidden layer. The hidden layer is taking the input data, combining it. Right? If you were to combine, you'd probably combine it in a certain way. But you're saying, you know what, I don't want to worry about this whole combining features business. Algorithm, you take care of this. Neural network, you take care of how to combine these features. I am going to take a back seat. I will just tell you if this output is good or not. You figure out how to combine these features. Right? So now, how do you exactly combine these features? That's where weights are going to come in. That's where these weights are going to come in. Because different values of these weights are going to help you combine weights in a different fashion. So now, hear this out. Hear this all play. It can be zero as well. Of course, weights can be zeros as well. It might decide that, you know what, one of the inputs is useless, and it might make the weight zero for that particular weight, for that particular input. It might simply say, you know what, for computing BMI, age is of no use, so I'll make W1 zero. Possible. But the question is, would you and I know what features it's actually going to create? How does it actually create this? Well, you and I don't decide that. Let's actually come to this example for a minute. And you and I don't decide what features or what information is getting generated in H1 and H2. In fact, I don't even care what's getting generated there. What I care is how that information, that H1 and H2 is contributing to my output. What I do care is how H1 and H2 is contributing to my output. What I don't care is what is actually in H1 and H2. I don't care. I mean, when I say I don't care, that's not the primary objective of this exercise. So it gives the algorithm enough liberty to explore any possible combination of your input data. Now, the thing is, there is no limitation to the kind of combinations that it could make. I can use W1 as, weights can range from minus infinity to plus infinity. Your weights belong to minus infinity to plus infinity. Your W values can be anything on the planet. So then what feature is it actually going to combine? So will these weights be random? Well, let's assume for a moment that it's actually going to be random. Hear me out. When you start, so the objective of the problem is, hey, there are a couple of inputs. There is x1 and x2. There is a target variable y. The x1 can be, let's say, the y can be, let's say, you're predicting sales. X1 can, let's say, be number of stores, the money spent on ads, or whatever features they are. Right? Now, the thing is, this is the problem, and you need to figure a relationship between x1 and x2 that can combine, that can predict y, or some kind of a dependency between x1, x2, and y respectively. So you have set up this network and you said, you know what, I'll pass all of this information through this network, and I hope that somehow I'll be able to learn that particular dependency. How will the learning exactly happen? Step one, when you randomly assign these weights and biases. So you randomly assign all the weights and biases. Now what do? For every input data, can you compute H1, H2 and Y hat? If you compute can you compute H1, H2 if you know W's and input data? Yes. Can you compute then Y hat if you know H1, H2? Can you compute Y hat? If you know W5 and W6 and B, you can of course compute Y hat. Brilliant. So you get the predicted value. You have the actual value, you have the predicted value. Now can you compute mean squared error? Fantastic, you can compute the mean squared error. Now, what do? Once you compute mean squared error, can you then compute the gradients that are contributing to this mean squared error, meaning dou MSE by dou W5? We'll start from here. Dou MSE by dou W6, dou MSE by dou B3. Do you think we can compute these gradients? If I can compute the gradients, what do you think I can also do from here? I can update my weights. Fantastic. I can update my weights. How do I update my weights? I can take W5 is equal to current value of W5 minus alpha times dou MSE by dou W5. This equation should seem familiar rather. Just the way we update W5, do you think we can update the other weights also? Fantastic. If you can update all the weights, now you have updated the weights. Once you update the weights, what do you do next? Repeat. Until when will you repeat? Until your MSE is 0. MSE can never be 0. Your MSE doesn't make, MSE and RMSE will never be 0. One thing you should have realized by now is you can never get to 0. You will need to get to minima, but you don't know if you're at the minima. Once you realize that there is no more improvement in the error, you don't see any change in MSE. From the previous iteration to the current iteration, you don't see any significant improvement in your MSEs. You don't see any significant reduction in your mean squared error. That's a neural network. If you understand a perceptron, what's happening in a neural network is exactly the same, but at a larger scale. But instead of one perceptron, you're doing it with a combination of perceptrons. That's it. The math changes a little. The way the weight updates happen will be a little different. There will be a little more complexity coming into the picture. This is where the whole idea of generating predictions, moving from left to right and generating predictions, is referred to as a forward pass. Using the computing the error and updating the weights backwards is back propagation. Exactly, that is back propagation. That is your weight update step. I was just referring it to as weight update, but technically this is back propagation. What is the difference between the weight update step that we discussed in Perceptron versus the back propagation that we are speaking about here? The only difference is that in the case of back propagation, in the case of weight update, you're just updating the weights then and there. But in the case of back propagation, you are doing it across different layers. The math is a little different when you do back propagation. The math slightly changes. The concept remains the same, the math slightly changes. So you start here, you start with updating W5, W6. See, here's the thing. The idea is simple. When I explain this back propagation better, it'll make it easier. It'll be easier for you to understand. But the logic is this. The logic is that you've computed the MSE here. The contribution of the error is maximum here. This error is contributed by H1, H2, or more specifically W5 and W6 and B3 actually. W5, W6 and B3. They are the ones that is immediately impacting the error. So if you were to update any weights, the first set of weights that you need to update will be these three. Once you're done with that, now if you look at it, W1 is also actually contributing. How is W1 contributing? Through W5. W1 is also contributing, but through W5. So you need to sort of do if you want to, let's say, compute the rate of change of MSE with respect to W1, then you will have to compute the rate of change of MSE with respect to W5 multiplied by rate of change of W5 with respect to H1 and rate of change of H1 with respect to W1. This is chain rule. So which is why you go one after the other after the other. This is the whole point that I was saying. The math will change a little because you're propagating backwards. Because you're trying to compute rate of change of the error at this part with respect to W1. But remember, W1 is directly not impacting MSE. W1 is impacting MSE through H1 and H1 is impacting through W5. So there's a bunch of different hops in between that I need to address before I get to the end. I need to take all of that into account when I'm making the updates. We'll understand the math when I do the examples. It'll make it super easy. So the biggest benefits of neural networks is that neural networks have this amazing ability of creating their own features. It can take the input features and it'll create its own versions of those features and generate the output. What I do want you to understand is the features that they actually generate. You and I cannot understand what those features are. These are mathematical features. Those features are not something for you and I to consume. I mean, you and I probably don't even understand what those features are. These are mathematical features. So it's hard for us to put a finger and say, this is this feature. This is the physical representation of this particular feature. This is a physical manifestation of this particular feature. No, it's not possible for us to explain all of that. Exactly. So here the curse of dimensionality is not a concern. It is still a concern, which is why we will deal with concepts like regularization. There's a bunch of different control mechanisms that are put in place when the training happens. So it is still a concern. There are certain mitigation strategies that are there. So whatever you saw here, right, can actually be written in the form of matrices. Whatever you just saw here, for example, let's consider this. So you have x1, x2, you have x1, x2, and so on and so forth. So if you take, for example, x, or in whichever form or shape, x1, x2, and 1. I'm just going to keep 1 over here, which is for the bias term. And then you have the weight matrix, right? And the weight matrix here is what? W1, W2, W3, W4. And the way we're going to be writing this is as a square matrix. We'll be writing this as a square matrix. And then, and of course, you can write it as, as transposes as well, depending upon however you want it. So H1, H2. So if you actually take a dot product of these two, or if you multiply these two matrices, W times X. So this is going to be what? W1 X1 plus W2 X2 plus B. So you'll get W1 X1 plus W2 X2 plus B. Similarly, W3 X2, W3 X1 plus W4 X2 plus B2 is what you got. So this is H1 H2. This is H1 H2. B can also be in a separate matrix, doesn't matter. B generally is not as a separate matrix, it's a part of the weight matrix. B is a part of the weight matrix. Okay. And here's where matrices are super, super helpful. And then what you can do is you have, so H1, H2 is equal to W dot X, right? You get the W matrix and you get the X matrix. You just do a W dot X and you get H1, H2. And then you need to go one level further, right? So your Y is what? W dot X, whatever your H1, H2 is, multiplied by another weight matrix. This is W1. So similarly, you get another weight matrix, which is W5, W6, and B3, and that will give you your Y, which is and 1. You need to have 1 also added here, H1, H2, and 1, and that will take care of H1W5 plus H2W6 plus P1, which is one output. That is essentially your output in this particular case. H1W5 plus H2W6 plus B1. So my point is that whatever you're seeing here, it's B1. Sorry, B3. You're right, B3. Whatever you're seeing here, whatever math that you are trying to see here, I'm showing it to you point by point, but technically all of this math simply happens through matrices. That's the easiest way to ensure that all of this math holds. That way, the number of observations should not matter. Even if you have many, many observations, X1, X2, how many ever big these observations are, you will still be able to perform this math very easily. That's one of the points that I wanted to make. But otherwise, this is generally how the output sort of looks like. All right, so let me pull up an example and then we can take it from there. So let's consider this network. It's a fairly simple network. So you have X1, you have X2, So 2 inputs, right? Very similar network to whatever we just saw a while earlier. And then you have H1, then you have H2, and yeah, let's just go one output for the moment, right? And this is output O. And every unit from here right? And then you have the weights, and of course you have biases here. There is a bias, but just to kind of simplify some of the math, I'm going to ignore the biases. I just want to simplify the computation here. For the moment, I'm just going to simplify the computation. For that, I'm going to just remove the biases. I don't want to confuse all of us. Just the way we computed for the weights, the biases are essentially computed the same exact way. So there's W1, W2, W3, W4, 5, and 6. And then I'm going to assign some random values here. Let's go 0.15. W2 is, let's say, 0.2. Let's say W2 is and this is 0.2. W3 is let's say 0.25 or something. You can basically, it's randomly being assigned, so you can actually assign anything or anything and everything you want. W4 is, let's say, 0.3. W5 is, let's say, 0.4. And W6 is, let's say, 0.5. I just randomly assigned some numbers. They can be negative as well. However you want, you can randomly assign these numbers. So this is a network. And what you also have is, let's say, a data set. Of course, you need a data set to train this particular model. So I'm going to consider one observation, x1, x2, y. So let's say x1 is 0.05, x2 is 0.1, and your predicted value is, let's say, 0.01. Let's go with something like that. Or, you know what, actually, yeah, let's stick with that, 0.01. X1 is 0.05, X2 is 0.1, and Y is 0.01. Using this data set, right, and assuming these randomly initialized weights and biases, we need to compute we need to predict the best possible values of weights in this case. So how do you train the model? Step 1 is randomly assign weights and biases. That the good thing is that has already happened. What may be the problem statement here? The problem statement, I mean, is, as I said, this is okay. This is the thing. This can be any kind of a problem statement. So, for example, based on the money that you spend on ads and the number of competitors you have, you're trying to predict the sales. Or it could be based on, let's say, the EBITDA of the company and let's say let's say the last month's stock price. You're trying to compute the current month's stock price. It could be anything, any regression problem. Exactly, like somebody was saying, you're predicting any continuous variable in this particular case. It can be literally anything. And that's the thing, that Neural networks, in at least the way we've currently defined it, they can be applied for any kind of a numeric prediction. So the first step is done. The second step is forward pass. What do you do in a forward pass? There are two steps in a forward pass. The step one is generating predictions, right? And then computing error. Given x1 is 0.05 and x2 is 0.1, right? That's the values that we have here. Let's generate the predictions. Sayud, you can use other errors as well. MSE is always used because it gives you a second degree polynomial and it makes the computations easier. So mean squared error is often the most preferred loss function. That does not mean that's the only loss function. You could use other loss functions as well. There is a hinge loss, there is an absolute loss, there is deviation, KL divergence, and so on and so forth. There's a bunch of different loss functions. But when you're solving a regression problem, the most preferred is often a mean squared error sort of a loss function. Okay, so let's generate the predictions. So 2.1, which is the predictions part of it, generating the predictions. How do you generate the predictions? So the first one, x1 is 0.05. So let's compute h1. What is h1? H1 is w1 x1 plus w2 x2. There is, of course, a bias here. I haven't considered the bias. h2 is how much? h2 is w3 x1 plus w4 x2. So what is w1 x1 plus w2 x2? w1 is 0.15, 0.15 times 0.05, 0.05, 0. Plus w2 x2, w2 is 0.2, x2 is 0.1. So you can, of course, do the computation here. Okay, mentioning this the third time. I'm ignoring the bias for the moment. You can consider the bias if you wish to, but for the moment, I'm ignoring the bias. Just for simplicity, no other reason. I just want to show the math. I don't want to complicate it. That's the idea. So H2 is W3 times, which is 0.25 times X1 plus X1 is 0.1 plus H2 and W4 times X2. W4 is 0.3 times X2 is 0.1. So what does that translate to? What is H1? Okay, 0.0275 and H2 is 0.3125. Okay. Okay, awesome. So these are the H1, H2 values respectively. Guys, this should not be very confusing, right? So W1, X1, W1 is this, X1 is this, W2 is 0.2, and W3 and X1 is, sorry, and X1 is X2, which is 0.1. And then H2 is, I made a small, 0.25 times 0. Yeah, that's my bad. Okay, I stand corrected. 0.05, and this is 0.3 times 0.1. And what does that translate to? 0.045. Fantastic. H2 is 0.0. Because it's 0.25 times 0.05, which is 0.0125 and 0.03. 0.425. Fantastic. All right. All right, fantastic. So I think we all get the idea. So we've computed H1, H2. Once you have H1, H2, how do you compute the output, the predicted value? You need to, of course, compute the output, right? So to compute the output, I'm just going to call it O1 because I don't want us to assume that to be 0. And then O1 is going to be how much? 0.4 times H1. So it is W5 times H1 plus W6 times H2. So it is 0.4 times 0.0275 plus 0.5 times W6, with W6 is 0.5 times 0.0425, which is essentially going to be, so O1 is going to be how much? 0.03225. Brilliant. Okay. Now, this is O1. Now let's compute the error. So you have computed the predictions. You have the prediction. The actual value is supposed to be 0.01, which is basically what you were expecting. But then the predicted value is 0.03225. So the MSE in this particular case, which is 2.2, computing MSE is what? Is actual predicted value minus actual value the whole square. Summation I is equal to 1 to n. Here I is just 1. And that is, of course, divided by n. So n is 1. So you're simply taking O1 minus y the whole square. O1 is 0.03225 minus 0.01 the whole square. This is 0.01 the whole square. And yes, you can, of course, do the math. 0.03225 minus 0.01 the whole square. Let's do it here instead. It's easier. 0.03 minus 0.01 whole square, which will, of course, give me whatever that number is. So 0.0000 or 0.0049. Fantastic. That's the number. So your error, MSE, is 0.000495, whatever. Now that's your mean squared error, right? Brilliant. Now what? So you have your predictions, you've generated the predictions, you've computed the error. Now the next part, the third step. Now do the back propagation, right? Now for me to do the back propagation, we need to start one by one. So I now have computed the error. The error here is 0.000495. And now I need to propagate this error backwards and then compute the gradients. So this will, of course, have two steps by in itself as well. What are the two steps in this case? There will be gradient computation. There will be gradient computation. and then there's going to be a weight update. Now let's compute the gradient. Let's take, so now from here you need to update. So you're going to update one weight at a time. So we'll compute what we need to get to, just to kind of make it simple for you, is, so W5 is equal to W5 minus alpha times dou MSE by dou W1. Alpha is something that you and I can understand. You and I can remember. We know what alpha is. Alpha is a learning rate. We will make an assumption of what the alpha is. Dou MSE by dou W1. This is the dou W5 is the gradient that we need to compute. Dou MSE by dou W5 is the gradient that we need to compute. W5 current value we already have. So we're going to make an update for W5. W5's current value is 0.4. We need to make a change in W4 in such a way that it has a positive effect on W5. That it has a positive effect on MSE, meaning it brings MSE down a little more. So how do you do that? And by the way, just the way you do this update, you need to do the same update for the others as well. W6 minus alpha times dou MSE by dou W6. And you need to do the same for all the other weights as well. So let's first start with one layer and then we'll come to the other layers later. So let's start with this layer. Let's start with these weights, W5 and W6. So how do you compute the weights here? So first let's talk about the gradient. 3.1. Exactly. This is gradient descent. Nothing different here. But you need to compute MSE. So if you come back here, what is MSE? MSE is, we just computed MSE. Predicted value minus actual value, the whole square. So O1 minus Y, the whole square. So MSE is equal to O1 minus Y, the whole square. And O1 is what? W5H1 plus W6H2. MSE is equal to, so W5H1 plus W6H2 minus Y, the whole square. Now from here, you can of course do two gradient computations, right? From here, you can compute dou MSE by dou W5 and you can compute dou MSE by dou W6. This is going to be 2 times O1 minus Y multiplied by, I'm going to differentiate with respect to W5. So I'm going to get H1 here. Similarly, on this side, this is going to be 2 times O1 minus Y multiplied by H2. Simple as that, right? 2 times O1 minus Y is, what is predicted value minus the actual 0.03225. That's the predicted value, right? 0.03225. 0.03225 minus 0.01 times, what is H1? 0.0275. So that is dou MSE by dou W1. You can do the math and let me know what the value, so dou W5, you can do the math and let me know what the value is. Similarly, on the right side, this is going to be 2 times, same thing again, 0.03225 minus 0.01 multiplied by H2. H2 is 0.0425. Fantastic. 0.0425. And of course, that will give you another value of dou MSE by dou W6 as well. So just, can you? We're trying to find the slope. We're trying to find the gradient. Gradient and slope mean the same. We're trying to find the slope or the gradient of this particular curve at, with respect to W5 and W6. Yes. 0.00 1, 2, 4. I'm taking this at face value. And the second one is 0.001891. 0.001891. Brilliant. Okay. Okay, 224. So you get the gradients. Now, once you get the gradients, now can we go back and do the weight update? Now let's do 3.2. The 3.2 part, which is the weight update. So for you to do the 3.2, what do you need to do? So let's firstly update W5 is equal to W5 minus, let's consider alpha as, let's consider alpha as 0.01 minus 0.01 times dou MSE by dou W5. What is the current value of W5? What's the current value of W5? 0.4. This is 0.4 minus 0.01 times. What's dou MSE by dou W5? 0.001224. 0.001224, whatever that number is. Now you get the final value of W5. Actually, let me do one thing. I'll just consider alpha as 1 for this example. I don't want to complicate this because the numbers are super small. So I want to make sure that the values are at least have some level of significance. I'm going to consider this as 1.0. Generally it is 0.1, 0.01 or whatever, but the values are super small, right? You might not be able to see significant difference, which is why I'm considering this as 0.1. So 0.4 minus 0.001224, that becomes 0.398. Fantastic. So W5 is 0.398,776. Fantastic. Congratulations. That's your new W5. You don't do anything with this. You keep that. What is the current value of W6? 0.5. So 0.5 minus, you have the other value on the other side of the screen. So this is going to be 0.5 minus 0.001891. So W6 becomes what? 0.498109. Fantastic. That's your new W5 and W6 respectively. Congratulations on your weight updates for W5 and W6. Brilliant. So far, so good. Now is where we've completed W5 and W6. So now let's go one level back, one level further back. Now we need to update weights for W1 to W4 as well, right? So you've done this for W1, W5 and W6. So now let's do the same for W5, W6. Sorry, W1 to W4. I'm going to just show you how to do it for W1 and the rest should the process should sort of be the same. So same thing again, the weight update step for W1 will remain the same. Nothing changes as far as the weight update step is concerned. So W1 is going to be W1 minus alpha times dou MSE by dou W1. Formula is the same. We just have to calculate dou MSE by dou W1. So now here dou MSE by dou W1 has to be computed. Here, this is a bit of a tricky aspect. There's nothing tricky about it. It's just the way it's sort of set up. Right? Let me just go back here. So for us to compute dou MSE or rate of change of MSE with respect to W1, as I said, you will have to make a couple of hops, right? The way you're going to be computing that is we are essentially going to be using something called as a chain rule, which is, by the way, the same sort of the formula that we just discussed earlier. Right. So in this particular case, and it depends on how complex the algorithm is, right? It depends on how complex your network is, rather. In this case, it's a little straightforward, so I'm going to try and keep it very short. So MSE here, right, is dependent on H1, right? Whatever is the value of H1, you kind of build it on top of H1. And then H1 is then further dependent on W1. So instead of directly computing MSE with X1, I'm sorry, with W1, you say dou MSE by dou H1, right? And then dou H1 by dou W1, right? That's how you're going to be computing it. So very simple. You're going to be jumping nodes, exactly, f of g of x. So this is composite functions or chain rule, however you call it. So dou MSE by dou W1 is dou MSE by dou H1 and multiplied by dou H1 by dou W1. Now what we're going to have to do is we're going to have to compute each of these different terms, right? You're going to have to compute each of these different terms. And that should sort of be pretty straightforward, right? So for example, how is MSE dependent on H1? MSE is equal to O1 minus Y the whole square. So how do you compute dou MSE by dou H1? By the way, this thing can be written as W5 H1 plus W6 H2 minus Y the whole square. So dou MSE by dou H1 can be 2 times O1 minus Y multiplied by W5 because you're differentiating with respect to H1. So you will have the current value of W5 over here. That is dou MSE by dou H1. And then what is H1? So that's this term. You can substitute the actual value. So you can take the current value of O1 and Y and W5 and you can get the dou MSE by dou H1. What's the value here? So 2 times what is O1 minus Y? We've already done that here, which is basically the same thing as this. Copy. And let's come here, right? And then that's where you get 2 times. And then of course you need to multiply this with W5. What is the current value of W5? The older value, not the current value, but the older value, 0.4. So you simply substitute 0.4 over here. So that will give you dou MSE by dou H1. Right? Not the new value, the older one. Not the new value, the older one. Similarly, dou H1 by dou W1. So H1 is equal to W1 X1 plus W2 X2. So dou H1 by dou W1 is going to be how much? This is simply going to be X1. And the value of X1 is, what's the value of X1? What's the value of X1? 0.05. Fantastic. So X1 is 0.05, right? Then you of course need to multiply both of these. So 0.05 times whatever this value is. So dou MSE by dou H1 is how much, by the way? What was this value? 0.0178. And then this is 0.05. So 0.0178 multiplied by 0.05, 0.00089. So this value becomes 0.00089. If this value is 0.00089, I'm assuming you can do the rest. If you get dou MSE by dou W1, can you do the rest? Which is W1 minus alpha times dou MSE by dou W1. Same as this one. So same as this one. So W1 is equal to W1 minus 1 multiplied by dou MSE by dou W1. W1 is minus 1 times 0.00089. So W1 becomes how much? 0.4911. Fantastic. Congratulations. That's your new value of W1. W5, W6, same way W1, W2, just the way you've computed W1. Do you agree that you can compute the same for W2, W3, W4, and so on and so forth? Now, the thing is, with all of these weight updates, what do you do then? So let's say you updated all these weights and these weights. Then what do you do? So once that is done, then your back propagation is complete. Then what do? You repeat. You again generate the predictions with the new weights and biases. You again compute the MSE. You again compute the gradient. You do the weight update, and then you continuously do it. You continuously do it up until where? Until you don't see that MSE is not reducing any further. Now that you all understand this, I'm going to try and summarize this, and then we'll progress a little more. So what have we learned so far? We made some progress. So we've defined a neural network. We understand what a neural network is. A neural network is essentially a setup that when given a set of inputs can generate a certain prediction, just like any other machine learning model. Neural network is the same. It's just that a neural network is made up of multiple smaller kind of neural networks, smaller kind of algorithms, right? Each of this is a perceptron. We know how a perceptron works. A perceptron typically works by the concept of gradient descent. You randomly assign weights and biases, and then you try and update. So the concept for a neural network is also the same. Just the way you will solve any regression problem, the same problem can be solved using neural networks as well. As I said, do not treat deep learning or neural networks or perceptrons as alien species. They are not. It's just that it's a more complex algorithm that does a lot more things, that has the ability to do a bunch of different things that other algorithms cannot. That's the only point. It's just a more advanced algorithm. That's the way for you to think of it. So we've introduced this idea of neural networks. We said that a neural network is a collection of multiple perceptrons. You have a hidden layer. So you have an input layer where the inputs are organized. You have a hidden layer where the inputs are processed, are taken in as inputs, and then you take a combination of your inputs in such a way that you generate an output. You generate a certain representation of your input data that is not already there in the original data. So essentially, feature engineering is sort of automated in a way. So the model already has the ability to combine input features and create newer representations of that particular data, and generate a certain output. Those features that are generated in the hidden layer can be further passed to other hidden layers to further create more complex features. For example, the hidden layer 1 can identify if there is an eye or not. Hidden layer 2 can probably combine those eyes and then helps you identify the color of the pupil and so on and so forth. And what we've also done is we have also created we also understood what the underlying math for a neural network looks like. It's a combination of a forward pass and a back propagation step. A typical forward pass and back propagation step has two substeps. A forward pass has prediction generation and computing the mean squared error. A back propagation step has gradient computation and weight updates. That's typically back propagation for, let's say, the first layer from the backwards is relatively straightforward. It is very similar to that of your perceptron, but for deeper layers, you will have to apply this concept of a chain rule, like what we just did here, right? You'll have to apply this chain rule. Requires a little bit of understanding of differential calculus. If you're familiar with differential calculus, this should be super straightforward. Now let's talk about adding hidden layers itself. What does adding hidden layers mean? If you add one more layer over here, so you have, this is your input layer, you have one hidden layer, and then you have another hidden layer, and then you have the output. So you have, let's say, added one more. Exactly. So this is already taking your input data and it is combining complex features. So as I said, if this is a photograph of a person, this is identifying if there is an eye or not in that particular photograph. right? The first layer is probably trying to identify if there's an eye or not in the photograph. The second layer is trying to capture the color of the eye. The third one is probably capturing, I don't know if the how is the person wearing, let's say, a lens or not. Maybe that's what the next layer is capturing. So the point is, the deeper you go, the more complexity you're trying to extract from the algorithm or from the data. And the nuance is here. Here you're trying to capture the if there is an eye or not. Here, and along with the eye, you're also maybe trying to capture, let's say, a bunch of different information. You're capturing the color of the hair, you're capturing the color of the skin. All of those put together, you're trying to maybe in the next layer combining that information to create something else. Because if I know if there's an eye, I know the color of the skin, I have the color of, let's say, the hair, and if I know the location that the person comes from, I can combine all of this information to identify what color pupil the person could possibly have. I don't know, I'm just guessing. Who am I don't know. My point is, the next layer is going to take all of this as inputs to try and maybe create one more complex representation of that input data. Then the next layer is going to combine this even further to create some slightly more complex features, and so on and so forth. Now, Joyita's question is, how do we know which node is capturing what feature? You don't know. That's the black box nature of this model. That's the problem. You don't know. You will guaranteed that you will get an algorithm that will get you better results. But what feature is it exactly computing? You will know what the value is, but you will not be able to understand what that value means. Meaning, it might be creating a mathematical feature, but you and I might not understand what that mathematical feature is. I mean, if I combine, let's say, somebody's shoe size with, let's say, skin color and create a feature, and if actually for some reason that feature is actually contributing to predicting the outcome well enough, what will you infer out of that? There's nothing that you and I can infer out of that. If it's working, I mean, the point that I'm trying to get at is that's the kind of features that it creates. Now, Shubham says, does it mean more layers means more accurate results? More accurate results in this particular case is not necessarily dependent on the number of layers. Because I mean, it could be one of the ways to contribute to the layers. But remember one thing, as you're adding more layers, what are you also increasing? You're increasing complexity of the algorithm, meaning you're creating more weights, you're creating more biases, you're creating the computational challenge becomes a lot more. So again, it doesn't guarantee you good results. It could give you better results. It doesn't guarantee. Nothing is guaranteed in the world of neural networks. Exactly. It could be overfitting. So it might so happen that you're fitting a super complex model in that case. So those are some of the challenges. If I tell you what the weights are and if I tell you what the value in the hidden layer is, can you do anything about it? The answer is no, I cannot do anything about it. If you say that I'm more comfortable to take a variable and cube it myself and then use that to generate a prediction, or take a square root of my original feature, original input data, and then pass it to the model myself, I am then more comfortable, then sure. So be it. I mean, then stick with a linear regression algorithm. You shouldn't even be going with a deep learning model. If you're seeking more complex results, if you're seeking better, more accurate results, then this is one of the options that we have at the moment. And the beautiful part of it is it works. There are techniques that can help you attribute even in a complex neural network setup like this. Given a particular input, you can attribute how much impact one of the inputs has on the output without worrying too much about the hidden layers. There are algorithms that can help you do that. There is a concept called SHAP. There is a concept called LIME. You can spend some time and learn about it, and that will sort of already take care of this. So what one of the things that I'm going to be discussing right now is we'll be building up upon the whole idea of neural networks, right? So far Our understanding of a neural network is a neural network, the hidden layers in the neural network help us add more complexity to the neural network. So let's take a neural network, okay? Okay. This is x1, this is x2, and this is, let's say you have a hidden layer, and then you have, let's say, a simple output layer over here, right? A simple neural network. And then you have these inputs flowing in from here to here, and then you have this is H1, this is H2, and you have your weights W1, W2, W3, W4, W5, and W6 respectively. Very simple and straightforward. So H1 is what? W1 X1 plus W2 X2 plus a bias, whatever the bias is, P1. H2 is equal to W3 X1 plus W4 X2 plus bias 2. And then your output or your Y here, Y hat, is equal to W6 H1 plus, sorry, sorry about that, W5 H1 plus W6 H2 plus a bias 3. For a moment, let's actually take H1 and H2 and populate them here. Let's actually do that, right? So Y hat is then going to be W5 times W1 X1 plus W2 X2 plus B1 plus W6 times W3 X1 plus W4 X2 plus B2 plus B3. So if you actually now do this, Y hat is equal to, if you actually take X1 as one of the terms, right? Then what this becomes is W5 W1 plus W6 W3 plus X2 is going to be W5 W2 plus W6 W4 plus, and then you're going to have some W5 B1, you'll have a constant term, which is W5 B1 plus W6 B2 plus B3. Right? Now, the point that I want to talk about is, if you think of this, your Y hat is what? This is sort of a constant value, an arbitrary constant, because W5, W6 will continue to change, but it is still a constant. So I could kind of write this as A times X1 plus, this thing can be written as B times X2 plus this whole thing can be C. Let's put this aside for a minute. What did we tell ourselves? We told ourselves that, hey, look, here are some inputs. If you actually take these inputs and if you combine these inputs in an interesting fashion, you can create some very interesting features of your input data. For example, if you have height and weight here, we said that, you know what, you can actually create features like BMI here. All of us agree on that? That's what we discussed. We said you can actually combine them and create features like BMI. Height square, whatever, doesn't matter. The point is that a feature like a BMI, you need to create BMI, you need to actually take a height, take weight, and you need to actually divide both of them. You need to square one of it and you need to divide the other with the other one. But H1 is being created like this, w1 x1 plus w2 x2 plus b. It is not actually dividing or taking a square or any of these complex mathematical functions. H1 is just a linear combination of your input features. It's taking w1 x1 plus w2 x2 plus b. So do you ever think H1 will ever be able to create features like a BMI? Because with this, you need to take, essentially what you're saying is it is x2 by x1 square is what this particular feature is supposed to be. But the way you've defined H1, can you ever create features like these? Like a BMI? You cannot. Now the question is, what if you add more hidden layers to this? Well, that is why I showed you what I showed you here. Well, you add as many layers as you want. This will only continue to be linear. What I mean by that is you will never be able to create non-linear representations of your input data. You will only be able to create linear representations of your data. You will never be able to create complex features like these. Complexity, when you refer to something as complexity means being able to create non-linear features. What do you mean by non-linear features? Non-linear features are if you have your data points that look like this. This is x1 and this is this is y and this is x. If your data looks like this, the ability to be able to build a line like that, build a curve like that, that is what you mean by non-linearity. To be able to capture that non-linearity. The unfortunate thing is, how many ever layers you add, how many ever units you have, you're only building a straight line here. You're only simply building a straight line here. You will never be able to capture this non-linearity. If you do not, but if you are unable to capture these complex features, then what's the whole damn point of this neural network? If it cannot capture such complex features, then what is the point of neural networks? Wasn't that the whole reason why we started with this? Wasn't that the whole point that we said, you know what, linear neural networks can do this, can do that. But if it all that it's doing is if it's an embellished neural linear regression, then man, the whole point is lost. Sayud says one hidden layer cannot, but more can do it. That's exactly the reason why I built this. That's exactly the reason why I built this. See, forget about this being an output layer. For a moment, let's just assume that this is a hidden layer 2. Instead of y hat, let's just assume that this is hidden layer 2. This is hidden layer 1. This is hidden layer 2, and this is h3. So for a moment, this is h3. This is h3. This is h3. And let's say this is h3. Now, what about h3? This is a second hidden layer. This is first hidden layer. This is second hidden layer. With the second hidden layer also, what did you get? You still got a linear combination, x1, a times x1 plus b times x2 plus c. You are still getting a straight line. You're still not capturing complex features. So my point is that you add as many hidden layers as possible. You add 1,000,000 hidden layers. You will still not be able to solve for it. Then what's the whole point? Then what are we missing here? That is where, my friends, we introduce an interesting concept called as activation functions. What are activation functions? Now, activation functions are small non-linear functions, right? Are small non-linear functions which can inject that complexity, which can inject that, which can basically make a curve from fitting a straight line to fitting that curve, right? It is going to slightly take your output and it will change the representation of the output. It will add a little bit of add a bit of twist, it'll add a bit of spice to it. For some of you who come from math, this is simply going to add a bit of non-linearity to it. Like what? Like this. So one of the very, very simple activation functions is that of just taking a square or a square root is also some kind of a small activation function. I'll give you the intuition here. I'll give you a very simple intuition here and you all will be able to understand this. So the intuition is as follows. So let's take this for a minute. Let's take this data. Okay. So you have this data. Right? There are these 5 observations. Basically, your data sort of looks like this. You have one variable X and then your target variable Y. You have your data as -1, 0, 1, 2, or -2, -1, 0, 1, 2. And then on the right side, you basically have this information, right? So this is X, sorry. Let me just change this. So this is X, X, X. This is like what? A simple classification problem, right? So you have 3 pink dots and 2 green dots, 2 blue dots. Now, let me ask you a simple question. Can you draw one straight line and separate the blue dots from the pink dots here? Can you draw a simple straight line? No, you cannot. Right? You have to draw a curve. Right? You have to somehow draw a curve like that for you to separate these 2 points. Right? So point is, these points are not linearly separable. You cannot simply draw a straight line and separate the points. Yeah. So this is okay. What are pink? Okay. Classification problem. It's like, let's say X is it's any classification problem. Doesn't matter what classification it is. Any kind of a, this is class 0, this is class 1. Think of it like that. Okay. Now the point is, what you can do is, forget about activation function. We'll come to activation functions in a minute. I'll just give you the intuition. So imagine I'm able to create one more dimension here. I take X, but instead I take X square. Instead of X, I take X square. Now what can I do? This becomes 4, 1, 0, 1, 4. So now this data suddenly looks slightly different. Now you have one more additional dimension and this data. So this is the point of adding nonlinearity. So now I've added this bit of squared nonlinearity here. Now, my friends, this data looks a little different. So the 2 here, and this is, let's say, 4, 3, 2, 1. Now this data suddenly starts to look differently. This point goes here, this point goes here, and the pink points and the points that you see in pink are now essentially going to go here, here, and here. Now, can you tell me, can I draw one single straight line and separate the points? You get the idea, right? The point is, by adding a little bit of nonlinearity into your data, problems which were not easily solvable earlier can be very easily solved. Or you can capture patterns that are far more complex. This is the whole point of activation functions. So activation functions are trying to add that little bit of twist into your data. They're just adding that little bit of oomph into your data. They're trying to add a little bit of complexity within your data. There are a bunch of different activation functions. Okay, so First question, why we understood, but why do we need to separate these points? That's the problem at hand. It's a classification problem. Let's say you're trying to solve for a classification problem. You're trying to predict which customers are going to buy a product versus not buy a product. So this target variable y here is your classification problem. Yes or no? So being able to draw a line that separates both of these is what you're trying to do. Logistic regression. That's the idea here, right? You're trying to separate your X's from O's or blues from pinks, like any other classification problem. Like a decision tree. In the decision tree, what are you doing? You're drawing decision surfaces that classify zeros from one classification, one class to another class. It's the same thing here. All right. So what you have done here simply is we've added this additional dimension of X. Earlier, you only had X and Y. Instead of just X and Y, I added one more dimension called X square. Now this X square term, what it was able to do is this X square is a nonlinear transformation. You're multiplying X with its own self. You're applying a bit of nonlinear transformation over here. The moment you add that bit of nonlinear transformation, now your data, instead of becoming unidimensional earlier, you just had X. Now you can plot the same data between X and X square. You see, now the data is being plotted between X and X square. The moment you plot the data between X and X square, data which was not linearly separable earlier has now suddenly become linearly separable, because now you're plotting -2, 4. So -2 and 4. Right? -1, 1, -1, 1, 0 and 0, 0 and 0, 1 and 1, 1 and, or rather 1 and 1, 2 and 4. So now you have this data, these data points on either side. Now you could simply draw we can build a very simple model in this dimension, in this space, and solve the same problem. That's the idea. So the ability to be able to inject that little bit of nonlinearity is what activation functions try to do. Now the question is, hey, can I add any kind of nonlinearity that I want? The fact is, technically you can, but in reality, it adds a lot more complexity to the math. Because remember, adding nonlinearity is not a bad idea. But when you add nonlinearity, you are also responsible for managing that nonlinearity as well, like in the case of back propagation and stuff like that. So there are a fixed set of activation functions that we use. What are the different kinds of activation functions that are available? Well, here you go. Some of the most popular activation functions, by the way, even before we get to the activation functions, just to summarize, one of the primary reason that we introduce activation functions is to add nonlinearity, or rather not add nonlinearity, but actually make neural networks capable to capture nonlinear patterns. You are not adding nonlinearity. Nonlinearity is already there in the data. Data is already nonlinearly, the target variable is nonlinearly dependent on your input data. If that's not the case, simple linear regression or a perceptron can solve the problem. What we're trying to do here is we're trying to make neural networks a little more capable to capture that nonlinear patterns. What are the different functions that are available? The first is sigmoid activation. Right? Sigmoid activation. What do you do with a sigmoid activation? A sigmoid activation, and I'll explain when I explain sigmoid activation how a activation function is also applied. A sigmoid activation is like every other activation function, but in the case of a sigmoid activation, what you're trying to do is you're taking the output f of z is equal to 1 by 1 plus e power minus z. What does a sigmoid activation do? Well, a sigmoid activation. Now you have all learned about what an activation, what sigmoid function does. What a sigmoid function does is it takes any data that is that spans from -infinity to infinity and squashes it between 0 and 1. Not 0 or 1, 0 and 1. It squashes it between 0 and 1. It is not 0 or 1. It doesn't make it 0 or 1, right? So this is 0, this is 1, this is, let's say, a variable z that ranges from -infinity to +infinity. Whatever may be the value of z, what your sigmoid activation does is it tries to squash it between 0 and 1. I mean, we call it a probability because it is between 0 and 1. And it almost gives you like a linear kind of an output, but it is, probability is just one way of thinking about it. But the primary capability of a sigmoid activation is to be able to squash the output between 0 and 1. So your f of z, which is the output, ranges between 0 and 1. Never either 0 or 1. You will never get a 0 or 1. You will only get between 0 and 1. You will never get perfect 0 or perfect 1. You will get a value that will range between 0 and 1. What you do with classification problems is you take that output and it looks like a probability. So what you do is you apply some kind of a threshold. You say anything that is greater than 0.5 is 0, any greater than 0.5 is 1, anything that is less than 0.5 is 0. You apply that threshold in the case of logistic regression. But here what we are saying is you are taking data that is linear in nature and you're applying that non-linearity. So you see this curve. Do you see that the curve is slightly non-linear? Meaning for most part, it might look like linear, but it's a little slightly non-linear on either sides. See that? That's the non-linearity we're injecting. Otherwise, your data would simply look like this, right? Otherwise, this data would simply look like this. It would simply look like a straight line. Otherwise, your data will simply be a straight line like that. But because of that, because of this non-linearity, you're able to nicely add that little bit of non-linearity and you've squashed it between 0 and 1, right? That's the beauty of this. So what we are saying is, so how does it get implemented? So let's take any neural network, right? Let's take a small neural network here. 2 inputs, 1 hidden layer and 1 output. Now what you're going to be doing is this is H1, this is H2. So you have inputs flowing in from here to here, here to here, here to here. This is X1, X2, X3. This is your hidden layer 1 and this is your Y hat. Now, if let's say you say, now here is how activation functions are implemented. What you do with an activation function is you say that you apply an activation function at the hidden layer level. So you say on this hidden layer, I will apply a sigmoid activation. Now, when you apply a sigmoid activation in the hidden layer, what that means is all the units have a sigmoid activation applied to it. Now you may ask, can I have individual activation functions on each of these? The answer is yes, you can, but it makes the math very, very complex. So you don't do it to individual units. You apply the complexity you apply the activation at the complete layer, right? So now the question is, if let's say, so how does H1 now look like? So H1 is going to be what? W1x1 plus W2x2 plus W3x3 plus B1. That is how X1 was before the sigmoid activation. But now, because you have sigmoid activation, there's a function around it. And this function is the sigmoid activation. So then now the updated H1 looks like this. The updated H1 is 1 by 1 plus e to the power of minus w1x1 plus w2x2 plus w3x3 plus b1. That is the output of h1. And the beautiful part of h1 is, for all the data points that you have within your data, everything that passes through h1 and h2 will all have gone through the sigmoid activation. Thereby, they would have all been non-linearly transformed. Now, it is not mandatory for you to apply the same activation function across all the layers. If you have, let's say, 3 hidden layers, on one hidden layer, you can apply an activation function. On the other hidden layer, you can choose not to apply an activation function. That is totally your choice. In fact, on one hidden layer, you can apply one activation function. On another hidden layer, you can apply another activation function, and so on and so forth. If I, let's say, want a feature like BMI to get calculated, now where is that getting calculated? Well, the thing is, again, as I said, I don't know. But if I have enough hidden layers, somewhere it might get calculated. Now, it might get calculated if my model believes it is useful for the output prediction. I don't know if BMI is required for my model or not. If the model believes it's required for the output, then it will get created. How am I saying it is important for the model or not? Back propagation. When the values get back propagated, automatically the weights will get adjusted in such a way that some of these features will get generated. I don't know where it will get generated, how it will get generated. That I cannot guarantee. So this is sigmoid activation. Similarly, there are other kinds of activation functions as well. What are other activation functions? Let's go for the second one. Rectified linear units, also referred to as ReLU. Yeah, why minus infinity to infinity in the graph? Because, and you're okay. Before applying h1, before applying the sigmoid activation function, this w1x1 plus w2x2 plus w3x3 plus b1. Okay. So what we are saying here is, whatever may be the input, negative to minus infinity to plus infinity, the output will always be positive and will always be between 0 and 1. The f of z will always be between 0 and 1. That's what we are saying. So the second activation function is, as I said, called as rectified linear units. And rectified linear units, if you've learned rectifiers from your electronics sessions, rectifiers and diodes, this is inspired by that. Very simple nonlinearity here. All that it does, I'll give you the formula or meaning the equation in a minute, but all that it does, same thing again. This is f of z. This is z minus infinity plus infinity. What it does is it says everything that is positive, I will let it be. Everything that is negative, I will squash it to a 0. That's it. So what it says is f of z is equal to z when z is greater than or equal to 0, rather greater than 0, and z is greater than 0, 0 otherwise. Otherwise it's 0. It's also written as f of z is equal to max of 0 comma z. It can also be written like this. Whatever may be the input value of z, it is always the maximum value between 0 and z. So it might seem like this is linear. I mean, if you just ignore this part of the curve and if you just focus on this part, it might seem like it is linear. Similarly, on the left side, if you just ignore that part and if you just focus on this part of the curve, it might look linear, but both of them put together is non-linear. Very little non-linearity, but absolutely worth non-linearity. In fact, rectified linear units are some of the best activation functions. simply because of their simplicity. Just because of their simplicity, they can capture some very small non-linearities themselves, right? They're very simple, very easy to implement. Yeah, man. So, okay, let me ask you a simple question. Is square and rectangle a linear or non-linear object? Square and rectangle are linear or non-linear object? They are linear objects. They are non-linear objects. I'm sorry. They're all non-linear objects. Each side may be linear, but if you take, for example, the complete curve, that's a non-linear curve. Each of this is a non-linear curve. Okay? Because as x increases, y does not linearly increase. It increases, and then after that, it stops increasing. And after that, it actually reduces, and so on and so forth. The point is, x and y are not linearly dependent here. Same is the case here as well. This part of the equation is linear. This part of the equation might be linear, but both parts put together are not linear. The third activation the question, when we say activation function, is it activating the next neuron? No, it is activating that neuron itself. It is activating. So when you refer to something as activating, it is activating the non-linearity within that particular neuron. So when you say this neuron is activated by sigmoid, what that means is there is an element of nonlinearity injected into this particular output, and that is the sigmoid nonlinearity. And that is what we mean by activated neurons or activation functions. These activation functions will activate a certain neuron. Then there are a bunch of other activation functions. I'll just discuss one more, and then we can talk about some of the others later. The third and the most popular activation function is referred to as a tan H activation, tan hyperbolic X. These are hyperbolic functions. The function looks like this: f of z is equal to e power z minus e power minus z by e power z plus e power minus z. This is the activation function, how it looks like. So if you see this, it's very similar to that of your sigmoid activation function. It's just that the output ranges from -1 to +1. Instead of 0 to 1, the output ranges from -1 to +1. That's the only difference. So this is -1, this is 1, and this is minus infinity. This is positive infinity. The curve looks like this. Kind of like that. I think I just... That's how it sort of looks like. So this is 1 and -1. Same like sigmoid, but it's just that it gives you that element of non-negative values as well. So the f of z ranges from -1 to +1. Now, all of this is great. There are a bunch of other activation functions, and there's a lot more for me to discuss about activation functions. Now that you understand all of this, I want to show you a bit of visual explanation of what we've discussed so far. We've discussed perceptrons, we've discussed activation functions, we've discussed neural networks, we've discussed activation functions, we've discussed adding additional layers in a neural network. We discussed about adding additional units in a hidden layer. Let's put all of that into some kind of a visual action, and I'll show you a very interesting visualization. Let me pull up something interesting here. So what you're seeing on the screen is a bit of a visualization of how a simple two-dimensional classification problem can work, right? What do I mean by this? Now, so what you're seeing here is essentially a data set that sort of looks like this. Okay, so you have, so you have x1, you have x2, and then you have y. Y is essentially a classification problem. So you have blue points or orange points, right? So BO, BO. It's not a clustering problem, it's a classification problem, a binary class classification problem. And you have two features, x1 and x2 respectively. So you have values 2.5, 3.1, 0.5, 0.6, and so on and so forth. And then you have blue points and orange points over here. The task at hand is to build a simple classification model that can classify the blue points from the orange points. The blue points and orange points can be customers who have taken a loan, customers who have not taken a loan. This can be the salary of the particular person, and on the y-axis you may have, let's say, the family size of this particular person, right? Somebody who's got a higher family size and a higher salary is probably not likely to take a loan. Higher family, lower salary is probably likely to take a loan, and so on and so forth, whatever the combination is. My point is, that's what you're seeing here. Now the thing is, what you're seeing here, now tell me something. Do you think this data is linearly separable? Do you think if I simply, can I separate these two data points using a simple straight line? Can I draw a simple straight line like that and separate it? Perfect. Let's do that. So what you have here is a simple perceptron. So you have x1, x2 as two inputs, right? And then you have a simple output over here, which is generating an output over here. And then the hope is that you'll be able to draw that. And then this is, of course, has W1, W2, and an associated bias. And the idea is you're able to generate that straight line that can classify both of these data points perfectly. What is the first step in terms of linear in terms of a perceptron? This is a simple perceptron model. What's the first step? The first step is to randomly assign the weights. So you see here, these weights are randomly assigned. If you restart, these weights are again going to change. Minus 0.33, minus 0.053. Different values of these weights will give you a different line here. Now, what we're going to start doing is we're going to start training. What do you mean by training? You do a forward pass and then you do a back propagation and update the weights. In the process of doing that, you see here epoch, by the way, simply means nothing but an iteration. Right? And there's a learning rate that is set up over here. For the moment, I'm not applying any activation. Linear activation means no activation function. And forget about everything else. Don't ignore regularization late, ignore all of this for the moment. Okay. I'll hit the play button and see what happens. Done. That's it. Now, do you agree that the orange points and the blue points are perfectly classified? You see the weights have now changed. 0.7, 0.72. The line has been perfectly formed, right? The line has been perfectly formed over here. Somebody may have defined the bias here as well. I don't see it here, but the bias is there. There is a bias associated with it. 56 iterations. Exactly, 56 iterations and the problem has been solved. No hidden layers. Do you think with this data, can I draw one line and separate both of these? No, right? Of course not possible. We need to add a curve. Now, how do I do that? So what I need to solve a more complex model. So, but my x1 and x2, these are the different features that I have. I just have x1, x2. What I can do is I can use my brain and then I can try and if I actually continue to train, you see this here, the loss is not reducing. I'm not able to build a model. I'm just not able to build the model here. Well, let me add a hidden layer. Let's see what happens. Am I able to build a model here? I've added a hidden layer. Is it improving the model performance? No. Well, let me add more hidden layers. Still doesn't solve the problem. Why? Because it still is linear. There is no activation exactly. This is still a linear activation. I can add as many neurons as possible here. I can add as many neurons I want here. I will still not be able to solve this problem. I can try as much as I want. I can build the world's most complex neural network. I will not be able to solve. Why? Because the activation is linear. Now, same model, right? I can do one of two things. I can either add a hidden layer and add an activation function, or I can use my own brain and I can try and come up with complex features like x1 square, x2 square. Remember x1 square, x2 square, I spoke about it? Well, if I create something like that, I am able to create a complex dimension, complex model here. If I add x1 square and x2 square as added features, how have I added this? I don't know. Yeah, somebody, Sriram is saying, hey, I can add x1, x2, and that will solve the whole damn problem. Yes, of course it will solve the problem. But how do you know, or how would I know what feature to create here? How would you or I know what feature to create here? I mean, here you are visually able to see the data, hence you said, let's create x1, x2, and we'll be able to solve the problem. But otherwise, I cannot guarantee what computation I need to do. You said x1 and x2, x1 multiplied by x2 here. What if it is x1 square by x2? What if it is x1 cube by x2 square? I don't know, man. I don't know. What if it is sine of, like somebody's saying here, sine of x1 divided by sine of x2? I don't know what feature to create. That's the whole point of neural networks. I don't want to break my head with engineering features. I want my model to be able to automatically create its own features. I will create the setup. I will let my model create its own features. So now what I will show you is we will stick with x1, x2 only, the same initial features. I'm not going to create any features myself, but we will solve this problem. How will we solve the problem? I'll add a hidden layer. I added a hidden layer. I executed it for a run with linear activation. It did not work. Now let me change the activation function. Now let me introduce a little bit of nonlinearity. Let me add a sigmoid activation to this. Let's see what happens. Same setup. Added a little bit of nonlinearity here. I added two features. I execute this. Look what happens. Look at that beauty. Do you see the nonlinearity getting injected into this? Has it solved the problem? No, it hasn't solved the problem. But has it gotten better? Absolutely yes. Now what do I need to do? Can I add should I? Okay, now you tell me, what do I need to do here? Do you think I should add more hidden layers? Do you think I should capture more non-linearity? Or do you think it's capturing non-linearity, but it doesn't have enough features to solve the problem? Exactly. I might actually just add another neuron here. I'll just probably add another neuron here. I'll try to run it again. Let's see what happens. Look at that. Do you see the beauty of neural networks? I haven't done anything. I haven't made any changes to the data. My data is as it is. I just created the environment. I added a hidden layer, and I added the necessary activation function, and it took care of this. Right? This is the reason why neural networks are referred to as function approximators. They're referred to as universal function approximators, meaning whatever may be the function, they can actually approximate for it. Given the input data and given a certain architecture, they can approximate for anything. Okay, let me actually stop this. Now, instead of sigmoid, let me show you the same thing, but with a ReLU activation function. Look at that. ReLU activation creates more sharper edges. You see that there? ReLU can create more sharper edges. Now, if I do the same with one more neuron, it almost solves the problem for me. So with ReLU activation, you can actually get to the best solution much faster, much cleaner as well. Here is where different activation functions behave slightly differently. Different activation functions have different behaviors, right? Now let's look at, it's not to say that one is better than the other. It's just that these act a little differently.
Hello everyone. Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also through this course we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.
All right. So we were discussing about activation functions. Even before we went all the way up until activation functions, we spoke about, why activation functions were required, right? So we introduced ourselves to the whole idea of why activation functions were required. We told ourselves that when it comes to neural networks, the hidden layers are only good if and only if you have these hidden layers doing additional math, right? For example, in this particular case, you have the initial idea was that your hidden layers will act like a perceptron, and these perceptrons are simply going to be doing linear combination of your input features. However, unfortunately, what we've realized is when we actually went about doing this, we realized that, well, just by keeping it like a plain vanilla hidden layer, it is kind of as good as just having how many ever layers you have. It doesn't really add a lot of value. And then, as an outcome of that, we decided to go ahead and have and introduce something called as activation functions. Activation functions are essentially small mathematical operations that are done on top of your hidden layers that will help neural networks capable of capturing nonlinear patterns. And we learned about a couple of activation functions. We learned about sigmoid activation, rectified linear units, tan H activation functions. And then we also went about understanding this through this one particular example. This particular example from TensorFlow Playground, wherein we looked at a bunch of different examples. We said a data set like this doesn't require any hidden layers. You can just solve it using a regular perceptron. But the moment you start adding a little bit of nonlinearity, without having a hidden layer, it's hard for you to solve a problem like this. But the reality is, even if you add a hidden layer, but if you don't add any kind of activation functions in those hidden layers, you will still not be able to capture this particular pattern. But the moment you start adding activation functions, you start seeing that nonlinear patterns start to get captured. And those nonlinear patterns are the patterns that those nonlinear patterns are what we are interested in capturing more and more. The moment you add more neurons, you see that more and more hidden features are often captured in this particular, or hidden patterns are captured in this particular case. The same, on the other hand, if you were to go for data sets that are further more nonlinear, as you can see, such kind of nonlinearity can be very easily captured using models like these, where the moment you have an activation function with a hidden layer, it becomes so much more easier. And we're going to take this one step further. We're going to try and solve the same problem, but we're going to try and address this using a little bit of code, right? In the process of trying to solve the same, we will also introduce ourselves to some very interesting concepts. We will introduce ourselves to concepts like number one, regularization, and a bunch of different topics that we will learn as we go along. So what we're going to be doing, as I said, is we're going to be focusing a little bit on the code. But before we jump into the code, I just want to introduce you to the lay of the land a little, and how and what we will be exploring as a part of this complete exercise, right? So the neural network space, the space of neural networks is sort of populated by a couple of players. You could build a simple neural network using multiple libraries, right? So first of all, multiple programming languages. You can build neural networks using MATLAB. You could do it using Python. You could do it using Java, and so on and so on. So many programming languages that will help you build neural networks. But the reality is that all of these neural networks are great, but it's just that these neural networks are all these programming languages are great, but it's just that some programming languages are better than the other, some are more production grade than the other. For example, some are a little more easier for you to debug and to work with. For example, you could build program your neural networks using Java and using Python. You could actually use both, but it's just that interestingly enough, the programming languages of Python are far preferred over Java simply because debugging is so much more easier. Iterative development is so much more easier. Within Python, right, there are many libraries that help you build neural networks. Starting from scikit-learn. Scikit-learn actually helps you build neural networks. There are libraries within Python, especially like scikit-learn. There are functionalities within the scikit-learn package that help you build neural networks. I'll actually show you that briefly. Then there are a bunch of different players. There is something called as TensorFlow, which is very popular, and then there is something called as PyTorch. Right, so you have TensorFlow, you have PyTorch, and then there are a bunch of other libraries as well. Like for example, there is something called as CNT. There was something called as CNTK. There was something called as ML.m. There are other libraries that had come in the past, which are not as popular anymore. For example, TensorFlow was something that Google had come up with. PyTorch was something that actually Facebook or Meta had come up with, right? CNTK was something that Microsoft had come up with, and so on and so forth. So there were a bunch of different players that were introducing multiple deep learning libraries. But that said, the libraries that kind of stuck, as you can imagine, are these two. These are the two libraries that kind of became very popular. TensorFlow and PyTorch have sort of become the go-to libraries as far as any kind of neural network activity is concerned. Yeah, PyTorch is a library, but eventually it's a library that provides a framework for you to build neural networks. It's a Python library. You write some piece of code using PyTorch, but it gives you a structure, an abstractive way of building neural networks, right? So this is the same with neural net PyTorch as well as TensorFlow. Both of these are the same. So what we'll do is we'll start with TensorFlow. I will also show you some examples of PyTorch maybe a little later. We'll start with a couple of examples on TensorFlow. Now the thing is, over the years and the history behind this is that when TensorFlow was launched, right? When TensorFlow was launched, so were a lot of other libraries. Right? TensorFlow got launched, CNTK was launched, and there were libraries like Piano and so on and so forth that were available. And people were running around left, right, and center trying to write code using all of these different libraries. Then came another Python library called Keras. Keras was a Python library that kind of abstracted. That was another high-level programming. That was like a high-level Python library that wrapped TensorFlow, PyTorch, and all of its implementations around it. So Keras sort of became now the most preferred and the most go-to library as far as building any deep learning model is concerned. So Keras gives you a very simple interface. When I say interface, it's not a graphical interface. It's like a very simple structure of code, a very simple framework that helps you build models using TensorFlow or PyTorch. To build it using native TensorFlow functionality in TensorFlow APIs and functions is very complex because TensorFlow uses very complex constructs, and that becomes very difficult for us to work with. So that is one thing that you have to bear in mind. So what we will be doing is we will be doing two things. We will be approaching it in two different ways. So first, we will be using Keras with TensorFlow, right? And then what we will be doing is I'll also show you some implementations of PyTorch, right? Now the question is, which one should you pick? Yeah, you don't have to work directly with TensorFlow. You will be working with TensorFlow through Keras. The one that Microsoft came up with is called CNTK, Cognitive Toolkit, which came and went. This doesn't exist anymore. This library is, it's an open source library, but it doesn't exist anymore. Cognitive Toolkit, CNTK. Now, the interesting part here is that across both of these libraries, the point that I want you to understand is TensorFlow and PyTorch, they're all just the same. They are all trying to do the same thing, right? TensorFlow is one interface, PyTorch is another interface. They're all trying to help you build models. Today, if you think of it, if you look at the world that is using that is building neural networks, TensorFlow around 40 to 50% of the cohort uses around uses TensorFlow, and the remaining 50% uses PyTorch. So the world is equally split. People use TensorFlow as well as PyTorch. There is no real reason to pick one over the other. The way I would want you to think about it is, it's just a library at the end of the day, right? I mean, if you're able to learn TensorFlow and Keras, you should also be able to pick up PyTorch. It's very simple, very easy for you to learn. So just treat it as a library, but I think use this as an opportunity to learn the core concept. And we'll implement some of it using TensorFlow and Keras to start with, and then eventually in the later parts of the session, I'll also show you some PyTorch examples. So that way you'll get a feel for both. All right. Now let's go. Let's actually take a small example, and then we can take it from there. Okay, perfect. So this is Visual Studio Code. This is the past implementation. Let me go new file, Jupyter Notebook. All right. Let's start with a very simple example. Okay. Let's pick any of the data sets that we are familiar of. Let's start with a regression problem only. With the Boston housing prices data set, very simple data set. I'm assuming most of you or some of you should be familiar with it. Okay, let's use the Python 3.12, and then most of this should be doable. So I'm going to use the Boston housing prices data set. Let me just quickly show you how the housing prices data set looks like. Give me a second. Okay. So I'm going to PS path, perfect, import pandas as PD, PD dot read CSV of this is the Boston, right? So this data set, if you look at this particular data set, this is a very popular data set. For those of you who are not aware, I'll explain what this data set is. This data set has approximately around, this data set has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns. And this data set is about the housing prices in Boston, right? This data set. So let me actually show you the Boston housing price data set description. So let's go here. Right. So this is the description of the Boston housing prices data set. There are approximately around, firstly, what is this data set? The data set contains information collected by the US Census Service concerning housing in the area of Boston, Massachusetts. It was obtained from the StatLib archive, and then you say it simply says Boston. And the idea of this particular data set, it is a naturally occurring data set. There are around 506 observations. So this data set has housing prices of different localities or different, I would say, parts of Boston. And within Boston, what you would see is what you would observe within Boston is you would see there are all of these different attributes that have been captured. For example, crime here stands for per capita crime rate by town, right? So every observation is for a particular town. So crime here stands for per capita crime rate. ZN stands for proportion of residential land zoned for lots over 25,000 square feet. So these are residential land that is zoned for lots over 25,000 square feet, essentially giving you an idea of what proportion of these houses are for larger bungalows or larger estates, so to say. Indus is proportion of non-retail business acres per town. Industries essentially. Chas is Charles. If it tracks the bounds of River Charles. River Charles is actually a very popular river in Boston, and if there is a particular town that is on the boundaries of the coast of River Charles, then it is going to be 1, else it is going to be 0, and so on and so forth. Right, so there's a bunch of different features over here. Like for example, if you observe, BK is the proportion of blacks by town, but this particular feature is a slightly, I would say, it's a handcrafted feature. There's some kind of transformation that has gone into that particular feature, but never mind. Last but not the least, you have MEDV, which is nothing but the median value of house prices. So in that particular locality, what is the median value of this particular house, of any given set of houses in that particular locality? So with that context, if you see here, this is the data set, right? So if you look at this data set has 506 observations, 14 columns, 506 rows, 14 columns. Typically, when you take this particular data set, we often use the median values of house prices as a target variable, and we try to use all these as attributes. These are all the attributes of that particular town, and MEDV is the target variable that we are going to try and predict. Now, remember one thing, everyone. When you're trying to solve a problem using the Boston dataset, bear in mind that you are not skipping any kind of task, right? Dataset description is in this location. The idea is not to skip any kind of a task. All tasks are important, all tasks are mandatory. Like for example, generally when you receive a new dataset, you would do an exploratory data analysis, right? You will have to do this for sure. I mean, if you're dealing with this dataset for the first time, this is required, like how you would do in any other example as well. I am going to skip it in this particular case because if I start doing exploratory data analysis right now, we will spend the next 2 hours just doing exploratory data analysis and we will not be able to progress much further. For that reason, I am going to skip it. You are still expected to do this exercise yourself, right? If you're actually solving this as a business problem, you will still need to do this because it is important that you understand what this data set is. Okay. That said, so now let's go. So you have X. So Y is nothing but your target variable, which is Boston of MEDV. That's your target variable. And then you have X, which is Boston dot drop columns equal to MEDV. That's it. So you get your X and you get your Y. So if you take a look at X, this is 506 and 13 columns. Y is whatever we just spoke about. Y is 506 and 1 column. Now what I'm going to do is you have your X and Y. So I'm going to also create the train test splits. Remember, train test split is still important, right? Nothing changes over there, right? So we will still have to create the train test split. So from sklearn dot model selection import train test split. I'm assuming you're all familiar with how the train test split function works. This is not familiar. This should not be new to any of you. So if you look at the description of the train test split, everything is nicely mentioned over here. So I'm just going to use the same thing as it is. So X underscore train, X underscore test, Y underscore train, Y underscore test, train test split of X comma Y, which is nothing but this is your target variable, independent variables. So I'm going to pass X and Y. And I'm saying 33% is test data set and a random state of 42, whatever the random state is. Make sense, everyone? X underscore train dot shape. There you go. 339.13, 339 observations, 167.13, and 167 observations because this is your test data set. Okay. All right. Let's move on. Now let's go to the next step. So your train test split is done. Now let's actually go ahead and build the model, right? So now let's talk about model building. Now, one thing that I want to talk about is Model building in TensorFlow has 3 steps, right? Model building, or in the bracket, I'm just going to say a neural network. Now, here is the point. The question is, why am I solving it using neural network? Can I not solve it using linear regression? Of course, I can solve it using linear regression. Of course, I can solve it using gradient boosting machines. Of course, I can solve it using any of the other regression models that I might know, or any model that can predict a numeric target variable. I would only come to this particular step after having tried out all of those different steps. So my point is, this is not something that I'm just going to go upfront saying, let me build a model using neural network. No, not at all. You would have tried multiple different techniques by now. You would have tried, let's say, linear regression. You would have tried a bunch of different models. Now you're at a place, you're like, okay, now let me try to see if there is a better way for me to get better results. So it's always a choice. It's always a level up. So if you want to say, okay, let me level up, let me see if there's a better way I can build a model, or if there's a model that I could get that could extract more patterns from the data, then I would come to neural network. Now your question may be, if you're like, why would I not want it? Of course, I would always want a better model. Why would I want to go for neural networks? Why would I not want to go for neural networks? It's a no-brainer that everyone wants to go for neural network. The reality is, yes, you can go for a neural network. But remember something, neural networks are not going to give you explainability, right? Neural networks are going to operate like a black box beyond a certain point. You cannot say what caused what, right? Change in what variable has impacted in what output. But if you do the same using linear regression, you will get coefficients. So much more easier, direct attribution. So the question is, what are you looking for? If you want a better model, if you want a better accuracy, neural networks might help. But if you're looking for better explainability, stay away from this side of the world. Stick to more traditional algorithms like the regression models, or let's say tree-based models. Okay. These of course require higher computation as well. It's a little harder to train as well. Now, building a neural network using TensorFlow has 3 steps, right? Step 1 is about model definition. Step 2 is about model compilation, and step 3 is about training. So there are 3 steps that are there. First is model definition. In the model definition step, you do some of these. First one, you define the architecture of the model, meaning number of hidden layers, number of nodes, and you define stuff like activation functions, etc., etc. Right. So all of that is sort of defined over here. Then in the model compilation step, you define the following. What you define is, you define the optimization algorithm, right? Like for example, is it stochastic gradient descent? Is it Adam? Blah blah blah. You remember the drill. All of those different optimization algorithms, and you'll also define things like learning rate and stuff like that. These are certain things that you will define here. Then in the training step, you're going to be defining. That's a good point. Actually, here you'll also define the cost function and stuff like that. Correct. So good point. In the last step, which is the third step, you define. Abhijit says perfect. The number of epochs. Epochs or iterations. Total number of iterations, right? And then you will define you will define the data sets, right? So your X, Y, test and train data sets, etc., etc. So these are broadly the 3 steps that you will have, that you would be using to build a neural network model using TensorFlow. 3 steps. So now let's actually see how this works. Okay. So here is where I'm going to say from TensorFlow dot Keras import Keras dot models import sequential. So here is where I have imported something called as a sequential model. A sequential model is simply nothing but, think of this framework. So the sequential model is like an empty canvas. This is the 3 steps of model building. Once you build a model, then you evaluate. There is some kind of evaluation that you also do during the model building step. I'll talk about that as well. Let's talk about building the model itself. Okay. Do we need to install the package for TensorFlow? Yes, you need to. Let me show that to you. Let me show how you can install a package. How do you install TensorFlow? So let's go here. So if you go to TensorFlow, download TensorFlow. So that's it. That's all that you need to do. Pip install TensorFlow. Just run this line of code. You don't need to do anything else. The moment you install pip install TensorFlow, it will immediately download TensorFlow for you and you'll be up and running. You don't need to do anything else. Make sense, everyone? That's as simple as it. If you're using Collab, you don't need to do this. TensorFlow is already available on Collab. Okay. Now, so from TensorFlow.keras.models, import sequential. So fantastic. The sequential library, sequential interface is sort of instantiated. What do you mean by sequential? Sequential, think of it like a blank canvas. So an empty canvas is what you have created. Now here, what you're going to do is you're going to start building one by one. So you're going to say model is equal to sequential. Okay. Now in this, you need to now start adding layers. This is like a blank canvas. Now here you need to start adding layers. What are the layers that you're going to add? Remember, this is a very, very simple model, right? To start with, let's build a very simple perceptron. Forget about everything else. Let's just build a very, very simple perceptron. Forget about hidden layers and everything. We'll just have one input layer and one output layer. Forget about the hidden layers for a minute, because we'll build a very simple perceptron and then we can build on top of it. So you're going to say model.add. Now I need to add a layer over here, right? What kind of a layer do I need to add? So from TensorFlow dot keras dot layer import dense. This dense is nothing but a fully connected layer. This dense is simply nothing but a fully connected layer. Okay. So model dot add. So I'm going to say dense. Now when I define a dense layer, I need to of course define a bunch of things over here. What are the things that I need to define? So when I say dense, let me just so when we define the dense layer, we need to define exactly the number of units. So for the moment, my network looks like this. So you have a hidden our network currently looks like this. Our network has an input layer, and then you have in the input layer how many inputs do I have currently? 13 inputs. Number of input features is your total number of units in your input layer. In your output layer, how many outputs do I have? One. That's it. As simple as that, right? So what I'm going to do is exactly that. So I'm going to say model.add of dense of 1. That's it. Nothing else. Nothing else. Actually, I can simply say units equal to 1, meaning only one layer, only one unit. No hidden layers for the moment, only simple perceptron. We'll just build a very simple perceptron for the moment. Okay, very simple perceptron for the moment. This is your output layer. Why have I not specified inputs? You can define inputs also. So you can also say from TensorFlow dot keras dot layers import input. You can define the input layer also over here. You can say model dot add input of and then you need to simply say input, I think it is shape equal to how many units are we passing over here? We're passing a total of 13 units as an input. So you can do something like that. You're saying, hey, my input. So but you need to remember one thing. No computation here at all. There is no computation here. It's just basically creating them. And this is not mandatory. This is not mandatory. Even if I don't pass this, this will automatically take those many number of inputs. I can simply say inputs, right? This will automatically infer the total number of inputs over here. This will automatically infer the total number of inputs. It's not mandatory for us to provide the number of inputs over here. So point is, even if you pass this, it's okay. Even if you don't pass it, it's fine. If for the moment to make it explicit, I'm just going to leave it there as input. So this is going to do W1x1 plus W2x2 plus W3x3 and so on and so forth. Makes sense, everyone? There is only one unit over here. Remember, everyone, remember one thing. So what is the objective that we have? Our data set has 13 features, right? So crime rate, LSTAT, blah, blah, blah. And then you have your target variable, which is this is X and this is Y. Your target variable is medv. What you're saying is, given all of this, you need to predict. Just a second. So this is your dataset X, right? And this is your dataset Y. You have all of these different features over here, right? Which is X1, X2, X3, all the way until X13, and then you have a target variable Y over here. The task at hand is given these features, you need to be able to predict your target variable. Given all of these input features, you need to be able to predict your target variable. The model that we're proposing to be able to solve this is this. What we're saying is, okay, so to build a model like this, all you require is or a bunch of inputs x1, x2 all the way up until x13, and then you have one output layer or one output unit where connections are connected like this, and then you're generating an output. This is generating y hat. For the moment, it is a perceptron. There is no hidden layer in this example. We'll add the hidden layer in a minute. Don't worry about it. There's no hidden layer for the moment. Okay. Then the question is, how many weights are going to be there over here? So this is what I've defined in the output layer. This is what I've defined in the case of inputs. This is what I've defined in the output layer. This is what is getting predicted as medv. Okay, fantastic. So I'm going to have total of 13 weights plus one bias. So there's also one thing over here which is going to be your bias. So you're going to have W1, W2 all the way up until W13 and one bias. All these 13 weights plus one bias. The output layer. Now the unit that I have defined here, when I say units equal to 1, I am simply saying in my output layer, I just have only one node. I just have only one node in my output layer. That's what I mean by output layer, one node. I'm defining layer by layer. This is the first layer or my input layer. There's nothing, no computation that's happening over here. This is my output layer. How many units do I have in my output layer? I have one unit in my output layer. Between this and this, because these are fully connected, this is a fully connected layer. Because this is a dense layer, all the units in the input layer will be connected to this particular one single unit. So automatically I'll have 13 weights and one bias. So the connections between these two are assumed. When I say assumed, TensorFlow will already take care of this. I don't have to explicitly define W1, W2, W3, W4. The model will take care of it. Kishore, fantastic point. There is no distinction between hidden layer and output layer. All that we use is dense. Spot on. Because an output layer and a hidden layer are what? They're exactly doing the same damn computation. If I just have one unit, it's output. If I don't have one unit, and if I have many units, it becomes a hidden layer. Okay. So the model is defined. Now let's come here. So the first step is done. The first step of model definition is done. We'll come to the next step, model compilation. Now let's define what algorithm is it going to be using. So model dot compile. Here's where I'm going to be using the optimizer. So optimizer equal to, now there are, as I said, a bunch of different optimizers are available. So let's go to Keras. So if you look at the optimizers, there are a bunch of different optimizers that are available. For the purposes of this example, we'll pick any one of these. Doesn't matter. Let's just pick maybe SGD or one of these. Or maybe we can pick Adam. One of these. Doesn't matter. Let's just pick Adam. You see the learning rate? Inside Adam, there is something called as learning rate. The learning rate is defined as 0.001 over here. In this case, you can of course always update it. Or you can just use the term Adam over here. I'm going to say Adam, just using the Adam optimizer. You can use any optimizer, doesn't matter. I'm just using the Adam optimizer. Then one of the other things that you also have to define is the loss. Loss function is also referred to as what? Cost function. Loss function is also referred to as cost function. So what's the cost function in this case? What problem are we trying to solve for? Regression problem, numeric prediction, right? So now let's go back here. So if you see losses here, there's a bunch of different losses that are available. Probabilistic losses, regression losses. Okay, fantastic. That's what we're looking for, regression losses. So you see mean squared error. There's mean squared error loss. Fantastic. Let's just use the mean squared error loss function. There's mean squared logarithmic error. There is mean squared this error. There's mean squared mean absolute percentage error, MAPE, mean absolute error, mean squared error. We'll just simply stick with mean squared error, mean squared error. That's it. So my model compilation is done. What's the third step? I still haven't passed my data sets to this. I still haven't passed my data set. Exactly. Model dot fit, which is the model training step. So in model dot fit is where I'm going to pass x is equal to x underscore train, y is equal to y underscore train. And then I'm going to pass epoch. Let's say I start with 100 epochs. I don't know how many epochs. I don't know how many epochs I need to train this model for. I just put 100. Let's figure. I don't know. 100 is good, 5 is good, 10 is good. I have no clue. Let's figure how many epochs it needs to be trained for. X train, Y train. And then there is something called as validation data. Guys, look, there's so many parameters here. I'm focusing on the most important parameters or most important arguments here. There's a lot of arguments that I can pass. I'm focusing on the most important ones. I'll introduce the others as we go along. I'll introduce more and more as we go along. So I'm keeping it super lean. We will keep adding more and more things to this as we go along. So don't panic if you think that sailing through the surface. We're not. We'll add more and more as we go along. So validation data. So here you simply have to pass your validation data sets, right? Which is x underscore test, y underscore test. That's it, done. X test and y test. Perfect, done. And if you just run, this should train your model. Congratulations. Your model is getting trained. What do you observe here? What does this loss mean here? By the way, we'll discuss each of this. What is this loss? MSE, fantastic. That's MSE. This is MSE training loss, and this is MSE validation loss. Right? And what do you observe here? It says 1 out of 100. This is 1 out of 100. Something interesting. Okay. I'll explain what is the difference between loss and validation loss. Now, if you observe, it went all the way up until 100 by 100. All the 100 epochs were complete and the model training was done. All the 100 epochs were complete and the model training was done. The train loss was 180. The validation loss was 167. Blah blah blah. There's a lot that we need to dig into over here. There's a lot of information here, first of all, that we need to understand. Right. Before we look at the output, don't look at the output. What is happening in these three steps? Step one, you're defining the model. So go back here. Step one, model definition, architecture of the model, number of nodes, activation functions. There is no hidden layer here, so there's no concept of hidden layers and activation functions, but you have defined input layer, output layer, input size, output size, and all of that. Step two is model compilation. What did we define? Optimization algorithm, cost function. Optimization algorithm, cost function. That's exactly what we defined. Step three is what? Training, epochs, datasets. So datasets, epochs, and validation dataset again. That's it. This is where the training is happening. So this is what has happened. So epochs means 100 epochs is 100 times the model has been trained for. Now what we're going to do is we're going to try and understand each of these things over here. There is firstly this 1 by 100, which is great. So what is this 11 by 11? Where is this 11 by 11 coming from? That's something for us to figure. Where is the 11 coming from? Who's defined this 11? What is loss? What is validation loss? How do I know if my model has been trained or not? Is this good enough or not? Is this good enough? Should I go even further? Should I stop? What do I do from here? Of course, less loss is better. But how much is less? How much loss is less loss? Is this good enough? A loss of 180, a validation loss of 167. What does that mean? What does that mean to you? 11 is not the number of inputs. There are 13 inputs. Okay, so we don't know if we reached minima. We will never know if we reached, but we'll figure. So let's try and double click into this a little. So what we're going to do right now is we're going to step away from the code for a couple of minutes and then we'll come back to the code. What I want to explain is I want to explain what this is, what you're seeing over here. I want to explain firstly, what is it that we are seeing here? This is extremely important. Whatever we're going to be discussing, super, super important. This is fundamental to a lot of the things that we're going to be learning moving forward. So what is loss and what is validation loss? Let's discuss that first. It's simple and straightforward actually. Loss and validation loss. The concept is simple and very, very straightforward. Nothing that you all don't know anyways already. So train, test, and validation set. So I'll explain. What did you do? In the model training step, when you defined the fit step, you passed two sets of data. You passed X train, Y train, and then you passed X test and Y test. Right? This is being used for your training data set, and this is being used for your test data set as validation. This is being used to train the model. This is being used to validate the model. What do you mean by validate the model? So what is exactly happening? is when you've defined the model, your model is this x1, x2, x3 all the way up until x13, and then you have this is your input layer, this is your output layer. In your output layer, you have this is your output layer. You just have one unit in your output layer. This is what is generating as an output. Now, the thing is, when you call the fit step, what happens is your train data set. How many observations are there? A total of 339 or some observations. I don't know, 337 or something. Those 339 observations are going through a forward pass. So you're doing a forward pass for those 339. So there is a forward pass for 339 observations. So here there is a matrix that is of size 339 by 13. Does this make sense? 339 by 13. Why 339 by 13? 339 observations, 339 observations and 13 columns. So 339 by 13 is what is being passed as an input. And then you're generating an output of 339 by 1 column, 339 by 1, only one observation. Does this make sense, everyone? Right? So here in between, there is a bit of math that's going on across these 13 observations, 13 features. Actually speaking, it's not just 13. There is 14 because of bias. What's going to happen is you will have, this is 1, and you'll have bias. So technically, though it is 13, in reality, internally it is 14. In reality, it is 13, internally it is 14. So this 339 by 14 is getting multiplied by what matrix? Your weight matrix. I want all of you to be on your feet over here. This is something that we had already discussed previously. So this is something that I expect all of you to know. So your X, which is underscore train, which is the original data set 339 by 14 is getting multiplied by a weight matrix, a weight and bias matrix. I'm just calling it W, which is going to be of size what? Which is going to be of size 14 by 1, 14 by 1, 14 rows and 1 column, right? A 14 by 1 matrix. This is giving you an output of 339 by 1. So for those of you who know matrix multiplications, the number of columns in the first matrix, and the number of rows in the second matrix should match for both the matrices to be multiplied. And this is, my friends, your y hat. Y is equal to x times w. Is this clear, everyone? And this is happening for all the 339 observations. This is forward pass. Then what do? Then you do the back propagation. For you to do the back propagation, what do? You take y, this is y hat underscore train, predicted value. Then you take y underscore train, the actual value. Then you do mean squared error computation. So for example, the value here can be 28, 35, 15, blah, blah, blah. And the actual value could be 22, 30, 20, and so on and so forth. So then you do actual minus predicted the whole square. So then you do the computed value, then you compute the mean squared error. So you take 28 minus 22 whole square, which is going to be 6 square, which is 36, 35 minus 30, 25, 15 minus 20, 25. And then you take a summation of across all of this. So that is going to be your mean of the squared error. And then once you compute MSE, then you back propagate. When you back propagate, you update all the weights in these 14 weights over here, the 13 weights and one bias. That's the forward pass and back propagation. That's the combination that's currently happening. Now, my friends, what you're seeing here as loss is simply nothing but this loss here is MSE after this iteration. This is mean squared error after this particular iteration. This summation that I spoke about, that's that loss. Now, similarly, just the way you did this on train dataset, do you agree that using the same weight matrix, you can do it on the test dataset as well? So you can use the same matrix instead of 339 by 14. What will this be? Whatever is the remaining. So 167 by 14, same weight matrix. The weight matrix doesn't change, the same W matrix. This is X train, this is X test. The same weight matrix will give you y hat underscore test. This is unseen data. And then you do the same thing, y underscore test. Then you compute your mean squared error. This is completely on unseen data. So this is a validation loss. This is on the train loss. This is on the validation loss. Does this make sense, everyone? Do you understand the difference, everyone? In your understanding, which loss is going to be lesser? Is mean squared error loss, is the train loss going to be lesser, or the validation loss going to be lesser? Which one do you expect to be lower? Train, of course. It's like this. You've prepared for an examination using a textbook. Now you're being asked questions from the same textbook. Of course, you're expected to do well. But you've prepared for an examination from a textbook, but now there are questions that are coming from elsewhere. They're conceptually the same, but the questions are not from the same textbook. The questions are coming from elsewhere. If you really learned, I would expect you to have performed well enough on the questions that are coming out from another textbook as well. That is validation data set. Conceptually the same questions, but not the exact same question. That is what validation data set is all about. Validation data set is unseen data. The model was not used to train, weights are not updated on this particular data set. That's what it is. And the weights are not the same. The weights are exactly the same. So that's number one. So you have loss on the actual data set. This is loss on the train data set, and this is validation MSE. It's saying it's loss, but how am I saying it is MSE? How do I know this is MSE? How do I know it's computing MSE? Why? Because we've defined MSE. Exactly. We told it to do so. I said, boss, train the model using mean squared error. Do your back propagation using mean squared error. Okay. So we're doing both train and test in the same step. So you train the model, one iteration, go forward pass, back propagation, weights are updated. Now you do the test. So you get the train loss and then you get the validation loss, both, and so on and so forth. So now you repeat this across all the iterations, across all the 100 epochs that we mentioned. Okay, which is why you see that both losses are reducing simultaneously. Now, if you have over epochs, if you have train and test performance, what can you also track? If you know the train performance and test performance over time, what can you track? If you know your model is performing well on both train and test datasets over multiple epochs, that means your model is a great model. It's learning very well. Whatever it has learned on the train dataset, it's able to replicate on the test world as well, right? But if your model is doing very well on the train dataset, but it is struggling horribly on the test dataset, the model is overfitting. Exactly. That is why you need this. You need loss and validation loss to exactly track if the model is performing over time or not. Is the model is learning well over time or not? At times, what happens is over time the model learns, but only tries to capture very intricate and complex patterns within your trained data set. It struggles on the validation data set. And that is the time you need to realize that this model is useless. So this is like a nice magnifying lens into how well your model is performing. You might not know if the model is getting to the bottommost point, but then you might not know if the model is reaching the minima or not, but at least you know that to the extent that it is being trained, it is actually learning on both cases. It is learning on trained dataset and it is able to replicate those learnings on test dataset as well. That is why this is very important. So here's a bit of insight into this. So what we are going to be doing next is exactly this. So for example, what we're going to be doing is we will plot over different epochs, right? First epoch, second epoch, all the way up until, let's say, 100th epoch. We will be plotting the train loss and we will also be plotting the test loss. What I would expect is I would expect both of these curves to have a very similar pattern over the number of epochs. Now, for whatever may be the reason, if I start to observe that after this, after what, let's say, 50th epoch or so, there is not significant improvement, then I probably don't need to train the model any further. Maybe just 50 epochs is good enough. But if I see that my model still has a lot of slope, for example, for whatever may be the reason, I see that, you know what, this is not like this. Instead, this is not like this. Instead, your train curve looks like this and your validation curve looks like this. What does it tell you in this scenario? If your train curve and validation curves both look like this after 100 epochs, what does it tell you? Tirunau Keras, what do you think? If both the curves are like this, pointing downwards, what does it tell you? It needs more epochs. As simple as that. It needs to learn more. It's not underfitting, but it needs to be trained for a longer amount of time. So you need to train it for a much longer amount. So the number of epochs that you chose is not good enough. You probably have to train for a little longer. Or you could maybe increase the learning rate and let it train faster. You get the idea? So these are the years where the patterns start to emerge. So before we jump the gun into deciding what next to do, this chart that you're seeing on the screen is extremely important. This chart is the diagnostic chart. This chart is everything that is important. How long will we increase until? So okay, we will not increase until infinity, because after a point, what you'll see is that the line will flatten out. So until you don't see any further improvement. When I say chart, I mean this curve. Whatever you're seeing, these curves. Okay. So as I said, one of the points that we had learned in the minute ago is the fact that it's important for us to track this curve, which is basically a loss curve. A loss versus epochs. It's simply referred to as a loss curve. If you can track the performance of the loss curve, typically you will understand how well your model is performing. If both the curves are together, fantastic. If both the curves are very steep, that means it needs more epochs or higher learning rate. If both the curves are not learning, meaning one curve is like this and the other curve is like this, clearly the case of overfitting. That is why it is important to track this particular curve. So first, let's understand how to track the curve. Import matplotlib.pyplot as plt, right? So plt dot. So what you need to understand is, if you look at model, so if you look at the model.history object, it has, if you look at dot keys, it captures the loss and validation loss over time, right? So it captures the loss and validation loss both over time. Okay. So what we're going to simply do is, I'm going to use that particular loss and validation loss. Now I'm actually going to plot it. So plt dot plot of train loss is equal to model dot history of loss. This is going to be validation loss, and validation loss is underscore loss. Plot of train loss, plt dot plot of validation loss, plt dot x label of epochs, dot y label of loss, plt dot title of loss, curve, plt dot grid, plt dot. So perfect. There you go. That's the curve. So here, if you look at both of these curves, what do you observe? So if you look at this loss started well above, nicely reduced. But if you even look at this part, firstly, both the curves are, actually, let me also plot one more. Plt dot legend. What's the first one? First one is strain, and the second one is, the blue curve is strain and the orange one is validation. So clearly, if you look at the blue curve, and the validation the train and the validation curves is nicely reducing. They are sort of together. Very clear indication that this is a good curve. Basically, this is a good model. So far, the model has learnt well. This is a good fit. However, if you observe, this curve is further reducing. If you look at the slope here, this is still tending downwards, right? Clearly, there is a little more gas to this. You could actually let it run for maybe a little longer, or you could just fasten the learning process, and you could maybe hope for this to actually train a little faster. You could do one of the two. For example, what you could just do is, you could just make it 200. So remember this number, which is 167. I'm gonna train. Actually, I'm gonna stop training. Just give me a second. Stop. Define the model. Compile. Train. So I'm gonna train this for 200 epochs. Let's see what happens here. So it's reducing. This model is actually worse than the older one. Let me train for a little longer. Yeah, it could happen. It's just randomly initializing it, so it could happen. That's totally okay. This one will quickly train. Just look at it. This one will train much faster. Look at this, kind of stuck here now. It's sort of stuck at this 75, 69 mark. It's not going any further. 66, 65, 63, 62. Okay. So now if you look at this curve, it's almost flattened out now. After the 100th epoch, it's almost flattened out. What you can do, of course, is, if you want to just focus in specific areas, you can simply also look for plt.ylim of maybe let's look for between 0 to 100, ylim of 0 comma 200. So if you look at it, I'm looking at only the between 0 to 200. So after almost like the 100th epoch, what you observe is it has kind of reduced, but from like 150 epoch onwards, or maybe somewhere here onwards, actually here, like after almost like the 120th epoch, the reduction from here to any of the rest is actually much lesser. So you're just zooming in into a specific area. When you zoom in, what you see is this is sort of taking a little, not really accelerating. It's reducing. In fact, it is still reducing. What do you observe? This is actually still reducing. If I actually train it further, I even still expect this to reduce even further because this curve is still tending downwards. So I can actually still further train it. It can actually train a little longer as well. But the thing is, and then we can actually maybe train it for maybe another 100 more epochs, a total of 400 epochs. Let's see how long it takes. Let's see what comes out of that. A total of 400 epochs. Let's see if it goes any further. Yeah, we reduced a little more. It went all the way until 60. Yeah, see. So it it's still reducing. Still very clearly a downward trend. Now the thing is, I can continue to do this, or I can make a small change. Exactly. I can make another small change. I'm gonna increase the learning rate a little. So from TensorFlow dot Keras dot optimizers import Adam. So I'm going to import the Adam optimizer. What I'm going to do is instead of using the Adam optimizer like this, I'm going to say Adam of learning rate. The learning rate was 0.001 if I'm not wrong. That I guess was the learning rate. Let's go to optimizers Adam 0.001. Instead, I'm going to go 0.01. I'm just going to go 0.01. Same model 0.01. Let me stick to 100 epochs and let's see where it takes me. Look at this. See that? So I slightly increased the learning rate, and my Adam optimizer sort of took care of the learning rate sort of took care of ensuring that this is this lens. Now it's almost flattened. Now with this learning rate, it is almost flattened here. It's probably not going to go any further. Right? So 40.9 and 46. Yeah, it's probably not going to go any further after this. Beyond this, probably just flattened out there. Does this make sense, everyone? Do you understand what changes we made? What does it mean if the validation loss is small? Nothing much to read there. Just probably because of a subset. It's okay. I mean, there's nothing wrong with it. Okay. So yeah, it's not going to be a massive difference. But if you see a little bit of aberration over here and there on that. All of this, remember, without a hidden layer. There's no hidden layer in this so far. Okay. So now let's go one step further. So now we know where can we actually stop. Both slopes should be the same or almost a straight line. So the question is, I mean, you can still continue to train here, in my opinion. You can still continue to train a little further. There's a bit of a little bit of a disturbance sort of creeping in, but still both are reducing nicely. So I would actually just continue to train. I would just go maybe another few more epochs. I would just continue to train and see how the model performs. So I would not maybe worry too much in this particular case. I would just probably train for a little longer. Yeah. Now what do you start seeing here? You start seeing the yellow curve and the blue curve start slowly starting to separate here. Not significantly, but slowly starting to separate, which means there's a little bit of very initial bit of overfitting that's starting to creep in this case. Right. Why are there some disturbances in the curve? That's because the model is slightly starting to overfit. It's capturing certain patterns that it probably doesn't have to. It's at times it's not necessarily predicting the error, predicting the target variable well enough in certain instances. So that's where a little bit of instability is coming into the model. So now here's the thing, guys. So if you are saying that the loss is 35.9034, what does that mean? The validation loss is 35, which means this is mean squared error. So the actual loss would be around how much? Square root of this. This is a squared loss. So the median values of house prices in the target variables units will be 6 point something or 5 point whatever. Does that make sense, everyone? Do you understand that? The original units of the target variable is going to be 5 point something. So what you're saying is you're making a prediction on your target variable, but you are off by 5 units. If it is 24, on an average, you're making an error of 5 units across all the observations. Meaning you're predicting something like a 19, 21.6, you're predicting something like a say 21, like maybe 20, something like a 28, 26, 31.7, you're predicting 30, 29. You're predicting, but you're sort of predicting on and off by like 5 units on an average across all data points. That's where you are right now. Now, what we should try to do is we should try to minimize this even further. Like, what are the options that I have at hand? Well, there are a few options. But before we explore those options, I also just want to show you how you can generate the predictions, right? How do you generate predictions? Model.predict of x underscore test. So because you're passing the test set. So now if you look at preds, that's it. These are the predictions that you have. So if you look at this is the 0th value. That's the other one, which is the actual value is 13.8 and the predicted value is 24.0. If you look at the 10th observation, so 26.08 and 24.1. This is not bad. So you get the idea, right? So across some data points, there is a bit of an error over here, 20.4 and 13.5. So in certain observations, you're all right. In certain observations, you're making a larger error, so on and so forth. So here, this is how you can simply generate predictions. Now the question is, how can you improve this model? But before we improve the model, I want to talk a little bit about this 11 by 11. What is this 11 by 11 now? Now this 11 by 11 is a bit of a longer topic. There's a lot of history behind this 11 by 11. So you'll have to stick with me for a few minutes and I'll explain what that 11 by 11 is. It's important for all of you to learn, all of you to know, but it's not a simple, straightforward answer to it. Okay. So I'll give you a bit of background. Now, when you talk about, the model training, right? We spoke about, in the earlier case, we spoke about one iteration or one epoch. What did we tell ourselves? One epoch is a combination of one forward pass plus one back propagation step. Right? Now, when I say one forward pass plus one back propagation step, what do I mean by this? So I could mean one of many things. Either I might mean one observation, right? Basically, I'm doing a forward pass for one observation, computing the error and doing a back propagation, or it could be for all observations. For all n observations, I'm computing the error. I'm making a forward pass, generating the predictions, computing the error, and then doing the back propagation. So this back propagation, when is it happening? Is it happening after each observation? Am I passing one observation after the other, or am I passing all observations as a forward pass? So here's the thing. If you remember, what did I tell you? You have this model, right? X1, X2, all the way until X13. And then you have the hidden layer. And then what you're doing is you're building a simple perceptron model. You can build any kind of a model if you want, but perceptron for the moment. This is your input layer. This is our output layer. And what did we said is the input layer has 339 cross 13 or 14 features. And then you have a weight matrix of how many ever, 14 by 1. And then the output is 339 by 1. Right? That's what we learned a while ago. This is X, this is weight, and this is Y hat. Right? And then you're essentially doing a matrix multiplication between both of these matrices to get to the output. The point is, what I mentioned is, I said, you know what, you're essentially passing all the 339 observations through the network, generating the predictions for all of them. Then for every observation, you're computing the error. You're comparing this with Y, which is the actual value. You're computing the error and then generating the predictions. You're computing the error. So from here you compute mean squared error. Then you compute the gradient, dou MSE by dou W1 all the way until dou MSE by dou W13 and dou MSE by dou B. And then once you compute the gradient, you essentially update all the gradients. But the point is, you're doing this at the end of all the observations together. So meaning, all the observations in your data set are going through a forward pass. You're generating the predictions for all the observations. You're computing the MSE based on all the observations. Then on that error and that gradient, you're making the update. This kind of a process is referred to as a batch learning process, or a batch learning, or a batch update. In this case, if you're using stochastic gradient descent, it's referred to as batch gradient descent, or this is essentially a batch gradient descent is the algorithm that's being applied here. On the contrary, I'll give you another completely different school of thought, which says, you know what, it doesn't matter. It says, instead of thinking this as a batch, why don't we instead of trying to pass all the observations, by the way, just to summarize, so in the earlier case, one epoch was equal to one forward pass of all observations plus a back propagation. I hope this makes sense. In the earlier case, in this scenario, what I'm going to say is the contrarian, or rather the alternate school of thought, is where we say, hey, you know what? One epoch is going to be one forward pass for one observation. You take one observation at a time plus one back propagation, and you repeat this whole process n times. Here, what you're saying is you're taking one observation at a time. You take the first observation, put it through the network. So you randomly, so how does the network start? Random initialization. So you generate one prediction, you randomly initialize all the weights. You take one observation, put it through the network, generate the prediction, compute the error, compute the gradient, back propagate, then pass the second observation. Then compute the then do the forward pass, generate the prediction, compute the error, back propagate, third observation. So you're doing one epoch in this case is a combination of one forward pass plus one back propagation times n, one for each observation. But just to kind of let you know, if you actually go back to this code and if you look at this weight update step, what was I doing here? For each observation, I was computing the gradient based on the error, updating the weight, and then going back and repeating the process. So in a way, what we had actually implemented early on was this and this, in a way. Okay? And just to let you know, the second approach is referred to as a stochastic process. The second approach is called as a stochastic process. The first approach is referred to as a batch process. Let's take an example. Let's take a simple example, x1, x2 by two observations, right? So the approach one. In the case of approach one, what would happen? You have x1, you have x2, and then you have a simple network, right? Like this, right? So you have some weight. Let's for the moment just consider some weight, doesn't matter. Instead of w1, w2, let's actually consider some weights. 1.0, this is 1, this is -1. Okay, randomly initialized weights. This is the network. This is the network for both approaches, let's say, for the moment. Randomly initialized weights. So this is randomly initialized, 1 and -1. So in approach 1, what's going to happen? Approach 1, or the batch process, what's going to happen is you're going to do a forward pass for both the observations together. What's both the observations? This is observation 1, observation 2. So when you do the forward pass, so if this is 5 and 1, what will be the predicted value? So the input is going to be 5, 5, 1, 2, 0. This is 2 rows and 2 features, right? And then you need to have a 2 by 1, which is 1 and -1 over here. So if you do a matrix multiplication of both of these, you will get a predicted value, which is 5 times 1 plus 1 times -1. This is 5 minus 1, which is going to give me 4. 2 times 1 and 0 times -1, which is going to give me 2. Predicted values of 4 and 2 respectively. This is x, this is w, and this is y hat. Everybody on the same page so far? Don't ask me to explain matrix multiplication. Now is not the time for me to do that. You can, this is matrix multiplication, this, okay? So now what happens after this is you have the actual values of 3 and 5. This is the predicted value. What was the actual value? So forward pass is done. This is the forward pass, right? And then what do you do? Within forward pass, you generated the predictions, and then the second step in the forward pass is to compute the error, right? How do you compute the error? That you have the actual values, don't you? What's the actual value? 3 and 5. So you have y. So you compute the mean of the squared error, which is going to be 4 minus 3 the whole square, which is 1, and 2 minus 5 the whole square, which is 9. 9 plus 1 is 10. The total mean squared error over here becomes 10. 10 by 2. Squared error, sum of squared is 10. Mean of the squared error will become 10 by 2, which is 5 approximately. Now what happens is now you do the back propagation. So back propagation, now what's going to happen is you take the error, now you compute dou MSE by dou W1 and you compute dou MSE by dou W2 and then you update these two weights. You update both of these. That is a batch process. And then you repeat. That's step 1 and then you repeat. Is this clear so far, everyone? This part I'm assuming so is perfectly clear. Brilliant. Approach 2, my friend. A little different. Approach 2, same network, but things happen a little different. So in approach 2, you do the forward pass. For the forward pass, you only take one of the ways. Take 5 and 1. Do the forward pass. So 5 times 1 is going to be 5. So the predicted value here is going to be how much? What is the predicted value? The predicted value is 4. MSE is going to be 4 minus 3, which is 1. That's the forward path. This is for observation 1, right? Step 1 in approach. And then you do back propagation. For this, you compute dou MSE by dou W1, dou MSE by dou W2 based on this particular error. And then you update W1, W2 are updated. Then substep 2. What's the substep 2? You do the same forward pass again for second observation. So 2 times 1, 0 times minus 1, which is going to be 2, 2 minus 5 the whole square. The predicted value is 2. The mean MSE is how much? MSE is 5 minus 2, which is 9. Then you do the back propagation, which is going to be dou MSE by dou W1, dou MSE by dou W2, and then you update W1, W2. The first process is called batch. The second process is called as approach 2, which is called as a stochastic process. So now the updated weights are, instead of maybe 1 and 1 minus 1, maybe now the updated weights are W1 is 1.1 and W2 is minus 1.1, whatever. So now you compute y hat. This is your updated weights. So now you compute y hat, which is going to be 2 times 2.2 and whatever the value is. So 5 minus 2.2, which is 2.8. Predicted value is 2.2. Mean squared error is going to be 2.2 whole square, 2.8 the whole square. I'm assuming this is clear. Weights did not get reinitialized. Weights just got repurposed from the previous step. Okay. Now, my friends, the point is, between both of these approaches, there are some benefits in this setup. There are some issues with both of these. What are the benefits and challenges with both of these? What are the benefits? The benefits is there is the let me just actually mention the batch process, and then there is the stochastic process. So the first one is so Joyita's question is then here with we in second one it won't retrain with the first observation again. No, this will again get repeated. This is all one epoch. So one epoch has 2 substeps. This whole thing will then get repeated. What is an epoch? An epoch is one instance. An epoch is one instance of the complete model looking at all the observations. An epoch is an instance of a model looking at all the observations at least once. So here, for the model to have looked at all the observations, it's just one forward pass and one back propagation. But in the case of a stochastic process, for the model to go through all the observations, it needs to go through every observation. There is one forward pass for each observation, one back propagation, and forward pass, back propagation, forward pass, back propagation for as many observations as you have. So to complete one epoch in the stochastic process, the model will have to go through n forward pass plus back propagation steps. Whereas in this case of batch, you only do one forward pass and back propagation step. Okay. So now let's come back here. Let's understand what are the benefits and what are the challenges of each of these. Now let's talk about how quickly do you think these models will get to the minimum, or between batch and stochastic processes, which of these is likely to reach minima faster or reach closer to minima faster? Which one? Stochastic or the batch process? Yeah, the stochastic process is going to reach closer to minima faster. This one, as opposed to the batch. The reason is in stochastic, you're doing far more weight updates than batch. In stochastic, you're doing far more, and you're doing weight updates more frequently. See, imagine if you have 1 million observations, then you're having to do forward pass for all the million observations and then back propagate once. In stochastic, you can essentially backpropagate for every observation. So the point is, because you're updating weights much faster, the likelihood of for you to make progress towards minima, you'll make much more progress towards minima much faster in the case of stochastic as opposed to batch. The second step is, the obvious one, which is computationally expensive. Stochastic is far more computationally expensive, or rather, I'll just put it like this. This is cheaper. This is way more expensive, right? So a lot more expensive computationally. Basically meaning you'll end up doing a lot more back propagation. Basically, you'll require a lot more, to complete one epoch, you'll actually take much longer here. See, I think the right way to put it, instead of saying computationally expensive, I think the best way to put it is saying time to complete one epoch. What is one epoch? One epoch is to expose the model with all observations exactly once. To complete one epoch, in the case of batch, it's cheaper, it's faster. In the case of stochastic, it's very, very long. It's going to take longer. The next, and the more, and I think the one to understand is in terms of stability, which one is more stable? Batch is more stable. Agreed. Why is batch more stable? Because you're taking all the observations and then you're generating the error and then you're back propagating. So even if there are some outliers in all the observations. See, I'll explain what stability means. See, when you do the weight update, and especially when you're doing weight updates very frequently, meaning for every observation, if one of the observations is an outlier, right? What you're going to do is, in the stochastic process will update the weights even for that particular outlier, because it doesn't know if it's an outlier or not, right? It's going to treat that one single observation as one instance and it will compute the error. Obviously, your model's error is going to be very, very large for that one outlier. The error is going to be very large, so thereby the weight update is going to be very large. Everybody agrees to that? So that way, your model will suddenly take a very, very different direction. And then the next observation, again, it will have to make a very different direction, because it will realize that, oh, I made a massive error. I took a very erratic decision on one observation. So it has to again course correct immediately. So every observation is going through this, back and forth for every observation, right? Whereas in the case of batch, what's going to happen? Because you're dealing with million observations all together at once, you will actually make, because in those million observations, there might be one or two outliers, but those outliers are going to get lost, because in the million, when you compute mean squared error, there is an averaging effect. And for that reason, what happens is, even if there is an error, you're not really going to get lost because of that one particular outlierish data point. So batch is a lot more stable, but batch is a lot slower as well, right? This is stable and slower, right? This is faster but less stable. You see the challenge here? You see the issues here? The reality is, we neither use left or the right. We neither go with batch or stochastic. What we do is the best of both worlds. What we use is called as a mini batch process. What is mini batch? A mini batch is like stochastic, but with, instead of one observation, you have more than one observation. You have let's say 20, 30 observations. You have batches of data. So if you have, let's say, 10,000 observations, if you have 10,000 observations in your data, what you do is you take the 10,000 observations and you break that 10,000 observations down into, let's say, I don't know, 5 or maybe 10 batches, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each batch has how many observations? 1,000 observations. Now what do? Now you take each mini batch and do a batch gradient descent. You take these 1,000 observations. So to complete one epoch, now what do you need to do? To complete one epoch, as I assume you have 10 batches now. So 10 times one forward pass plus one back propagation. And in this case, this forward pass and back propagation is for 1,000 observations or for each batch. Does this make sense? Earlier you were doing, instead of 10, what were you doing? You were doing 10,000. We're saying, man, no point doing 10,000. Don't do 10,000. Do 10. It's okay. Do 10. So you're going you're essentially saying it's a mixture, exactly. It's a mixture of both batch as well as a stochastic process. So to complete one epoch, exactly, there are 10 mini batches now. 10 mini batches. Each mini batch has 1,000 observations in it. So now, after each batch is complete, you will have a back propagation. After the forward pass of each batch is complete, then you do the back propagation for that batch. Then you repeat. Okay. Now that you understand all of this, now let's come back here. Let me show you something. So one thing that I want to show you is this. So in the fit method, there is something called as a batch size. And the default batch size, my friends, is 32. Number of samples per gradient update. It's 32. So now if you come back here, if you have a total of how many observations do you have in your training data set? 339 observations. So 339 observations. If in each batch you have 32 observations, how many batches will you have? 11. That 11 by 11 is this. That's the status for all those 11 batches. So in the first epoch, you have 11 batches. Make sense, everyone? Of course, it's the same for all because every epoch has the same number of batches. Okay. Of course, you can change the batch size from 32 to 100. So by default, this is doing batch gradient descent. Now, if I say batch size equal to 1, what is it doing? If I said batch size equal to 1, what's it going to do? Stochastic. And if batch size equal to 339, what is it doing? Batch gradient descent. The default is 32. So if I set this to, let's say, 50, automatically the batch size will change. 7 by 7. If I set the batch size to 50, the number will automatically change. Which is why if you observe, if I set this number to 1, see, look how long it will take to complete the epoch. I'll set it to 1. Look how long it will take to complete one epoch. It's taking almost 2 milliseconds per each step, and then there are 339 steps over here. So this is actually going to take, to complete 150 epochs, look how long it's taking. As opposed to, if I set this to 339, that's how quickly it will be done. As opposed to, but it's not going to probably work as well as you would want to, which is why you sort of go for something in between, right? So you set it to 30 and then you'll get a certain number of batch sizes. I hope you get the idea. I hope you get the idea of batch gradient descent versus this. Awesome. All right.
Back again. So we started with a simple example using the Boston dataset, and then what we did using the Boston dataset was we went about defining how the Boston dataset was. We created the train test split, and then what we had also done is we went about building a neural network using the Boston dataset. Actually, we did not actually build a neural network. What we built was a simple perceptron, right? What we did was we had in this particular case, we told ourselves that there are 3 steps in building the model. There's a model definition step. There is a model compilation step. And then there is the training step or the fit step, wherein you're actually going to be passing the epochs, number of iterations, and data sets respectively. We went about implementing those 3 steps. The step number 1 was over here, wherein you were defining where you define the model definition, the size of the model, the shape of the model, and so on. In this particular case, we decided that we will keep it very simple, and then we'll focus on a perceptron, sort of a model for this particular exercise. And then what we also told ourselves is that to be able to build a model like this, you will require you would need to in this case we chose not to have any kind of hidden layers to start with. We just went with a simple perceptron, so the input layer and then the output layer was a simple dense layer. Then we decided to run the compilation, and when we did the compilation, we chose the Adam optimizer, and then we chose the mean squared error as the loss function. We went ahead and we trained this particular model. We decided X train, Y train, number of epochs, validation data set, and so on and so forth. So that is what we had done. Now, once the model got trained, we had we saw something like this, where you saw the number of epochs, and then you saw something over here called 12 by 12. We went about explaining what that really meant in this particular context, right? So we discussed what a batch gradient descent was, what stochastic gradient descent was, or either a stochastic process was. In the case of a batch process, all that you're doing is you're, in the case of a batch process, what you're doing is you're taking all of the data set, you're doing one forward pass for all observations, and then doing one back propagation. That was essentially one epoch. In the case of a stochastic process, one epoch was essentially defined as one forward pass for each observation plus one back propagation. And then you're repeating that for all the number of observations that you have. And then we told ourselves that there are certain benefits and or certain advantages and disadvantages, not disadvantages, but certain limitations of how batch and a stochastic processes would work. Batch processes were a little slower to get to the minima, stochastic process a little faster. Time to complete each epoch in the case of a batch is cheaper or faster. In the case of a stochastic process, it is longer. Stability wise, a batch process is slightly more stable, and this is less stable due to making updates through this particular through because you're making an update for each observation. Then we said you probably require a best of both worlds kind of a situation. That's when we decided mini batch. Mini batch is where you basically take a data set of, let's say, 10,000 observations. You break that data set down into 10 smaller pieces, or the number of pieces you want to break it down to is a hyperparameter that you have. You can decide how many pieces you want to break it down to, and then you take one at a time. You take each observation at a time, and then you start to, or rather, each bucket, or rather each batch at a time, and then you perform the gradient descent on each of those batches, right? That is where, and then so to complete one epoch, this would be the total number of batches times one forward pass plus one back propagation for each batch. So you're sort of doing a stochastic process within a batch and a batch process within stochastic. So it's sort of a combination of both of these. That is where and then we saw that getting implemented in the sense over here, because you had batch size. The default batch size was actually 32, and which is why whenever you were training the model, you were always seeing 11 by 11 earlier. If you change this number, automatically the number of batches will change as well. If you choose a model with a batch size of 1, but that means you're doing a complete batch process. And if you choose a batch size which is equal to the total number of observations, then you're running a completely stochastic process. And you would tend to see the same kind of behavior in the model as well. So when you take one batch, you would see generally a faster epoch, but a slower convergence. If a batch size is 1, then you're essentially going to be running it as a stochastic process. If a batch size is equal to 339, then you're running it as a you're running it as a batch process. And if you pick each one of those, then you would automatically see that the behavior of the model and the behavior of how your loss curve also looks changes a little. So that's where we are. So what is one epoch? You will only consider something as one epoch if the model has been exposed to all of your data set at least once, or exactly once. Not at least once, exactly once. Now it can be exposed as a batch or multiple batches or individual observation, doesn't matter. I will only consider something as one epoch if my model has seen all the observations. Okay. So I will not say something as one epoch complete if my model has not gone through all of the batches. If I say 1 out of 150 epochs, if I say one epoch is complete, then that automatically means that all the batches have been exposed to the model. All the batches have been have gone through a forward pass and then individual back propagations respectively. So there are 12 weight updates over here, meaning 12 back propagation steps. 12 forward pass plus back propagation steps have been complete over here, one for each batch. Okay. You have a data set. There is one data set. In the case of the way models are trained, is a particular data set is broken down into equal parts, right? So in this case, 1, 2, 3, 4, 5, 6. When I say equal parts, if I have 60,000 observations, then each of this will have 10,000 observations each, right? Each of this will have 10,000 observations with each. All of them will have 10,000 observations with each. That's number one. Then once you have 10,000 observations each, what you're saying is, now to complete the way your model will get trained is your model will take one observation at a time. What it does, or rather one batch at a time. So this is batch 1, batch 2, batch 3, batch 4, batch 5, and batch 6. 6 batches, each batch of 10,000 observations. So you take batch 1, which has 10,000 observations, you put it through a forward pass, right? You will generate the predictions. So forward pass essentially means you're going to generate predictions, you're going to compute the error. Both of these will be complete. And then basis that, what you also do is you perform a back propagation, meaning the model is essentially going to go through a bunch of weight updates over here, right? Weight updates. Okay. Both of these is what is going to happen as far as the model is concerned. That is when you say one batch for batch 1, that is what's complete. Then you repeat the same process for batch 2. Then you repeat the same process for batch 3. Then you repeat the same process for batch 4, all the way until all the batches are complete. Once all the batches are complete, then one epoch is complete. That is one epoch. So now you tell me to complete, and then you repeat this. Then you repeat this. You redo the whole thing again with batch 1, batch 2, batch 3, batch 4, batch 5, batch 6. Second batch will be run for the updated weights of batch 1. After batch 1 is complete, whatever weights are updated, batch 2 is going to be running on those weights. Yes. So incrementally also the model is improving over here. The model after each batch is getting improved because you are going to have one back propagation after the other over here. So to complete one epoch, you would have to go through all the batches. So if you have 6 batches, then you would have had 6 times forward pass plus back propagation steps over here. So 6 weight updates have already happened. That's where we are right now. Okay, that is what we refer to as an epoch. An epoch is when you would consider something as an epoch. I mean, you might loosely use the term iteration, but that's not what an iteration is. An iteration is a sub-step is what is referred to as an iteration. An epoch is when all the observations in the dataset are exposed to the model exactly once. Okay. Now, what are we going to be doing? We'll build on top of this. We started with a model, right? We defined this particular model. Okay. So if you look at this, this is the model that we had run, right? Now, what we're going to be doing is we'll try and build on top of this. So what we'll decide is, so far we built a very, very simple model. This is a very basic Perceptron model. There is no complexity here whatsoever. Instead of the only differences, instead of using stochastic gradient descent, we used Adam optimizer. But apart from that, and we used the batch learning process. Those are like the subtle differences in comparison to that of, let's say, your regular, linear model, so to say, right? Now what we're going to do is we're going to try and build on top of this model. We're going to try and improve this model. How can I add more complexity to this model? Well, that's where we will talk about adding hidden layers in this particular model. Exactly. So we will try and add a bunch of hidden layers in this particular model. So let's look at how you can add a set of hidden layers. The question is, why are we adding a hidden layer? The reason we are adding a hidden layer is because, for example, what you have done so far is you've built a model, you started the training of this particular model, and you've suddenly realized that, okay, what, looks like my model is not, my model is learning, but at this particular point it's sort of not really accelerating as well as I would have ideally wanted it to. And I might want it to I want to see if I can extract more juice out of this particular model, of this particular data set. Secondly, this is a linear model for the moment. I'm just capturing linear patterns over here. So there could be more complexity involved. There could be more non-linear patterns within the dataset, which I'm probably unable to capture at this moment. By adding a hidden layer with an activation function, I might be able to capture more non-linearity from this particular model. Some of those complex features. That is why we are adding the hidden layer. So now let me quickly show you how you can add a hidden layer. So as I said, a hidden layer and any other output layer, or any layer for that matter, there is no fundamental difference between them. I'm just going to say, hey, I'm going to add a hidden layer, and I'm going to say I'm going to add a hidden layer with 2 units. As simple as that. Simple and straightforward. But I also will have to mention one more thing over here. What else do I have to mention? I also have to define an activation function. 2 is the number of nodes. I'm adding one hidden layer, 2 nodes, and I have to define an activation function. And let's say I use relu as my activation function over here. So this is a hidden layer that we are adding. In this particular case, this is my hidden layer 1. I've just started with 2 units. Let's see how it goes. Started with 2 units. Let's see if it's able to capture any more nonlinearity than what we are already able to capture. Same optimizer. I'm not changing the optimizer. I'll keep the same optimizer. Let's train the same model. Let's see how it goes. Doesn't seem like it. It's still sort of stuck there. Maybe one of the things that I'm probably going to do. Yeah, it's not. I mean, it's still reducing if you look at it. The train and validation, there's a gap here continuously. So clearly, one of the reasons for it is that there is a bit of gap between how the training between your validation and your train set is happening. Some bit of overfitting is happening throughout the model, but that's okay. We can maybe change a bunch of things over here. I can maybe add. I'll just try to increase the number of units over here. I'll just add one more unit, and I want to see directionally if it is improving my model or not. Is it directionally improving my model or not over here? Not really. Not a lot. Not a lot. You see this here? What do you observe here? It's a little, it's improving, but you see there's a lot of instability sort of kicking in this particular model. It's a little bit of instability sort of creeping into this particular model. So one of the things I could do to handle that particular instability, moving more towards the batch process or moving towards the stochastic process, what will make the model learning a lot more stable if I move more towards the batch process. So I'm going to increase the batch size to, let's say, 64. I'm doubling the batch size, reducing the number of batches. What you will observe is interesting. So look at this. I'm increasing the batch size. Yeah, but the moment I increase the batch size, look what's happening. I've increased the batch size. It has stabilized, but the loss is very high now. So that's exactly the point that I was trying to refer to over here, right? The moment you go to batch, you will reach minima much slower, but it is more stable. You'll get a more stable behavior over here, right? So maybe not 64. I'll just maybe increase that to, instead of halving it, maybe I'll just increase it to 48 or something. Let's see. Look at this. It's learning faster now. I'll probably have to run this for a few more epochs. I'm just going to go 300. Let's see. I'm going to run this for 300, total of 300 epochs. Let's see how it goes. Look at that. Model has improved a little bit. You see the model has improved a little bit over here in this case, but there is still a bit of instability there. You see that? There's still a bit of instability here in the model, especially in the later half of these epochs. See a lot of instability over here in this case. So that's not helping, clearly. There's a couple of things I can do here. I'll stick with the number of units. I will not change the number of units because I see there is improvement in the model, but I'm going to try and make the learning a little different. So I'm going to maybe change this to sigmoid. One of the things I can try is I can maybe change the activation function one thing at a time. I'll probably change the activation function to a sigmoid. I'm not changing anything. I'm keeping the learning rate as it is. Let's see if it improves the model. Yeah, clearly the model is training much slower in this case. It's learning a lot slower than what I had expected, and it's slowing down. The learning process is stable, but then clearly it is sort of just triple the learning rate. Let's see if it learns any faster. There you go. Look at that. Stuck. It's kind of stuck here in this minima now. Some kind of a local minima. It's stuck. It's not getting out of here. This is what I mean by getting stuck in a minima, right? So the model trained. Earlier, we were able to get to another model. See, this is what I was saying. So earlier, we were able to get to a model with a lower amount of validation loss and loss. But what happened here in this case? The model just couldn't train any further. It just flattened after this. Why? What happened here? With these parameters that we have defined here, the model got stuck in a local minima. It was just unable to come out of that. And it just couldn't learn any further. Does that make sense? Do you understand what happened here? So this is how you infer if you're stuck in a local minima, right? These are some cues for you to. There is no other way to explore this. There's no other way for you to infer it. You need to infer this. Yeah, first time you probably might think it is global minimum unless you try. You just have to try. You have to try different learning rates. You'll have to try different optimizers, and maybe it'll help. One of the biggest change that I can bring in is probably a learning rate change. Sorry, an optimizer change itself. I still haven't brought that in. Let's see if that works. Nope, stuck there. Not learning. Still stuck there. It's just not learning. So the sigmoid is not helping. The sigmoid and the, at least the way we have defined it, the sigmoid is not helping. I'll probably go back to let's try tan h in this case. Let's try tan h in this case and let's see if that will help. Nah, not really. I'm just gonna stop. I'm gonna go back to a ReLU. It's probably also the issue of the learning rate. The learning rate could also be fairly high, and that might be one of the causal factors here. This activation function is not, this learning rate is not working. So I'm going to make a couple of changes here. I'm going to maybe just switch back to 0.01 because that definitely got us a little further from where we are. And I'm going to switch back to my best model. My best model was here, 3 units, same thing, but with a batch size of 32. Yeah, this sort of got me to my best model so far. So I've sort of reset back to my best model. And then we'll try and build on top of this. We'll try and see if I can make any further progress from here. So what do I want to do? I want to see if I can get a little more into if I can extract a little more juice, if I can extract a little more nonlinearity from here. So one of the things I might try to do is I might maybe add a few more features. I can also change the optimizer. I can maybe also change the optimizer. I see some comments coming through. Yeah, this is fine. There's nothing wrong with this model. This is okay. There's a little bit of instability here in this particular case that I'm observing, but we'll come to it. There's a bit of instability here in this particular model. We'll try and address this somehow. But one of the other things that I'm also observing in this particular model is the fact that one of the issues with this particular model is also that you slowly start to see a bit of a pattern getting crept in this particular case. You just start seeing that, the yellow curve is there and the blue curve is slowly starting to kind of separate over here. So slowly start to see this gap sort of coming in. A little bit of overfitting sort of creeping in this particular case, right? One of the things that I might also want to measure, one of the things that I can maybe try and change. So how do I improve this model from here on? One of the things, there are a couple of changes we can do to improve this model, right? Maybe I can increase the number of nodes. One of the things, I'm still stuck with Adam. I can change the Adam optimizer in this case. Barun is saying ReLU 0.001 and Adam might work. I'm with ReLU. I'll just increase the number of units and let's see if this helps. I'm just going to add one more unit to this. We can hope that this might add a little bit of, if this is going to help me extract more nonlinearity, sort of flattening here. It's not going any further from here. Still that 32 mark that it is flattening out at. Yeah, it's added a lot more. See, look at this. It ended up adding a lot more instability in this case. So clearly adding one more activation did not help. One more unit did not help. Now, what I'm going to try to do here is I'm going to try and change this a little. Instead of using the Adam optimizer, I'm going to go for a bunch of other optimizers that we have. So I'm going to use something called as AdaGrad, which is adaptive gradient. And I'm going to use the same loss function, which is mean squared error. Now, along with this, I'm also going to add one more thing called metrics. Now, what are metrics? Metrics are basically, if you go back to is a function that help you evaluate how well your model is performing. So you can pick any metric that you want. It's like loss metric. It's like your loss function, but it doesn't have to be exactly like a loss function. For example, in this particular case, I can pick one of the regression metrics. I can simply say, hey, I want to capture root mean squared error. I can simply say, I want to capture root mean squared error. So what you could do is you can say, along with mean squared error, also compute root mean squared error. RMSC probably doesn't work. I'll have to import RMSE from TensorFlow.keras.metrics import root mean squared error, and I'm simply going to say root mean squared error off. That's it. Metrics are okay. Sorry. My bad. This has to be in a list. Okay. So it will consider mean squared error as the loss function, and it will consider root mean squared error just for reporting purposes. That's it. I'll repeat again. Loss is going to be used as the loss function for you to do the weight updates. Metrics is only for reporting, is only to report. But because it's hard for me to understand what validation loss is. Maybe I can track, because this is mean squared error, right? Maybe I can track RMSE. RMSE is something that probably is more useful for me in this particular case. I might actually track RMSE otherwise. So that's the only difference between these two. That's the difference between a metric and a loss. So now when I execute, you see it'll report both for me. It'll give me loss, root mean squared error, and it'll also give me validation loss and validation root mean squared error. It'll give me both in this particular case, right? Clearly my model is not learning. I chose AdaGrad, and it's clearly not working in this case. I'll have to change a couple of things over here. I might have to go back and make some changes over here. Let me just go back here, AdaGrad. I'll have to probably increase the learning rate. So let's look at what the default learning rate is over here for this one, and we can change accordingly. There's EDA delta and there's EDA grad. This is continual decay of learning rates throughout the training. Actually, let's actually use EDA delta, right? What this does, do we have like an activation or an algorithm that automatically reduces the learning rate? So here is an continual decay of learning rates throughout the learning, need for manually selected global learning rate. So it sort of, you start with a learning rate, and what happens is it automatically reduces the learning rate as you get to the minima. So let's actually use EDA delta instead of EDA grad. We'll come to EDA grad later. EDA delta, right? And then I'm going to say EDA delta, and learning rate is, the default learning rate is 0.001. Let's see how it goes. Clearly not helping, clearly not serving the purpose here. It's learning, but learning extremely slowly. As you can see, it's learning, but learning very, very slowly. And it's reducing the error, but the error reduction is super slow, because it started at 182, it's at 172. So it's learning. So clearly it's very slow. Something for me to change in the context of learning rate, right? Let's just change the learning rate a little. Yeah, still very high error. Still a very, very high error here in this case. It's still learning, as you can see, still reducing. So I'm gonna increase the learning rate a little more. Let's increase it to the order of 10. Let's see if it works. Reducing, I'm gonna go a little further up. Yeah, this is not solving the problem, right? Clearly not solving the problem. So what do I do then? So my multiple functions, we've tried EDA we've tried Adam, we've tried EDA delta. I mean, it's increasing, it's reducing super slow, like very, very slowly. Still, my best model is still the previous one. My best model is still the Adam one so far. 3 units, Adam is still my best model so far. What I generally look for is, I look for the rate at which the error is reducing. If my error does not reducing as quickly as I want it to, and I'm not even in the ballpark, but here actually it is reducing, interestingly. There you go. It actually got out of the minima. So it worked. It worked out well here in this case. It did get out of the minima though. But what I typically look for, the rate at which it is reducing. That's what I typically focus on. That's where I'm going to generally place my bets on. Again, see, look at this. The loss again sort of stuck in sort of some kind of a local minima here. It needs to get out of that. This is at a delta. This is at a delta, right? Yeah, it should be able to get out of it. It has a little. It has actually improved. Still, definitely not where I wanted it to be, because the validation loss, I would have expected it to be around the 30-ish. But this is not bad. I think it has definitely improved. And if you just let's look at the curve here in this case, right? See, this is fantastic. This is great, right? And it's still reducing. So I might actually run it for a few more epochs. This is a nice and a very smooth model. I might actually run it for a little longer as well. Just to let you know, what you could do, and if you just want to run for a few more epochs, you don't need to run the whole model again. I can just put 300 over here and just run the fit step. Don't run everything else, just run the fit step. What it will do is it will continue from where it left off. So you look at the loss here, and if you actually just run this, it'll run the next 300 epochs from where it left off. So it's a warm start, right? So you can just build on top of the model. So you don't need to redo the whole thing again and again. So let's see if it improves any further. It's actually improving. It has actually improved. I might actually run for a few more. I'll probably run it for 1,000 more. Let's see if it drains for a little further. Yeah, but you get the idea, right? I mean, this is basically what you need to do. Yeah. Now it's almost gone right now. Like it's almost flattened out right now. It's not much anywhere. Not much anymore. You see this blue curve is now slowly starting to separate, but clearly it's sort of maxed out almost right now. Even if I run for a little longer, the slope is not large enough for me to run it. It's not going to go any further than, let's say, a 6 point, maybe zero. So to say, this is probably the max that it'll go. All right. So right now we're still our best model is still Relu with Adam, right? This sort of got me to what 6.13, right? This sort of got me to 6.13. But my best model is still this one, right? With a 0.01, with one maybe with one unit, one hidden layer. This was still able to get me my best model performance so far, at least. Actually, let me stop. Let's actually plot metrics as well over here. This sort of gave us I think I've ended up running this for 1,000 epochs. Let's see if this improves any further. Okay. What was the learning rate? I think it was 0.01. What was the best model? No, our best, because this one doesn't still seem to be giving you your best model. This is still far away from your best model. What was the best model? Oh, yeah, maybe it was 2 units. There you go. It's 2 units. So I put it for run for like 1,000 epochs. Let's see what it does. If it can maybe give me a better result over here. Yeah, there you go. This is doing all right. It's not doing a bad job at all. Yeah. So clearly your Adam is giving you a much better model. A little bit of instability in the model in this particular case, but clearly this is giving me my best sort of the model, at least as of now. 24.7. Yeah, this will of course have a lot of it did reduce, but clearly a little bit of instability in this case. Yeah, clearly some amount of overfitting creeping into this model. But still, this is sort of by and large, in terms of strictly the error, this is by and large my best model. See, look at this. This loss of 13.17 and 24.73. Clearly, there is overfitting here. There's a bit of overfitting that's going on over here. And 4.9 is sort of the lowest amount of error that we were able to sort of get to so far, at least with this particular model. Yeah, maybe we probably didn't have to go that far for this kind of a performance. Maybe just 400, 500 epochs was good enough. I think if you technically think about it, around after this part, there's now no learning that's happening. If you think of it, almost after 400 epochs, nothing really happened over here. So you could just kind of stick to just those many number of epochs. What you could also do is, one of the things that I just want to show you here is you might want to, let's say, quickly view the model itself. So what you can do is print model.summary, and look what it prints for you nicely. Or rather, actually, let me just remove this I just want to remove the print statement over here. Yeah. So if you see, this is the this is the model summary here. It says that there are two dense layers. Clearly, of course, in this case, first one with 2 units, and it says 28 parameters. Why is it 28 parameters over here? 13 times 2 plus 2, basically 13 times 2 plus 2. 13 times 2 is the total number of weights, and then it says 3 over here. Why does it say 3 here? Between this layer and this layer, there are two parameters over here, 2 weights over here, or rather 2 units and 1 unit. So 2 weights and 1 bias. These are the number of weights and biases. Okay. So input had a total of 13 units, 13 inputs, right? And then you had two hidden layers, or one hidden layer with 2 units. So you're going to, of course, have this is x1 all the way up until x13. So you'll have 13 weights, w1 all the way up until w13, and then you'll have 2 sets of it, clearly, right? So 13 times 2, which is 26, and 1 bias over here and 1 bias over here, basically b1 and b2 over here. 26 plus 2, that is 28 parameters. And then you have the output layer, and in the output layer you have, again, W1, W2 weights, and then associated with this, you're going to have one bias as well. So 2 plus 1, you'll have total 3 parameters. So total 28 plus 3, a total of 31 parameters in this particular model. That is what it says. Total trainable parameters are 31 parameters. Okay. Now let's come back here again. Now I'm going to talk a little bit about some more things that you could do to improve the model. So we've tried all the parameters that we have. So we've changed the hype, changed the number of units. Increasing the number of units didn't help. Just two units probably solved. Changed the optimization algorithm from EDA delta, EDA grad, and then we stuck with Adam. That probably worked the best for us. And in this particular case, we increased the number of epochs. So clearly, we've tried a few options over here. I wouldn't say we've tried the entirety, but we've tried a few options. But there is a couple of things that you could do even before you get this far, right? Even before you get to the modeling itself, there's a couple of things you can do, a couple of additions that you can do to improve the model performance. One of the most important things that you could do is you can do a bit of pre-processing to your model, to your data set, right? You could do pre-processing, right? What kind of pre-processing can you do? See, what you need to understand is, remember that this is a model that is dependent heavily on magnitude of the values itself, right? The numbers itself. The magnitude of the value plays a very, very important role, right? Hence, a couple of things that you should do is you should, if possible, always do some kind of outlier treatment, right? This is not like your random forest of the world, which will which will get rid of all the outliers and everything. I mean, which is unimpacted by the outliers. Neural network models are impacted by outliers because at the end of the day, you're computing a loss. A loss is computed as a numeric value, right? You're subtracting actual minus predicted. You're actually taking that actual value and then you're doing the back propagation. So outliers do have an impact on this particular model, number one. Number two, one of the things that you should always also think about is the scale of the value. So you should also think about scaling, right? Scaling is an extremely important part of the complete model. So scaling, when you talk about scaling, exactly, initially your data set might be in very, very different scales. But if you do any form of scaling, like for example, you could do something like a standardization or normalization. Standardization or normalization. Standardization will bring the values between -3 to +3, whereas normalization will try to bring it between 0 to 1. Basically, range scaling, you could do any of those processes to also shrink the spread of your data. So that will help. Either is fine, absolutely. You could do one or the other. Both works, absolutely, yes. The third thing is also about dealing with some kind of of course, null value treatment is mandatory. This is mandatory. Null values have to be treated if you deal with it, or if you like it or not. And then you also will have to think of multi-collinearity. What is multi-collinearity? If you were dealing with linear regression models, you would have remembered about multi-collinearity, where you have a couple of columns that are highly correlated with each other. So you look at a correlation plot, right? And you say, you know what, x1 and x2 are highly correlated. So you know what, you keep the one, you drop the other, or stuff like that. Or you look at VIF, variance inflation factor, and then you try and make a decision based on that. This is all nice and great, but you need to deal with multicollinearity. It's important. Multicollinearity is an important contributor. But then we deal with multicollinearity very differently here. We don't deal with multicollinearity using correlation plots or VIFs. We deal with it using something called as regularization. And regularization is also an approach that you follow in linear regression models to deal with multicollinearity. So we will deal with multicollinearity, but I will explain something called as regularization, and regularization will help us handle this multicollinearity. Now, this is not necessarily a part of pre-processing. Remember, this regularization and multicollinearity is not necessarily a part of pre-processing. This is during model building. This will be taken care of during model building. right? So that is what in most cases, multicollinearity is dealt with before the model building. But in the case of neural networks, multicollinearity is dealt with during the model building using this technique called regularization. So we will talk about regularization in a bit, and I will explain how to do that. But in, just to kind of show you, one of the things that we will do, what you're actually doing is you're adding more dimensions to the data. By adding more dimensions to your data, you're making the model more complex for no reason. You are unnecessarily you're unnecessarily adding an additional dimension, and that is causing unwanted variance in your model. So in such cases, what you deal with is you try and get rid of one of those features. This is something that you would have manually done in the case of linear regression models when you're dealing with regression. There are certain techniques that will automatically handle it, and that is where regularization comes in. Regularization is a way for you to is a way for you to deal with multicollinearity. Okay, makes sense. So what I'm going to show you is we'll try and implement some of these, right? Maybe we'll start with scaling, very simple scaling. You know how to do scaling and outlier treatment. Actually, if you do scaling, you can also do outlier treatment in parallel. But let's quickly do a bit of scaling and see how it actually impacts the model performance. Right? We'll normalize our input data sets, input features, and what you will see is you'll see a certain impact on your data. So let's actually take x underscore, here let's actually do this pre-processing here before I do the train test split. So you could use any technique you want to do the scaling. We can simply do x minus x min by x max minus x min, sort of min max scaling for some of the features. You could also do the same on your target variable, as well. You could do that scaling on any feature that you want, but just doing very simple scaling on your input features can significantly improve your model performance. So let's actually take some of the features from your dataset, maybe crime, zone, indus. This is anyways already scaled. So we'll take some of these features and we'll actually do a bit of min-max scaling. I'm just going to go all out and do like very, very simple scaling here. So from sklearn dot, so you must have heard of min-max scaler, right? And I'm simply going to say scalar dot fit underscore transform of x, sorry, and dot. So again, so same thing. So this has already performed the fit underscore transform on this. So if you look at, so this is the first column in your data set. And if you look at the minimum value, this is 0, and the maximum value is 1. So clearly every column has been, and you can take any of the other columns as well. You can take the 5th column, maximum is this, and minimum is 0, clearly. So the min-max scaling has sort of happened in this particular case, right? So I'm just going to switch back to x. So this is now my new x, which is scalar dot fit underscore transform. And we're simply going to be using that x here for the train test split. Nothing changes here. Train test split, the data sets are exactly the same. Now I'm going to be using that train test split on this data, on this model. Now remember something. Your distribution of the data has changed a little now. Not significantly, but it has changed a little now. The values and everything have changed. So technically, whatever you're seeing here, whatever you have, whatever tuning that you had done earlier might not necessarily work now because you had tuned the model for a certain kind of error distribution. That may or may not necessarily work right now. That's one thing you need to bear in mind. Make sense? Does that ring a bell? Do you, because your data is not, so you will have to probably train the model again. But that's okay. Let's see. Let's just start with where we had left off, and let's see how this performs. I'm not going to go all out 100 epochs. Let's stick with maybe 300 epochs and see how it goes. Actually, you know what? Let's stick with this. Let's actually run this for maybe 1,000 epochs and see if it improves the model. I think it's continued training from where I left off. But let's see if it improves. But anyways, I think it depends. It's not necessarily one way or the other. At times, your outliers are at times valid data points. So getting rid of them is probably not always a great idea. So you might actually still want to keep them. But if you observe them as extremely outlierish, then you can just maybe clip them, or rather just you can try and cap them to a certain number. That's probably one of the ways to handle it. That's generally what we do, right? We try and cap it to a certain level, and that's probably how we deal with it. That's one. Right. So in this case, clearly the model is clearly overfitting in this case. The model did learn until the 25 validation loss, and after that it's simply just flattened as far as validation is concerned. But the model did learn as far as training is concerned, right? So it means that it was able to extract certain more non-linearity, but that was more from the training standpoint. It was not able to replicate that with the validation data set clearly in this case. Let's see how that works. I also just want to briefly touch upon one small thing here. What you can also do is, if you don't have a defined validation data set, right? When you're actually defining it here, what you could do is, if you don't have a proper validation data set, what you can do here is you can simply say validation split. You have a parameter called validation split, and you can simply say 0.3. And what it will do is it will automatically take this 30% of the train set in every epoch, set that aside, build the model, and test. So it'll automatically take care of that 30%. So that's up to you. If you want to use, you could sort of use all of the data set in that particular case to train. But anyways, coming back here. So clearly overfitting issues. So one of the things we need to cover is, how do I deal with overfitting, right? How do you deal with overfitting? So one of the things, two things we need to discuss. How do I handle overfitting? Second, how do I deal with multicollinearity, right? So these are two things we need to still learn. We'll talk about that. Then this particular model has improved, but then it's sort of still, again, in this particular case, just making that min-max scaling has not had a massive impact on my overall model performance, so to say, in this case. Well, what if I do something similar on my target variable? Right? Will that improve my model? Right? If I just do some kind of a scaling on my target variable, will that help? Well, maybe it might help. I might be able to fit a better model in that particular case, right? So for example, I can simply say scalar underscore target min max scalar, and I can simply say scalar dot fit underscore transform. Let me actually fit first. Scalar dot fit of y, which is nothing. I need to reshape this into two-dimensional. Dot reshape of expected two-dimensional container dot all the rows comma one column. What is y? Okay, y is a panda series. Okay, so this is the min-max scalar. And then I can maybe try and fit on top of this, which is, I can simply say dot fit dot transform of y dot array, which is the actual NumPy dataset itself, right? So that's the transformed array in this particular case, which is nothing but your target variable. Here, if you look at it, dot min should be 0, dot max should be 1. So this is your target variable now. One of the things I may have to do is, I'll have to flatten my target variable, of course, but we'll come to that. I'm flattening it because I have 2 dimensions in my target variable. I'm just going to flatten that out, which is why I'm putting flatten. Now I'll hopefully fit a better model. Clearly my validation error is going to be much lower. Why will it be lower? Because this error, remember, is not the same error as my target variable. Remember that this error is a scaled, this is an error on the scaled value. I will have to then compute a model on, I'll have to essentially transform this target variable back and then compute the error on the test data set. So I'm actually just going to run it for, so you're running like how many ever epochs, and this is still running for 1000 epochs. Okay, let it train. Let's see. The loss is reducing. Let's see. So once you get the output here, what we'll be doing is, of course, you can look at the loss curve and everything. This loss is going to look very different because this loss is in the decimals. Doesn't seem to be a significant improvement from where it started. It's still stuck at the same place. But what we'll have to do is, let me just remove this. Almost done. Perfect. So this is my loss again. There's a bit of overfitting there, clearly, but that's okay. What I want to show you is, let's generate the predictions on the test data set. These are going to be the predictions that you would generate on the test data set. But remember, these predictions are, what are these predictions? These are predictions on the scaled data set. Fantastic. This is on the scaled value. So what I will have to do is I will have to say scalar dot inverse transform of spreads, and that will give me the inverse transformation of that. So this is the final spreads. Right now here I can compute the predicted value and the actual value, which is my x underscore test, sorry, y underscore test. The y test has now also been, I'll also have to reverse transform my y test. Actuals is going to be scalars dot inverse transform of y underscore test and dot. So you have your final spreads and then you have the actuals, right? So now what you can do is you can now actually compute the difference between the two. You can do whatever comparison you want to do. For example, what you can do is final spreads dot flatten. I'm just going to flatten. See, this is two-dimensional here, right? Here, what does flatten do? So if I do a flatten, so if you look at the shape right now, this is 167 by 1. There's one column over here. I'm going to make it unidimensional. So if I do flatten, it's going to make it unidimensional. So I'm just going to put flatten over here as well. Dot flatten, dot flatten. So that's final spreads. And so now all that I'm going to do is, if you look at final spreads now, it is a unidimensional array. So predicted value minus actual value. What is RMSE? What is MSE? Whole square. And you need to, of course, do a sum of it, right? Dot sum. Or you can take a mean, basically mean squared error. That will give you a mean of the squared error. And then you, of course, want to do a square root of it. Dot, there's no square root, raised to the power of 0.5. So yeah, 4.93, a little bit of improvement, maybe not actually. So again, clearly in this particular case, not a massive change, even if you do the transformation of your target variable. But is this clear, everyone? Do you understand what is it that we've done here? We've inverse transformed the target variable, and then we firstly transformed, fit the model in the transform variable. Then we again did the inverse transform to bring it back to the original value and then compute the error on top of it. So 4.93 is where we've kind of landed with this model. Maybe a bit of improvement from where we had stopped earlier. With this, I'm hoping you understand the entire gamut of everything that we need to do as far as modeling is concerned, or as far as building a neural network is concerned. At least first level. We'll build on top of it. What we'll have to look for is, we'll have to look for more complex problems. So what I've asked it to do here is, in this case, I'm saying, hey boss, look, where did that go? Yeah, I'm saying I'm taking the target variable y and I'm converting this into an array. And then I'm saying I'm applying the reshape and I'm saying create one column and as many rows as you want. So I'm converting it into a two-dimensional array with one column, 2D arrays with one column. So if you look at the shape of y, it's going to be 509, 1. It's going to be one dimension, one column. So one column matrix. That's essentially what it is. Okay. So what are we going to be doing now? So I want to discuss, as I said, a couple of topics. So there are two topics that we are yet to cover. Topics to cover: how to handle multi-collinearity and overfitting. These are the two topics that we need to cover, which we will try to discuss. But before this, right, I just want to also talk about one more interesting problem. Let's pick another interesting problem and we'll try to solve that particular problem using neural networks. Again, it's a very simple problem, very small data set. But I want to introduce you to the concept. What I want to introduce you to is classification problems. How do you deal with all of this, but for classification problems. What changes do we have to do here to solve for a classification problem? What is it that is fundamentally going to change here to solve when you solve classification problems? So that's essentially what we're going to be discussing in this part of our session. And then in addition to that, once we finish that part, so now then you would know how to basically build a small training set of steps for classification as well as for regression, for classification as well as for regression problems. Then we will try and then I'm going to introduce concepts of multicollinearity and overfitting. Okay. So how do you solve for classification problems? What are the different aspects that you need to take into consideration when you solve for a classification problem? So let's take a small example and then try and build on top of it. What would a classification problem sort of look like? Take for example any data set, and these data sets can, let's say, be classic churn sort of a problem, a multi-class or a binary class classification problem, any set of features that you have x1, x2, x3, and then your target variable y. Maybe in this particular case, what you're trying to predict for is, let's say, like somebody was saying, you're trying to predict for churn. Is a particular customer going to churn? Yes or no, right? Or 0 or 1. 0 means the customer is not going to churn. 1 means the customer is going to churn. A classic binary class classification problem. And then you could have features like, let's say this is a telecom domain. And this is, by the way, the kind of problems that I used to solve for when I was working for this telecom company. Churn is like a classic problem. So x1, x2, x3, the features in this particular case are, let's say, the monthly bill of the customer, right? The location of that particular customer, network quality, and so on and so forth. There could be a bunch of different factors that could go in that can help predict if a particular customer is going to churn or not. Yeah, tenure, bunch of different factors. Now, when you take, for example, a problem like this, what you are trying to predict is you're trying to predict at any given point, is a customer likely to churn or not. So very, very similar and straightforward sort of a problem. In this setup, what you're going to try and do is your neural network is going to look very similar. So you will have same features, input features, x1, x2, x3. This is your input layer. You could have a hidden layer as always, right? And these hidden layers could have, this is the hidden layer, and these hidden layers could have your regular ReLU kind of an activation function. This is hidden unit 1, hidden unit 2, same, nothing changes. And by the way, just to let you know, these features can be numeric, are all numeric in this particular case. When I say numeric, meaning even if there are categorical variables, like for example, if you have location, you would have to do one-hot encoding of that particular variable, right? I'm assuming you're all aware of one-hot encoding. So if you have location as a feature, so you have, let's say, Delhi, New York, and blah, blah, blah. You try to create location underscore Delhi, location underscore New York, and 1001, so on and so forth, one hot encoded representation of this particular variable. So same thing. Any categorical feature has to be one hot encoded. So this is your hidden layer. You could have a hidden layer, and then you could have maybe one hidden layer, two hidden layers, depending upon how your network is, and then your output layer. Your output layer, again in this particular case, is going to be a single unit. What are you predicting for over here? Is label encoded accepted? Yeah, I mean, label encoding is for target variable. You do the same. If it is for a target variable, you call it label encoding. Else you call it one hot encoding. The same thing. There is a bit of a subtlety there. We often prefer going with label encoding and not necessarily one hot encoding. Sorry, we prefer going with one hot encoding and not label encoding. The problem with label encoding is that label encoding is for, if you have, for example, a particular feature like a city, all that you're doing is you're just mapping city to, a city, let's say in this case, Delhi. Delhi becomes 1, New York becomes 2, and let's say let's say Hyderabad becomes 3 and so on and so forth. The problem is that when you do it this way, you're converting this into and you're saying this is an integer column. You're saying this is your integer column. The problem with this is that when you have 1, 2, 3, you are innately saying, for whatever may be the reason, this one has a higher value than this. Now, whatever that value is, magnitude wise, you're saying this is higher than this, or the distance between these two is lesser than the distance between these two. So you're in a way sort of implicitly injecting that ranking or that kind of order into your data, which is not what you probably want, right? You would want all of these cities to be treated equally, or they're just cities, they're just categories. So why do you want to treat a category as an ordered variable? So in that case, you often prefer something called as one-hot encoding. One-hot encoding increases dimensionality. I agree with you on that. But one-hot encoding is the way for you to handle, I mean, if you do it using label encoding, then you're not necessarily treating the variable the right way. One-hot encoding, I agree, increases the dimensionality. You can always, what you can do is you can look at the frequency distribution of that particular variable, and maybe only take the top 20% that contribute to 80% of the frequency and then keep them as categories. The other ones can simply be clubbed as others or something. Okay. Yeah, see, guys, this is all traditional machine learning content. I don't know. This is all something that you all are aware of. So nothing needs to change. Nothing's different. My point is, nothing's different from a regular machine learning setup. That's the point. Okay. This is your target variable. Same here as well. But remember something. One question that I have: what are you predicting for here? So you're predicting for 0 or 1, or you're predicting for a value between 0 and 1, right? Anything between 0 and 1 is what you're predicting. Basically, trying to solve for probability, right? You're trying to solve for likelihood or the probability of this particular observation, of any given observation being a label 1. Probability that a particular class is going to be label 1, or a particular observation is going to be of label 1. That's what you're trying to predict for, right? So how many units would you require here? Do you require 1 unit or 2 units in your output layer? In the case of linear regression, we put 1 unit. In the case of Boston house prices, in the case of regression problems, we put 1 unit because you're predicting one target variable. But here, how many units do you need in your output layer? Yeah, you don't need 2. You can 1 is enough, because this is a binary class classification problem. If you predict the probability of 1 given x1, x2, x3, and so on and so forth, that is as good as saying probability of 0 given x1, x2, x3. You can simply say 1 minus this is the other one. So you don't need to predict both. Just predicting 1 is good enough. So when you're solving for the binary class classification problem, you are simply predicting for one target variable, or one node in the output layer, which is essentially giving you the probability that the observation belongs to class 1. Okay. Now, in this case, what is it that you are trying to predict for? As I said, you're predicting for the target variable y. You're predicting for a probability. So in the case of, let's say, your earlier problem, which is, let's say, where you're predicting for house prices or any kind of a numeric outcome, you were able to predict the way you computed the error. How did you compute the error? The error was computed as mean squared error, MSE, right? And your target variable belonged to minus infinity to plus infinity. The output range belonged to minus infinity to plus infinity. But in this case, you need this to belong between 0 and 1, right? You need for it to sit between 0 and 1. And the error cannot be mean squared error. You cannot compute the same exact error as mean squared error. You need to compute a different error in this particular case. You'll have to pick a different loss function in this particular case. And that is going to be the fundamental difference between both of these networks. So I'll just start drawing a quick parallel over here. So what are the fundamental differences? In the case of your regression problem and classification problem, I'm going to stick with binary class classification for the moment, right? Binary class classification for the moment. In the case of regression, your y hat simply was w1 times h, or for the whatever 6 w7 times h1 plus w8 times h2 plus bias 3. That is what y was. Agree on that, everyone? This is W7, this is W8. That is what y hat was, right? But in the case of a classification, binary class classification problem, and by the way, this made sure that your output was always linear, meaning it was always numeric and it was always between minus infinity to plus infinity. But in the case of a classification problem, your y hat is not, it cannot be W7 times H1 plus W8 times H2 plus B3, because you need the output to range between 0 and 1. So you need something that can squash the values between 0 and 1. What can I do here to make sure that the values are squashed between 0 and 1? What do I have to apply over here? I'll have to apply a sigmoid around this. So this is going to be a sigmoid activation. So in the last layer, in the case of a classification problem, we apply a sigmoid activation function, a sigmoid of W7 times H1 plus W8 times H2 plus B3, which is essentially 1 by 1 plus e to the power of minus W7 times H1 plus W8 times H2 plus P3. This I hope, and what this ensures is it ensures that the value will range between 0 and 1, right? That is the whole idea, because you would want the output to range between 0 and 1. That's the idea. This is basically like how you would have done in the case of your logistic regression as well. No difference over here. That's one of the biggest differences between your regular regression problems, where you're predicting a numeric outcome, versus a classification problem where you're predicting for a binary outcome. So remember something here, you're predicting for a binary outcome. But what is this going to give you? This is giving you a probability. This is giving you a probability. Then what do you need to do once you get a probability? Then once you get a probability, what are you going to do? You're going to then try and make this binary. You will then apply some kind of a threshold, right? This is the probability. You will decide if this is greater than 0.5, you will assign it to 1. If it is less than 0.5, you'll assign it to 0. Is that equal to 0.5, let's assign it to 0 or whatever. Okay, this is what you're going to be doing. We'll come to multi-class classification later. We'll discuss multi-class classification at a later point. So this is one of the fundamental differences, most important differences. Number one. The second, and the second biggest difference, once you get the predicted value, then you compute your loss function. In the case of mean squared error, what do? You compute mean squared error is equal to 1 by n into summation of predicted value minus actual value, the whole square, where I is equal to 1 to n, I and I respectively. This is what you would do. The question is, can I use the same loss function here as well? Well, the answer is no. Why? Remember that this is a value that ranges from minus infinity to plus infinity, right? Y and y hat range from minus infinity to plus infinity. When you look at loss, you need to treat a classification loss very differently, because you're predicting a probability. Remember, this is giving you a continuous outcome, right? Your predicted value and your actual value will look like this. Something for you to understand, right? When you're solving for a classification problem, your predicted value and your actual value will look like this. So this will be 0.5, or rather 0.6, 0.3, 0.85, 0.39, 0.15, and your actual value could be something like this, right? This is your predicted value and this is the actual value. This is what is coming out of the network. This is what the actual value is. So you need to find a different kind of a loss function that can compute the, how far or how close are you with the actual value. Why is that the case? I'll give you a simple idea. Let's take, for example, both of these, right? Actually, let me take this. Let me give you a slightly different example. Let's take both of these observations, right? 0.49 and 1 and 0.51 and 1. So the actual value is 1, but the predicted value is 0.49. The actual value is 1, the predicted value is 0.51. Okay. Now you tell me, according to you, if you take, for example, the absolute difference between both of these, the absolute difference is just a difference of what, 0.2, right? This is 0.4 and this is 0.5. The difference is only 0.2. But if you think of it, if you take, for example, 0.5 as the threshold, which is most likely going to be the case, this and this are predicting two completely different things. This is saying that this actually belongs to 0, but this belongs to 1. So in reality, this would have turned out to be a correct prediction. This would have turned out to be an incorrect prediction. Though the actual values themselves are very, very close, and though they're actually, this is actually a borderline prediction. I'm just taking this as an edge case and I'm showing you, I want you to understand this. But the point is, when you have 0 and 1 over here, the absolute difference might be very, very small, but you need to take into consideration that taking the absolute difference is not how you evaluate error in the case of classification problems. You need to look at, because if you are closer to the actual value, if you're closer to, let's say, 1, then I would actually penalize this much lesser than penalizing this one. This I might actually penalize much lesser than penalizing, let's say, a 0.49 and 1. Similarly, I'll give you another example. When you take, for example, 0.65 and 1, between these two, I would penalize this one significantly lower than this one. This one will get penalized much, much higher. The amount of error that this would contribute will be much, much, much higher, because this is a borderline prediction. I could have made a much larger error because of this. When I say penalizing, basically error contribution. The contribution of this error, this is also contributing to an error. I would have ideally expected this to be 0.99, but this is 0.51. This is still making an error, right? There is an error that is getting contributed because of this prediction as well. But I would contribute, or I would associate the error of 0.51 very, very, very highly in comparison to 0.65. Why? Because this is sort of a borderline prediction. So I need an error that takes all of this into account. That understands all of these boundary conditions into account. Does that make sense, everyone? Do you understand why MSE is not going to fly in this case? You need a sort of a different kind of an error. And that loss function generally is referred to as a log loss or binary cross entropy loss. Here this is mean squared error. Here it is called as log loss or binary cross entropy loss. How does the binary cross entropy or log loss work? Very simple, very straightforward. So log loss is equal to summation of I is equal to 1 to n for every observation minus y into log of y hat minus 1 minus y into log of 1 minus y hat for each observation. Minus y into log of y hat minus 1 minus y into log of 1 minus y hat. It's actually very easy to understand. Let's take a bunch of boundary conditions and you will understand what I mean by this. So log loss is equal to, let's take for one observation, minus y into log of y hat minus 1 minus y into log of 1 minus y hat. So y is the actual value, y hat is the predicted value, and y hat is the probability. Exactly. Y hat is a probability here. Now let's take a couple of examples. Let's take boundary conditions. Okay. When I say boundary conditions, what do I mean by it? Here you go. Edge conditions. Remember, actual value loss. So let's say the actual value is 0 and you have predicted 0. But remember something, your y hat can never actually be 0. You will probably predict a value like 0.000001 or something like that. You will never actually be able to predict 0. Why is that the case? It'll always be between 0 and 1 and never actually 0 and 1. This value, right? Sigmoid will always tend towards 0. It's an asymptote. That's the right term. Okay, sure. Perfect. Cool. Anyways, so now if you actually put these values in here, right? 0 and 0.001, if you actually substitute it here. So 0 times whatever, the first term will become 0. This term is completely 0. The second one is 1 minus 0. This is going to be 1 minus 0. The first term is already 0. So minus 1 minus 0 into log of 1 minus predicted value, which is 0.0001, whatever, right? So this is going to be what? Minus 1 into log of almost, this is almost equal to 1. Everybody agrees to this? Is almost equal to 1. So this what? So log of 1 is how much? 0. Fantastic. So this is approximately equal to 0. I'll not say exactly equal to 0. It's approximately equal to 0. And that makes sense, right? The actual value is 0 and you've predicted approximately close to 0. So the loss is also approximately equal to 0. Let's go for the other side of the world. So this is 0, actual value 0. But let's say you've predicted completely on the opposite side, 0.9999. So in this case, what's going to happen? So again, the first term will still continue to be 0. 0 times whatever the first term will be 0. So 1 minus 0 into log of 1 minus 0.99999. So what happens here? Minus 1 into log of 0.00001, whatever that number is, right? Log of 0.000001 is going to be what? Minus log of what is this going to be? Can this be written as 10 to the power of, I don't know, minus, I mean, whatever this large number is, minus 100 or something? Log 0 is not 1. Log 0 is never 1. Log 0 is not defined. Exactly. Log 0 is, log 1 is 0. Log 0 is not 1. So again, hear me out. So this is 0.0000 something. It's a very, very, very small value. That's what I'm saying. So this is a very, very small value. This is a very small value. I can sort of write it as 10 to the power of minus 100. So, or like a very large value. This is basically a very large value. And if you actually take this out, assuming this is 10 to the base 10, yeah, you can consider E natural logarithm or base 10 logarithm, doesn't matter, whatever. The point is this can be written as a very, very, very large value. This is a value as large as infinity, but not actually infinity. This is a very, very, very large value, or approximately value. So a negative of a very, very large negative value will become it will become infinity. So there's a minus over here, minus of minus infinity will become positive infinity. Okay. Then next one, actual value 1 and predicted value, let's say, is same again, 0.001. What would you expect? So by the way, the rationale here is what? The actual value is 0, but you predicted 0.9999 as the predicted value. So the actual value is 0. You said that the person will not churn. In reality, the person would not churn, but you predicted that the person will definitely churn, which is why the loss is very, very large. Make sense? The rationality makes sense over here. Same here. 1 and 0.0001. What's going to happen? So the second term over here will become 0. So minus 1 into log of 0.0001. So again, the same logic. So this will become minus infinity, approximate minus of minus infinity, which will become infinity. The negative is here over here. This is minus infinity. This is approximately infinity again. And actual value 1, predicted value is 0.9999. What will this become? Again, the first term will be there. The second term will become 0 here in this case. So 1 minus 1 into log of 0.9999, which is approximately 1, which is almost going to be approximately 0. Make sense? That is the loss function that is often preferred whenever you're solving a classification problem. Is this clear? So these are going to be the two major differences when you're solving a binary class classification problem. We don't ever get an infinite loss. I mean, okay, so here's the thing, Jay Kumar. If you have a scenario like these are boundary conditions, whatever I showed you are boundary conditions. You will never get a minus infinite, you will never get an infinite loss, neither will you get a zero loss. The likelihood of this happening is very, very, very low. These are boundary conditions. I just wanted to show you how the error operates in boundary scenarios. In general, your predicted values are never going to look like this. Your predicted values will never be either 0.0001 or 0.9999. They will be 0.9, 0.8, 0.01, 0.02, and so on and so forth. Okay, make sense? So now let's come back here. Let's take any kind of a classification problem, and then we can try and solve for this. Pick any classification problem. You know what? Let's actually take the Titanic dataset itself. Right, so new file, Jupyter Notebook. Let me save this TensorFlow2.ipynb. So here in this case, I'm assuming you are all familiar with the Titanic example, the Titanic dataset. I'm just going to load the Titanic dataset file. I have it available. Import pandas as PD. So the Titanic dataset is equal to pd.read CSV of, so I have this dataset Titanic, the same dataset, 1309 observations, 14 columns. I'm just going to pick a few columns from you're all familiar with this dataset. I'm not going to try and explain what this dataset is. I'm just going to pick a few columns. I'm going to exactly, we're just going to work on that. Titanic is equal to, we'll pick the columns, which is survived. What else are we going to be working on? Let's pick P class. Let's pick sex. Let's pick age. Please share the dataset. You don't have it. Really? What is the likelihood that you don't have a Titanic dataset? Come on, guys. I'm sure you have done some examples with this. Titanic is equal to Titanic of, sorry, my bad. So this is the Titanic data set. Just going to keep these columns just to kind of keep it simple for the moment. You can pick the other columns as well. I just want to show you how to build the model. I don't want to over engineer this. which is why I just want to keep it super easy. Just a couple of things. One thing is the survived as your target variable. So y is equal to Titanic. So Titanic, this is the target variable, dot drop of, and we're just going to keep the columns is equal to survived, which is nothing but your x and y respectively. Just a couple of housekeeping stuff over here. One thing that I know from my past experience is age and fair actually have some missing values. So if you look at dot is NA dot, so you clearly see that age has a lot of missing values, fair has a missing value. You can treat it the way you think it is right. So how would you treat the age column? Okay, so you can do that, which is just basically using the fill NA values, and then you can simply fill the NA columns in this particular case. And you can use any of your different you can sort of do that across all of your different variables, and then you can do this. So it's pretty straightforward in that particular sense. So I can simply pick x dot fill NA of and then you can simply say dot value is equal to mean. That should take care of filling. That should take care of what is the function that I need to pass here. Just let's just use for the moment. Yeah, you can use a lambda function, but anyways, x dot of x of age is equal to x of age dot fill NA of that is 1, and then you have the other one which is fair. You simply fill this in the fair column. So this is filling the missing values. Hopefully this should have sorted this out. And then you have x dot. So if you look at x, this is sort of taken care of right now. Let me just yeah. So x is sort of taken care of. Just a couple of householding stuff, which is P class is categorical, right? It has passenger class 1, 2, and 3 respectively. So you can convert that into one hot encoded representation. You can convert that into one hot encoded representation in this particular case, and same with the column x as well. I just want to change if you look at the D types for the moment, it says P class is integer, and P class is integer, and then sex is an object, which is fine. I'm just going to change everything to the same data type dot age, sorry, dot P class dot as type of categorical category, sorry, or object, one of these. Basically, this has converted this into three categories. 1, 2, 3 are the different values. And you could just do it for x of, I think there is an in class over here. I'm not sure if there's an in place. Yeah, there's no in place here. So that's converting everything into categorical variables, and then same with x as well, which is a category respectively. So now if you look at x, and if you look at x dot d types, there are two categorical variables in this particular case. PARCH is not a categorical variable, it is a count variable. Number of parents and children. That's what PARCH stands for. Parents and children. That's not a categorical variable, it is a count variable. So now all that I'm going to do is I'm simply going to say pd.getDummies. I'm just using the getDummies function for the moment. And you can use one hot encoding as well. You can use the one hot encoder, or you can use getDummies. Command drop first equal to true, and then so x underscore dummies is this. So now if you look at the data set, that's what you have at this particular point. Make sense, everyone? Why is the get dummies prefix separator sparse? Perfect. That's it. That's an integer column, zeros and ones respectively. So because I want it to be an integer column, I'm just creating that into an integer column for the moment. So that's it, done. So now what do you do? So your data set is created. What's the next few steps? The next few steps should be very, very predictable, which is train test split. And this has got to be x underscore dummies, so x underscore dummies, and y is y. And then you can quickly look at the shape. So that's it, 877, 877, 432, and 7 respectively, 916 and 393, 30%. And then model building as it is, nothing changes here. Same as the other, right? I'm going to copy the same exact lines of code But the only difference, my friends, what's the difference here? This, I'm going to remove the hidden layer. I mean, if you want, you can keep I'm going to ignore the hidden layer for the moment. Same process as as earlier. What's the input shape? 7, right? The input shape is 7. Output layer is what? 1. But what else? Activation. Activation is sigmoid. Remember, we're applying activation, but we're applying a sigmoid activation. Why are we applying an activation layer here? Activation on output layer. Activation on output layer is sigmoid as it is binary classification. Clear, everyone? I'm hoping this part is clear. Fantastic. Then, same step. But here, I'm actually going to keep it simple. Yeah, let's copy this line. Let's come here. So we'll stick to the default learning rate for the moment. We'll stick to the default learning rate for the moment. But what loss should I be using here? Now let's go to losses. Probabilistic losses. What losses do I see here? Binary cross entropy. See the binary cross entropy loss? That's it. Let's come back here. Let's simply say binary cross entropy loss. Log loss and binary cross entropy mean the same. Just to let you know. I mean, if in case you're worried, this is what it is. You will see the implementation somewhere here. But this is exactly the same. There should be a function here somewhere, not implemented. But basically, it's the same loss function. It's a log loss, logistic loss. Okay. And then what metrics am I interested in capturing here? See, remember, this is a loss function. This is a classification function. So what metric should I be focused on? Now I can focus on accuracy metrics. I mean, why I can plot cross entropy, but why would I plot R squared? This is classification problem. I can plot accuracy, or I can look at all of this. I can look at AUC. I can look at recall, precision. I can look at all of that. How will it decide the threshold in sigmoid for 0 and 1? The higher class is assigned to class 1. So for example, if you get a probability, basically 0.5. In the case of binary class classification, it's 0.5. You can change it if you want to. So for example, accuracy, if you come here, you can actually change the threshold. Binary accuracy, you see this threshold? 0.5. You can change the threshold if you wish to. Okay. So it doesn't decide anything. It's up to you to decide this. So now let's come back here. So instead of metrics, I'm simply going to say accuracy, and I can maybe also plot AUC if I'm interested. Let's actually stick with accuracy for the moment. We'll come back to the default is 0.5. Optimizer is optimizer, loss is binary cross entropy, metrics is accuracy. If you use accuracy, then the default is 0.5. If you want to change it, you can use something called as binary accuracy, and then you can change the threshold. Okay, fantastic. Then moving on. What do you do next? You train, X train, Y train. Let's stick with 100 epochs. Validation dataset, X test, Y test. Batch size, default is 32. Fit. Let's go. That's it. Do you get the idea, everyone? Like hardly anything. We didn't even put a hidden layer over here. Fairly decent model that you got, right? 76%, 80%. Now here, when you plot this, right? I mean, you can of course plot the same loss curve over here. You can plot the loss and and whatever, right? You can basically plot the same loss curve. What you can also plot is this. You can also plot the accuracy curve. Training accuracy, validation accuracy, validation accuracy. Because if you look at the history, you see this here. This validation accuracy is also getting captured here. So you can also plot accuracy and validation accuracy instead of loss accuracy curve. So how do you expect this curve to look like? See this? The accuracy is increased. The loss, of course, will reduce, but the accuracy will increase. Clearly, there is a gap between your train and validation accuracy. Definitely a bit of gap here in this case. Right? So I would expect this to be nicely growing. No, there's nothing to it. I mean, yeah, sigmoid. If I plot the probabilities by the predicted values, then yes, it is probably going to look sigmoid. But this is predicted values over epochs, the accuracy over epoch. So as time increases, I would expect the accuracy of the model to increase. In this case, the model I would have expected this model to perform a little better. I mean, I still feel that the model is not really performing at its best. Maybe I can do a little more for it to perform a little better. Like maybe what I can do, I'm just thinking, maybe what I can do is maybe I can add one more hidden layer over here. So I can simply say model.add The gap signifies overfitting, but the overall accuracy is itself on the lower end. Remember, the overall accuracy itself is at the lower end. Is around 70-80%. So I would have expected this to be a little higher. Accuracy is at the lower end. That's not. I would have expected it to maybe perform a little better, which is why I would consider this sort of underfitting a little. Not necessarily. There is an issue of overfitting, but there is a larger issue of underfitting itself. So let's deal with the underfitting to the first extent. Units is equal to 2, and activation is equal to relu. Let's see if this. What's the issue? Sorry, spelling. The model is stuck. Added an additional layer and actually deteriorated the model performance in this case. This is the problem with smaller data sets. With smaller data sets, actually adding dimensions is not a great idea. Let me add more features over here. Yeah, it's improved a little. Fewer dimensions didn't help. Still stuck there. So look at this. It has definitely improved the performance of the model. Let me just quickly look at the loss curve. The loss is okay. It's nicely reducing. There's actually more scope for it to improve. Look at this, all over the place. The curve is all over the place. Okay. I think we're probably looking at it the wrong way. Yeah, that's the way to look at it. That's the way to sort of look at it, because if you zoom in only on this part, you'll of course it'll almost look like it is bad. But if you actually look at it like this, it's okay. I mean, there's a bit of issue here, and it's not all that bad. It's not all that bad. There's a bit of overfitting. It's okay. It's not all that bad either. It's actually my validation is outperforming my train here in this case. It's actually not that bad. There's no overfitting here actually. It's actually my validation set is outperforming my training data set. So there's no overfitting here clearly. Does this make sense, everyone? Slightly improved performance on my validation dataset. What I can actually do is I can maybe slightly increase my batch size. What's the batch size over here? I have 29 batches. I can actually maybe shrink this down to, I can increase the batch size a little, and I'll increase the number of epochs to maybe 200. And there you go. The model slightly improved again. Again, slightly more improved performance on the validation data set. The train is still struggling a little in this case. Okay.
Hello everyone, Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application-based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also, through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.
We're going to spend some time trying to understand a couple of interesting topics. But before we go to these pre-processing topics, and what we told ourselves that we, in our session, we'll spend some time on some of these post-processing, steps, model diagnosis, sort of post-processing steps, or rather techniques that you have while model building that will help you at times, in certain specific instances, help you build better models, right? What are the kind of problems that we're going to be looking at? We're going to be looking at, or rather, topics such as patch normalization. We'll be looking at dropouts. We'll be looking at regularization. These are going to be like a couple of topics that we will specifically focus on in our today's session. Before we go that far, I just want to close out on one small topic that we had started over here. So one of the things that I want to talk about is when you look at the regression and the classification problems, what we told ourselves is when you're solving a regression problem, so as I said, there are two types of problems, right? So we started with regression and as well as classification. On the left side, when you look at the regression problem, you are looking at y is equal to w1 h1 plus w2 h2 plus p3, which is essentially like a typical regression equation. And then you would, the loss function that you would generally use in this case is something like that of a mean squared error sort of a loss. And then we told ourselves that in a typical classification setup, specifically a binary class classification setup, the equation is essentially the same. It's just that in the last layer, you would be applying a sigmoid activation. One of the things that I would like to discuss here in this particular case is, as I said, we spoke about regression and classification. On the left side, we spoke about regression, which is like basically a typical regression equation. On the right side, we're talking about classification, which is essentially like a binary class classification problem. We looked at the binary class classification problem, and a typical binary class classification problem would mean that you would have a 0-1 output, a binary output as far as your target variable is concerned. That said, one of the things that I wanted to talk about in our session is how would you solve the same thing, but in the case of a multi-class classification problem, right? So when you say a multi-class classification problem, you're talking about a scenario where you have more than two classes as in your target variable. A good case in point is, for example, if you're trying to solve for, let's say, you're trying to solve for in this. For example, if you're trying to solve for a given particular image, you're looking at what kind of image is it? Is it a dog? Is it a cat? Is it a mouse? Or given a particular type of soil, you're trying to figure out what kind of a soil it is. Given a kind of vegetable, you're trying to figure out from a category of 10 different vegetables which vegetable it could be. Given a particular image, you're trying to understand what digit it is. Given a particular character, you're trying to identify what alphabet it is, and so on and so forth. So in all of these problems that I just mentioned, your target variable has more than two levels, right? Has more than two categories. In such a scenario, how do you go about solving the same? So what you saw in the previous example was we looked at a binary class classification problem wherein you had a 0-1 in the last layer, but the moment you have, and which is where a sigmoid worked perfectly well, because what you simply had to do is you had to simply put a neural network that just had one unit in the output layer, right? So you essentially had a neural network, and all that you had to do is you essentially had to put one unit in the output layer, but the only change that you had to do is you had to apply for a sigmoid activation in the last layer. In the case of a multi-class classification problem, the setup is slightly different. Not a lot, but slightly different. Let me give you an example of a particular problem, and that's one of the problems that we're going to try and solve for over a couple of over the next few minutes. We will be looking at a data set called as the MNIST Dataset. I'm not sure if you've heard of the MNIST Dataset. MNIST is actually a fairly popular dataset where you have, these are the digits, handwritten digits dataset. Handwritten digits. And then what you're talking about is you essentially have an image of size 28 by 28. What do you mean by a size 28 by 28? An image of size 28 by 28 typically means that you have an image that has a set of pixels of size 28 by 28. It's essentially nothing but your resolution of your image, right? I'll give you a simple example of, let's say, a 5 by 5 image. A 5 by 5 image is simply going to look like this, right? So 1, 2, 3, 4. Let's go 6 by 6. A 6 by 6 image would sort of looks like this. So you have 6 pixels row wise, 6 pixels column wise, right? And 1, 2, 3, 4, 5, and then one more. That's essentially a 6 by 6 image. And what you have is, let's say, for example, you were to represent, let's say, a digit 1. And the way to sort of represent a digit 1 in this scenario is something like this. What you would have is, let's say you have a digit 1. that's a digit 1, right? That's a digit 1. Why is that a digit 1? If you actually zoom out and if you look at this particular image from afar, if you see, this is simply digit 1, right? In that small box, you have just one full column fully painted, and that's a way to represent a digit 1, if you think of it. The thing is, when you have an image like this, and you can think of, let's say, how you would represent a digit 4 as well, right? A digit 4 would probably have maybe a couple of more pixels, maybe something like this. Right? All of those pixels sort of painted. You could kind of think of that as digit 4, right? Because you essentially have all of these pixels painted. That's a digit 4 for you. So what I'm trying to get at is, when you are representing a particular image, a few pixels, when I say a pixel is nothing but a box, right? A box is what typically gets populated or gets painted or shaded, so to say. So in this case, this digit 4, this pixel, this pixel, this pixel, this pixel, so on and so forth got painted. One thing to note is a few pixels got painted a lot more than the others as well, right? It's not that all pixels got painted equally. Some pixels got painted a little more than the others. So a way to sort of represent that scale is generally 0 to 255, right? So you represent that in the scale of, let's say, 0 to 255. What do you mean by that? Any pixel that is extensively painted would have would essentially be in the range of 255. Any pixel that is not painted would have a value of 0. So what you would think of this as is, see, all of these are essentially zeros. Maybe this one is not a complete 0. This is a 0, 0, 0, 0. This is a 0. This is a 0. This one is probably not a 0. Why? Because you still have some color kind of coming into this. So this might probably be something like a 5 or something. All of these which are not painted are going to be fully zeros. Not fully shaded are going to be zeros. The ones that are heavily painted, like for example in this particular case, this might be, instead of a 255, because you still see some white space over here, so this could be probably something like a 230 or so to say. Point is that different cells in this particular matrix would be painted differently or would be weighted very differently, and the numbers represent the intensity of that particular shading. So point is that in this particular case, the point is you could take this matrix that you see here and you could simply represent it as a 6 by 6 matrix. The point that I was trying to get at in this particular case was that you have approximately, in this case, a 6 by 6 matrix. And the thing about this particular 6 by 6 matrix is that you have values ranging with different levels of intensity. A matrix that has values typically ranging from 0 to 255. So, for example, in this particular case, this matrix would have values that would go like this: start 0, 0, and this would, instead of 0, this would probably become something like a 240, 0, 0, 0. And then this cell would probably have a value of 10 or something. And then the next cell would probably have a value of, if you consider this particular column, it would have a value of around 240, 230, 0, 0 respectively. So you can think of how this complete matrix would get populated. So every digit, in a way, is simply nothing but is simply represented as a matrix, like how you see on the right side. That's images under the hoods are simply matrices, right?
Now, if you sort of think of this, if you can sort of think about this particular setup, what, one of the things that you need to sort of think about is, given a matrix like this, you're expected to predict. So what you could do is if I give you, let's say, a bunch of these matrices, you're expected to predict what digit it is, right? Is it digit 9? Is it digit 10? Is it digit 1? Is it digit 4? And so on and so forth. Why? Because if you think of it, certain positions in this particular in this particular matrix would be painted a certain way for certain digits. So you can think of how that matrix could be extremely predictable. It'll help you make it'll help you basically make the matrix a lot more, or rather the input, a lot more predictable, and thereby you could build a simple model around it. That's how your data set is. So just to kind of give you an idea of what the data set is, the data set has the MNIST dataset specifically has a total of 60,000 images, and these are all handwritten digits. These are all handwritten digits, each of size 28 by 28. So your input data, the input data is 60,000 by 28 by 28. It's essentially a three-dimensional matrix, each of size 28 by 28. So you have 60,000 images, each of size 28 by 28 respectively. And then you have a target variable, I'll provide you the data set. And the target variable is essentially, you will have single label, but you will have values ranging from 0 to 9. Absolutely right. You'll have essentially all the unique digits, 0, 1, 2, all the way up until 9. So that, not 99, 0 to 9. Exactly. Because you just have 10 unique digits, so to say. That's how the problem is set up. So as you can clearly see in this particular case, this is a multi-class classification problem. So your target variable has more than two levels, has a total of 10 levels in this particular case, or 10 classes in this particular case. So what we are trying to solve for is essentially a model, or rather what we're trying to solve for is essentially a multi-class classification problem. Given a particular data set, you're trying to predict across all of these 10 different classes. That's how your problem is set up. Now, let's get into the weeds a little. Let's actually look at how to get this data set. Let me first quickly show you where this data set is. So if you look at the MNIST dataset, this dataset was actually published. It's a super popular dataset. Continue. This is the dataset. Actually, this is the original website of where this particular dataset was published. This dataset was actually published by this man called Yan Li Kun. Yan Li Kun is considered as a pioneer in the field of image recognition. He currently works at Yan Li Kun currently works at Facebook's artificial intelligence and research labs. So everything that Meta does today in AI, a lot of it happens under his supervision. So he's definitely one of the pioneers in this particular space. So this is a data set that was published like long time ago. As you can see, this data set has 60,000 examples and 10,000 test examples. And each one is of size 28 by 28. You can actually download it directly from here, from this location, or there are better ways to get access to this data set. The Keras already has this data set inbuilt, so we'll use the inbuilt data set. If you want to download and unzip or do an unzip on this particular GZ file and you load it, you can do it as well. But I would simply recommend you to load it from Keras. Let me quickly show you how you could do that. So I'm gonna load this particular data set directly from Keras. So Keras, yeah, there you go, MNIST dataset. This is the dataset. You could actually just load it from this particular path. Let me just show you how you could do it. Do it from TensorFlow dot Keras dot what's the one? Datasets dot MNIST import load data. That's the load data function. And then how do you load this data? That's how you simply load the data, right? You simply say x test y test, x train y train x test y test is equal to load data of, and that's it. So that already should help you load the required data set, as you can imagine. Now, so x train x test y test and load underscore data should quickly read your data set in this particular case. Now, if you once you have this data, so if you quickly look at print of x underscore train dot shape, and I'm going to quickly do this for y train x test and y test. So if you look at this, that's how the data set currently looks like. So 60,000 by 28 by 28 and 60,000 in a single column. Let's quickly look at this data set, right? So guys, remember, so what am I trying to solve for here? I'm trying to introduce you to how you could solve for a multi-class classification problem. That's my objective. We will deal with some of the complexity of this image data set much later in much more detail, but stick with me for a few minutes and then I'll be able to explain some of this very easily. So from matplotlib dot, okay, let me actually quickly show you. Import matplotlib dot pyplot as PLT, and let's quickly visualize some of these data sets. So let's take a couple of images from the trained data set. So let's take maybe the first 5 observations for I in range of 5. So I'm plotting the first 5. PLT dot IMShow. IMShow essentially is an image. IMShow essentially gives you helps you plot like a given image. And I'm going to take x underscore train of I, right? So I'm picking one observation at a time from x underscore train, and then I'm going to plot it. So if you say, for example, x underscore train of 0, it gives you an array. And if you look at the shape of this array, that is 28 by 28. So that is one image, as you can think of. The data sort of looks like this. If you see this, there are a bunch of zeros, right? A bunch of zeros, a bunch of, I don't know, a bunch of numbers ranging from 0 to 255 and so on and so forth. There's a very fancy way to show you what this number is. Let me actually try it. PLT dot rather. Dot this is essentially the data frame, as you can think of, right? And dot to clipboard. So I just copied this data set to a clipboard. Let me show it to you here. Yeah, okay. This you should be able to share. Awesome. So I'm just going to remove both of these columns. I'm going to remove the first column I'm going to take the first row, and all right, one small change, which is red lines, and one small change. Right. So if you kind of look at it, you know what digit this is. That's a digit 5. Absolutely right. That's a digit 5. So you kind of get the idea, right? So there you go. If I just conditional format it, that's this digit 5. Point that I'm again trying to get at is if you sort of that the cell widths are the same, but you get the idea. So if you see, these cells are colored a lot more than the ones around it, because yeah, for whatever maybe the reason, that's the resolution of the image. This is a 28 by 28 image, so you have 28 pixels row wise, 28 pixels column wise, and then you have certain numbers which are extremely dark, certain pixels are have a very high intensity, and certain bordering pixels are slightly lower intensity. I mean, it is possible, right? There are some which are low, have lower intensity. That's because when you have a stroke, the edges are probably going to cut across more than one pixel, right? So the edges could probably cut across more than one pixel, and which is why you would see that some of the pixels might just have some of some part of the stroke going in, and for that reason, maybe that complete pixel is not shaded, which is why the intensity of that pixel is lower. That's why you would see that the edges generally have slightly lower intensity. The internal parts are fairly dark, as you can see here. The internal parts are fairly dark. The edges are generally the ones that have slightly less shaded, if you think of it. Exactly. So now PCA doesn't do the same thing. PCA does something else altogether. PCA doesn't do this. But anyways, so I'm going to plot the first 5 images over here. One more small change. CMap is equal to, it's a grayscale image. So I'm just going to put in the grayscale. So I'm taking each image and I'm simply plotting it. That's a digit 9. Yeah. It's digit 5, digit 0, digit 4, digit 1, digit 9. Those are all the digits that you see here. Right? These are the first 5 images, so to say. Now, what I'm also going to show you quickly is, let's look at the target variable. Right? And what I'm going to do here is I'm simply going to say plt dot title. Let's actually go for a title here, and I'm going to say v of I. Right? So y underscore train of I. So I'm essentially simply plotting the value over here, which is essentially the ith variable, which is actually a target variable. So your target variable reads this. It says this is 5, this is 0, this is 4, 1, and 9. That's your data set, guys. So you have your input data set, which essentially has a bunch of matrices and a column, which is basically nothing but your target. Now, what are we going to do? So I'll have to use this data set to build my model. The unfortunate reality is that so far, everything that we've learned about, let's say, everything that we've learned about, let's say, predictive modeling, only allows you to pass a two-dimensional array as an input. Sorry, a unidimensional array as an input. So for example, every observation that you pass into the data set, right? Like for example, you take any of your neural networks or take any machine learning model, so to say. Every row, every observation is unidimensional. What do I mean by that? So take, for example, any data set that you've taken so far. Let's say you're trying to basis the money that you've spent on ads, and you have, let's say, whatever other features that you have. Let's say number of competitors that you have, and whatever other features you can think of, which is nothing but, let's say, the stock price of this particular company. You're trying to predict the sales of this particular company. Now, for every observation, every observation over here, in this particular case, is simply a row of data, right? This is your target variable. This is x1. This is x2, x3 for a given set of values. What you're saying is, given this array of values, a unidimensional array of values, you need to predict this target variable. That is, that is how you would typically have any row or any observation sort of created in your data set. That's how we typically allow it, and which is how even your neural network so far, so to say, that we've discussed so far is like that, right? So you have a bunch of inputs. Each input, this is x1, this is x2, this is x3. Then you have a target variable y, and then all that you're saying is these inputs are essentially passed into the neural network, and you generate an output. Each of this is an individual value. The point is that every row has to be a unique one-dimensional input. However, in this case, our data set is not unidimensional. Each observation is not unidimensional. It is actually two-dimensional. Why? You have a matrix. Do you understand the complexity here, everyone? Do you understand why this is a little tricky? Why this is not the same? Each input data set, or each row, is two-dimensional, is 28 by 28 in shape. So one of the things that we need to do is we sort of will have to convert this into a two-dimensional matrix. So what we do, or rather every row into unidimensional. So what we're going to be doing is we'll take any observation and we'll flatten it. We'll sort of simply flatten it. So the shape previously is 28 by 28. But all that I'm saying is that I'm going to do is I'm going to convert this into a unidimensional array of 784. Why 784? 28 by 28. 28 by 28 is 28 times 28 is 784. So all that I'm doing is I'm essentially taking and then creating this into a one large unit vector. That's all that I'm doing over here. So simply put, a good way to sort of understand this is all that you're doing is you're essentially taking this row, putting it here, taking again this row, putting it next to this, and then taking this row, putting it next to this, and so on and so forth. That's all that you're doing, right? This row, putting it here, this row, putting it here, this row. So essentially stacking the whole thing up, as you can think of over here. So that way you'll end up, instead of a large image, you will essentially create it as one row of data. So each image is going to be, so image 1 is going to be one row of data of 784 columns and one target variable. So when you do that, what happens as a result of that, when you do something like that, what happens as a result of that is your observation now, your data set, your input data set, which was previously 28 by 28. This is, and your target variable, which is y. This is digit 9. And it says this is digit 9. This is x and this is y. First observation. Second observation was another matrix of 28 by 28. This is digit 8. And it said this is 8. The third observation, which is again another two-dimensional matrix, which is again of size 28 by 28. But this time, let's say digit 0 is represented as 0. Instead of a data set that looks like this, what you now have is a nice two-dimensional matrix where you had, instead of these 3 rows, now you have 3 rows times, instead of individual 2 by 2 matrices, you now have 784 because you've converted each image into a one long unit vector. Each image is now one long unit vector over here. So this image that you see here is essentially converted into a long unit vector. Same, the second one will be a long unit vector. This is essentially going to be a long unit vector in itself. And then the third one is also going to be long unit vector, each of size 784. This is 784, this is 784. This is basically 784 columns, x1, x2, x3. So you'd end up having x1, x2, x3 all the way up until x784, and then one target variable over here. So it sort of converts that into a simple two-dimensional matrix that you could use for building your model. So you have flattened the complete data set. That's what you've done. Okay, so how do you do that? How do you flatten the image? So simple, x underscore train dot reshape of x underscore train dot reshape of -1 comma 784. What does -1 here stand for? All rows. This basically means 60,000. It's a placeholder, but it's essentially says 60,000 auto computed value, because x underscore train's initial shape was how much? $60,000 by 28 by 28. So if I say a reshape of -1 comma, instead of 28 by 28, I've let's say converted into 784. So what would the remaining be? That would be 60,000. So now x underscore train is that. Similarly, x underscore test, I will do the same thing. So now if you look at the print, now if you actually go back and reprint the same thing that we had done earlier, which is the printing the shapes. So I think let me actually just hide this. That's it. So now that's how your data set looks like. So we started with 60,000 by 28 by 28. Now your data set is 60,000 by 784, and your target variable is still 60,000. So you have the data set. One small change that I want to, or one point that I want to call out here. So if you look at your training y underscore train, it's essentially a bunch of these values. So if you look at the top, let's say 5 values, it is 5, 0, 4, 1, 9 respectively. So my question here is, so if you look at the target variable, which is y here, one of the things that I want you all to understand is your target variable is, as I said, a multi-class classification problem. And this is a categorical variable. Though you have numbers in it, digits in it, but it's a categorical variable. And how do you treat categorical variables? What do you do with a categorical variable? We discussed this. You convert it into what? We do one-hot encoding of a categorical variable. That's exactly what we're going to do, right? So we'll perform one-hot encoding. There is a small function in TensorFlow that will do this. You could use TensorFlow's functionality. You could use scikit-learn's one-hot encoding. You could use anything you want, right? Keras utils import to categorical. You could use this. You could use pd get dummies. You can use any variable. Doesn't matter. Any function, right? And all that you're going to be doing is you're going to say, that's it. So you take the y underscore train, and now what you have is you have your categorical variable one-hot encoded. So if you look at the shape, what do you think the shape will be here? 60,000 by 10. It's going to be 60,000 by 10. Why 10? You have 10 unique variables. So when you one-hot encode a target variable which has 10 levels, you will end up having 10 unique levels. That's it. So that's one more piece of pre-processing that you will have to do, which is y underscore one-hot encoded is equal to y underscore train underscore one-hot encoded is 2 underscore categorical of y underscore train. That's it. Now that's your data set. So 60,000 by 784 is x, and your y is 60,000 by 10. Is this clear so far? It is not multivariate. It is still okay. So clearly you guys haven't solved for any multi-class classification problem so far. See, the thing is, when you solve for a multi-class classification problem, remember one thing that, okay, so 10,000 is test. Only 10,000 observations in the test data set. So you need to understand this, right? When you have a target variable y, the current numbers, the values in that are, let's say you have a data set x, which ranges from x1 to x784, basically columns. And then target variable says it's digit 8. The next one it says digit 5. Next one it says digit 0. Next one it says digit 9, and so on and so forth. This is your target variable. Now, in this case, you're predicting for numbers. You're predicting for digits. In another problem, you may be predicting for, let's say, categories, right? These are also this is also a category. You will be probably predicting for other kind of categories. What categories would you be predicting for? You would be probably predicting for, let's say, cat or dog. Given an image, you're trying to predict if there's a cat, if there's a dog, if there's a mouse, if there's a human, and so on and so forth. So fundamentally, your target variable is categorical. That is established. Why? You may see numbers over here, but it is a categorical variable. That is an established fact. Now, how do you treat categorical variables? We've discussed in our previous session. Be it target variable or be it your input data set, it doesn't matter. The treatment is the same. You just use them, you convert them into one-hot encoded representation. So how would you convert something like this into one-hot encoded representation? So you're going to simply have y underscore 0, y underscore 1, y underscore 2, y underscore 3, all the way up until y underscore 8, y underscore 9, right? You'd essentially have 10 new columns getting created, and a digit 8 here would now simply be represented as 0, 0, 0, 0, all zeros, 1 and 0 respectively, right? A digit 0 would be represented as 1 and everything else is zeros. Just for some context setting, you would not have done something like this if you had solved for, let's say, a decision tree. Why? A decision tree does this internally. Or a random forest would not. You don't have to do this because random forest and decision tree classifiers are innately multi-class. They don't need for you to do this kind of stuff that you're seeing over here. Oh, I hope that makes sense. Okay, anyways, going back here again. So your data set is ready, your train test split is done, and now let's go. Let's actually build the model. So how do you build the model here in this case? Same way as you did the earlier case, nothing different, same setup again. I'm just going to copy this as it is, and then we'll try and build the model. Just give me a second, please. Somebody's at the door. Just a second. That's two observations. This is for digit 0, this is for digit 8. That's why you would see 2 rows. So same setup as we just spoke about. So what you will have to do in this particular scenario is, as I said, everything remains the same. You will have to, of course, start with this defining the model itself, sequential. What's the input here? That's 784. That thing changes over there. And let's for a moment forget about the hidden layer. We don't need a hidden layer for now. We'll come to the hidden layer later. If we really need it, we can come to it. And then the output layer. Now in the output layer, when we solved for a classification problem earlier, we said, you know what, there's one unit, and then we applied a sigmoid classifier. But now how many units do I have in my output layer? Exactly 10. We have 10 units in the output layer. And now here's the tricky part. The thing is, when you are solving for a binary class classification problem, you need a probabilistic output. If you have one value that ranges from 0 to minus infinity to infinity, if you apply sigmoid, it will bring it between 0 and 1. That is why we were using sigmoid. Now you have 10 values. You don't have one value. You have 10 values now. Meaning for every input observation, your network sort of looks like this. I'll show you how the network now looks like. Your network looks a little different. These are inputs, 3, 4, all the way up until 784 inputs. This is your input layer, and then you have your output layer. In the output layer, you have 1, 2, 3, all the way up until 10 outputs. That's what you have here. 3, then you have 10 outputs. So this is how your network now looks like. Yeah, of course, this is also there, this is also there, so on and so forth. So you get the drill now. You now can understand how your network looks like. This is x1 all the way up until, sorry, y0, y1, all the way up until y9. Right? This is x1, x2, all the way up until x784. Now the point is, for every input row that you have, now remember an input row here has how many values? An input row here has 784 values. For every input row that has 784 values, how many outputs are you getting here? 10 outputs, 10 values. Right? You're essentially getting 10 values as outputs over here. So your outputs over here, if you just take the output matrix, you're getting 10 outputs. So a typical matrix representation of this would look like this. So you would have an input matrix of size n by 784, where n is the total number of observations. This is x. How big is the weight matrix? It's 785 by 10 plus 1, basically 785, because you also have the bias. You'd also have the bias, right? So it's 785 in a way, but that's okay. 784 by 10, which is essentially the the same number of weights, which would result in an output of n by 10, which means where n is the total number of observations, and each observation is going to have 10 values as output. Now, what are these 10 values? You fundamentally look at it without any activation function. It will give you 10 numbers that will range from minus infinity to infinity. Currently, without any activation function, this would give you values that will range from minus infinity to infinity. Each value will range from minus infinity to infinity because there's no activation for the moment. But that doesn't solve the problem, right? You need to get an output that will range between 0 and 1. Earlier, what you were able to do, it should be between 0 and 1. You will not get it between 0 and 1 because there is no activation for the moment. Forget about this activation. If you don't have this activation, because a sigmoid activation is something that you would use only in the case of binary class classification. Now the question is, how do you get the output for all of these 10 to range between 0 and 1? But remember, one of the other things that you also want to ensure here is that while you have your 10 outputs ranging between 0 to 1, meaning 10 outputs ranging between minus infinity to infinity, you want them to sort of be, in a way, summed up to 1, right? Even if you want them to be between 0 and 1, you want them to sum up to 1 because it's probability at the end of the day. What do I mean by it? Given a particular image, what you're saying is whatever the image is, you would want to predict for the likelihood that the the likelihood of the image being 0, likelihood of the image being 1, 2, all the way up until 9. You want the probability that that particular image belongs to each of these different classes. What we're going to be doing, if you just simply put, let's say, a sigmoid on each of these, hear me out. If you put sigmoid on each of these, what's going to happen? Every value will range between 0 to 1, but it's not guaranteed that all the values will sum up to 1. At the end of the day, you would want all the values to sum up to 1 because this is one image. This is not 10 different images. It is one image getting classified into one of the 10 different classes. For that reason, what we do is instead of applying sigmoid on everything, we apply something called as a softmax. Softmax is basically like an elder cousin for sigmoid. So we apply something called as a softmax. What does softmax do? Softmax is like sigmoid, but what it ensures is given a particular distribution of values, it will ensure that it normalizes those values between 0 and 1. In a way, it's sort of a normalizing function. I'll repeat it again. Hear me out. In a typical classification setup, binary class classification setup, you have an image, you're classifying it into, you're getting one output from your neural network that ranges from minus infinity to infinity, and then you're saying you're going to apply a sigmoid on top of it. So the moment you apply a sigmoid on top of it, you will get a value that ranges between 0 and 1. Right? So you apply sigmoid on top of it, the sigmoid will return a value between 0 and 1. Straightforward. Same setup, same image, but instead of 1, you're going to get, for the moment, let's just take 3 outputs. 3 class classification problem. It's giving you 3 outputs, right? Y0, Y1, Y2. This is a multi-class classification problem, 3 class classification problem. You're trying to predict if the given image is a cat, a dog, or a mouse, whatever it is. Each of this, without an activation function, is giving you a value between that will range from minus infinity to infinity. Without any activation, it will give you values that will range from minus infinity. Now, this image only belongs to one of these 3 different categories. If I tell you, if you apply a sigmoid on this, if you simply apply a sigmoid on top of this, what's going to happen? This will give you a probability ranging, this will give you a value like, okay, this is 0.6, this might tell you 0.3, this might tell you 0.4. If you sum it up, this doesn't have to sum up to 1. Why? Why doesn't it have to sum up to 1? Because you have applied sigmoid independently, and basis the way where the value is in terms of the distribution, it will convert that into it will individually apply the sigmoid transformation on top of it. So technically speaking, there is no one image is essentially getting classified into 3 different classes, one of the 3 different classes, but the probability is not summing up to 1. Do you understand why this is a bit of a challenge? Right? You have one of 3 cards and you're saying that each one, when you draw, the likelihood of one of those cards being, let's say, a spade is, of the 52 cards, is let's say 13 out of 52. It's 1/4. Same, and if you think of it exhaustively, it is 13 out of 52 for spades, for hearts, for clubs, and for diamonds, respectively. That is a perfect classification, right? But if one of those classes is a little higher, and let's say 2 of those classes are a little higher, then you're not dealing with a fixed set of observations. Then that's not a perfect random variable. You're dealing with a very complex environment in that case. So the small objective that we have over here is to try and sum this up to 1. How do you sum it up to 1? The simplest way is you can apply min-max scaling. Remember min-max scaling? You can actually just apply min-max scaling on top of this and it will convert everything into 0 and 1. We don't use min-max scaling or normalization. Instead, we use something very similar to it. We use something called a softmax, which is like min-max scaling, which is like normalization. What it'll do is it's not going to take these numbers. It's not going to take the probabilities. It'll take the raw outputs. Which is whatever the numbers that come out of that'll range from -infinity to infinity. And it'll apply a softmax classification, a softmax activation. How does a softmax work? I'll show you how a softmax works. So let's take a set of values. Let's say a softmax is returning values like -100, or rather, your neural network is returning values like let's actually keep it smaller for the moment. Let's say it's giving values like -10, 5, and 3. Let's say it's giving you values like these, -10, 5, and 3. This is essentially the output from the neural network. The neural network is returning these values, let's say. So how do you apply a softmax? The way you apply a softmax is you say e to the power of this value, whatever this particular value, e to the power of -10 divided by summation of each of it. Summation of each of it is going to be summation of, or rather, e to the power of -10 plus e to the power of -5 plus e power -3. That's the first one. The second one, e to the power of same thing again, but in this particular case, you're doing the same thing, but e to the power of -5 divided by same thing again, e to the power of the same, whatever you have over here, you simply put it over here. Right, I'll just copy paste it. And the last but not the least over here, which is the third one. So this value becomes this value becomes this, and then this value becomes e to the power of -3 divided by, oh, I'm so sorry. Actually, I think I made a small mistake, but nevertheless, we'll correct it. E to the power of -10 plus e power -5 plus e power -3. I think the small mistake that I've made is it's not negative. because if it is negative, then this will actually become the smallest of the lot, and that doesn't make sense. If you think of it, this has to be the smallest. So this is, let me just make a small correction here. Correction. That's it. E to the power of minus 10 by whatever is the constant value that you see at the e power 5, and then this is e power minus e power 3. That's it. That's how it kind of turns out to be. So that way, what you get, yeah, it's an exponential because you would want it to get into like an exponential curve. Like in the case of sigmoid, if you see sigmoid also is an exponential curve. It's an asymptote, right? You want your probability curves to sort of be in that exponent form. That's why you sort of go for an exponent over here. There's a little bit reasoning to it, specifically because you would want values that are closer, closer to 0 to sort of get separated much more than the others and stuff like that. But you get the idea. So this is more like, and the denominator is the same across the board. That way you're normalizing the values. E power minus 10 by a constant denominator, e power 5 by the same denominator, e power 3 by same denominator essentially becomes partial fractions across the three. So that way you are normalizing the values in this particular case. So what happens is if you just apply those same values, quickly over here, if you just import numpy as np, and let's say np.exp of minus 10 divided by np.exp of minus 10 plus 5 plus 3. So that is np.exp of minus 10. Similarly, this is one value, and this is 5, and this is 3. So, and I'm just going to put a print around this so that it becomes easy. So those are the three values. You could round it, of course, but you get the idea. So if you see this here, so you look at the values here, what does it say? This is 0.88, meaning your value 5 is 0.88, 3 is 0.11, and minus 10 is 2.6 into 10 to the power of minus e to the power of minus 7. So this is almost close to 0. So if you actually sum up these three values, 0.88 plus 0.119 is almost 0.999, and then this is like that super small value, like super small value, which all sums up to 1 in this case. And these are probabilities that sum up to 1. That is softmax. So point here being 0.88 probability of being y1 exactly. So what you need to do here, the small change that you need to apply here is, in the case of a multi-class classification, what you will end up doing is the activation that you choose is not sigmoid, but rather it is softmax. That's the only difference you need to, that's the only change you sort of will have to bring in this particular case. So this is how you define the model. And after that, everything else is the same. No changes whatsoever. The only other change that you need to bring is, instead of binary cross entropy, you would be using something called as categorical cross entropy. That's it. Categorical cross entropy is what we'll be using for. It's cross entropy loss, but across all the categories. So there's basically a summation across each class. That's it. Right. That's it. And then, yeah, the rest of the story remains exactly the same. No changes whatsoever. X train Y train underscore OHE X test G. Perfect. There you go. That's your model. Yeah, this is log loss. Same thing. Cross entropy loss. Same loss, but it's written. I mean, it's for all the different classes. So there's a summation across every class. All the 10 classes, there's a summation. That's it. Here, let's quickly take a look at the curves. Right. So I think validation. So look at that. This is the loss curve. Train and validation. Clearly, some issues here, of course, because what I ended up doing, and I think one of the things I ended up, fixing here was the batch size, and I picked a very, very small batch size. Smaller batch sizes mean what? Smaller batch sizes are, if you see, in every epoch you have a lot of batches. It takes a lot of time. It's much closer to a stochastic process, and as you can see here, you can see a lot of the performance is a little all over the place. It's a little unstable, clearly because of the batch size. Let me quickly show you how the accuracy curve looks. That's okay. I mean, it's pretty much stayed flat. If you look at it, it sort of stayed flat across. If you just zoom in a little, pretty much stayed flat across the board, right? Hasn't changed much, so to say, but there's a bit of the loss sort of because the loss was all over the place. You could see that the accuracy and the validation accuracy also had a bit of an instability. If you just go back and make a small change, I'm going to reduce the number of epochs. We don't need probably 200 epochs. And what I'm going to do to the batch size, how many observations do we have in this data set? We have 60,000 observations, right? Right. I'll probably go with like a batch size of 1,000 over here. I'll redefine the model. And with just 100 epochs, look, this is so much faster. And if you see the validation accuracy, it's not really going beyond the 89% mark. The loss is reducing a little bit, but it's not really going beyond that, right? Almost 100 epochs is quickly done. But automatically, what you would observe here is that with the larger batch size, look at the model performance, right? You look at the accuracy, right? Nice and smooth with a larger batch size. And even if you look at the accuracy, it's a much more, I wouldn't say it's like super clean, but it's so much more smoother than the earlier one as far as accuracy is concerned. Now the question is, you could of course do like a bunch of different things over here. But before we actually fine tune the model, I just want to complete the end to end, and then we'll come back to fine tuning the model. But I just want to quickly show you the predictions. Model.predict of x underscore test. So these are the predictions that you get. So if you look at the preds, what will be the shape of the predictions data set? How many observations do we have in the test data set? 10,000. And what will be the size? How many predictions will you get? What will be the output shape? Fantastic, by 10, not 784, by 10. The predictions will be 10,000 by 10. So now what I'm going to show you is if you take, let's say, preds, this is how you have for each observation, you have values that range that for each observation, you have basically 10 predictions. So if you just take the first observation, you have 10 predictions. This is class 0, 1, 2, 3, all the way up until the end. So looking at these numbers, can you tell me which class does this observation belong to? Yeah, so 0, 1, 2, 3, 4, 5, 6, and 7. That's the highest one. So this observation is classified as digit 7 in this particular case. So if you quickly look at the observation, right, plt.imshow, let's look at x underscore test, but just one point, x underscore test dot shape is currently this. So I'm going to just reshape this -1, 28, 28. I'm reshaping it back to the 28 by 28 so that I can actually plot, right? And I'm going to plot the 0th observation on this, and I'm going to say function home plt.imshow and cmap equal to gray plt.show. That's digit 7. It's perfectly classified it as digit 7. So now the thing is, how do you extract these probabilities for all observations? Meaning, how do you extract the classes for all the observations? So what you can do is you could do something like the following. So you take the predictions, and I'm going to be using one function from, so if you take of0, I need to pick the index of the largest value. Do all of us agree on this? I need to pick the index of the largest value. So I'll use a method called np.argmax. So in an array, you would want to pick the index of the largest value. That will give you this number. It will return the index of the largest value in a given array. Similarly, you have np.argmin as well. So you have argmax and argmin. So it's essentially the minimum or the maximum value in a given array that you have. So now let's quickly take a look at how you could extend this for all the predictions. Comma, axis equal to 1. There you go. That's the predictions for everything. That's the predictions for all the observations. So if you look at the shape, 10,000 to have the predicted class. Now what we're going to be doing here, these are indexes of the predicted values. In this case, the good thing is the index, I mean, in this particular problem, the index is as good as the class itself. So you don't have to, again, cross-reference it against the class. But in this problem, the index is the class itself. Yeah, because it's 0 to 9. So we were lucky in that sense. But I'll show you much later in a certain problem where you will have to extract the maximum value and then sort of pick the value from a certain, you'll have to cross-reference that against a particular label itself. You'll have to do that. From here, it's the same, right? I mean, you could do all the, you can compare it with the actual target variable. Joyita, in the case of binary, you just put a threshold, right? Like for example, in the case of a binary class classification value, meaning, for example, if you get probabilities like this, just give you an example. So let me just show you how you could do it in the case of a binary class classification. So imagine np dot so I'm just picking, like, I'm just randomly creating an array over here, right? So just to kind of show you how you would do it for in the case of so the low is 0, high is 1, and the size is, let's say, I don't think this works because this only picks from integers, but let's try. I think this doesn't work between 0 and 1, but let's try. Perfect, it works even for the other ones. So good. So these are like 10 digits. Let's go 100. Okay. So these are 100 random predictions, binary predictions for a binary class classification. Remember, in the binary class classification, you're going to get values that look like this. In the case of binary class classification, you'd sort of get just unique, individual numbers, right? So for each value is simply nothing but a probability that's coming out of a certain, for that particular observation, this one value is generated as an output. From here, you can simply say np dot where of pred if it is greater than 0.5, then 1, else 0. That's it. Converting probabilities to classes using a threshold. Now that's up to you what threshold you want to use. You want to put greater than or equal to, greater than 0.6. That's your choice. Let's go back here again. So you get the probabilities, red class, and then from here, what you can do is you could do any kind of your comparison. So from sklearn dot model performance, what is it? Is it metrics? I'm blanking here. Where do you find the metrics? So classification report. Actually, classification report makes no sense. Confusion matrix. And same thing. So confusion matrix of what is the actuals, which is y underscore test, comma pred underscore class, and that's it. That's your confusion matrix. So if you see class 0, class 1, class 2, and there are certain observations which are misclassified in this case. So what I would want us to call out, what I would want to show here is we started with no hidden layer. So one of the things you could do to improve the model performance, one of the things we've observed from this model is that look at like how many of our epochs you're running, the accuracy curves are pretty much staying flat. So now let's go back and let's see if you can improve this model. And that's where model.add of a dense of, now I'm going to add a hidden layer. So my first is 784, my next is 10. So I might probably go somewhere like maybe 100 units or something, like approximately 100 units or something. And then activation is equal to, I mean, again, my idea here is to try and, I would ideally gone for like midway, but you could also maybe start like 10 or something and then try and increase. But I'm guessing like it's 100. And that's sort of what my hunch is telling me. But you could pick anything, right? I mean, you can start with like 10 units, and then you can go from there. Let's actually start with 10. Activation relu. What's wrong? Units. Right. Same thing. Same model. See, my model accuracy has dropped significantly because I just have 10 units over there. And of course, my model has slowed down. Clearly, my model has slowed down in terms of training. Why? Because I added one more layer over here. It's improving, slowly improving, slowly picking up. Just one thing I want to show you here. It's kind of a very weird sort of, it seems like it kind of got stuck at multiple places over here. But the good part is both train and test curves are going up together. So I could kind of train it for a little longer. I could maybe just execute the same thing for a little longer and it might actually improve the model as well. I'll just run it for maybe 100 more epochs. It might actually improve the model as well a little more. Yeah, not improving. It has reduced for the next 100 epochs, but it's sort of flattened again. after it hit like the 80% mark, so to say. So one thing I'm going to change, I'm going to go up a little. I'm going to increase the number of units over here because it's underfitting right now, clearly. I'm just going to increase the number of units over here, increase it to 20, rerun the model. So one thing to note is slowly you see that split coming through. It's a good fit already. The model is a good fit. It's like 93% accuracy. But then there's clearly a bit of overfitting that's happening here in this particular case. You could actually train this more. The split will start getting bigger and bigger. For example, if I just train this for a few more epochs, instead of let's say 100, let's say we go to 200 epochs, same model, not going to change much with the model. I'm going to just rerun it. Let's see if anything interesting comes through there. So, yeah, I mean, visually speaking, so you see that the error is definitely dropping, the loss is dropping. But if you observe the validation loss and the train loss, the train loss is reducing much faster than the validation loss. The train accuracy is 96% now, almost 97%. The train accuracy, the validation accuracy is still around the 94% mark. So yeah, I mean, this is a probably even better model. The validation has definitely improved, but then the gap is slowly starting to increase. All right, so now let's talk a little bit about how can you reduce this gap, right? So what are the things that is causing your model to behave the way it's behaving? So let's quickly take a look at something, right? So if you look at the model summary, right? So input 784, first hidden layer 30 units. So 784 times 30 plus 30. Sorry, 784 times 30 plus 784. That will give you the total number of weights and biases. And then, of course, the next layer, which is 30 times 10, which is 300 plus 10, which will give you a total of 310 weights. So a total of 71,000 weights is what you have in this particular case. Sorry, yeah, total of 23,860 weights is what you have. That's essentially what you're currently focused on as far as this particular model is concerned. We'll come to the optimizer params later. Now let's come to how can you address some of these issues in this model. So what you need to know is when you're building a model like this, more often than not, this overfitting is a bit of a, when you're building neural networks are prone to overfitting, right? So because you're always trying to extract complex features, you're always trying to extract nonlinearity. So in the process of extracting nonlinearity, you might end up getting drawn into this whole scenario of a situation of overfitting. So overfitting is a very, very common issue as far as neural networks are concerned. So what are some of the different ways to handle overfitting? One of the most simplest ways of handling overfitting in the case of a neural network model is using a concept called dropout. And then there is another technique which is also fairly popular, referred to as regularization, right? What is dropout and what is regularization? Let's discuss dropout. Dropout is a very simple concept. If you have a model with, let's say, a certain number of inputs, 3 inputs, and then let's say 3 hidden layers in this case. Sorry, one hidden layer with 3 units. And then let's say what you could do, and then let's say you have an output layer. So this is x1, x2, x3. I'm assuming only one hidden layer. You can assume as many hidden layers as possible. One of the causes for overfitting is because your model is extracting a lot more complexity from the training dataset. It is actually trying to fit for a noise within your dataset, and it is extracting patterns from your training dataset, more extensive patterns from your training dataset, but it is unable to generalize them on test dataset. So what it means is it's almost like you're walking into an examination and a test and you have, let's say, you not only learned the concept, but in the process of trying to learn the concept, you also ended up memorizing a few things, a few problem statements, and their solutions in your, from your textbook. And that's an issue, because if you start memorizing things, then that's a problem, right? So you're trying to extremely carve out very, very niche patterns from your data set, which will not help you in an exam, because if you start memorizing question and answers from your textbook, it's not guaranteed that your exam will have exactly that question and answer. So that's what's happening here. So what you need to do is you need to get your model to be a little less complex. The other way to say it is you need to slow down how the model learns, right? So what you observed here, as the number of epochs increased here, your train performance started to go up, right? Your train performance started to nicely go up, but your test performance did not go up as quickly as you wanted to, right? So one of the things I might want to do is I want to sort of try and bring both of these curves closer. So in a way, if you think of it, I want my test to do, when I train the model, I want my model to slow down in terms of its learning. I don't want to hit this, I don't want it to get to this maximum very, very quickly. I would say, you know what, don't try to quickly get to minima on your train performance, slow down a little. In the process of slowing down, it might not try to extract too many complex patterns. So I'm going to make the model a little less complex. Perfect. Now, how do you do that? Well, in the training process, there's this fantastic step called as, exactly, you're deferring the learning. So that's where dropout comes in. What dropout does is very interesting. What dropout does is it says, you know what? Let's randomly initialize the weights. Let's randomly initialize the weights across all of these, all the weights that are there in this layer and this layer, and randomly initialize the weights. Let's do the forward pass. Right? Let's do the forward pass. Let's do the back propagation. That is essentially and in the forward pass, all the weights are going to help you generate the values of H1, H2, H3. And then all the weights over here in combination with the values of H1, H2, H3 will help you make the prediction. But imagine if I randomly pick in every batch that I pass from left to right. Batch, remember, I'm not talking about epochs, I'm talking about every batch within an epoch. Every epoch might have many batches. So for batch number 1, what I do is I randomly pick a few weights from one of the layers, and I can turn off those weights. I turn off those weights. When I say turn off those weights, I'm temporarily going to disconnect those weights, those connections. I'm disconnecting randomly some weights. So when I disconnect some of these weights, what's going to happen? I'm going to be using, let's say I have a total of 300 weights over here. Of the 300 weights, I might randomly disconnect, let's say 10 weights. Not all the weights are going to contribute towards generating the output here, right? So thereby, the prediction that I generate is not going to be extremely bad. It's going to be worse than the earlier one, but it's going to be fairly okay, right? And when I back propagate, right, I only back propagate the weights that are turned on. The weights that are turned off do not get trained. So for that batch, I'm using for this particular batch, of the 300 weights that I have, I've turned off 10 weights. So now only 290 weights are in play. Those 290 weights will help me do the forward pass and the back propagation. When I do the back propagation, I only update the 290 weights. Now I select the next batch. Now I do take batch 2. I repeat the same process, but this time these 10 weights are again picked randomly. These weights are again picked randomly, right? Now a random set of 10 weights are currently turned off. Now remember, when I say I'm turning off the weights, I'm not making the weights 0. I mean, you can consider that as turning off the weights to 0, but they're temporarily being made 0 only for that batch, only for that forward pass and back propagation, they're being made 0. And when I resume the next epoch, the older weights will get resumed. Exactly. The old weights with the old values are resumed. Absolutely right. And that's it. That's like a super simple way of, so what you're doing as a process is you repeat the same for batch 2, batch 3, batch 4, and how many other batches you have. So it's like this. So you have weight 1, weight 2, weight 3, weight 4, and then let's say you have batch 1. In batch 1, the current weights, let's say, are 0.5, -1, 0.5, and 1.5. Let's say these are the weights that you currently have. Temporarily, I might pick one of these weights and I say, you know what, this is temporarily 0. This is temporarily 0. So I do the forward pass with these weights. And when I do the back propagation, of course, all of these weights are going to get updated. So my new set of weights, the new set of weights are, this 0.5 might get updated to, let's say, 0.53. This 0.5 might again get updated to, let's say, 0.49. This 1.5 might get updated to 1.6. Now, for when I do batch 2, I will resume -1 over here. I will have -1 over here. So now these are the set of weights for batch 2. Now when I do forward pass for batch 2, I randomly pick another weight. Maybe this time I pick this weight. And I currently say, you know what, you're turned off. So I only use these weights and I try to train. So now what's going to happen? So now this 0.53 will probably become 0.535. This -1 can become -1.5. And then this 1.6 might become 1.65. And this 0.49 will get again resumed. When I do batch 3, I again randomly pick a weight and then I repeat the process. So in the whole process, what's going to happen? Because I'm randomly picking the weights and dropping them out, at some point or the other, all weights will get trained. But it's just that I'm not letting all the weights get trained simultaneously at the same time, thereby slowing down the process. Now the question is, if I drop too many weights, what's going to happen? If the dropout is very low, model will start to perform very badly. You'll have an underfit. If I drop too few weights, what's going to happen? The overfitting will continue. So it's a balance. It's a balancing act. Now you need to pick what's the best kind of dropout you need to apply. And you generally apply this dropout in layers where you have the most number of weights. All right, perfect. So we spoke a little bit about how you could build a multi-class classification problem. And then what we also solved for in our previous session was we also looked at how to solve for overfitting. That two overall techniques. One was dropout and the other is regularization. We discussed dropout in greater detail. We'll discuss a little bit about regularization. All right, perfect, cool. What dropout basically tries to do is during the training process, you could essentially apply dropout between a couple of layers. And what dropout does is it tries to reduce the rate at which your model learns. In a way, it kind of disconnects some connections in every forward pass and back propagation step. For every given batch, what it tries to do is it tries to reduce the number of weights that get utilized during a forward pass, and thereby also adjusts the number of weights that will be trained, that will be also updated during the back propagation step. That is essentially what we had discussed. And then we had also actually seen this in action during the, when we had actually applied the overfit, dropout in the model. You had also observed the same behavior. So what we had done is we had applied dropout between the first and the second layer. And what we observed is, we were able to significantly address the overfitting. We kind of brought both the curves together. That is how dropout sort of works. We'll discuss another technique. And in this particular case, we'll be discussing a technique called as regularization. What is regularization? Regularization is another technique that is often utilized for managing overfitting. Let me give you a bit of a context as to how regularization works. I'm sure you may have heard about regularization, right? So regularization is a pretty old concept. It is not completely novel. So just to kind of take one step back, right? If you think, for example, and just to let you know, regularization as a concept is not only applicable for neural networks, right? Regularization is an out and out machine learning concept which can be applied for any kind of algorithms. So you would see regularization being applied to regression models. You would see to basically linear regression, logistic regression, linear models. You would also see regularization being applied for tree-based models. And then the same concept is sort of also borrowed into the neural network world as well. I'll give you a bit of background of how regularization works, and then we'll also see how it works in action. Once we finish regularization, there's one more small concept called as batch normalization that I will discuss. Okay, so regularization. So let's take, for example, a very simple perceptron. If you take, for example, a simple perceptron model, so you have a be it a perceptron or even, for example, a simple regression model as well, doesn't matter. So you have a bunch of inputs, and then you have a bunch of inputs, x1, x2, all the way up until xn. How many ever inputs you have, x1, x2, all the way up until xn, and then this is your y hat. So y hat is equal to w1 x1 plus w2 x2 plus so on all the way up until wn xn plus bias. Now, when you take an equation that looks like this, and this, by the way, is a classic regression model as well, as you can think of. So in a model like this, one of the challenges that we have is, when you had solved for linear regression models, what you may have done, if you remember briefly, is if you have, let's say, a model with your data set with 100 features, right? If you have, let's say, a model with 100 features, a data set with 100 features, when you pass these 100 features into the model, when you pass all of these 100 features into, let's say, a regression model will take all these 100 features and try to build a model for you, try to build a regression model for you. And then what you may have done is, once your model is built, you take a look at the features or the p-values across each of these features, right? So you look at the significance scores of each of these variables that you have, and you then decide which features are important and which features are not important, and thereby drop the features that are not very important. Make sense? This is how you would have built your regression models earlier. What that basically tells you is, while the model is getting built, the regression model by itself does not have the ability to decide which features are important and which are not important and automatically drop them. So the regression models doesn't drop features by itself. What it tries to do is, it tries to maybe deprioritize some features by reducing the coefficient values, but it doesn't really drop features. Why am I saying this? Simple. Think of this. If, let's say, you have two models. Model one, you have features, and I'm just using the word error over here loosely, whatever the error is. So let's say model one is built on same data set, but you, of the 100 features, you have used all the 100 features. Let's say I have built a model using all the 100 features, and the error percentage that I get, let's say, is 20%, right? And then what you decide is, you say, oh, you know what? Let me take the data set with all the 100 features. Let me pick the ones that I believe are the most important. So you do some pre-processing, right? You do some pre-processing, you do some exploratory analysis. And then you say, hey, you know what? I don't need all 100 features. I will only use, let's say, 40 out of these 100 features. And then from those 40 features, you build a model. And when you build a model, let's say you get almost the same error, right? Model 1, Model 2. Model 1 uses 100 features and gets 20%. Model 2 uses 40 features and gets the error of 20%. According to you, which is a better model? Is Model 1 a better model or Model 2 a better model, right? Model 2 is a better model. Why is Model 2 a better model? Model 2 is a better model because you're able to build the same model with lesser amount of complexity. You're able to get the same model performance with lesser complexity. Why do I use the word complexity? The reason I use the word complexity is because the moment your number of features increase, automatically your model becomes very complex, right? For example, if you were simply building a simple, regression model with one feature and one bias, you're building a straight line. So for example, if you just have one feature, y is equal to w1 times x plus c. The moment you have two features, you're building y is equal to w1 x1 plus w2 x2 plus b. And the moment you add three features, this is w1 x1 plus w2 x2 plus w3 x. Point is, here, this is a very simple straight line equation. In this case, the moment you add one more feature, you're now trying to model for data in a three-dimensional space. You're trying to sort of model for data in a three-dimensional space. You're building a plane in a way. This is actually a plane. This is not a line. This is a plane, right? The more and more features you add, what's going to happen? The model will become more and more complex. The shape of the model will become more and more complex, right? The moment you add more complexity, higher dimensions means the moment you start using higher dimensions, higher number of dimensions, you're also introducing the possibility of overfitting because you're making the model more and more complex. Making the model more and more, you're getting the model to capture very, very complex patterns. And in the process of trying to accomplish that, you might actually end up, fitting a very, very complex curve. And this high complex curve might end up being might also introduce a little bit of overfitting. Do you all fundamentally agree on this analogy here? More parameters, more number of features means more complexity. So if I were to just summarize, higher number of features means higher amount of complexity, so a higher complexity complex model, which could mean higher amount of overfitting. I'm not saying you will always overfit. I'm saying there's a higher chance of overfitting, right? What I would always want to do is I don't want to use all the features that are needed. I want my model to be smart enough to only pick features that are relevant, that are useful. If I just because I have 100 features, it's not the case that all the 100 features are actually contributing to the model. Maybe only a few of those features actually contribute to the model. So I would always pick a model that gives me almost the same performance, but with lesser complexity. Okay, that's the premise. Now the question is, how do you provide your model with that kind of a capability, right? That is where regularization comes in. What regularization tries to do is to automatically identify which weights or which features are required to help build the model. How does it do it? Here's how it does it. So when you're building when you take, for example, any kind of an equation, so y hat is equal to w1 x1 plus w2 x2 plus all the way up until wn xn. When you take an equation that looks like this, your typical cost function, or assuming this is a regression problem, you would be computing mean squared error. A mean squared error is going to be 1 by n into summation of predicted value minus actual value, the whole square for each observation. I is equal to 1 to n for every observation. But what regularization does is regularization says, you know what, this is great, but I will also add an additional cost for using more number of features. So what does it do? It says summation of k equal to, or actually let me use a slightly different notation here. The notation is inappropriate. 1 by k is equal to, sorry, just a small correction here. The notation is inappropriate, and there is 1 by k, where k is number of observations. Remember, k is number of observations in the data, right? And what you do here with regularization is you're saying, you know what, while you penalize the model, while you associate the cost of the model as simply the error of prediction, along with that, you also penalize the model 1 to n. Actually, let me use the other one, k squared. Look at this for a second. You should be able to understand this. It is very simple. So what you're saying is, hey, you know what, go ahead and try to find the best possible values of w in this particular equation. That is what this cost function is. This is a regularized MSE, a regularized cost function. So 1 by k into summation of y minus y hat minus predicted value minus actual value the whole square. Plus, along with it, I'm also saying try and minimize the total number of or the square of the weights that I use over here. So what am I saying? I'm saying now my objective is this. So now I need to try and minimize this whole thing together. Now I need to minimize this whole thing together. So my objective is find best values for W1, W2, W3 all the way up until Wn such that your MSE, regularized MSE is minimum. So now I need to not just minimize for the prediction error. This is the prediction error, but along with minimizing for the prediction error, I also need to minimize for the W's over here. I also need to minimize for the Wj over here or the square of the W's over here. We'll come to that. What is L1, L2? Yeah, this is L2, but I'll define that later. But does everyone understand this notation here? So here, what we're saying is try and minimize for not just the model error, but along with the model error, also minimize the total number of weights or the square of the weights that I'm using over here. So in the process, what will happen is now in the process of trying to find the best possible values of W's, I might simply decide, you know what, adding maybe W10, W11, W15 is not useful because it's not really reducing my error as much. Well, even if I keep, you know, W5, W15 over here, I might be reducing this, but I am actually increasing this particular part. So you know what, there's no point in actually keeping the W's. I might actually shrink the values of W's, W1, W5, W15 drastically in this particular case. So you are trying, this is a multi-objective function where you are trying to solve for both in parallel. You're trying to simultaneously solve for this. This is referred to as regularization. This is regularization. That's it. This is the concept of regularization. What regularization tries to do is it tries to find the best weights and also tries to find the best number of weights that you should be using. Not just the best weights, but also tries to find which weights to keep and which ones to drop. Yeah, k is the number of observations. That's a good point. K is the number of observations where n is number of features that you have. N is the number of features that you have. J is for this. Wj meaning for any given value of j. So okay, so if I were to take, write the regularized equation for a small function. So what you're solving for is, let's say you have an equation that looks like this. Earlier, your MSE would have been what, right? 1 by how many weights? 1, 2, 3. For the moment, just forget bias. Bias is also taken care of, but for the moment, let's just forget bias. Simply for simplicity. So 1 by 3 because W1, W2. You have not 1 by 3. And let's say you have a data set that looks like this. You have x1, x2, x3, and your y. So you have 1, 2, 3. Let's say you have 1,000 observations over here. You have 1,000 observations over here. Yeah, I'm exactly doing that, Vignesh. So listen to it if you can, please. So if you have a model or a data set that looks like this, x1, x2, x3, and your target variable is y. Whatever is the data set, doesn't matter whatever the data set is. You have 1,000 observations and 3 features, right? So you have 1,000 observations and 3 features in this particular data set, right? Your mean squared error without regularization would have looked like this. You would have written it as 1 by 1,000 by 1,000 because you have 1,000 observations. You need to compute the error across each of these 1,000 observations, right? 1 by 1,000 of whatever is the predicted value. Predicted value is W1 x1 plus W2 x2 plus W3 x3 minus y the whole square, right? You would have to do this. Remember, you would have to do this for each observation. You would have to do this for each observation. So you would have to write something like summation of I is equal to 1 to 1,000, and you would put an I over here. Everybody agrees to this? 1 by 1,000. You will do this for every observation. I is equal to 1 to 1,000. For each of the observations, you will compute the predicted value, you will compute the actual value, and take the whole square. But in the case of regularization, if you regularize this MSE, then plus what you're going to have is plus, and now you do this across each of the features. So you're doing W1 square plus W2 square plus W3 square, right? Plus you're essentially adding this additional term over here, right? Instead of writing it this way, instead of simply writing it this way, what I could write it as, do all of us agree on this? This is the regularization term. Now, what you're doing with the regularization, okay, put the 1 by 3, doesn't matter. Yeah, you can put 1 by 3 here also, doesn't matter. Okay. Here in this particular case, this has nothing to do with the number of observations. This has only to do with the number of features that you have. This, my friends, has to do with the number of observations, because you compute the error across each observation. The error is across each observation because for every observation, you compute the predicted value, you compute the actual value, and then you take a difference across each of these. You do that for every observation. That's what you see on the left side. What you're seeing on the right side is the summation of each of these, how many ever features you have. You're essentially taking one weight. Remember, weights are not for each observation. Weights are for the complete data set. Weights are for your complete data set. They depend on the number of features. So you have one W1 here, W2 here, W3 here. So what you're saying is, I will take the sum of each of these weights, also sum of squares of each of these weights over here, right? Now what you're doing is that what you're saying is, in this particular case, you are saying, look, in the earlier scenario, you will minimize the error in such a way that you find the best possible values of W1, W2, W3. You do the back propagation, you do basically the same story, right? But along with it, just add one more squared term of the W's over here. What will that do? What that will do is, it is going to put an additional amount of load on the model to not only find the best W's, that minimize this error, but you're also saying you would need to reduce the total number of weights that you use, or you will have to basically you're adding an additional penalty over here for using too many weights. You're saying you accomplish this, but you accomplish this with less number of weights or lesser impact of those weights. That's what you're saying. So you're basically applying a bit of a penalty. So it's more like saying, you know what, you can, to win a match, you need to score 5 goals, but you'll have to do that with let's say 5 players. Instead of 11 players, you'll have to do that with 5 players. So you're adding an additional constraint over here. You're adding a little bit of additional constraint over here, right? Now, how does this work? How does this actually work? So if you logically think about it, remember, this is a squared term. So what do you have here? W1 square plus W2 square plus W3 square. So if you actually expand this whole thing, you are essentially going to get a second degree polynomial. This is a second degree polynomial in W's. Everybody agrees with that? So you're going to have something like A times W1 square plus B times W2 square plus C times W3 square plus blah, blah, blah. You're just adding an additional W1 square, W2 square, W3 square over here. So it is still a second degree polynomial. The whole thing is still a second degree polynomial. Nothing changes. So logically, you're just adding an additional amount of penalty over here. That's all that you're doing. Okay. Let me show you something. You all remember this. Okay. So in this scenario, what did we say? You can build a model with without hidden layer. The moment you add a hidden layer with a linear activation, it still doesn't work. You apply a bit of, let's say, a ReLU sort of activation. That the moment you do that, you start seeing a little more complexity getting kicked in. You add more features. Automatically, the model starts to become more and more complex. Okay. Now, the moment you add regularization, right? Forget about what L1, L2 is. I'll explain what L1, L2 regularization is. The moment you add regularization, right? I add a lot of regularization, heavy amount of regularization, the same model with a lot of regularization, the model starts to underfit. Why? Because you're forcing the model, you're increasing your model, you're increasing the impact of this part of your model extensively. You're saying, hey, this is very, very, very important, is what you're saying. So thereby, your regularization is very large. So just to kind of give you a bit of idea, the way this is generally written is your regularized MSE regularized is equal to your current MSE, whatever is your current MSE, plus some kind of a regularization parameter over here. You put lambda or C or whatever. Generally, you use the term C, which is basically a regularization rate, times some kind of a regularization factor, which is in this particular case, your regularization term. I'm just going to put it as R over here. This R is this. This C is like a multiplier, which tells you how much importance do you want to provide for regularization. And then your regular MSE. That's how you write it. So if I increase the impact of this regularization, what's going to happen? Then I'm saying, you know what, this is very, very, very important is what I'm saying. And automatically as a result of that, what's going to happen? You're saying you should always try to have less number of weights. You should always try to have less number of weights. And for that reason, you'll end up fitting a very, 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 you'll end up fitting a model with very, very few weights. And thereby your model will underfit. Your model will never learn in that scenario, right? On the other hand, if I start reducing the amount of overfitting, the moment I reduce the amount of overfitting again, no success, right? Let's go one step further. I reduce it even further. So now you start seeing with a little bit of regularization, look, my model has fit the model, but it is again less complex than the previous one, right? It is still a little less complex than the previous one. I reduce it even further. Now you'll start seeing a little more complexity kicking in over here. So what you're trying to do is the regularization is helping you only use a few weights during the model building process, which is very much like dropout. If you think of it, what was dropout doing? Dropout was also only it was slowing down the whole learning process. It's doing the same thing over here as well, in a way, right? And if I put a 0 MSE, 0 regularization, my model fits normally, like how it would have fit otherwise. Do you get the idea? Do you understand with this? That's what you're doing. You are trying to reduce the number of features that get used in the model building process. That's what you're doing. You don't decide to have you don't decide if you should have a regularization or not basis how the dataset looks. None of it is dependent on how the dataset looks. It will depend on how your model is performing. If your model performance shows situations like overfitting, where it is overfitting, that's when you actually introduce regularization. Otherwise, you don't need to, right? So for example, you're fitting a model like this, 0 regularization. It will slowly start fitting better here. And then what I can do is, if a model is fitting here slowly, like what you see over time, it is slowly trying to learn. But the moment I add a little bit of regularization, it will smoothen it out. Look at this. It'll make the model, like what somebody said, it will make the model a little less complex. That's what you're going to be able to accomplish by using regularization. So regularization is more like you're adding more load on the model to learn, and thereby you're putting a lot more pressure, saying don't use all the features, use only a few features, work with lesser complexity. That's what you're asking your model to do. All right, okay, so let's go. So now, just to kind of give you an idea, so I'm assuming you all understand how this is set up. So just to give you a bit of understanding, so a regularized cost function, and I'm talking about it in the context of MSE. MSE regularized is equal to, as I said, 1 by K. K is the number of observations. Summation of I equal to 1 to K, right? I is equal to 1 to K. Predicted values minus actual values, the whole square, plus C times. Now here is where the regularization parameter comes in. C times lambda of, stick with me for a second. I'm just going to elaborate on this regularization parameter. Lambda times summation of I equal to 1 to n wi plus beta times summation of I equal to 1 to n, sorry, wi square. Square doesn't matter, whatever it is. This is your complete regularization equation. Now I'll explain each one of these. Stick with me for a few minutes. K is number of observations. Now, just to let you know, these parameters that I've mentioned over here, different literature use different variables, but broadly the concept is the same. K, n is number of features that you have. K is the number of observations. N is the number of features. C is your regularization factor. C is the regularization factor. Generally, the regularization factor is a value that ranges from, again, 0 to positive infinity. It tells you how much impact you would want this whole regularization term to have. In certain cases, the C might not exist. That depends on scenario to scenario. Now, earlier, what we saw was, we saw this, right? We saw this one. So this part that you see over here, this is called L2 regularization, also popularly referred to as ridge regularization. This part that you see here is called as L1 regularization, also referred to as lasso regularization. C can be any number that goes from 0 to infinity. Yes. Now, I'll explain what is the difference between lasso and see. When you do L2 regularization, when you do L2, forget about this term for a minute. Forget about this term for a minute. Let's just focus on this part. You're adding a second degree polynomial over here. You're adding second degree value of W over here, right? So when you differentiate, you're essentially adding, so no values of W are going to become zeros over here. Rather, you will just reduce, just to simplify it, when you only do L2 regularization, the effect that you get, and I don't want to get into too much of the detail here, but when you do the L2 regularization, the effect that you get is no W's are dropped, or rather W's are not made zeros. No W's are equal to zero, or W's are not equal to zero. W's are not forced to zero, but less impactful W's are made approximately zeros. Your weights are not dropped, your features are not dropped. So if you pass 100 features, all the 100 features will be there, but only for a few less impactful features, the impact of W's will be made very, very small, meaning the weight values will become super, super small. It's almost like killing it, but you don't kill all the features, you keep the features. I'll tell you in which scenarios it works. For example, when you're building, let's say, some kind of models in the case of healthcare, or let's say banking, if you pass 100 features, your output should have all the 100 features. Why? Because there are certain regulatory impacts around it. So, meaning if you're passing, let's say, age, or let's say some specific features, there are some rules around how certain features have to be used, and certain features cannot be used while model is being built. So to prove that all the features are being used in the model, you could use, let's say, an L2 regularization. So that way, if you pass 100 features into the model, you will end up getting 100 features as the output, but the weights of those features will be super, super, super small. So you're not actually dropping the features, but the weight contribution of those features is going to be very, 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 very small. So the W's will become 0.001, 0.00001, and so on and so forth. That way, you might not be reducing the dimensionality, but you're still reducing the impact of those dimensions. On the other hand, if you do lasso regularization, what happens is a few W's are actually made zeros. Few W's are actually equal to zeros. So less impactful weights are actually dropped. So if you pass 100 features as an input and you use lasso regularization, what will happen is, as an output, you might only end up building the model with 20 features or 30 features. The remaining 50, 60 features might get dropped. Now, how many features will get dropped will also depend on how much regularization you wish to have. Like whatever is the impact of C will also determine how much regularization will be percolated into the model. But in the case of lasso regularization, weights are dropped. In the case of ridge regularization, weights are not dropped, but the impact of those weights, or the magnitude of those weights, is made almost close to zero. So simply put here, if lambda equal to 1, and beta equal to 0, you're applying lasso regularization. If lambda equal to 0 and beta equal to 1, then you're applying ridge regularization. Now you may ask, can I do both? Can lambda be equal to 1 and beta be equal to 1? Then in that case, yes, you could do both. Some weights are made zeros, some are killed. That is referred to as elastic net, where you are applying both L1 and L2 regularization simultaneously. You could do both. You can drop some features, you can keep some features, whatever. That's totally up to you. You could apply both. Okay. Now, it's like a balancing act. What is the benefit of applying both? It's a balancing act. So if you're applying L1 and your model is underfitting, you're applying L2, your model is not really doing as well as you want. So you do both. You're not able to completely get rid of the overfitting. So if you want to find balance, then you could do both. You can do L1 and L2. So it's like getting, kind of striking the both, striking the balance between the both. It's a flexibility that you have. There's no advantage. I mean, it's more like it just gives you a little more benefit in this case. We've done both. In my world, we have used both. We've done Lasso, we've done Ridge, we've done Elastic Net. So there's nothing like this is better or the other is better. I mean, if you want to replicate, in a way, what Dropout does is Dropout sort of replicates the L2 regularization, not the L1 regularization. Now, just to kind of give you an idea, in certain scenarios, not on the data, it depends on the model performance. The data itself doesn't matter, right? So it depends on how the model behaves. So now in certain scenarios, what happens is this parameter C may not exist. I mean, certain implementations, like in the case of Keras, this C parameter doesn't exist. They just make lambda and beta numeric. So I just showed it to you as booleans over here, true and false. Instead of making it 0 1s, you simply have L1 value, L2 value. So they just make these parameters non-zero in a way. I mean, they make them non-Boolean. They make them proportions, or they make them percentages or actual numbers. That way you can get rid of this additional parameter. Does that make sense? So lambda is not equal to 0, beta is not equal to 0. Then you're applying elastic net. So instead of going for both C, lambda and B, you can just deal with lambda and beta respectively. All right. I'll show you how it works, right? Instead of having C as a single parameter, what I'm saying is you can have lambda and beta alone. If lambda is not equal to 0 and beta is not equal to 0, then you're applying elastic net. If lambda equal to 0 and beta value can be whatever number, can be 5, 10, 0.5, 0.2. Instead of making lambda and beta Boolean, because the way we set it up is lambda and beta are Boolean and C is the regularization factor. Instead of having a separate regularization factor, you can make lambda and beta itself as regularization factors. That's what I'm saying. So let me show you how this works, how you can actually implement regularization in the case of TensorFlow. Let me show you how it works. So generally, you don't apply both dropout and L1, L2 regularization. You either do L1, L2 regularization or dropout, but you don't do both. Okay. So from TensorFlow, so this is without the dropout. I'm just running it without the dropout. So I just turned off the dropout for the moment and I executed the same piece of code. I haven't applied regularization yet. Just to kind of show you how the model performs without regularization. You remember this, right? Without regularization, you saw that these two curves were getting split, right? So you had a bit of an overfitting over there. If you remember, that's what I want to quickly show you. So that's the baseline, and I'll show you how L1, L2 regularization can help. Perfect, fantastic. So let me just run this, and you start seeing this behavior, same behavior as the previous one. So you see this nicely. There's a clear scenario of overfitting over here. Now let's come back and now let's apply L1, L2 regularization. So how do you apply regularization? So from TensorFlow dot Keras dot regularizers import L1, L2. Okay. So this is the L1, L2 regularizer. So you have only L1 regularizer, or you have only L2 regularizer, or you have both L1, L2 regularizer. You can just pick L1, L2 regularizer. I'll show you how you can implement it. Okay. So now what you would be doing here in this case is you would say, so you said, let's say I'd like to apply a regularization in this particular layer. So I'm going to say here, there is something called as kernel regularizer. Kernel is also another way for referring it to as referring to weights. Weights are also referred to as kernels, right? Kernel regularizer, which is basically nothing but the regularization term. And then you say L1, L2 off. Now here, if you see L1 is what I can define. So if you see here, let me actually go here. So I can say I want to apply L1 regularization of 0.1 and L2 of 0. I don't want any impact of L2 regularization. So I'm applying lasso regularization over here. Actually, you know what? Let's start with no L2 no L1 regularization, but let's say a little bit of L2 regularization is what I've applied over here. Very little amount of L2 regularization. So just to kind of show you, Keras. So the way you would apply is you would say L1, L2 off, and then you're going to say L1 is whatever value and L2 is whatever value, like super small L1, L2 regularizations. That's how you apply the regularizations over here. So kernel regularization is L1 off, whatever the number that you just applied over here. That's what we are doing here. Okay. Now rerun this. Nothing changes. Everything else is the same. So L1 is off for the moment. I'm just doing ridge regularization for the moment. Applied a very little amount of ridge regularization. Let's see if it has any impact. So when I say L1 regularization, I'm essentially applying the value of lambda, which is what I was saying. You don't have a concept of C in the case of TensorFlow. You're just doing lambda, whatever the value of lambda is over here. If you're doing L1 and if you're doing L2, then you're applying beta. So you don't have a separate value of C over here. So look at this, you're almost able to replicate the same performance across both. It's giving you the same sort of an effect if you look at the values over here. Does that make sense? So you look at this 9691, 969, 9616. Look at that. Sort of gave you the same exact effect as that of your. Now, if you choose to, let's say, go back and do L2 regularization, L1 regularization, and you say, hey, you know what? I don't want, I put L2 as 0, which is basically beta as 0. And I say L1 is 1 point. Let's say I just use a slight, let's actually just use a slightly higher value of L1. And if you actually try to build a model this time, same thing, but with lasso regularization, higher amount of lasso regularization, I would suspect it to underfit. I would suspect it to underfit in this particular case, but let's see. See, look at this. No, it's actually okay so far. But let's see. See, somewhere here it went down to 0.52 almost. Suddenly went down to 0.52. It's not even hitting 90 if you see this. It's not even hitting the 90% mark. So clearly what do you observe? The model is underfitting in this scenario. Significantly underfitting. Look at that. It's super unstable with the L1, L2, with the L1 regularization. Extremely unstable for some reason. And then the model is also underfit. We are clearly in this case. In the earlier case, we are getting 96% and stuff like that. So with higher amount of L2, L1, the model is struggling. So I would simply then maybe reduce this even with, let's see if the model does okay with L1 of 0.1. If my model is doing well with L2, I would not expect it to do well with L1 to be honest, but let's see. A little better, but it's still clearly a little unstable. The model is unstable here in this case. Very, very unstable because the features are getting dropped and that's making the model extremely unstable. So look at this. Slightly better. It went up the 90% curve, but it's still extremely unstable here in this case. Clearly, this is maybe we can go a little lower. So, but you get the idea, right? So with this, you have a lot more control than that of, let's say, your dropout. Both dropout and this both are good. There's nothing wrong with it. You can pick whichever one you want. Okay, that's it.
Hello everyone, Intellipaat offers executive postgraduate certification in data science and artificial intelligence in collaboration with iHub IIT Roorkee. Through this particular course, you'll get to learn multiple tools like Python, PySpark, SciPy, NumPy, Pandas, Matplotlib, TensorFlow, Git, etc. You are going to learn multiple skills like data science, natural language processing, deep learning, fundamentals of generative AI, prompt engineering, and application-based generative AI, as well as recent trends like agentic AI. This course is designed to get you ready for the AI world. So do check out link available in the description. Also through this course, we have already helped thousands of learners take positive step in their career. You can check out their testimonials on our Achievers channel.